Hey everyone and welcome back to PrepFusion. So today we will start a new chapter of power electronics. So we have studied about basic switches, power semiconductor devices. Then we have studied about rectifiers, which are AC to DC converters. Now we'll study about DC to DC converters. Why do we need them and how actually we created the DC to DC converter, what components we needed to make a DC to DC converters, and also we'll cover step down choppers in this first lecture and few questions with pure resistive load, and then we'll do with the other loads in the next lecture. So this is the first lecture, introduction to DC converters and step down chopper with pure resistive load. So here, first of all, what does a DC to DC converter do? Basically it converts fixed DC to variable DC. Now it may have many applications, right? Like we may need, like I have a DC supply of almost 100 volts. Obviously I cannot charge it to my battery, so I need a fixed DC to DC converter to convert that 100 volts into a 10 volts supply, right? So due to all these reasons, we may need a DC to DC chopper converter. And another thing is that here, right, the current will not always be continuous. It depends on the configuration. If the load current is continuous or not, it depends upon the configuration. But the inductor current will always be continuous. Don't worry if you don't understand this point. I will actually, when we will go through the analysis, right, of each choppers, there you will see. Okay, so what do I mean? I will write a very important point at the starting lecture itself, that in DC to DC converters or choppers, choppers, load current, continuity, of load current, depends upon construction. Okay, like what depends upon the type of chopper, depends upon the type of chopper. Okay, and what about the other thing? The the inductor current will always be continuous. It doesn't depend upon the which type of construction I'm using. So this is another important point here. I will write it down. Inductor always be continuous. By continuous mean always be in conduction mode. Else, like we need some impulse voltage across the inductor, right? That we don't want. Okay, continuous. Okay. So this is the case basically. Let's now move on. So this is the block diagram. So here, right, for a step down chopper, what we do is we actually turn this, make this voltage 0 for certain periods of time. So the overall average DC voltage comes out to be lower than this. This is some fixed voltage and this is some variable voltage. Okay, so these are the things. This is the block diagram, and actually what we can do is, in rectifiers, what we did, we took a single phase or 3-phase supply AC and converted it back to in the rectifier circuit, converted it back to into a fixed DC. Now I may not want this DC value, although with changing this alpha, phase angle alpha, also I can change the average voltage, but it may so happen that I don't that is too hectic to change the value of alpha and all those things. We can do one thing. We can create another device, that is chopper, that will convert this fixed DC into a variable DC with help of simple switches and all those things. So why do we do this? So maybe changing that triggering angle or the firing angle alpha is a bit complex to us, so we don't want to change that triggering angle or firing angle alpha. What we'll do, we'll use choppers, and with the help of choppers I can convert my fixed DC into a variable DC, which is simpler than the previous case. Okay, LC and load, all these things are there. Okay, so basically here few things, theoretical things are written. So chopper voltage controls. Choppers allow us to obtain desired DC voltage at the load by switching a fixed DC voltage using a power electronic device. So what we do is we actually turn the output voltage off and on for some time. Here you are seeing that output voltage is 0 and then it is totally equal to the input voltage. So we need a switch. Basically, right, choppers are combination of switches. So everywhere, whatever we learned, we have used switches, and here also we'll use switches only. So with the help of switch, what I can do is I can turn this switch on, and then it will totally come across my output, and then I can turn it off. Then what will happen? It will totally go to 0. Okay, that's it. And like after that, what we use a LC, low pass LC filter. So this is a filter, low pass LC filter, to pass the totally DC component, low pass LC filter. Now let's read, like I was talking about all these things, few more like applications of choppers, right? So choppers are useful for voltage control, and what they do is basically, what are the applications? They are highly popular in applications like HVDC systems, controlling DC motor components, and other areas. So there are many use cases of choppers. We'll obviously not learn that. We'll first understand how to actually make a chopper device and how to analyze a chopper. Then obviously we can use it for many application purposes. Now mainly we use choppers as a switch. Choppers operate by switching at high frequencies using components like SCR, IGBT, MOSFET, track. Okay, the chopper switch, right? It can be anything. If they are like, we mainly operate choppers at high frequency. So if we are operating at very high frequency, we'll use MOSFET or IGBT, and if we are using it at low frequency, we'll use SCR, right? So these are the things, like I have already told you the division of frequency and all those things. I hope you understand. And like mainly chopper, right? Chopper is mainly a switch, and we'll also understand like there is few modification of the chopper device as well. So only switch is not the case, but for now you can understand chopper, right? For now chopper is only just a switch. Later on, once we go through the levels, I will also explain like what does chopper mean in a different manner. Okay, now DC, like what are the applications? DC to DC converters are used in speed control of DC motor, regulated power supplies, MPS, provide input power to the inverter, and solar power converters. Solar power converters also use choppers because they, right, we are getting some DC content, DC voltage, but some at very low voltage. So we may want to increase the voltage and all those things. That may be the reason. Okay, so let's actually take an example for now. Let's take an example and how did the chopper device got invented. So I told you, right, chopper is, for now, this is just a switch, and any power electronic device I can pick. Okay, just like you can take SCR, you can take triode, you can take IGBT, you can take MOSFET, depending on the frequency or the switching frequency, and depending on our application, we might switch pick the switch. Now this is my this is not my output, this is actually my input, right? This is actually my input. This is my input VI. Okay. Next, this is VDC. It is constant voltage, right? It is VDC. It is constant voltage. Then what I do, once I turn it on, right? Once the switch is on, okay, once I turn it on, what will happen? Totally my output voltage will be what? VDC, right? Simple, it's just a parallel circuit. Once I turn this on, this will become short circuit, and my output will be basically input voltage. Next, once I turn it off, right? Let's assume here is a R load here. For now, let's assume there is a R load. Once I turn it off, right? So as no current is flowing, so drop across the R is 0. So hence the voltage will become 0. Okay. So this time period is from T on. So at T1 I turn it on, and then again at T next, like after next cycle, I will again turn this switch on, and this will continue. So what will be my VO average? So if you want to find out VO average, right? How do you find out average of a signal? So VO average will be what? Area upon time period. So what is the area? Area is VDC into time. How much, like what is this area of this basically rectangular box? It is VDC into T on. VDC into T on. Okay. Next, divide by what? Divide by T, because that is the total time period, right? That is basically the area. So this is like, we can use integration as well, but this is much simpler, right? We can directly do it with the area formula. So what will be this? This is VDC T on upon T, and what we write, this particular expression, right? This ratio T on upon T is actually very important. So we write this as alpha into VDC, and what does this alpha means? Alpha means duty ratio or duty cycle. Duty or cycle. Now you may have seen this with some other symbol. So this other symbol, right? This is basically what? This can be written as alpha, or this can be written as duty, D, capital D. This can be written as delta. Okay. What else? Any other sign am I missing? This can be written as D. All those things, like they provide, many educators teach different symbols, so don't get confused. All these mean basically T1 upon T, this ratio, right? This is T2 ratio, and this is my average voltage. So you can see my alpha, right? Always just remember this thing, that your alpha will always lie between 0 and 1. Why is that the case? Why will alpha lie between 0 and 1? Okay, why alpha lie between 0 and 1? Alpha will lie between 0 and 1 will be basically due to the reason that what is alpha? Alpha is T1 upon T, right? And T1 will always lie between T and 0. It is not possible to go like on period more than the time period of the switching, right? That is not possible. So that is the reason that T1 will lie like this, and the same reason as alpha is between 0 to 1. Now here what we observe is, when this is off, right? When this is off, this is not perfect actually. This is not perfect because I have still ripples, huge amount of ripples, right? Like I'm not getting this constant DC, so I may want bit of filtering here. So I'm getting ripples here. Okay, not perfect, right? This is not perfect DC voltage. This is very bad. So I want to reduce ripple. So what I do, I just put a LC filter. If I put a LC filter, what will happen is, once this is on, right? So this inductor will get charged. Don't worry, we'll analyze this later on. Just I'm giving you the intuition now. Once I will close this, I will like totally charge this inductor. Like the current will increase, and this C will actually charge with increasing the voltage. So once the switch is closed, right? Once this switch is closed, what will happen is my output voltage will still be remaining at the average output voltage. The average output voltage will be only this. Okay, average output voltage will be only this. Don't get scammed by thinking that this will be always Vs or Vdc, right? That will not happen. I will explain when we will analyze the working. There I will explain. So this capacitor actually reduces the ripples in output voltage, and inductor actually reduces the ripples in output current. But here, right, one problem arises. What is the problem? Once I open the switch of the chopper, right? Once I open the switch of the chopper, we actually, what do we need? We actually need a discharging path for this inductor, right? So I will write here, once I close switch of the chopper, we need a discharging path, right? Or de-energizing path of inductor. Okay. So what we do is actually, right, we connect a anti-parallel diode with this load, not here, just before the inductor, so that it has a discharging path. So here we actually, in this section, right, we connect an anti-parallel diode. I'll just use some other color if possible. Here use anti-parallel diode. What will happen is, this will not discharge like this will not make the inductor totally open circuit. Suddenly the current won't go to 0, whatever the current is, right? So it will still flow through this diode, and there won't be any impulse voltage that will appear across the inductor. Okay, so yeah, that is the reason we place a diode. So once we study the step down chopper, right, there is a diode as well. So this is the basically reasoning of placing the diode. So many educators, they directly start with step down chopper. They don't tell you what was the reasoning or the intuition behind all these things, right? Like, why am I placing diode here? Why are the components like this? So yeah, I will tell you, and obviously I will tell you, like, there are a lot of formulas here, but the best thing about choppers, right, you can derive the formulas in 30 seconds. So I will recommend deriving the easy formulas. The difficult formulas which take a higher amount of time, there are 1-2 formulas which are very, very difficult. I will tell you to remember them, simply memorize. But most of the formulas you can derive, and I will recommend that only, because in question, right, you may have to derive a new formula. because question can come different, and it has happened. I will also solve that question as well, where formula doesn't work. You have to derive the formula on the examination hall, so that also may happen, right? So these were the things about like chopper and the intuition behind chopper. Now we will certainly directly go to our step down chopper. So first of all, choppers, right? They have few switching frequency range. So low frequency choppers typically use uncontrolled diodes and simpler design, or we can use SCRs as well. So low frequency diode can work very well in low frequency. Now high power rating choppers require sophisticated components like inverter grade SCRs, IGSCRs with switching frequencies around 2 kHz. Now for low frequency it is fine, we can use diode or any other thing, right? But for high frequency, why do we use diode? Diodes are here, right? Diodes are used here, not here. Chopper will be a switch only, control switch only. Now these are the main important points, that if I have a high power rating, right? If I have a high power rating, which device can be used in high power rating situations. We have done this from rectifier. We use SCRs. In 3-phase there is very high power rating, so that's why we use SCR. So SCR we use. So SCRs if we use, right? Here as well, if there is some high power rating requirement, so we will use SCRs, inverter gate SCRs. They are known why? Because we are using them at higher frequency as well, 2 kHz frequency as well. So that is the reasoning behind inverter gate, because inverter means at inverter, right, we use very high switching frequency. Once we will study inverter, there we will know. So there we need to use inverter gate SCRs because we use this around 2 kHz frequency. Next, since SCRs are semi-controlled devices, DC to DC converters using SCRs required force commutation circuits to turn them off as natural commutation is absent. Okay, so since SCRs are semi-controlled devices, DC to DC converters using SCRs require force commutation, because right here, right, I need to turn this off as well. Now here there is no AC is present to naturally commutate this switch, so I need force commutation. So we'll study about force commutation circuitry as well after finishing the choppers. Okay, don't worry about commutation right now. We'll study about force commutation circuit after this chopper is finished. And why our SCRs doesn't naturally commutate? The reason is no AC present, no AC, right? No alternating current present, just like DC is present. Another thing is medium switching frequency choppers are designed for just hold on, this I need to. Medium switching frequency choppers are designed for moderate power ratings, typically operate in the range of less than 10 kHz. So as I increase my switching frequency, right, I cannot support very high power ratings, because in those cases, right, I have to use GTO, IGBT, BJT, all those high frequency devices, and those are not very good in terms of power rating. So obviously as switching frequency increases, something has to reduce, and that is the power rating. Next, high switching frequency choppers are suitable for high power rate. Okay, just hold on. This point is wrong actually here, right? This should not be present, just this should be present. That typically for high frequency choppers, right, we use MOSFETs. So these type of divisions can also come. So remember, just keep this in your mind. For high frequency applications, very high frequency applications, we'll always use MOSFETs. MOSFETs are very good actually for high switching frequency applications, because switching happens very fast there. We have learned this in the device physics part. Then for medium frequency applications, we use GTO, IGBT or BJT, and for low frequency applications or for high power rating applications, we use SCR. So these, right, you can put in your short notes. What do you need to put in your short notes? Just low, high, medium frequency, low, high, medium power ratings. These are the things that you need to put in your short notes. Okay, else you will forget all this. Like I've already explained to you what are the device physics and all. So these are the few points. Now let's come to the types of choppers. So choppers is also called a DC transformer. Why? Because in AC, what do? We just simply convert the level of voltages and currents. Right? So that is why chopper is also called a DC transformer. A chopper may be designed with respect to what? A chopper may be designed with respect to their voltage levels. What voltage levels they are actually doing. So whether at the output, the average voltage level, is it lower than the input voltage, or is it higher than the input voltage, or is it or we can do the both. So according to that, we can actually design a chopper. So first thing is step down chopper. This is the most basic chopper, or this is also called buck converter. It is also called as a current boost chopper, because current actually increases but the voltage reduces, or step current converter. Okay, so these are just name. Just go through them once and just keep these things in your mind. So the standard relationship for a buck converter, right, step down chopper, is that this is the most important relationship that you should know. What is it? It is VO upon VS. VO upon VS equals to IS upon IO equals to alpha. V upon Vs equals to Is upon Io equals to alpha, right? So alpha is T1 upon T. Alpha is T1 upon T. So basically here what I can say is that what is happening. So alpha, I told you, right? Alpha is between 0 to 1. So if I multiply Vs on that side, I see Vo is equals to alpha into Vs, that I derived just 2-3 slides back. So alpha is always between 0 to 1. So our Vo will always be less than less than Vs. So hence it will be a step down chopper. Next, like here I have mentioned, Vo is always less than Vs. But this current relationship, this also I will derive when we will analyze the step down chopper. This one, right? This here the opposite will happen. So just like transformer, if you remember, just like transformer, in transformer what used to happen, if the voltage is reducing, right, current will increase, okay, as to make the power rating same on the primary and the secondary. Main power like kVA same at the primary and secondary, right? So that is the same thing that we're doing here. So as voltage reduces, the current will increase, okay. Alpha is between 0 to 1. And like for ideal converter, if there is no switching losses, main important is if the converter is ideal, that means there is no switching losses, okay. So this is what my ideal converter is, and this is basically the chopper block diagram. This I've explained. According to the alpha duty cycle, I can make my output equals to Vs or it is equals to 0. So all these things are there. Now like the next division is step up chopper or a boost converter. So what does boost mean? It is boosting the voltage. So here obviously we'll use a different, like construction will be different, components will be same, but how they are placed, right? You have to understand how they are placed. So what better I could have done is I could have actually pasted here the circuit diagrams as well. So I will do that and then I will come back. Yeah, I added the circuit diagram. So for a for a buck converter, right, for a step down converter, what will happen is the inductor will be on the load side, and okay, I haven't drawn the filters yet, but the filters will be somewhat like this here. We'll see. So for a buck converter, right, you just remember the switch and diode positions. The switch will directly be connected across the supply, okay. And for a boost converter, like this is the equation relation. We'll obviously derive all this, don't worry, just giving you overview what we will study. For a boost converter, this is the equations, and here, right, basically the switch will be actually in the parallel and inductor will be actually connected with the source. The reasoning I will explain when we will do the analysis part. Then for a buck boost converter, we can obviously increase the voltage and reduce the voltage as well in a buck boost converter. So in this case, right, what we will do is, in this case, basically my inductor will be actually parallel to the converter and the switch will be directly connected across the supply. All this we'll analyze, don't worry. And like relationship, you can see all these things. So if my alpha is not less than, if alpha is less than 0.5, okay, because the formula comes out to be something like this, V upon Vs is 0.5. So if my alpha is less than 0.5, what will happen? This will be 0.5, let's say 0.4, right? This is 0.4 and this is 0.6. Then this will be 4.6, right? This will be 4, this will be 4 by 6, which is 2 by 3, which is what is it? 2, 3, 1.67. So obviously my VO is actually less than Vs, as VO is equals to 0.67 into Vs. Now what about this? If my alpha is greater than 0.5, let's say this is alpha is 0.6, so this is 0.6, right? So at the top I have 0.6, at the bottom I have 0.4, so this will be 3 by 2, 1.5. So my VO will be greater than Vs if my alpha is greater than 0.5. Obviously both of them, like alpha has to lie within this range 0 and 1, but there is a middle point as well where the value of VO depends upon Vs as well. So this is the thing about buck boost converter. All this is we'll analyze. It's just I'm giving you an overview, okay. And what other things we have? So chopper, right, we can analyze it in 3 different zones. First one is the supply zone, then we have the converter, then we have the load zone, right? Obviously next another thing is that filter. So we'll analyze it like this. The analysis of chopper will be in this sequence: supply, converter zone and load zone, and obviously the filters. Now our Vs, right, just like our AC supply when we were studying rectifiers, our Vs will be an independent ideal DC volt source, and it will not, like the Vs value will be constant. It will not depend on the circuit conditions and all those things. So Vs value will be independent of anything, but Is, right, the source current will be dependent quantity and it will depend on the circuit configuration and all the other things. So what will be supply power? Supply power, PS is equals to Vs into Is average. PS is equals to Vs into Is average, and my Vs is actually constant, okay. In this case Vs is constant. Now our supply power actually, how do I find out this is just a DC, right? This is DC power. and like why does this formula came up? Our Vh is constant. And what is supply power? Supply power, if you remember, what is like power anyways? Power, if you remember, it is integration of V of t into I of t. So if any one of them become constant, right, what will happen? I can take that outside of the integration. So our voltage of this supply, right, is constant. It is independent quantity. So I can take the Vs outside. It is basically integration of I of t divided by t is also there. Integration of I of t divided by t, which is basically IO average. Which is basically IO average, right? So that's why I write here, this is IS average, not IO, sorry, IS average, right? So that's why I write here Vs into IS average as the supply voltage source is DC. So it will be basically IS average. Now converter zone. Converter zone is what, like this was a supply zone, then converter zone. Converter zone, mainly we talk about switching frequency and all those things. The switching frequency is the rate at which the chopper is switches on and off to generate the output voltage. So the rate at which the chopper is turned on and off. So then the frequency is referred to as the chopper frequency also. In general, chopper or switching frequencies are high to ensure efficient application. I will show you why we need high switching frequency. Passive components like inductors and capacitors may not perform low switching frequencies, because if I reduce my switching frequency, right, you will see the like purpose of putting capacitor and inductors was to reduce ripples. So they are not actually able to reduce the ripples. The performance I'm getting is same only if I put inductors or not. So for those particular reasons, my switching frequency must be high. We'll take the examples there also, we'll see. So what is the formula switching frequency? Basically the formula switching frequency, F switching, is basically 1 by time period. Okay, F switching is basically 1 by time period. Okay, so why do we actually need here high switching frequency? Because we are charging the source, right, and we are discharging as well. So it like our passive components won't act as source for longer duration of time. So that's why my switching frequency needs to be very high. So the reasoning here is, basic reasoning here is, I will show you in the analysis part as well of when we will do the analysis. Passive components won't be able to act as source for longer duration. Okay, so this is the case for our switches. Now, like I have already told you about converter zone, there is this important parameter, that is delta. So these are the symbols that I explained there as well. So alpha is T on by T, but T on is the conduction period of the main power electronic devices, or I can say switches, and T is the switching time period. And our T, right, I can divide it into two parts. One is this T on, and another one, this distance is T on, and this distance is T off. Okay, so obviously T1 plus T off will be total switching time period, and T1 you can write it like as alpha into T as well, and T off you can write. So this, right, this portion will be basically 1 minus alpha. Okay, so you can write it as 1 minus alpha into T, or you can derive as well. So what you can do here, this is T minus T alpha into T. So alpha into T is T1, so T1 plus T is equals to T1 plus T off is equals to capital T, and from there you can like do the back calculation or the back derivation. Okay, so all these things are there. Next, let's go to the another few things. So in the converter zone, we generally assume that our device, right, switching device is basically basically totally ideal, but it may not be ideal. So we can replace our power electronic device with R on and V on. Okay, voltage on on resistance. Another thing is that we generally use a power diode while designing a chopper. We generally we also use, like obviously we use switching devices, like control switching devices. We use we also with controlled devices, we generally use a power diode for designing chopper. Why do we use power diode? Just for this specific reason explained here, right? My inductor current needs to be continuous. And due to that reason, here is I have already switching device, control switching device, but I use a diode as well just for the freewheeling action, so that when the switch is off, the inductor can discharge through this path. So here this will cause freewheeling action. Freewheeling action, due to the freewheeling action, or I can say discharge of inductor. Okay, so this is the case basically. And our conduction loss, if the switch, a practical power electronic device in a conduction mode, can be represented like this, and the conduction loss we already know. So I'm not giving this much more emphasis because we already know all these things. We have learned this in switches itself. So just giving you a bit of revision. Chopper, right, will go smoothly. Everything you will be able to understand very smoothly, and you will be able to solve the questions as well. Don't worry. Now load analysis. What load can I get? I can get resistive load, RL, RLE, LE, RE, load power, right? There is a bit of problem here. So load power in this case will be actually VO average into IO average. VO average into IO average. Why is this the case? I couldn't get a good explanation for this. It would not be basically that resistive IO RMS whole square and that. So if you are able to find out the reason, right, I will go through next slides as well. There will see actually our output power comes out to be this instead of IO RMS R square plus E. If I have a RE load, right? Why does it come like just? I found out one reasoning is that my input power is total DC. Input power is DC. Hence output power will also be DC. This is the only reasoning I was able to find out, but I was not able to find out why this is happening, that my load power is VO average into IO average. Then volt second balance criteria. PL is equals to 0 watts and VL will be 0 volts. So VL average will be 0. Overall average voltage across the cycle, right, will be 0. That all these things we know. And current second or AM second balance criteria. So AM second balance criteria is what basically when you use the capacitive filter, right? So the basically average current through the capacitor will be 0 at steady state, and our conduction loss will be 0 watts. All these things will be there. So one important thing that I wanted to share with you is that this waveform. So this waveform, right, this will be the inductor current waveform. This waveform we will see multiple times next. So I want to establish few things about this waveform. If you have studied signals and systems, then you can follow the derivation. If you haven't studied signals and systems, skip the derivation, just remember the formula. Okay, so these point I need to make. So in up here, right, I wanted to find out about there is a current through the inductor. The waveform is something like this, just like it is increasing and reducing. This is showing more ripple, but in all honesty, our inductor current will be something like this. Right? So then what I can do is I need to find out this following parameters about this inductor current. What are the following parameters? First of all, I have IL max and IL min. Then this is delta IL, right? So basically the peak to peak ripple. So delta IL is also known as peak to peak ripple. Peak to peak ripple. Okay, then what I can say is then I can say delta IL2 and delta IL1. Okay, delta IL1 and delta IL2. So what is delta IL1? Basically, right, it is a difference from the average like this is actually IL average, right? This is IL average. This point, this yellow line is IL average, and IL RMS will be higher than IL average. You know this, right? RMS value is always somewhat higher than the average value. So like the distance from average to the maximum value is what? IL max minus IL average. That is, okay, this is wrong. This is like, this should be delta 1. IL max from this is RMS only, so this is not the case, this is the case. Okay. So the difference from the average to the maximum is delta L1. Okay, and the difference from the minimum to the average is delta L2. Obviously delta L1 and delta L2 will be same only. I will just explain all those things just as we move along. So first of all, what is delta L? How can I write delta L? Delta L is basically IL max minus IL min. Okay, so they have, first of all, they have asked me to find out IL average. So delta L is the amplitude of this particular triangle, this triangle, right? This triangle has the amplitude of delta IL. Okay, but how do you find out average? So first of all, what is the average? So I need to find out the area between 0 to t. What is the area? The area of this triangle and area of this rectangle. So IL average is equals to delta L into basically this, what is the full length, like what is the width of the triangle? It is t, and obviously I have to multiply half as well, so delta into t by 2 plus, what is this? This is basically this, right? This is IL minimum into t. Divided by what is this, capital T, right? This will be capital T. So this will be equals to, well, actually this, right? This will be basically delta IL by 2 plus IL minimum. You could have written this in terms of this maximum as well, IL maximum as well. So what will your formula become? So your formula, right, it will become basically like you can say for the IL, what is IL minimum? IL minimum will be basically IL average minus delta IL by 2, and IL maximum, similarly IL maximum will also be just half. IL maximum will be IL average plus delta IL by 2. Okay, delta IL by 2. Okay, so this is my IL minimum and IL maximum. What about the other things? So what is delta IL? Delta IL 1 is basically the difference between IL average and IL minimum. Okay, so like the difference between, IL average and IL minimum. Delta IL1 is this, and what is that? Basically that is delta IL by 2. So our delta IL1 will be equals to delta IL by 2, and similarly our delta IL2 will also be this delta IL by 2 only, right? So these are all the things, IL max, IL mean formula I have got. Another important is I have written IL RMS, right? How do you find out IL RMS in terms of max and min? So obviously like here I have written the things here. The basic thing what you can do is you can write this like this has different slope and this has also different slope, right? So you can write the equation of this in terms of t. Now this is not omega t, right? This is simply t Okay, simple t. And then you can simply integrate from integrate the square of this between 0 to capital T and divided by t, and then take the under root. So all these things you can do, right? But this will be very difficult. Okay, what if I tell you you can have a formula for finding the ILRMS, because they can ask. It's very rare they can ask, but they can ask from here as well sometime. So what I have done, if you have studied signals and systems, please you can understand this. If you haven't, just directly remember the formula. I will tell you what is the formula. The formula, basically, what I can break this down, break this like just this period up until t on, right? I can break this as a sum of a triangle and a rectangle. So I have a triangle and a rectangle. I have broken this down. So our signal x dash of t is basically x1 of t plus x2 of t. What is x1 of t? x1 of t is this, x2 of t is this, right? And another thing I will do, I just multiply these two signals and I will paste it here. Why am I doing all this? If I have studied signals or systems, if I have to if a signal is sum of two other signals, right, and they are not orthogonal. If they are orthogonal, things become very simple. But if they are not orthogonal, I can write the energy of the signal as sum of energy of the first signal, sum of energy of the second signal, and the common area between x1 and x2. If they are orthogonal, the common area will go to 0. If they are not orthogonal, the common area won't go to 0, right? So this will be the energy of x dash of t. So energy of x dash of t, what is the energy of the first triangle? So the energy of the first triangle is very simple. Height is this delta L, and basically this is the half width, right? Half width is t on, so that's fine. This is t on, and yeah, that's basically it, right? By 3, they will be by 3, because this is just, I'm just computing the energy of the half sided, so it will be 1 by 3 only. If it was double, it would have been 2 by 3. Then area of a rectangle, energy of a rectangle is very simple. That is IL minimum whole square into T on, basically. And the area of this, what is the area of this? Simple, half into base into height. So this will be half into IL minimum into delta L into height. Into width is T on, and there is obviously a 2 here, so that 2 and this half gets cancelled, and I'm just left with this IL minimum, delta L, and T on. And obviously I can take the T on common. If I take the T on common, what will happen? If I take the T on common, that will be basically this energy signal, right? So yeah, next, what is this? This basically, right, this basically is x3 of t and x4 of t. So I just wrote down the remaining half portion from t on to t. So from t on to t, again I will do the same thing. Again I will find the energy, and as this x double dash of t and x dash of t, right, they are both orthogonal. Why? Because from here I have this signal present, the other part is 0, and for x dash of t I have this signal present over here, and the other part is 0 basically. So these two parts are 0, so I can obviously compute my energy like this, and energy of x double dash of t is the same procedure I followed. And then if I simply add, because x dash of t, how can I simply add? Because x dash of t and x double dash of t are basically simply orthogonal. Okay, why am I not writing down the proofs and all in front of you? Because not that important though this is, to be honest, just revising your signals concept, right? So energy of x of t will be simply x dash of t and x, summation of x dash of t and x double dash of t. So what is my x of t? X of t, right, is x dash of t plus x double dash of t. Okay, then what is p? P is equals to e by t. So basically I will divide by the total time period. What is the total time period? If I divide by the total time period, right, so what will happen is this actually will become T on plus T off, because the first part is multiplied by T on, the second part will be multiplied by T off. So this part will actually become T on plus divided by t. Okay, t on plus t off divided by t. This is my power actually. So I got my power, and what is the RMS value? Just the under root of the power. So if I take the under root, what will happen? This TT will get cancelled, and I will only be left with this. So if I take the del IL whole square, if I expand it, what is del IL? Del IL is IL max minus IL min. So if I expand it and write it in some other form, so I will get my final form as this, and it is recommended that you remember this. So you can put this in short notes, and it is very easy to remember. How to remember? Basically the RMS of a triangular waveform, right? How it will be if it is basically not starting from 0, if it is starting from some constant value IL minimum, and it is ending at the same point. So it will be basically IL maximum whole square plus IL minimum whole square plus IL maximum into IL minimum divided by 3. Okay, so it is IL maximum whole square plus IL minimum whole square plus IL max into IL min divided by 3, and I take the whole under root of that. Okay, that will be my RMS value. That will be my RMS value. Okay, so these few prerequisites that you need to go through before obviously starting our first chopper, that is step down chopper. So we'll actually start our first chopper, that is step down chopper. So this is the step down chopper with pure resistive load, and first of all just need to clarify that our complete time period will be t on plus t off, and it is an ideal chopper. So PED is ideal, like the PED means what? Power electronic device is ideal. Okay, no losses. Ideal means no losses. Obviously in practical life there will be losses, but ideally there won't be any loss. So in case 1, as soon as I turn the switch on, right, so as soon as I trigger the switch on, because this right hand side is 0 voltage and this left hand side is basically plus Vs, so obviously it is in forward blocking mode, and as it is in forward blocking mode, I can trigger the SCR anytime I want. I trigger the SCR at t equals to 0, then it turned on. Then what does my output voltage become? Output voltage VO, right, will be directly equals to Vs, and my chopper voltage VCS will be 0 volts. What will be the current? Current is same, right? Everything is in series, so current is same. It will be IS equals to ICS CH equals to basically VO by R, right? Or I can write this as IO equals to VO by R equals to, what is VO? VO is simply Vs. VO is simply Vs. Vs by R. Okay. So IS, ICS, IO is equals to VO by R, and this is Vs by R. So all these things are simple because I have a pure resistive load. And what is happening after that? So important point is I turn off the chopper. So here, right, actually switch is closed, and here I turn it off. So chopper is off. I will say chopper is forcefully commutated off. Okay, so I use forced commutation. So chopper off. How do I turn off the chopper? Because it is still in the forward blocking mode, right? So I use forced commutation. There is no natural 0, so I have to use forced commutation after, like at some time t on, where the chopper will be off. So when the chopper is off, right, so current becomes 0. So my IS is equals to IL. There is no IL, sorry, I did IL previously. No, the chopper current is equals to the chopper current is equals to the output current is simply 0 amperes, right? Why is it 0 amperes? Because there is no current flowing through it. Then next is what? Then the VO is also 0 volts because there is no current flowing through, so the drop across the resistor will also be 0 volts, right? What is VCH? VCH will be simply, on the left hand side I have Vs, on the right hand side I have 0 volts, so VCH will be plus Vs, so it is in the forward blocking mode again. A triggering angle will come in the next cycle, and that will again turn everything, all the devices on. So what are the waveforms? Basically very simple. Chopper waveforms are very simple. So here input voltage Vs is always constant no matter what, but the output voltage, right, when my chopper is on, I'm getting plus Vs, so this value is plus Vs. Yes, this value is plus Vs, and then when it is off it is simply 0 volts. Then again when it is on it is plus Vs, and then when it is off it is simply 0 volts, and it is going on like that. So what is my IO current? What is my IO current? IO current is simply Vs by R. IO current is Vs by R, right? Why? When it is on, so my output voltage is Vs, and obviously that if I divide it by R, I will get the current. So same as the output voltage, what will be the chopper voltage? Right? When it is on, it will give out 0 voltage. So here I have also written, I think, VCS is 0. When it is off, right, so it will totally block the forward voltage, that is Vs. This value is Vs because on the right hand side, on the cathode of the chopper, we have 0 potential as the current across the resistor is 0. So this is Vs. Okay, So yeah, this is a voltage and average voltage. I've already proved it to you how does the average voltage come, V into T on by T, which is V alpha. IO average will be same, right? It will be simply V average upon R. So you can derive that, and our this time, right? For this case, IO is equals to IS equal to ICS. For the next few cases, that may not be true, right? So you have to take care of that as well. RMS, what will the RMS? So here, right, how to compute the RMS? So only for this one I will show you basically how you are computing the RMS. Here, right, what I do is, what is RMS? Basically it is the square of the it is a square of the waveform, some of the squares of the waveform, then I take the mean of it, then I take the under root. So what I do, under root is all outside, and what is the mean? Mean is 1 by T, and I sum the squares of it. So what is the squares of it? So from this T on to T, right, it is always 0. From this T on to T, it is always 0. From this 0 to T on, it is always Vs. I'm talking about the voltage. It is always Vs. So if I square it, simple, it will be Vs square, but the shape will be same, right? Shape will be simply rectangle only. So this will be Vs square, constant Vs square, and dt going from 0 to T on. Except 0 to T on, right, it is always 0. Output voltage is always 0. So obviously, what will this become? This will, right? I'll just quickly do one thing. Reduce the size here. So this will be equals to what? This will be basically Vs square. So I can take the Vs outside, and it is under root of T on, because Vs square is constant, T on upon T under root, right? What is T on upon T? It is alpha. So that's why I gave this comes up like this. So these are basic things. If you have studied signals, you will be able to solve this in seconds. Simple integration and stuff, right? IS RMS also will be the same thing only. It follows the output voltage only. So it will be 0 for the T off period, and it will be on period for the T on period. So obviously that's why we're getting our voltages something like this, and all these are same. Chopper current and all these are same. Just here, right, if a converter is not ideal, our output power will be PS minus PO. Don't use the output power VO average into IO average. That may trick you, okay, because I have not been able to find out a good explanation for the output power expression. What is VO average into IO average? I have to study more. I don't know if you are able to find out a good explanation why our output power expression is VO average into IO average. I will just show you one explanation. I will show you just in the summary part, just once we go through this. So here, what is the analysis of supply? This was the analysis of load. Analysis of supply is as my load voltage is constant, so obviously the supply power will be Vs into Is average always, okay, as Vs is constant. Now we directly go to the analysis of chopper. So chopper, right, what is the average voltage? So here, instead of T on, this will be T off. Why this will be T off? Because my chopper voltage is blocking the forward voltage in the duration of T off period. So that's why this will be V into T off divided by T. So this is V into 1 minus alpha into T divided by T, okay, which is equals to V into 1 minus alpha. That's it. That simple thing is there. And VCH RMS. VCH RMS is what? VCH RMS is equals to V into 1 minus alpha 1 by 2. Okay, so this is my VCH RMS. Basically I take the under root. Same reasons as the previous derivation, right? You can derive for yourself. All this you try to derive by yourself. Chopper efficiency, these things you should know, is basically output power minus input power. So what I do is I find out output power through this formula. So use this formula. Don't use the other formula, right, which I told you, VO into IO average. We may use that formula, but I will just not recommend it. Use this. Why? Because if I subtract the losses from the input power, whatever I get back, right, it's basically the output power only. So that is my chopper efficiency. And efficiency of chopper will not give us any information about the ripple component present at the output. Why? Because here, right, we are not talking about this PDC upon PS, right, or PDC upon PO. Okay, we're not talking about that. We're only talking about the output power and the input power, PO upon DC, and it may have ripple components. All those things it may have. So I'm not able to comment about the ripple content present at the output. Efficiency of chopper simply gives us information about losses in converter. Efficiency of chopper simply gives us information about losses in converter. So what does efficiency of chopper simply gives us information about losses in the converter. So yeah, simply just it gives us about these losses, whatever losses is present inside the converter due to the conversion process, that only it gives us. It doesn't give us any information about the ripple component. The efficiency of the chopper is generally more than 95%. So as this has no moving parts, as we are using electronic components, the efficiency is very, very high. So how do you analyze the ripples? So you analyze the ripples using the old formula. If you remember, right, our VOAC will be what? VO RMS whole square minus VO average. So this time RMS value will also come into the picture. Average value will also come into the picture. Why is this average? This average means basically this is VO DC, right? What is it? I'm just subtracting the DC part from the AC part. Then what is the voltage ripple factor? The voltage ripple factor is basically VOAC by VODC. Voltage ripple factor will be VOAC by VODC, which is equals to under root alpha VS whole square alpha VS minus 1. Okay, so yeah, under root alpha VS whole square divided by alpha VS minus 1. I know what is VOAC, I know what is VODC, right? I know what this VO RMS and this VO average. So that's why I just put it over here. Then your voltage ripple factor will come out to be like this. So don't need to remember, just know how to derive. Okay, no need to remember, just know how to derive all this thing. Okay, next what is happening? Next, input resistance is Rin equals to VSDC by ISDC, which is equals to R by alpha. So this is just a parameter. This is just a chopper parameter. What is a chopper parameter? Parameter is input resistance. So this is a fictitious, I will say here, fictitious resistance seen from source center. Okay, so if I see this from source end, like I can use anything, but as VSDC is the easiest one, so I will choose VSDC. And what is the resistance? The resistance is basically voltage upon current. Both of them need to be same type, so it is VSDC upon ISDC. So what is VSDC? VSDC is VS only. VSDC is VS only. It is always constant, right? What is ISDC? If you remember, or can I write it in terms of VO? What is V? Like VSDC equals to VO. So like what is VO here? VO, right, is basically this is VS, right? VS alpha. So what will be VS? VS will be basically VO upon alpha. VO average upon alpha. What is IS average? What is IS average? So IS average, right, basically is what? Okay, I need to go to the output current as well. So if you see here, use the same formula for IO as well. IO average will be VO average upon R. So I can write it here, right? It is VO average upon R. So not this is my IO average, and IO average is same as the source average as well, right? So it will be VO average upon R. VO average upon R. So what will happen here is, basically VO average will be cancelled, so R will go at the top, and this will be R by alpha. This will be R by alpha. So the value of the input resistance seen from the converter, seen from the like input supply side, is basically R by alpha. So actually that the resistance increases as I see from the source, and it makes sense, right? Basically what is happening? Basically we're using a voltage divider only indirectly. Okay, and there is no power loss. Using like without the like what is happening, I'm like the resistance, input resistance seen from the voltage source is more, hence it is reducing the voltage drop across the output resistance, and without any power loss, because there is no actual resistance present. All these are like electronic components and passive components. Like switches obviously has an active component present to it, the commutation circuit, except that. Okay, so I hope you understand that the input resistance has increased now. So like we have few questions here, so what you can do is we can solve few questions. These are pretty simple and easy questions. Okay, so let's solve this first question. What I will do, I will give you the screenshots. You take the screenshots and try to attempt it by yourself. This is the second, and this is the third question. I think these were the only questions. Okay, we have a fourth question as well. This is the fourth question, and that's it. You can take the screenshot, type for yourself, and I will come back with the solutions. Let's start with this second question. So here, right, if switching frequency of the chopper is 1 kHz, so they have given us the switching frequency, and the on time of the switch is 0.5 milliseconds. So what is switching frequency? Basically F switch, right? F switch is 1 kHz. can I write this in terms of time? Yes, I can. So what is time? Time period of the switching is basically 1 by f switch. So here this is 1 by 1 kilohertz. So 1 by 1 milliseconds. So this will be 1 milliseconds. And like this is our switching time period, right? But what is our T on time is 0.5 milliseconds on time, and you can cross verify as well. Your on time can never be greater than T switching time period of the switching. Obviously then you have done something wrong. So on time is 0.5 milliseconds. So if your on time is 0.5 milliseconds, right? So basically our T on upon T is basically 0.5 milliseconds upon 1, which is basically alpha, which is basically 0.5, which is basically alpha, right? It's basically alpha. Okay. So that is the case over here. So what is my average output voltage? What is my average output voltage? My average output voltage is basically what? If the switch is present like this, so I can draw the waveforms, but you already know, right? When the switch is present, my voltage will be basically Vs, and when the switch is not present, my voltage will be 0. So I can roughly draw the waveform. So it will be VO. So this will be Vs, this will be T on, into T. Okay. So this is Vs 0 and T on T, and this will go along like that. Okay, this will go along like that. So this will be Vs, like what is my V average? V average equals to Vs into T on divided by capital T. So this is alpha Vs, and we know what is alpha. Alpha is 0.5, and what is Vs? The input voltage. Input voltage is basically 100 volts, right? Input voltage is 100 volts into 100. So this will be 50 volts. Output voltage, average output voltage will be 50 volts. Now what else they have asked? They have asked us to find the RMS output voltage. Simple, right? The RMS output voltage, you can remember the formula. Like there is nothing to remember over here. So your VO RMS will be just whenever we are finding under root, like whenever we are finding RMS, right? So we have to under root this thing. So if as I am squaring, I have to take the under root as well. So the time period gets under rooted, right? That is the only issue. So here this will be Vs only 100 only, and under root of alpha, which is 0.5. So if I take 50 into under root of 0.5, what answer do I get? So this will be 0.5 under root into 100. So this will be 70.71 volts. Okay. 70.71 volts. Okay, next what else is there? Next basically then average voltage across the chopper. So the average voltage across the chopper will be what? It will basically be the opposite, right? When this input is on, then chopper voltage will be 0. When this input is off, then the chopper voltage will be totally Vs, because current through the R is simply 0. So my VCH average will just be the opposite. What is it? It is 1 minus alpha into Vs. So I have derived this as well there. Okay, it is basically what? It is basically T of Vs into T of, and what is T of? T of by T. So what is T of? T of is 1 minus alpha. T of by T is 1 minus alpha. So this will be 100 into 1 minus alpha into 0.5. So this will be 50 volts. Okay, this will be 50 volts. What about other, like this is a V, like chopper average voltage, right? Chopper average voltage. Okay, chopper average voltage, this is 50 volt basically. And then RMS chopper voltage, just the under root, right? Just it will just the under root of this. So VCH RMS will be under root like Vs into under root of 1 minus alpha. This case, right, 1 minus alpha and alpha are same, so it will be same as the RMS of the output voltage as well, which is 70.71 volts. What is efficiency of the chopper? Efficiency of the chopper will be 100% as nothing is said about losses, right? This is, I will assume this as ideal switch, so efficiency is 100%. Assume ideal switch as nothing mentioned. Okay, next, average source current. What is the average source current? So the average source current, right, what I can write is like this. So average source current, average output current, all those things are same. So average source current is actually IS average is basically IO average. And what is IO average? It is basically VO average by R, right? Because I have a resistive load only. So VO average is what? VO average is basically 50 by 10, which is 5 amperes. So your average current, right? Average current of the supply of the source will be simply 5 amperes. What about the RMS current? Next, I think they are asking us the no, not RMS current, maximum chopper current. What is the maximum chopper current? How do you find out maximum chopper current? When the current, right? When IO is maximum. So ICH maximum. Have I written the RMS value of the current? No, I have forgotten to write the RMS. So we have to find out the RMS as well. So RMS of source current also I will write down here. RMS source current. So how do you find out RMS source current? Same thing, right? It's under root, because everything else other than the period for which it is on, it is basically okay. So like it is 0 basically. For if it is off, then the IO is 0. When the switch is off, right, IO is 0. So our IC, I will do this later. I will first do IS RMS. What is IS RMS? IS RMS is basically equals to IO RMS, which is basically equals to what? Which is basically VO RMS by R, right? As there is a single component only. What is VO RMS? It is basically alpha under root alpha into 100, that is 70.70. So 70.71 by 10, it is 7.07 amperes. amperes. Okay, so this is basically the current. This is basically the IS RMS current, right? Next is maximum. What is the maximum chopper current? Maximum, like we need to know about the ratings and or we need to decide on the ratings, right? That's why we need these parameters. Maximum chopper current. Just hold on a second. Let me check if everything. Yeah, everything is recording. So ICH max, right, will be when what? Basically, whenever this switch is closed, right, some constant current is flowing, and that is the maximum current only, because average current will be lower, because for some periods, certain periods, it is the maximum current. For certain periods, the current is totally 0. Okay, so my average current will be something in between the maximum and the 0, and my maximum current will be when the switch is on. So when the switch is on, what current do I get? I get totally VS by R, right? VS by R. This is the maximum amount of current. So Vs is 100 by R is 10. So this will be 10 amps of current. You can observe, as for 50% of the time my switch is on, that's why my average current comes out to be 5 amperes. That is a 50% of this 10 amperes, and the maximum current that the chopper has to pass, right, is 10 amperes, right? So it has to pass this. So accordingly, I will choose my rating of the chopper. So this is the maximum chopper current. Next is what? Input resistance seen by the source. So input resistance seen by the source is what? So Rin will be basically Vs by Vs is a DC quantity. So it will be Vs by Is average. What do I know about Vs? Like I have found out Is average here. From I can do it like that also. I can derive the formula as well. So what is Is average? Is average is simply VO average by R. And what is VO average? Alpha into Vs. So Vs by alpha into Vs divided by R equals to this. So this is R divided by alpha. Okay. So this is R divided by alpha. So what is R basically? R is 10, alpha is 0.5. So it will double. Just the resistance, whatever the source has seen, right? It has doubled actually. On an average, the resistance seen by the source is double. This is just a parameter. This is not actual resistance. There is no physical significance. This is fictitious, right? Now what next they are asking? They are asking about us the okay. They haven't asked us the power. So I need to ask about the power as well. Load power. So how do we find out load power? Actually, one interesting point is here, right? As my chopper is 100%, like chopper has 100% efficiency, it is ideal. So my PS will be equals to PO. PS will be equals to PO, right? Whatever load has consumed, that will be supplied by only by the supply. None other elements will absorb that supply power. So actually, what is happening here is that what is my PO actually? How do I write my PO? So PO, I am not writing it specifically. What I will do is I do this. So what I know this relationship, right? So from here I can justify how my output power is coming as VO average into IO average. So VO upon Vs for a step down chopper is equals to Is average upon, this is VO average, right? IO average equals to alpha. Now, so these quantities are same, right? Because the ratio is same. So that's why I can, if I cross multiply here, my Vs into IO average will be equals to VO average into IO average. So basically this, right? This is equals to what? This is actually, okay, this is not IO average, this is IS average, right? IS average. So this is equals to what? So Vs into Is average. So Vs into Is average is basically equals to the PS, right? Because only the battery can supply DC power. So this is PS. This quantity is equals to VO average into IO average. So hence, as this quantity is equals to VO average into IO average, and another thing I know that PS will be equals to PO for a ideal converter. Ideal converter. Hence, I can replace my PS here, right? I can replace my PS. Replace my PS here. Instead of PS, I can write PO. So, PO will be equals to VO average and IO average. So, this is the only explanation that I was able to find out, that my output power for a chopper, this is only valid for ideal choppers, right? Only valid for ideal choppers. Okay, so this is the output power basically, which is VO average into IO average, right? So yeah, that is the thing here. That is how you find out the load power. So what is the load power? Basically it is Vs average into Is average, or VO average into IO average. All those things we have computed. So our load power rate will be simply, I can use any of the formula. What is Vs average? 100. What is Is average? Is average is 5. So 100 into 5 will be simply 500 watts. So 100 into 5 will be 500 watts. Okay. Next another quantity is a voltage ripple factor. So voltage ripple factor is simply very easy. It is the amount of AC present on the DC. So ratio of VOAC by VO DC. Okay, so this will be VO RMS whole square minus VO square into DC divided by VODC. Basically VODC is what? It is basically average, right? Okay, under root. So this will be basically VO RMS whole square divided by VO average. So what will this value be? So this comes out to be 1 by alpha minus 1, right? So 1 by alpha is 2, so 2 minus 1. So 2 minus 1 is basically 100%. So if I want to write this in terms of percentage, either this will be 1 or 100%. So my ripple, right, is 100. So maximum ripple that I can get is, I believe it is 200 or something if alpha is very low. Okay, maximum ripple can be anything if alpha is very low, right? Maximum ripple can be anything, but the minimum ripple that I can get is if alpha is equals to 1. So at alpha equals to 1, I get minimum ripple, that is 0%. So this is also important point. At alpha equals to 1, I get minimum ripple. Why? Because it is constant DC, because my switch is never turning off, it is always on. So minimum ripple. Okay, so let's move on to the next question. This question is also pretty simple, but here, right, we have a RE load. So obviously we will not analyze RE load separately. I will just do the analysis here, RE load, and next slide, next class, we will do RL and RLE loads. So here a DC to DC converter provides a DC voltage at load of 80 volts. So they have told us that DC voltage at the load is 80 volts. So VO average okay, and duty cycle of converter is 0.5. Duty cycle of converter is 0.5. So duty cycle means alpha is 0.5, right? Alpha is 0.5, that is T on upon T. Find RMS, then find the RMS output voltage. So I need to find out the VO RMS. Okay, what will be the VO RMS? So first thing, right, they have provided me the duty cycle and the VO average as well. They provided two things here. So and the input voltage is also present, right? One thing I can do is, like, this is a step down chopper only, because step down chopper is very simple, just a simple switch, series switch is present. So here, can I use the formula? If I go with the formula and find the VO average, am I getting the same value? Because if I have only R load, I know the formula with only R load. Okay, only R load. What formula I know? The formula is that my VO average is equals to alpha into Vs. Okay, so what is my VO average? It is alpha into Vs, and alpha is what? Alpha is, in this case they have provided us 0.5. So Vs is what? Vs is 100. So it will be 50 volts. But actually they are talking in the question that I am getting more than this 80 volt. How is it possible? So if the switch is on, right, that voltage will always be equals to 100 volts. But when the switch is off, I assumed for a resistive load that voltage will be 0 as no current is flowing. But if I assume here a RE load, right, then things will change. How will things change? So if I assume here RE load, so let's take this value, let's take this switch itself, and let's change the things over here. So this will be okay. So this is the RE load. So here what will happen, if my switch is off, right? If my switch is off, what will happen? The output voltage will directly clamp onto E, because this current is 0. So drop across the resistor is 0, but output voltage will clamp onto E, not 0. Not 0. So the voltage waveform will something look like this. So average, right, will be shifted up. It will increase. Average will increase, obviously. So previously, if during the off time my voltage was 0, now during off time voltage is also some positive value. So the average voltage will also increase. And due to that reason only, the like here in the question they have given, the average voltage is more than the voltage that I was supposed to get if my alpha was 0.5 for a pure resistive load. So here, how do you compute the VU average? You don't need to remember formula. You can, but always you can derive. So in choppers, right, you can derive in 30 seconds. So what is my VU average for this waveform? So T by 2 is what? T by 2 is basically alpha into T, right? 0.5 into T. So VU average is basically, so this will be 100 into T by 2 plus E into T by 2, okay, divided by T. So this is the value of VU average. And like if you find it out, right, they have provided in the question itself what is VU average. VU average is 80 basically. VU average is 80. So if it is 80, I can write it like this, that my E, what value will be my E of? My E value will be basically, this will get divided and 50, that will get subtracted. Extra E value will be 30, right? E value will be 30. That will be my, okay, am I doing this correctly? Okay, I have E by 2 as well, right? Sorry, this is E by 2. It's 50, yeah. E will be, right? E will be basically 60 volts. Okay, this is the voltage that I will get. Now what have they asked us? They have asked us the RMS output voltage. So I need to find out the RMS of this. How do I find out the RMS? Same formula, just a different. So VU RMS, right? VU RMS will not be equals to that formula, under root alpha into VU average. Okay, I think it will be that formula only. Is it? No, it won't be. It won't be that formula. It won't be that formula, because why this won't be the case? Previously, how I was doing this, I was doing this because it was 0. Signals were orthogonal, okay? But here it was not 0, it is some value. So I have to take that into account as well, right? Not this, not under root alpha into V average, sorry, under root alpha into Vs. It will be not this, right? And like previously, this formula also got violated. This formula also got violated. So these two formulas I cannot use. So obviously, that's why I recommend you to basically derive, right? So it took you very less amount of time to derive. For this square waveform also I can easily find out the VU RMS. How? What will be the VU RMS? VU RMS will be simply this 100 square into T by 2 to the time period. 100 square into T by 2 plus E into E square E is going to T by 2 divided by T and the under root, okay? So this is basically, this will be what, now I know the value of E, right? So from this average condition I was able to find out the value of E, and that I will put in this equation. So this will become 100 square 10 raised to the 4 divided by 2 plus 60 square I have, right? So this will be 36 into 10 raised to the 2 I have divided by 2 as well, and whole under root. So I can take a like 10 square divided by 2 common. So this will be 10 by under root 2, because I am taking the under root as well. This will be 100 plus 36. So if I just compute this real quick, right? If I just compute this 100 plus 36 under root into 10 divided by under root 2, this will be 82.46. 82.46 4621 volts. VRMS is 82.462. So this will be the solution of this question. And what is the next question? A DC to DC converter operates at switching frequency of 1 kilohertz. A DC to DC converter operates at a switching frequency of 1 kilohertz and duty cycle is 0.8. Duty cycle is 0.8. During conduction, it provides turn on resistance and 1 ohm turn on voltage of 2 volts. Then find the efficiency of the chopper. DC to DC converter, what's the switching frequency of this? Okay, duty cycle is this, conduction, it provides turn on. Okay, now this is not a ideal. This is not an ideal chopper, right? Not ideal. Not ideal. So if this is not ideal, right, how do I solve it? How do I solve it? So case 1, I have to go by case and I have to obviously write down the results. So case 1, right, I will just replace when the chopper is on, I will replace it with its turn on resistance and turn on voltage, forward drop. So it has two things, turn on voltage and turn on resistance. Now what will be the current? So I'll go with the help of current. So what is the current? Current is same in everything, right? Current is same. So it is IS, IO, and the chopper current all are same. So IS equals to IO will be equal to simply how much? 100 divided by 100 minus 2, because here I have 2 volts as well, divided by 10 ohms. Okay. So this will be 98 by 10. Okay, 98 by 10 ohms. So that is ampere. So this will be 9.8 amperes. Okay, this will be 9.8 amperes. Next, about the T onto T, capital T. Next is the T onto capital T when the switch is off. When the switch is off, obviously there is no loss because current is 0. So my current will be 0. That is IO equals to IS equals to 0 amperes. Okay, current will be 0. So basically, what will this be? This will be the time, right? So my IO IS will be this, and my current waveform will be that like this. That is 9.8 amperes, and this will be 0.8 T and T2 1.8 to 2. Okay, so waveform will be something like this. As my duty cycle is this, right? Duty cycle they have provided us as 0.8. Okay, and switching frequency is 1 kilohertz. So what will be my time period here, right? My T will be what? T will be 1 by F switching is equals to 1 kilohertz. Okay, 1 kilohertz means simply it is 1 milliseconds. Okay, so yeah, that will be the case. Then find the efficiency of the chopper. So what will be the efficiency of the chopper? The efficiency of the chopper will be what? Efficiency of the chopper, I have told you, right? Efficiency of the chopper is basically, I will write down PS, the power what is supply is providing, minus losses. Basically it is PS minus PO by PS, and PO is PS minus losses, right? So we'll write it like this. So how do I compute losses? What is PS basically? What is PS? PS is VS into IS average. And I know the waveform of IS. Can I compute the average? Very surely, right? I can compute the average. So VS is 100 only, right? VS is 100, yeah. And what is my IS average? So IS average will be something like this: 9.8 into 0.8 T divided by T. So this will be this here. And 9. So what will be this value? 0.8, 9.8, and into 100, right? Into 100. So this value, right? This PS will be 784 watts. So our power supplied by the source is 784 watts, but all of it will reach the load? No, right? All of it will not reach the load. Why? Because there is some losses in between. So what is the losses? So our loss is something like this, that what are the losses? So loss you can compute. How can you compute the losses? So loss will be basically the loss here, right? What is the loss? It is basically IS, like as the chopper current is same only, or I can write it like this: ICH whole square into R plus V on into, this is R on actually, R on into V on into I CH average. So this is the loss across the device, right? This is the loss across the device. So if this is the loss across the device, what will be my power basically? So what is this is ICH RMS, right? ICH RMS. What is ICH RMS? Basically chopper current is the supply current only. So I can write it like this, that what is the RMS of this? RMS is very simple, right? RMS will be simply 9.8 whole square into 0.8 divided by T under root, and I'm taking the whole square of this. This is the RMS, right? Whole square into R on. R on is 1 ohms plus V on. V on is 2 into IS average. 2 into IS average. 2 into IS average. ICH average is what? ICH average is basically I have computed, right? What is I? Okay, I haven't computed. I will compute it. It is 9.8 into 9.8 into 0.8 T divided by T only. So what will be this value? Equals to 9.8 into 0.8. So this will be 7.84. Okay, 7.84. So this value is 7.84. I'll just quickly compute these things. This is 2 into 7.84 9.8 whole square into 0.8 and into 1 as well. I have to do 1 as well. So this is 76.832 plus 2 into 7.84. So plus 2 into 7.84. So this is equals to 92.5 watts. So now if I subtract this, right, this is the losses with the actual power that has been provided, that is 784. So it comes out to be 691.484, right? 691. So P loss, conduction loss is this, right? So what is my actually what is my output power? PO will be PS minus P conduction, which is comes out to be 691.488. So if I now find out the efficiency, what will be my efficiency? Efficiency will be basically PO by PS, which is equals to this 691.88 divided by PS. What is PS? PS is the supplied power, which is 784. Okay, 784. Now into 100 I will do percentage. So this value will be what? Divided by 784. This will be 88.2%. okay, so this efficiency will be 88.2%. So this will be the answer to this question. That's it for this lecture, and then in the next lecture we'll do the analysis for step down chopper with RL and RL. Hey everyone, and welcome back to PrepFusion. I'm Anish, and today we'll start the second lecture of choppers, basically DC to DC converters. So previous lecture was basically introduction, and we learned about step down choppers with pure resistive load. Okay, we didn't had any inductor or all those things. Now in this lecture we'll include inductors and RLE loads. So we'll analyze for both these cases and then see what changes it makes. Because previously what was happening was our current was not continuous and it was discontinuous, and we may not want that. One more thing is that previously I didn't had any like freewheeling diode type structure, right, in a step down chopper, and generally we don't use simple just R and simple this one switch in step down chopper. Obviously there are other elements as well. So other two elements, in case of other two elements, this is the diode that is present, and an indicator will also be present, okay, in any of the choppers. Let it be step down, step up, or step up down chopper. In any case, indicator and diode will always be present for providing in the path when the indicator has totally this switch has been turned off. Okay, so that's why that was for the understanding purpose, that was for the learning purpose. But obviously in practical life we don't use those type of choppers just with pure resistive and just with the switch. That is the simplest thing, right? So in RL load, what happens, we connect a diode anti-parallel. So basically what happens, it is a freewheeling diode. This diode provides a path when the switch is off, okay, provides a inductor can get a discharge path when the switch is off. That's why diode is essential for design of choppers. And while we will analyze, right, what assumptions we'll take, just same as rectifiers. That's why I'm going very smooth and very fast here, because all the basics have been cleared in rectified itself, right? Analysis part, this is easier actually, because we have done the tough analysis. So this thing should be cakewalk for you, this type of analysis. So assumption is IO is continuous. How is IO continuous? Basically this indicator, right, the amount it gets charged, and the discharge, right, discharge is very low, or you can say discharge is very low, so again it comes back to its next current. Okay, and yeah, power electronic devices ideal. So these two are assumptions. So from 0 to t on, what will happen, this switch will be turned off, and as this switch is turned off, right, so I have triggered this switch. As this power electronic device has been triggered, what will happen is this diode will be off. Why? Because if I just measure the voltage, so VD, right, VD will be what, VD will be what, VD will basically minus VO, or it is equals to minus VS, right? So it is negative. So obviously if this diode will be off. No matter what, diode will be off. What will be on? Power electronic device will be on, and my output voltage will be Vs. And one more thing is that initially I had assumed that my initial current, just this for the one transient, this is for the first cycle itself, and after that things will change. I will explain what things will change. Okay, just for one transient I will explain here, then I will come back to that transient. So if I am starting from 0, right, what will happen is that my IO 0 minus, or IL 0 minus will be equals to IL0 minus will basically equals to 0 amperes, right? Why? Because inductor would not try to change its current, as some impulse voltage is directly not getting applied here, right? So that it will keep its previous current. So what will be the voltage across the inductor? So VL0, right, will be basically, so this will be equals to IL0 plus voltage across the inductor you observe is this total Vs, right, will come across this, because no current is flowing, so all the drop, there will be no drop here, and all the voltage will come across this. So VL0 will be simply Vs. Okay, VL0 will be simply Vs. So which is basically positive. As it is positive, what will happen? As it is positive, my DIL by dt is positive, because V is equals to DIL by dt, and as it is positive, my IL, right, IL will increase, and power will flow from what? Power will flow from source to load. So power will flow like this. For power will flow from source to load. Okay, as this, due to this voltage source, this is energizing the inductor. Okay, and what will be the equation? Basically, what will be the equation of the current? So that is also another interesting fact. What will be the equation of the current? Just script this down. equation of current, this is simply what? A DC voltage source is connected, and this is simply RL circuit. So it will be simple transient equation. So what is the final value? Final value is Vs by R. It would try to reach to Vs by R. So my IL of T, or you can say Is of T, will be equals to Vs by R 1 minus e raised to power minus T upon tau. And what is tau? Tau is simply L by R. Tau is L by R. Okay, this will be the equation from 0 to T on, right? Then this is just a transient. I'm just explaining the converter in the transition zone. In steady state, right, things will be a bit different. I will explain that as well. And then in the next cycle, when T on, from T on to T, right? Because from T on, what is happening? I am force commutation what? Force commutation, the power electronic device. Okay, so I will forcefully commutate my power electronic device. Next, what is this? So if I forcefully commutate, right, this will be off, and as soon as this turns off, right, inductor wants the current to flow. So the current across the inductor will be some current, let's say IL of T on minus, which is not equal to 0, and the direction of current is something like this, right? So it will want to flow the current. Now here, right, this path is off, this is open circuit, this has only this path, this is the path. So it will obviously turn on the diode, and it will change its polarity. Inductor itself will change its polarity and turn on the diode. So D is on, and as the D is on, inductor will discharge. Basically inductor will discharge. So my current, chopper current, source current will be 0 in this period, but my diode current will be equals to my output current will be equals to what? It will follow again exponential relation. It has reached to, let's say, IL of T on value. I don't know what is the value, IL of T on, and then it decays, right? E raised to power minus T upon tau. Then it decays, and here, right, it will be T minus T on, because from T on we are starting. Okay, from T on we are starting. Now what next we will do is that it is discharging. Basically power is not flowing from load to source, but our VL this time, right, VL will be negative. Why it will be negative? You just simply apply KVL, you will see it will be negative. So our VL will be negative, hence our DIL by dt will be negative. DL by dt will be negative, hence our inductor is what? Inductor is actually de-energizing. Okay, inductor is actually de-energizing. Fine. So basically what is happening is that only due to the first cycle, my waveform will look something like this. So the waveform, right, if I just reduce the sizes a bit, waveform will be something like this. It will if I just directly start from the zeroth cycle, first cycle, so it will discharge totally from 0 to some voltage, then it will discharge, charge, discharge, charge. So after this, right, the cycle will be like this, right? So here, if I again do it in the steady state, now that was a transition zone just for the first few cycles. Then once we reach like 100 cycles after that, right, so basically my inductor will be inductor will have some already current IO minimum, because that is the minimum possible current it can go. Why? Because from 0 I am turning the switch on, before that switch is off, hence inductor was de-energizing through this diode. So it reached to some minimum value, then as soon as I turn on the switch, again the inductor will energize. As the inductor energizes, what will happen is the current will increase. Okay, that is the reason. So if I talk about steady state, everything will be same, that my VO will be equals to VS Okay, VO will be equals to VS. My V chopper will be equals to V 0 volts because it has turned on. My what will be the inductor voltage this time? Inductor voltage will not be directly equals to VS, but it will be something other than that. It will be VS minus VR, right? The whatever the voltage this resistor has, it is that voltage only. So what is the inductor voltage now? It is VL equals to VS minus IO minimum into R. This is the voltage right now. Okay. And of course, this will be something positive. We'll assume this will be something positive because my current will only increase from here. So if my VL is greater than 0, what will happen? My IL will increase, and as my IL increases, what will happen? My IO minimum basically my current increases, right? My current increases, and again what is the direction of the power flow? Direction of the power flow is from source to load. Power will flow from source to load. Okay, so yeah, this is basically the currents, and obviously the diode, this D will be off only. And in the next case, right, in the next case, what will happen is that this power electronic device will be turned off. This will be forcefully turned off, and again now inductor has current. The current has IO max because it was only charging only, so current was only increasing, and just as soon as this is turned off, right, so inductor will de-energize. As this will de-energize, the current will reduce. So current will reduce. As current reduces, my VO will be what? So this time my VO will be 0 volts. Why? Because this diode is turned on, short circuited, right? So this VO will be 0 volts. Chopper voltage will be same only. Chopper voltage won't change. VS, just the currents will change. VS, and my chopper current equals to source current will be 0 this time, right? And what else is there? So here, right, actually my this I didn't write the current expression. So current expression I will write. What is the current expression here? What will be the current expression? So that is IL of T equals to IO of T. What is the current expression? Equals to IS of T equals to, so steady state, what it tries to do, it at steady state obviously it again does the same only, VS by R. It wants to go to VS by R because this will be short circuited. So I will not explain the transient here. Transient you have studied in network theory. So it will steady state, it will go to VS by R, and it is starting from what? It is starting from IO minimum, right? It is starting from IO minimum. So what can I write? What things can I write? So steady state, this will go plus IO minimum minus VS by R e raised to power minus T upon tau. Okay, so this will be what? This will be VS by R 1 minus e raised to power minus T upon tau plus IO minimum. Basically at T equals to 0, this will get cancelled, only this will be remaining, and at T equals to infinity. Okay, anything I have done wrong over here? Wait, just over. Okay, actually, right. Oh yeah, this equation is correct only because this at steady state it will try to go to 0. Yeah, so here, right, like a steady state the value will be VS by R, but initially at T equals to 0 the value will be IO minimum. Now let's go to here, right. Here basically my source current, chopper current will be 0, but my diode current, which is equals to my output current, which is equals to my ILT. So this will have some equation. What equation it wants to have? So here, right, I will start with IO max. What is IO max? I don't know. At T equals to T on, whatever value I get will be IO max. So I will start from IO max, and I will obviously want to go to 0, right? Because like that is my assumption. At T equals to infinity, the circuit, if the circuit is like this only, I'll try to go to infinite 0, right? My current will try to go to 0. So it will be e raised to power minus T upon tau. So this will be the equation basically of the second half cycle, like second half, right? This will be the equation. Okay, one thing I made a mistake, but here, right, but from where I am starting from, that is also we have to take care of, right? So I am starting from IO minimum, right? I'm starting from IO minimum. So starting from IO minimum, okay, IO minimum. Here one thing I can do is VS by R to go to IO maximum. Yeah, starting from IO minimum, and I want to go towards 0 voltage, right? 0 current. So this will be minus T T minus T on actually. T minus T on divided by tau. Because why T minus T on? Because I'm starting from T on here, right? That's why everything is shifted. Everything is shifted now. IO minimum, because I'm starting from IO minimum. Not okay, sorry, not IO minimum, sorry, IO max. So that was correct only. That was correct only because I'm starting from IO max, not minimum. Sorry. Starting from IO max only, right? Yeah. So at t equals to infinity, what will happen? This will go to 0. But I obviously will not go until t equals to infinity. We'll go until t equals to capital T, right? Then this value will become IO max minimum, because this is discharging. So one more thing in this equation, if you put here t equals to capital T, we will get IO minimum, like our IL of T will be IO minimum. Okay, and at t equals to T on, what will happen? At t equals to T on, this value will be equals to IO maximum. So that's the basic thing basically that you have to understand. And the waveforms will be something like this. So this will be the supply voltage, and the output voltage, it will be 0 because due to the freewheeling diode, as the chopper is off and the diode is on, and it will be totally equals to Vs if the chopper is on. So my output is directly coming across the supply. What about diode voltage? So diode voltage will be just the opposite. It will be on when the chopper is off. So when it is on, so it gives 0 potential, 0 drop, and when it is off, it totally blocks the minus Vs voltage, right? And chopper voltage will be opposite of diode voltage because it is blocking when the diode is on, and it is passing when the diode is off. Same very simple waveforms for this currents. So here next what will happen is about the current waveforms. So current waveforms, you can see I will always ripple from IO minimum to IO maximum. So it will go reach IO maximum, then again it will come down to IO minimum, IO max, IO minimum, IO max, IO minimum. This will be the equations for the currents. Okay, this is the output current, and this output current is also equals to the inductor current for now. Okay, because inductor and the output, like the load, that is R, is connected in series. Okay, connected in series, and drop will be just mimic the current, because drop across the resistor, because it is just proportional to the resistor, proportional to the current. What will be the voltage? So the inductor voltage, right, when this is on, when the inductor voltage is on, it is equals to, let's name this as VL1. Okay, let's name this as VL1, and let's name this as VL2. Okay, VL2. Let's name this as VL1 and VL2. So why am I naming all this? So here, if you observe one thing, let's this time is what, T on. So current is reducing after this. Why is current reducing? Because the inductor voltage is negative. And why is the current increasing? Because the inductor voltage is positive. So, but overall throughout the cycle, right, the change in current is 0. Okay, because it started from IO minimum, ended to IO minimum. And overall cycle, if the change in current is 0, obviously the average voltage will also be 0. That obviously has been proven in the volt second criteria. So if the average voltage is 0, right, what equation I can write? I can write this equation. Okay, from this particular graph, I can write this equation, and this equation we will actually use. This is the equation that we will use for solving most of the cases and deriving formulas as well. Okay, so here the areas are like should be equal, and obviously overall area should be 0 under the time axis throughout a cycle. So here I can write VL1 into T on minus VL2 into T off equals to 0. So VL1, T on is what? T on is alpha into T. So VL1 into alpha, and T off is what? 1 minus alpha into T. So this will be 1 minus alpha into VL2. So VL1 into alpha equals to 1 minus alpha into VL2. So these are the things that you have to understand, and from here we will derive most of the formulas. Next is source current. So source current, right? Source current and the chopper current are same only. Source current is equals to chopper current. This time is for source. It is on when the chopper is on. So for the from 0 to T on, it will be same as the load current, and for T on to 0 T, right, what will happen? It will be off. As it is off, source current will not be like some non-zero value. It will be 0, and this will repeat. Diode current will be just the opposite. So it will be on when the source of chopper is off, and it will be off when the source of chopper is on. And VL voltage, these are same only. So these are the few formulas. Okay, this formula has been already derived to you. I can still derive this formula, okay, for you, that your average output voltage, right, average output voltage will be Vs times T on by T. How do you find it out? Just simply area over the time period. Simple area over time period. That is the formula that I'm using. Then IO average. What will be IO average? Simply IO average is basically equals to what? IO average is VO average. Sorry, not VO. VO average by R. Why? Because the average voltage across the inductor is 0. So only VO average is left, and I can find out my IO average like this. And IS average will be equals to I chopper average, and it will be lower than the IO average. It will be basically equals to like, as my IO average is I chopper average plus ID average, my ICH average, right, in terms of IO average will be simply alpha times IO average. Why is it alpha times IO average? Because from 0 to T on, this is present. So the area will be what? This area will be simply IO average into alpha into IO average into T on. IO average into T on. That will be the area from 0 to T on. And then I will divide by T, and that will give me the average value of the source current, right? Because my source is present for this whole T time period, but my my load conduction is present for this whole T time period, but for the source conduction, right, source conduction is from 0 to T on only. From 0 to T on only. That's it. That's the only point where my source is conducting. Okay, so that is the case. Next is the RMS, VORMS. Next is the RMS voltage. So the RMS voltage is this. So this is actually Vs. I will write this as Vs. That will be much easier. Okay. Okay. RMS. How do you find out RMS? Simply, I have derived this, right? Previously, in the previous lecture, I have derived this. You just simply square this waveform rectangle. You square this rectangle, you will get a rectangle itself. Just the this amplitude will be Vs square and not Vs. As it is Vs square, a Vs square will I can take common, but the time, right? Time will be under root. What is the time? Time is T on upon capital T. So it will be under root alpha basically. So your VORMS will be under root alpha Vs into under root alpha. Okay, your IORMS will be what? Your IORMS will be what? 1 by T and this. Okay, 1 by T and this. And like IORMS, you can compute it like this, or what you can use is you can use the formula. I will say you what formula, because now I cannot use the formula because the graph is not linear, and it is very difficult to use this formula and like compute all this, right? Very difficult to compute. Okay, this should not be Vs by R. Done something. This should be IO maximum. If T equals to T on, this is not Vs by R. This should be IO maximum. But like we will not use this, and this will not come. This will not come in the examination. You have to find the RMS value of this weird waveform. This is the weird waveform, right? IO is this weird waveform, and like it's very difficult to find the RMS value for this. Obviously, I will say you how to do. Okay, this will also be wrong. This will be actually also wrong. This will be IO maximum. This will be IO maximum. Okay, so that is the case. So my output power PO will be PS minus losses. Output power PO will be PS minus losses, right? Like you use this only to find out the output power. You don't use the other formula. I will tell you what the other formulas are. Now, analysis of supply. Until now we have been analyzing the load. What is the analysis of supply? IS average. IS average, again I will use the same formula. This will be from 0 to T on only. So my IS average is actually not present after T on. So if I just integrate up until 0 to T on, what was the expression for the IO, that will work. But obviously I won't do that. I will just do this. IS average I will find out with the help of IO average, because IO average is very easy to find out with respect to VO average by R, right? So your like IO average will be alpha into IO average by alpha into IO average, right? Because it is only present for T on time. Okay, we understand. And IS RMS, again the same, you will square and then take the under root, which is very difficult, and this won't come. Don't worry, this won't come in the examination hall. What will be your PS? PS, right? PS will be simply VS into IS average. VS into IS average. Why? Because this is DC, right? This is DC, so hence I have to multiply DC current. Okay, that's why the PS, and from PS you will be able to compute your PO, because if you subtract the losses, you will get back your PO. So this is the standard relationship between input and output chopper, but you have to remember that your VO average by VS and IS average by IO, this ratios will be equals to alpha, but you have to remember only valid if IO is continuous, only valid if IO is continuous, else it is not valid, only valid if IO is continuous, else it is not valid. Just remember this, keep this in mind, because this is a very very important point. So now attention, because in the question sometimes if it is not continuous, right, you can't write this, and if you can't write this, you have to go to the derivation. So that's why understanding the derivation is also very important. So from here I can say is that what I can say is basically if I cross multiply, right, if I cross multiply, I can observe that my VS into IS average will be equals to VO average into IO average, VO average into IO average. So VS into IS average will be equals to VO average into IO average, right? So this will be my power, because this is the power, right? This is the power. I surely know this is my supply power. And what is this? So as I assume there is no losses in the converter, so I assume this has my load power. There are no losses. Okay, no losses. Then my PS will be equals to PO. As PS is this, and which is equals to PO, so PO will be equals to VO average into I average. That's how this comes along. Okay, you have to understand this. Now next, analysis of chopper analysis, like the average voltage, right? Chopper, when it is off, it will totally block VS voltage. This will be VS. Total block VS voltage. So as it is VS, all these are VS, right? Yeah, fine, all these are VS. So this will be VS, and this will also be VS. This will be VS only. Like I hope you understood how we did this. Simply find out area under the curve, then VCH RMS, I'm just squaring it, and just time period will get under root. That's why this will be 1 minus alpha into VS. ID average, again ID average, I like when is the diode active? Diode is active for T off time. So from T on to T, diode will be active, and if you integrate this, right, you will get this as results. Basically it is the 1 minus alpha into IO average. Then what is ID RMS? ID RMS is basically square and under root, which is very difficult to compute. They won't ask. So these things, right, won't be asked. Okay, and like these things will be asked for a particular condition. What condition is that? That we will analyze in the next few slides. So skip it. Okay, and this one is fine. This one is fine. This one you can skip. Which one? This one you can skip. Okay, this RMS values you skip, right? RMS also you skip. This won't be asked, but what will be asked, there will be a special case for this particular type of circuit, and from there we'll solve. Okay. So what is chopper efficiency? Chopper efficiency, again I told you the same thing only. It will be PS. This is not PO. PS minus losses. It is PO upon PS. So hence, what is PO? PO is PS minus losses divided by PS, right? That is my PO. That is my chopper efficiency. And like again, if you want to find out the ripples, same formulas. I don't need to explain much. Just one thing you have to take in mind is that you have to make the average inverter voltage 0. So analysis of chopper. One more analysis I will tell here, that the VL average, right? VL average is 0 volts. So this thing is very very important. From here only we will derive the formulas. Okay, this is a very very important point. Okay, so now, right, I can comment about the ripple. I can comment about the ripple of the load. I can comment about the ripple of the load. So what is the ripple basically? What is a ripple? So ripple, right? Ripple of load current is what it is. Delta IO equals to IO max minus IO min. That is a ripple, right? If I just take copy and paste the waveform, IO waveform. So ripple means like how much is the voltage current is changing, right? How much is it changing? What are the boundaries of currents? Not voltage or currents. This time we are talking about currents only. Okay. So here, if I paste this, reduce the size. Okay, so ripple means basically this, right? This from minimum to maximum. What is the difference? How much is it rippling? Okay, how much it is changing? Because I don't want very wide values. I want DC, right? DC means a constant value. So I have to take care of this as well, so that the ripple is minimum. So here del IO is IO max minus IO min. How do you compute IO max and IO min? I have the expression for from t equals to 0 to t equals to t on. So here what is the expression? It tries to go to Vs by R 1 minus e raised to power minus R by L t plus IO minimum e raised to power minus R by L t, right? And IO max will be what? IO max will be the value of this IO of t at t equals to t on. So if I put in this equation t equals to t on, I will get my IO max value. And what will be IO min? So IO min, so this, right? This is after this is closed. Sorry. This not IO min, actually this is IO of t. Just hold on. IO of t IO of t from t on to capital T on to capital T. Okay, so what will be this? This will be from t on to capital T. And like what will be my IO minimum? IO minimum, if I want to write it in terms of IO maximum, IO minimum will be in this equation. Okay, I have done something wrong here. Okay, I have directly written the expression for IO minimum. Shouldn't have done that. So this, first of all, this is the IO of t expression from t on to t. This is the additive expression. Why? If I put here t equals to t on, what will you say? You will say IO max. And yes, exactly, at t equals to t on, I am getting IO max. And infinity, right? The inductor obviously will go to 0 voltage because freewheeling diode, 0 current, because freewheeling diode is present. It will discharge totally. But obviously in between, the chopper will again get turned on and it will charge the inductor. It will energize the inductor. So it can't go to 0. But the equation will be something like this. So here, if I put, like if I want to find out IO minimum, it is discharging, inductor is discharging at t equals to capital T. It has reached to minimum value. So it will be IO max e raised to power minus R by L capital T minus T on. Okay, it has reached to this value. So this is the value. Now what I can say? I can say is that what is the ripple basically? So if I want to say the ripple, right? Max 1 minus VR. Here it is the IO minimum. Okay, fine. And this IO minimum, right? This IO minimum is this value, and here I have, if I put this IO maximum value here, right? IO maximum is equals to this. If I put this value here, what will I get? So my IO minimum, or what I can do is I can put this maximum value as well. So if I just multiply e raised to power R by L t minus t on both sides, what will happen? I can write IO max as in terms of IO min. So it will be IO min into e raised to power R by L capital T minus T on equals to Vs by R one minus e raised to power R by L T on plus IO min e raised to power minus R by L into T on. Right? This is the value basically. This is the equation basically. So if I now bring this IO min on the left hand side, and take common things, so this will be IO minimum into e raised to power R by L T minus T on minus e raised to power minus R by L T on. Okay, and this is equals to what? This is equals to Vs by R 1 minus e raised to power minus R by L T on. I could have written here tau as well. So the best thing that I will do is I will write this tau. Yeah, sorry for the interruption. Actually, I just wanted to put everything in terms of tau because it's just an extra exercise, right? To write R by L every time. So I change everything to tau. Tau is L by R. So here I can directly find out my IO minimum expression in terms of this exponential and Vs by R. What is my IO minimum expression? So if I take this e raised to power minus t on common, right? If I take this e raised to power minus t on common, what will I get? So I just put this in the ratio. So my IO minimum will be Vs by R, and 1 minus e raised to power minus t on divided by tau divided by so what I can do is I can take the e raised to power t on common, right? If I take the e raised to power t on common, I will get some value like this. E raised to power t on is common here. This will be should I take e raised to power t on common? What? Yeah, e raised to power t on I should take common. But what else I can do? T minus t on, right? E raised to power minus t minus t on upon tau is there actually. Minus one, right? So now if I just multiply e raised to power t on minus t on here, this will be e raised to power minus t on, and this will be minus 1 only. So if I multiply minus on both sides, I will get by my answer as this. So this will be capital T upon tau. So actually my final IO like expression, right? This you can remember actually. This is good to remember. Okay, like you can always derive. I've derived, and you can always derive. If your transient is very good, you can always derive. But it's better that you remember this. Okay, that so that you will be able to solve questions very quickly. Minus T1 by tau and 1 minus e raised to power minus capital T upon tau. Okay, so this should be the expression for IO minimum. And similarly, if you want to derive, like if you know IO minimum, right? What is IO maximum? IO maximum is basically this multiplied by IO minimum. Okay, you can simply do it like that. So your IO maximum, just hold on, IO maximum will be equals to IO minimum into e raised to power t minus t on divided by tau. Okay, divided by tau. So we can do it like this. We can find out our IO maximum like this. So if I put this, if I multiply e raised to power t minus t on, right, what will I get? I will get this value only. This will come out to be like, if I keep the e raised to power t at the outside, what will I get here? So t on into this is correct, right? Okay, minus is also there. Sorry. Oh no, minus is not there. This is plus only. This will be plus only. Yeah, this will be plus only. Yeah. So here this will be Vs by R. This will be e raised to power t minus e raised to power t on. This will be minus 2t on. What am I making mistake here? Okay, if I multiply in the bottom, this should remain the same as it is. The top I will remain same as it is. What I'll do, I'll multiply this in the bottom. If like this will become minus then. So if I multiply this at bottom, just why am I doing this? Just to like keep the format symmetric and all, else like answer is same only, however you write the expressions. So if I multiply this in the reciprocal, so what I will do, I will add extra minus sign here. So if I add a minus sign, this overall thing will become e raised to power minus t plus t on by tau. Okay, I'm getting cramped out of space. I'll just write the expression, then again I'll come back. Yeah, one mistake I made, like I took this as negative. This should not be negative, right? Minus t on and minus t, this should be positive. So hence our IO minimum will come out to be something like this. Now if I multiply, like I want to find IO maximum, right? If I want to find IO maximum, I'll just multiply. So what equation I will get? If I multiply this t on and t on will get cancelled. This will be IO like e raised to power t, and what else will be present? So this part, right? This part will again be e raised to power minus t. So what will happen here is this will be e raised to power t minus t on divided by tau minus e raised to power t divided by tau. And what will be this? This will be e raised to power. This will be same, right? This will remain as same. This is 1 minus e raised to power t upon tau. This is not 2, mind you. This is tau only. So now what I can do is I can take this e raised to power t upon tau and common. I can multiply this at the bottom. Okay. So what will I get? I will get somewhat like this. Vs by r. This will be e raised to power minus t on upon tau minus 1, then divided by, this will be e raised to power minus t on. So this will be basically e raised to power minus t upon tau minus 1 again. So again I can multiply minus 1 on both sides. Like I'm just want to tidy this one up. This will be 1 minus e raised to power minus t on upon tau, and this will be 1 minus e raised to power minus t upon tau. Now this formula, right? This formula, unfortunately, you actually have to remember. I don't have any option here. You have to remember this. So like obviously you can derive, it will take you a bit of time, right? So that is a problem. Like you have the backup at least, that if you forget you can derive it, but it's better to remember this. So I don't ask multiple times to remember many things, but I will ask you this one. You have to remember this, right? This IO maximum and IO minimum, pretty simple only, because at the top it is always exponential raised to power t on upon tau, but when is the plus sign and negative sign, that you need to remember. The negative sign is in the case of the maximum current, right? Maximum current, and the positive sign is in the case of minimum current. So you can remember it like this. It is the opposite. It is just the opposite. This one and IO minimum. Like if you are also able to remember one, right? Other one you can remember it like this. Okay. So yeah, these two formulas you have to remember. And another thing is input resistance. Again, the input resistance will be same only. It is VSDC upon ISDC, same as like you can derive the formulas. Like Vs will be what in terms of VO and IO, and from there VO average upon IO average will be R, and an extra term alpha will be present. Now we will do the analysis of RLE load. What will be the analysis of RLE load? So again, the same thing, everything will be same, just the equations will be different. In this case, again, the assumptions are same. ID continuous, IL minimum is greater than 0. Okay, it cannot go to 0. It cannot be discontinuous conduction. Power electronic devices are all ideal. Again, for case 1, now I will directly do this in steady state. I have assumed that my initial inductor current is some minimum current, IO minimum, right? It is not 0, it is greater than 0. So obviously, what is my VO? So here, my VO is equals to VS. My VO is equals to VS, right? VO is equals to VS. What is my chopper voltage? Chopper has turned on. It is triggered, so it is 0 voltage. My inductor voltage is what? My inductor voltage. And this time inductor voltage has reduced a bit. What is it? It is basically VO minus IO minimum into R minus E. Okay. So VO is what? VO is VS. So VS minus IO minimum into R minus E. So this will be the, like, it will charge, but charge slower, right? It will charge slower, and obviously it is finite. So, and it is greater than 0, that is my assumption, it is greater than 0, then only this will turn on, right? Else this won't turn on. So obviously the thing is that my IL will increase, and as my IL is increasing, what else can I say? What is the equation of IL? So what is the equation of current, or IO of t equals to IL of t equals to, at steady state where it would try to reach, the inductor voltage would try to go to 0. So at steady state it will be Vs minus E by R, just hold on, plus initial, what is the current? Initial current is IO minimum minus again Vs minus E by R into e raised to power minus t upon tau. So this will be the equation. Basically you can derive the, but you don't need to write this in simpler terms. This is the equation that you need to follow. Okay, this will be the current equation. Okay, and obviously here power is flowing from source to load. Okay, power is flowing from source to load. Now case 2, what will happen? Case 2, right? From T on to T, again this I will forcefully commutate this power electronic device chopper, that is the switch. Then I will then what will happen? Inductor will try to flow the current, current IO max current, because it was charging, so it has increased to IO max. It will try to flow the same current, so it will flow through the diode. It will change its own polarity. So VO this time, VO is 0 volts obviously. And what is my chopper voltage? Chopper voltage previously was 0, now it is Vs, totally blocking this voltage. What about the current? ICH is 0 again. Is is equals to 0. Okay, all these are 0. But what about the inductor voltage this time? So if you observe, right, inductor voltage will be simply, as VO is 0, it is minus IO max into R minus E. So it is overall negative voltage. Is it overall negative voltage? So obviously it is less than 0. So as it is less than 0, what I can say? IL is reducing. So obviously it will reduce to what? Reduce to IO minimum, but actually inductor will behave as if it want to reduce to 0 current. So how will I write the equation? The equation will be pretty simple. My IO of t will be basically IO of maximum initial current e raised to power minus t on upon tau. Minus t on, why? Because the reasoning is simple. T minus T on by tau. Okay, so this is the current. This is the current basically. So it will reduce to this, but obviously it won't go to 0. It will go to IO minimum at t equals to capital T, right? So then the waveforms, every waveform will be same for RL, RLE. Waveform will be same except the current slopes and all those things, right? Else everything will be same waveforms, because here just the expression for current is changed, but between what it is rippling, it is rippling between IO maximum and IO minimum. So obviously all the waveforms will be same. Nothing will be different. This formula will also be same. It will be VO average will be equals to Vs into T on by T. It is Vs alpha. V average minus E by R. IS average is ICH average, IO average is same, ID average, all those things same. Just here, right, an extra minus E will come up. Okay, in the IO average, extra minus E will come up. That is just the extra thing. So I will just highlight this. Extra minus E will come up, except that everything will be same as it is, right? Everything will be same as it is. So this all this I don't need to explain much here. I've already explained the previous previous topic. So previous RL load. So everything will be same. Nothing will be different. Okay, so now next what we'll do is we will actually study with the linearized format. Why linearized format? If my tau is very, very less than my capital T, then what will happen, and then how will my things behave, and what will be the ripple voltages. Now let's come to the point where my time constant is very, very higher than the time period. What do I mean by that? So this is the equation, right? So let me just take one example. What is the one example? My IO minimum, not this. Where have I derived it? Ready to go. Ripple is this. Okay, this was for the RLE load, right? So if I find here, what is my IO minimum? If I just I have derived here, right? So this is my IO of T. Okay, this is my IO of T in the case 2. It is reducing from maximum value. So if it is reducing for maximum value, if my tau is very, very higher than t, right? Let's say this is t. Then what will happen? This will be very, very low value. Then I can linearize it. Then what I can do? How do we approximate exponentials? We can write exponentials as the power of x. E raised to 1 minus x is equals to 1 plus x by 1 factorial plus x square by 2 factorial. But here, as this is minus x, so for the odd powers, the coefficient will be negative, minus 1, right? Now, as my x is very, very small, what will happen? I will only keep the linear terms and the terms which are in greater power, right? X square. So if I take the power of 0.1 whole square, it will be 0.01. So it will be very low. So I can ignore that. I can only take the linear part. So my graph, right? Instead of looking like this, it will be almost linear. Why? Because if I compress this, right? If I compress this, what will happen? If I compress this, like this will be almost like a straight line, because this doesn't have enough time to charge and discharge. That's why it gets very low amount of time. And I hope you have studied this in transient. All those things I hope you have already studied. Okay. Or what I can do, if you haven't studied and if you are not able to understand this concept, just study Pulse Response Marathon by Anish Shah. There, if you want to understand this concept, there I have explained this in a detailed manner. Don't have to watch the whole marathon, just watch the initial question, starting question. There I have explained all this, right? So just search that. So if I linearize the things, right? If my tau is very, very greater than capital T, that is time period, switching time period. So what will happen? Everything will be linear. Everything will be a straight line. Okay. Basically, power of x, single power of x. So this will be linear. This will be linear. This is like VL1, VL2. This will be same only, but the current waveforms and all the other waveforms will just be linearized. Why do we do this? First of all, this is anyways happening. This we anyways want. Okay. To reduce the ripples also. The ripples also reduce by a large amount, and for easier computations as well. This is very, very helpful to us. What do we mean by easier computations? Now what will be my IO average? IO average computation has become very simple now, because it is basically what? Output current is basically this rectangle and this triangle, right? Again the same thing. So I can simply write the area of the triangle, which is delta L into T. So this distance, right? This distance is what? Ripple, that is delta L. Delta L is what? IO maximum minus IO minimum, and plus this rectangle. If I simplify everything, it will be IL max plus IL min divided by 2. Now what will be IL RMS or IO RMS? I told you, right? At the starting of the previous lecture, I derived a formula for computing the RMS of these type of waveform, which has rectangle and triangle. So the formula will be IO max whole square plus IO min whole square plus IO max into IO min whole under root divided by 3 obviously will be there. This will be the IL RMS, that is the inductance average RMS current, or the load RMS current. This is the IO average, that is the load average current, and the inductance average current. Okay. So this is the case. Then IS. What is IS? IS is equals to ICS, that is chopper current. It is in series with the chopper. So it is equals to IO of T for alpha between 0 to T, because when the chopper is on, it is same as the load current. When the chopper is off, it is equals to 0. So how can I compute the average? Again, right? It will just contain the area from 0 to T on of the current output. So basically, it will be alpha times that, right? Alpha times IL max plus IL min divided by 2. You can compute with the help of graph as well. This is my IS, right? This is my IS. So if you want to compute this rectangle and this triangle, your result will come out to be this. I don't have time to derive all this, but this is simple basic mathematics. So I hope you can do this. Again, what will be the RMS? Just the under root of this alpha, right? Just the under root of the alpha. Again, the same reasons, as everything is linear. If I square, then take the under root. The common terms will be outside, and the time will get under rooted, right? It will be under root. So that's why this is under root alpha, and this expression is what? This is IO average, and this expression is IO RMS, right? Already computed all those things. And what will be ID? ID is equals to IO when my chopper is off. So the second case. So again, this will be 1 minus alpha, because this is the case for the duration of T off, not a T on. So this average will be 1 minus alpha, and again, if I want to compute the RMS, it will be 1 minus alpha whole under root, same reasons, into IO RMS. So these are the equations basically. Now one thing what we can do is, we can analyze the inductor current for linear case. So for linear case, if I want to analyze the inductor current, then I can do the computation for ripples. So there the computation was very difficult. If you remember the formula, right? IL max and IL min, the computation was very difficult. Here the expression will come out to be very, very simple. What is the expression? So when the chopper is on, right? When the chopper is on, what is my voltage across the inductor? The voltage across the inductor is Vs minus Vr minus E. That is the voltage, right? And when the chopper is off, the voltage across the inductor is minus minus Vr minus E, right? Now, one thing I know is that what is the voltage across the inductor related to current? It is basically L times change in current. So I can write L times delta IO by T on. How can I do this? Because the period of time is very small. So I can, instead of writing D, I can write it delta IO. I can write, as the time period is very small. What is delta IO? Delta IO is a change. So what is a change basically? Change is basically from minimum it is going to maximum. So what I do? I write final minus initial, right? I write change. Change means final minus initial. So initially it was IO minimum. Finally it is IO maximum. So this is a change in current divided by change in time. So what is the change in current? IO max minus IO min. What is IO max minus IO min? It is delta IO. And what is change in time? It is 0 to T on. So T on minus 0. So it is delta T, right? So delta IO divided by T on equals to Vs minus Vr minus E. Okay. So next what will happen? Minus L delta IL divided by T off equals to minus Vr plus E. Okay. Yeah, this will be L delta IL. So this is for the on period, the expression. This is for the off period. So from both cases, right, you will be able to find out the change, like the ripple in the current. So I will just make this IO, because IO and IL are same only, but same things are there. So here, right, actually it is minus delta IO. Why is it minus delta IO? The reason being is that basically here the current is reducing. Actually I am going from maximum to minimum. So finally is minimum, initially is maximum, so it becomes minus delta IO L into, and the duration is T off during the off period, and obviously here the voltage is negative, so it anyways gets cancelled. And if you want to do the derivations, right, if you want to do the derivations, basically for case A, your okay, what have I done? For case A, right, I want to find out I want to write my Vs in terms of this delta IL and stuff that I want to find out. Okay, so for case A, I want to write my delta IO, right, no, in terms of Vs and E, not in terms of not in terms of this VR, because VR is unknown to me. I know E, I know Vs, but I don't know VR. So I want to write my delta IO in terms of VR. So exactly that is exactly what it will do. And I am assuming the current is almost, the ripple is very low, current is almost constant. So the drop in the resistor in this case and drop in the resistor in this case are almost same. So VR in the case 1 is this value, VR in the case 2 is this value. Now if I equate this, right, equate the VRs on the both sides, I will get Vs, like minus E will get cancelled. So Vs will be left out here, and I will take this on the right hand side. So Vs will be L delta IO into 1 plus T on plus 1 by T off. So you can remember this, or you can derive. That's up to you, right? How much time you take to derive. I will also share a few shortcuts. How can you remember this? Okay, without doing all these things, right? I will also say a shortcut. But for now, you can remember this, or I will share the shortcut to you how to remember. Now, if you put the expression of T on and T off in terms of the switching period or in terms of the switching frequency, then what will you get? You will get, this will be Vs, like I can put this L here, I can put this T on and all those things. After reframing the equation, you will get Vs alpha 1 minus alpha by, into T by L, or T I can write as switching frequency as well. So this will become 1 by FL, Vs alpha 1 minus alpha FL. Okay. So here, what will this be? Here, what will this be? This will be right. This will be right. This will be basically very important formula. Okay. So this also you can remember, or I will tell you a shortcut how to remember. That also I will tell. Don't worry. Now, important points to note about the ripple of the output current. Ripples of output current is independent of R and E. So it does not ripple, right? Overall ripple. Ripple means the maximum minus minimum. How much, is it varying from the average? That is the main purpose, right? We have to be as close to the average as possible. So ripple actually is not a function of R and E. It is independent. Ripples of output current only depend on the inductance. So if my inductance is very high, the ripple will be very low. You can see, right? If my inductance is very high, the ripple will be very low. If my switching frequency is very high, the ripple will be very low. Okay. So actually, right, it does not depend on the load, right? It does not depend on the load parameters. It is independent of load parameters. Okay. So with the help of the device itself, I can understand, I can keep the ripple as minimum as possible, right? So actually, yeah, that is the case. L is here, alpha L, and ripple is function of alpha L, F, and Vs. All these are either supply parameters or either the chopper parameters. Now, what is my IO max? Basically, right, IO max is what? This maximum value, right? What is happening? If my IO average will be somewhere around here, in between, exactly between the ripple, right? IO max will be somewhere around here. Okay, IO average will be this, like IO average will be between IO max and IO min, and here, right, this will be the half the ripple and this will be the half the ripple, like the distance from the average to the maximum will be half the ripple, and the distance from the average to the minimum will be again half the ripple. It will be exactly at the midpoint. You can compute all these things, already explained right here, like here as well. Whenever we have tried to compute this IO average, what did it go here, right? It was IL max plus IL min divided by 2. So if I want to write this in terms of delta, you can write, right? So like you can change this in terms of delta and then you can follow. So what is your delta IO? Delta IO is basically IL max minus IL min. So you put delta IO plus IL min equals to IL max. So you replace here delta IL plus IL min. So what will happen? This will be 2 IL min and delta IO. I will divide. So this IO average will be equals to IL min plus delta IO by 2. Same thing, right? Same thing. So you can do that. So that's how we get, like, it is at the midpoint. So IL max will be this, IO max will be this, IO min will be this. Like IL and IO are interchangeable. If I ever speak IL and IO in step down chopper, they are the same thing, because inductor current and the load current are the same. They are in series. Okay, just don't get confused by that. Now, few important points you need to find out is about the duty cycle and the critical value of inductance. So here we want to find out the boundary condition for which actually the device actually is just on the boundary of conduction. So first of all, I will find the critical value of duty cycle. So the value of the duty cycle for which the device is just conducting, it will stop conducting after that. It is just conducting. So my IL minimum, right? IL minimum or IO minimum will be 0. It is at the boundary of continuity and discontinuity. Just I think in the previous rectifiers also we know what this boundary means. So as this is a boundary, right, that's why this is the name speaks for itself, that it is a critical value of duty cycle. So my IO max will be delta IO, IO average will be delta IO divided by 2. Okay, because my IL minimum has gone to 0 and my IL minimum value was this only. IL minimum value was this only. So it is equals to IO average minus delta IO by 2. So this has 0. So IO average will be delta IO by 2. Okay, delta IO by 2. Exactly that. So why is it so interesting to us? It is interesting to us because this was the equation, right? This was the delta IO equation. This was the ripple equation, and this is just continuous. So this equation is still valid. So I will replace my delta IO with what? I will replace my delta IO with IO average. 2 IO average. Delta IO will be 2 IO average equals to, what is this? Vs into alpha is changed to alpha critical, because this is the critical value of alpha for which I am just continuous. Alpha C into T, or I can write F as well, doesn't matter. F into L. Okay. Okay. So IO average will be what? IO average is what actually IO average, if you remember, right? If I don't have E, right? So assume this is only assume for RL load. For RL load, what can I say? RL load, I can directly say that my IO average will be VO average by R. And for a step down chopper, if you remember, I derived the VO average formula. It was alpha into Vs by R. Exactly that is what I will replace. So for RL load, I will replace this. Okay. So basically, have I done it already here? Oh no, this was the analysis of inductor current. So here, if I replace everything, right? Just do this. Just hold on a second. I'll just replace everything. This value will be simply 2 times alpha into Vs by R equals to Vs. This is alpha C, right? Alpha C Vs alpha C into 1 minus alpha C divided by FL. Right? So what will happen? Alpha C will get cancelled. Vs will get cancelled. I just want this expression. So this will be 2F times L equals to, now there is R here, and this will be 1 minus alpha C. So alpha C will be 1 minus 2FL by R. So this will be alpha C. Do you need to remember this? No. Just remember that formula, right? Just remember that formula. What formula? This one. Okay, you can remember this one, or this one also you can derive, and from here you can come to here, right? How you can come, just how I came. Okay, no need to remember, you can derive. So my recommendation will be derive. If you want to remember, obviously you can always remember, that's up to you totally. So my recommendation will be derive. Now next is same analysis of inductor current for the critical value, this time, right? Critical value of inductance. So I'm just, what is happening here, right? I was reducing my alpha. So as I was reducing my alpha at max can be what? Alpha at max can be 1. Okay, if my R is infinity, alpha at max can be 1. But alpha minimum will be 0 only, and here we can see that duty cycle ratio is actually depending on the this resistor and frequency, all those things, right? And inductance. So what is the critical value of inductance? Again, same thing I will do. That for critical value of inductance, I'll just replace L with LC. And if I do the same thing, just as I did for alpha C, if I do the same thing, I will get my expression of critical value of inductance like this: 1 minus R in 1 minus alpha into R divided by 2F. Just do the same derivation and same thing. So this also I will recommend you to derive. Just remember, like if you can remember this. If you like, I will tell you a shortcut how to derive this as well. Don't worry. Okay, so you can derive this as well from this. So this is the mother formula, and from here you can derive all the other formulas. Okay, critical value of alpha. So another another thing there can be, right, critical value of switching frequency. So here, right, instead of this, if I replace my FC, if I replace this with FC, so basically critical value of switching frequency, like you can remember this as well. Like this is the critical formula. So if I replace L with L will be a just simple value, constant. But if I replace F with FC, everything will just be flipped. So it will be 1 minus alpha divided by 2 LC divided by 2L, because L is constant value. Okay, okay. So FC is equals to 1 minus alpha into R divided by 2L. So let us basically summarize everything, whatever we have learned. Let us quickly summarize that these are the formulae, and which ones you need to remember. You can remember this. Okay, you can remember this formula, and yeah, that's pretty much it, right? All this you can derive, right? All this you can derive. You can remember this formula, and with the help of this formula you can derive this. So this is the recommended, and remember this is for the RL load only. These formulas are valid for RL load. So this is the recommended one that you should remember. Okay, only this formula, right? Others you can derive. This is for a step down chopper, and remember what is the condition? Condition is IO is continuous, load current is continuous, and switching frequency is very very high than the critical frequency, right? At this frequency, like it will be just continuous, and it will not be it will be linear though. Actually my switching frequency, right, must be very very higher than the very higher than the R by L, right? R by L basically very very high. Then I can linearize. Why? Watch that video, pulse response marathon video, just the starting question, and that should be enough. And another few criteria which we have used here, like what you need to remember. You need to remember all these conclusions. Remember? No, you can derive, right? Just understand how did I derive all this. That's the important point. And this formula you can remember, or how did I derive, that also you can remember. Then two things we will use in like volt second criteria and amp second criteria. In this lecture we have used volt second criteria, and in the next lecture with the help of capacitive filter we will use amp second criteria. But before that we'll do a few more questions, and the next lecture we'll do a few more questions, and we'll Hey everyone, and welcome back to PrepFusion. I'm Anish, and today we'll start our lecture 3 on choppers. So basically we have learned a lot of theory about choppers, with like what is a ripple in current, okay, and what are different formulas that we can get. Obviously I've told you how to remember them, how to derive them, all those things I've explained. So in this lecture we'll do questions on step down chopper, as well as we'll do step down chopper with low pass filter. That also we'll do, right? Low pass filter, basically we will have a capacitor, and the inductor, instead of it being in the load, it will be outside the load, right? It will not be included in the load. Okay, so first of all let's do few questions. This is the only one question that we'll do, and this will cover up almost everything whatever we have learned till now. So a DC to DC converter operates at a switching frequency of 1 kilohertz. So it has a switching frequency of 1 kilohertz. So if switching frequency is of 1 kilohertz, what does that means? That means that my time period, right? Time period of switching will be 1 by 1 kilo, that is 1 milliseconds. Fine. Duty cycle of 0.6, so that means my T on will be 0.6 milliseconds. Okay. Next, draw the load waveform. We have to draw the load waveform, load current. We have to draw the load current waveform. Find the average RMS values of the following expressions for two cases when L is very high and L is 10 millihenry. Okay, so when L is very high, right, then that becomes very easy. Why? My time constant for this case, the time constant is very high than the time period. That means the waveforms that I will get will be linear. And what about the load current expression? So here, right, the load current expression, if they haven't told me anything, what I can do is when this switch is closed, right, what will happen? Totally 100 volts will come across this RLE load, and if like at steady state, what will happen? This inverter has some current IL minimum, so it increases from IL minimum, then again reduces from IL minimum to then again reduces from IL maximum to IL minimum, then again it like goes like that, right? So it ripples around like that. So if L is very high, right, I can assume that as basic simple straight line. So I can assume that. So case 1, if L is very large, so those ripples will be very small. If you remember correctly, previously, right, L was in the bottom. If you remember, L was in the bottom of del I formula. So if L is very high, then obviously I will have minimized ripples. I will have very low amount of ripples, right? So I can almost make it constant, so it will be I only. Okay, and what about like this diode voltage will be simply negative of VO. So once this is closed, this is minus Vs, and if this is open, this is simply 0 volts as this is on. Okay, so this is the current waveform. Okay, or you can draw it like this as well, like from here to here, if you want to actually show what is happening. So when the source is on, the chopper is on, this will go from IL, like this will be very minuscule, delta IO will be very minuscule. Okay, and it will go from IL max, IL min, it will go around that. Okay, so like, but my assumption will be my IO average is equals to my IL average equals to IO. Okay, I will assume this value as the IO. Now what have they asked us to find? The load current and the voltage. So first of all, how do I find out the voltage? Simple, right? Like what is the a VO average? What is the VO average? Simple, right? So when this is closed, VO is equals to 100. When this is open, VO is equals to 0. So again 100, like I am directly writing it, but I hope you remember the formula: 100 into Vs into T on divided by T. So it will be alpha, VO average will be alpha into Vs. So I'm not just remembering the formula, I'm deriving in my mind as well that formula, right? Like visualizing what is actually happening. Alpha into Vs is basically alpha is 0.6. So 0.6 into 100 it is. So it will be 60 volts. 60 volts will be your VO average. And what will be your IO average? IO average will be equals to, okay, you have to find out the average and RMS. So I have to find out the average as well as the RMS value. So first of all, I am computing the average values, then I will compute the RMS values. So IO average will be simply, it is a RLE load, so it will be VO average minus E divided by R. So it will be equal to, what is VO average? VO average is simply 60, and what is E? E is 20 minus R. R is 10 in this case, I believe. Yeah, 10. So it will be 4 amperes. Okay, so this is the IO average. Next, what is the thing? Next, right? Next, the RMS values. What about the RMS values? Same, right? RMS, like as I have assumed that this is almost equal, that my IO, that delta IL is very small. So IO minimum is almost equals to IO maximum. So when that happens, right, basically my IO RMS is basically my IO average itself, as I have assumed that it is almost constant. So it will be IO RMS equals to 4 amperes. Okay, and if you assume something, right, you will get us this value only. Okay, but what about my VO RMS? So VO RMS, right, will be different. It will be under root alpha times Vs. I hope you understand why. In the previous lectures I have derived this. So under root alpha is 0.6 into Vs. What is Vs? Vs is 100. So I'll just write down the formula as well, else like you might get confused. So what will be this value? So if I do the under root 0.6, right? If I do the under root 0.6, what is this value? 0.6 under root into 100. So this will be 77.46 volts. Okay, 77.46 volts. So this is the value of the VORMS, and IORMS is same. What about the source now? So if I draw the source, right? So source current will be equals to IO, basically the constant value when the chopper is on. As soon as the chopper is off, what will happen? It will have zero current and the diode will totally flow the current. So how can I compute the ISRMS? ISRMS will be again the same thing only. I have derived this previously as well. ISRMS will be under root alpha into IO, because IO is constant. So if I do, what is IO? IO is, I think, 4 amperes. 4 like 0.6 under root into 4 is basically 3.1 amperes. So ISRMS will be 3.1 amperes, and obviously before computing that, right, I have to compute the IS average value, because they have told us to find the source current as well, right? Source current. So like I'm directly going from load to source. It doesn't matter whichever one you do. So if I do source current, right? If I do source current, what will happen is, if I do source current, what is it? So average value of source current. So if you remember the formula well and good, it is alpha times IO. But like you know, right? What is the area? Area is IO times alpha into T divided by total time period T. So it comes out to be alpha into IO itself. So yeah, you can remember the formula. You can derive it through the graph, whichever way suits you. So it is alpha into IO average, which is equals to 0.6 into 4. So it will be 2.4 amperes. And this makes sense, right? Your average value is less than the RMS value. Okay. So we got this value. Anything else they have asked us? So they have asked us to find the diode current and voltage as well as the chopper current and voltage. So chopper current, right? Chopper current is same as the source current. Chopper current is same as the source current. So this, right? This will be equals to chopper as well. I will write this here itself. IS average. Okay, and what about ISRMS? So like again, right, a chopper RMS current will be same, so hence I can directly say that ICH RMS equals to ISRMS equals to under root alpha into IO. Okay, so we got this value. And diode current, what about diode current? So diode current, right, so diode will be on when the chopper is off or the source current is 0. So it will be for this period, for the off period. So what will be ID average? So ID average will be simply equals to, just hold on, ID average will be simply equals to IO into T off divided by capital T. So it is 1 minus alpha into IO average. So which is equals to what? 0.4 into 4, which is 1.6 amperes. What about ID RMS? What about ID RMS? Same thing only, just a extra under root will be present. So 1 minus alpha under root into IO RMS, which is equals to 0.4. If I do the 0.4 under root, right, 0.4 under root into IO RMS. IO RMS is 4, which is 2.53 amperes. Okay, 2.53 amperes. So this is my ID RMS. So this is the case. amperes. Now next, what we can do? I haven't computed the VCH average and VCH RMS as well. So what is VCH average? So here, right, if you observe, when like this is diode voltage. So from diode voltage also I can say what is the VD average. So from here I can compute the VD average. Basically VD average will be what? It will be something negative. So it is minus Vs for the T on period of time, because whenever this chopper is on, right, this diode is automatically turned off. So as this diode is also, the whole 100 volts comes across in the opposite direction. So then whenever this chopper turns off, so this diode conducts and hence the voltage becomes 0. So this will be minus Vs into T on divided by capital T. So this will be basically minus into VO average. So because this diode, right, is directly connected across VO, so VD will be minus VO, and whatever RMS values we have computed, all those will be same. So VD, okay, I have to use some other color because all this, right, is becoming very, very messy. So I will use some other color. VD average will be negative of VO average, which is minus 60 volts, and VD RMS will be negative. Oh, RMS cannot be negative, right? RMS cannot be negative. So what it will be is it will be same as this. So it will be 77.46 volts. So RMS cannot be negative, but I hope you get the point, right? I hope you get the point. That's why with RMS we are not able to see the sign, because if I square this, right, the information about the sign goes away. This becomes positive, plus VS square. Okay, and if I square plus VS, that also is plus VS square only. So that information goes away. Next, what we'll do is we'll find it out for the chopper. So for the chopper, right, so whenever this IS is equals to IO, the chopper turns on. Okay, and whenever this IS is off, that means chopper is off, and it is blocking what voltage? This is totally shorted, right? It is totally blocking this 100 volts. So it is in the forward blocking zone because current flows like this. So I can see it like this, that the chopper voltage is like this only, VCH, right? So this, yeah, this will be like it will block. What will be the VCH average? VCH average will be T off into Vs. Okay, T off into Vs. So it is 0.4 into Vs. So like 1 minus alpha into Vs. So 0.4 into 100 equals to 40 volts. Okay, so this is my VCH average. VCH RMS equals to what? 1 minus alpha Vs. Okay, into Vs is what? 100. So this will be 63.24. Okay, this will be the answer to my VCH RMS. Okay, this will be the answer to my VCH RMS. So all these are voltages and currents. Basically, next what have they asked? They have asked few other things as well, right? Current waveform we have drawn. Average RMS value following cases when L is very, so case 1, source current, diode voltage. So also I forgot to add here, right, few other things like efficiency and all. Efficiency will be 100 only, right? Why efficiency will be 100? Because basically these elements, right, they are totally ideal. So my efficiency will be 100%. Efficiency will be 100%. So as my efficiency is 100%, that means what? That means basically my power will be like supply power, PS, will be basically PS power will be what? PS power will be simply, what do I say, Vs into Is average, which is equals to what? Vs into Is average is Is average is where is it? 2.4, and Vs is 100. So 100 into 2.4, 100 into 2.4 is basically 240 watts. 240 watts. So this will be the supply power, and this will be the load power as well. So I have to write here, compute the also compute the efficiency and load power of the chopper. Okay, I don't have enough space here, so what I will do is, this is unfortunate, what I will do is just shift this on the right hand side, just reduce the size a bit. Yeah, this one is fine, this one is more fine. I can shift this in the bottom as well, right? Yeah. So all these are good and fine. So what about L equals to 10 millihenry? So if L equals to 10 millihenry, right? So first of all, we have to make the comparison. So if L is equals to 10 millihenry, what I can say that L equals to, case B, L is equals to 10 millihenry. So what is my L by R? L by R is basically, R is 10 ohms, so it is 1 milliseconds. Okay, 1 milliseconds. And this is my tau. And what is my switching time period? Time period switching time period is also what? Switching time period is also 1 milliseconds, if you remember, right? Switching time period is also on 1 milliseconds. But T on is 0.6 milliseconds. So T on is 0.6 milliseconds, right? And at steady state, how much time will it take to discharge overall totally? So it will take 4 tau time, right? After 4 tau, the current will go to 0. If you remember, for a first order circuit, at 4 tau, the current goes to 0 for a source free network. Why am I talking about source free? Because when this chopper will be off, it will not charge through the source. It will just discharge to the diode. So what is my T off? This is my T on actually. What is my T off? T off is 0.4 milliseconds. So here the inductor is discharging. And what is 4 tau? 4 tau is 4 milliseconds. So I still have 10 times the time to totally discharge at steady state. So it will reduce. Currents will reduce, but not totally towards 0. Okay, not totally towards 0. I have still enough time. So what my assumption is, the current waveform will be something like this. Previously my L by R was very large. So it discharged but a very small amount. So that small amount is negligible. That's why delta I at that point of time was 0. But here I will get some delta I will get some ripple, but that will be very small amount of ripple. That will be linear here. Like waveforms will be linear, except calculating ripple will be very difficult. You will get linear waveforms only because my T off is smaller than this 4 tau. Not very small, but still small to a good extent. Like it is 10 times, right? So it is small to a good extent. So this is the case here. So in this case, right? In this case, I will have different IO max and IO min. So basically, this time IO max minus IO min will be a new parameter, that is delta IO. That is basically the ripple, right? Ripple basically. So this is IO max and IO min. This is delta IO. But the voltage will be same. So again, if you compute, remember, right? The voltage waveform doesn't change. So voltage VO average will be what? VO average will be alpha into Vs, which is equals to 0.6 into Vs. 0.6 into 100 is 60 volts. And your IO average will also not change. Your IO average will be still same. What is IO average? IO average is VO average minus E by R. VO average minus E by R. So what is VO average? VO average is basically 60 volts that we just computed. E is 20 and R is 10. So that IO average value will remain same. So it will ripple around this what? Ripple around the 4 amperes only. Okay. So it will ripple around 4 amperes. Okay. So next what I can do? This is what I can do, right? So I want to compute the ripple. If you remember the formula, what was the formula? The formula was like this. It was Vs was equals to L into del IL divided by 1 by T on plus 1 by T off. Now, is there any easier way out to remember this formula? Is there any easier way out? There is actually easier way out. How we can remember this formula? So this, after like doing all the computations here, like I will compute the values and then I will show you the easier method. So this was the formula that I told you to remember previously. So here Vs is what? Vs is 100. Okay. L is L. So L is what? How much? I forgot. L is actually, okay, L is 10 millihenry, right? L value they have provided. So L is 10 millihenry. So I will just keep that as milli into del IL or IO, I can say, because IL is IO, same series connection. 1 by T on. What is 1 by T on? T on is 0.6 milliseconds plus 1 by T off. T off is 0.4 milliseconds. Okay. So this is T on and T off. So what will be my delta IO? 10. 1 divided by 0.6 plus 1 divided by 0.4 into 100, right? So this is 37 point. Okay, am I doing this correctly or not? Just hold on. 1 divided by 0.6 plus 1 divided by 0.4, 10 into, yeah, 10. So this is 2.4 amperes. 2.4 amperes is actually pretty big. 2.4 amperes of delta, that is actually pretty big delta, right? So now what is happening over here? Basically what I can say is, what is my IO max and IO min? So from here I can compute my IO max and IO min. Before that, right, I want to recompute my delta IO. So if I want to draw the circuit here, I have the filter here, right? If I want to draw the circuit, how can I compute this thing, right? Intuitively. What I can say is, what is the voltage VL when this is on or off? So when this is on, right, the voltage VL will be what? VL, I can write this VL, like this is method 1 directly through the formula, or if you want to go with like method 2, which is deriving the formula itself. So method 2 is this. So here what I can say is, VL will be equal to what? Like the voltage across the inductor, it will be 100 minus IO into 10, which is like, I will assume IO average here. IO average into 10 is what? IO average is what? 4. 4 into 10 is 40. So I will write this IO average into R minus E, right? Minus E. So this will be IO average into R is what? IO average into R is 40. 40, 20. So it is 60. 60 minus 100 is 40. 40 volts. VL equals to 40 volts. So VL is equals to 40 volts. Okay. So that is the case here. Now what I can say is this, right? What I can say is VL is 40 during the on time. VL is 40 during the on time. So what formula I know? VL is equals to what? VL is equals to L DIL by dt. Now one thing I know, as the time period is very small, right? I can write this as delta IL as they are linear. So this will be during the on period, VL is equals to 40. This is L into delta IL. Delta IL into T on. Okay, T on. Changing time is T on. Now, what is L? L is, I remember it is 10. So it is 4 into T on is what? 0.6. And this is delta IL. And I get the same answer. Delta IL is equals to 2.4 amperes. So this is the shortcut, or like the way to I was telling you. You can remember, like you can remember the method, and this will be helpful in the later choppers as well, right? This will be helpful in the later questions as well, like in the different choppers. So this is how you can do without the formula. Okay, just directly with basics. So you can compute the delta L like this as well. Now what is like what we have to compute? We have find out delta L, but the purpose of finding out delta L was to find out IL max and IL min, so that I will be able to compute my IL RMS. So what is my IL max and IL min? So IL max will be equals to IL average plus delta IL divided by 2. IL min will be what? IL min will be what? IL min will be equals to IL average minus delta L divided by 2. So here the value IL max will be what? Simply 1.2 I have to add with 4, so it will be 5.2 amperes, and here I have to subtract 1.2. I have to subtract 1.2, so this will be 1.2 I have to subtract, so this will be 2.8, I believe, right? Yeah, 2.8 amperes. So my maximum and minimum current are like this. So from here I will be able to compute my IL RMS, that is the inductor RMS current, or the output RMS current. What is it? It is simply under root the formula I told you, right? It is IL max square plus IL min square plus IL max into IL min. So 5.2 whole square plus 2.8 whole square plus 5.2 into 2.8. So this divided by 3 will be my answer. So what is my ILRMS basically? So if I just quickly compute this thing, so 5.2 whole square plus 2.8 whole square plus 5.2 into 2.8 divided by 3 under root 4.06. So your IORMS, right, or ILRMS will be 4.06. So this question is becoming lengthy, but we are computing everything. Right? So everything is getting cleared in one question only. So we have computed IORMS. Voltages will be same. Okay. So voltages I am not computing. Voltages will be same. Whatever the voltage waveform was there, the same voltage will be here. So case 2, I will just write here case 2. Voltages will remain same. Actually, like if you see, right, your how you can confirm that your current will be continuous, you check whether your L is greater than LC, and if you check, right, with this formula, you can use this formula as well. Where did it go? Yeah, this here, right? So you can use this formula as well, and you can put L equals to LC, and this delta L will be what? Delta L will be 2 IO average in case of just boundary condition. So you will see that whatever critical inductance we are getting, that is still lower than the inductance that is already present in the circuit. So definitely, if my current inductance is higher than the critical inductance, so I am safe, my current will continue. So I meant by writing this here, I meant this only. I didn't check it, but from the assumption of time constant, I did it. But from here also, if you check the critical inductance, you will see that your actual inductance value is greater than the critical inductance. So that is the case here. So IORMS is this. What about the other values? What about the ISRMS and ICH RMS? Okay, so it is basically under root, like it will be what? Under root alpha into IORMS. This is the same thing, right? It will be the same thing only. Under root IORMS, so under root alpha into IORMS, so into 0.6 3.144 amperes. Okay, this will the IORMS will be 3.144 value. And what about the chopper? So average currents will be same. Average current won't change because the previous average voltages were also same only. So like ICH or IS average or ICH average will be simply alpha into IO average, which is same only. So this will be 2.4. Okay, this will be 2.4 amperes. And your other value, right, that ID average will be same only, that is 1 minus alpha into IO average, which is 1 minus alpha is 0.4. 0.4 into 4 is 1.6 amperes, and ID RMS will be 1 minus alpha 1 under root into IO RMS. So it is if I want to compute this, 0.6. So this will be 4.06 into 0.4 under root alpha. So this is 2.567 amperes. So this will be all the values, basically diode currents and all those things. So power, right? Power again will be same. So PS will be same only. PS will be Vs into Is average, as average currents have not changed and voltages have not changed. So it will be 240 watts only. Okay, and that will be equals to PO, as my efficiency is 100%. No losses are happening in the chopper. All elements are lossless except the resistor, right? Okay, so that is the case here. You don't write PO equals to that other value, right? IORMS square into R. Don't write that. That can cause a bit of mistakes. Just solve according to this. I couldn't find a reason till now that why we don't use that formula, that PO is equals to IORMS square into R plus E into IO average. I couldn't find that find that question. I couldn't find the solution to that question, that why we are not using that formula. Okay, I will look it up. And I will try to find out the reason. So now, right, all these things are done. Now one small topic is left, that is our step down chopper with low pass filter. So step down chopper with low pass filter we'll study now. So first of all, same assumptions I will take, that IO is continuous, IO minimum is greater than 0, power electron device is ideal. But this time, right, my inductor current and the load current are not same anymore. So the inductor is not connected in series with the load. What is happening? I have a low pass LC filter before the load. So if you remember, I have shown you the block diagram in the lecture 1. So there I have shown the filter as well. There will be a filter. So this is the low pass filter. Okay, this is a low pass LC filter. So S equals to 0, the whole signal is getting passed, and at S equals to infinity, none of the signal is getting passed. It is 0. So that's why this is called a low pass filter. So we'll just analyze. So here one thing is that just analyze in steady state. At steady state, like this inductor has some voltage at t equals to 0, I0 minimum voltage, and then it increases as this chopper is turned on. So it will energize this inductor and it will increase, and at t equals to t on, what will happen? It will reach to IO maximum, and then from there it will reduce, and like obviously the voltage has also gone to some VO maximum or VO minimum, right? So now what will happen is, this is a capacitor. Now actually capacitor passes AC components. So as soon as I close this power electronic device, what will happen? AC component of the current will pass through the capacitor. So all the AC component of the current, right? So if there is high ripples of the current, all those things will pass through the capacitor. Because why? Because AC means what? AC means omega is high. AC means omega is high. If omega is high, that means what? That means my XC is low. It is 1 by omega c. If my XC is low, that means this will provide a low resistance, low resistance path to the AC current. So all the ripples and AC current will flow through this. None of them will flow through the load. So that problem has been resolved. Okay, that problem has been resolved. This is XC, not XL. This is XC, not XL. Okay. Next is like so the main thing is your IC will be equals to delta IC. Basically the AC component is what? Delta IC. If I subtract delta IC, I will only get the DC component back, right? So yeah, the ripple, all of the ripple will be taken care by the capacitor, and none of it will be passed through the resistor. And so inductor tries to like block the change in current, and the capacitor tries to block the change in voltage. So that this is the job. So capacitor will control ripple control ripple of IO, and inductor will control ripple of IO, because inductor doesn't like change in current, and all the extra change in current will go through this capacitor, because capacitor allows that change in current. Capacitor to control ripple of VO, because capacitor doesn't like change in voltage. So whatever change in voltage there is, right, that will come across this inductor, that will be absorbed by the inductor, and the capacitor voltage will remain constant. Once we do the analysis, we will understand. So here, right, from t equals to 0 to t on, what is happening? My IL, basically my inductor current IL equals to IO. IL equals to IO plus IC. IL equals to IO plus IC. So basically, what will happen this time, right? As soon as the switch is on, what will happen? Extra current will charge this capacitor. So I will charge this capacitor. So what will happen is, this inductor current is increasing. As this inductor current is increasing, the capacitor current is actually increasing. Why? Because my load current is constant. My load current will be constant, right? So the extra increasing current, right, as this inductor is charging, that will flow through the capacitor, not through the resistor. Okay, I hope you understand, because that AC component will be passed through the capacitor, not through the resistor, because capacitor allows sudden change of current. So what will happen is, that extra change, right, will flow through the capacitor, as it will provide low impedance path. So there is a change, right? What is happening? The inductor is energizing. So the current IL across the inductor is increasing. So that increasing current will be reflected in the capacitor and not in the load. Load current will be constant no matter what. So if the capacitor is charging here, right, like the IC is increasing, what will happen? In this region, actually IC is negative. Why IC is negative? Because, like, what is this IC? IC is basically, what is IC? If I say what is IC, so IC, if I find out IC average should be equal to 0. Why? because at steady state capacitor should behave as an open circuit. All these things have been explained in pulse response marathon video. You can watch the first video, you can watch just the first bit of the pulse response. I think from there you will get an idea. So first, at steady state, like these two are the simple equations, right? At steady state, IC average will be equal to 0 and your VL average, right? VL average will also be equal to 0. So if my IC average is equal to 0, so basically all the ripple components are gone, because IO average and IL average will be same and IO is constant. So if I subtract IO with some IL, and as IO is constant, what I will get? I will get IC. So I am just subtracting IO. IO is basically IO average. So this is the IL average value, and that is what I am subtracting. So this is the value. IL average. Okay. So here one interesting fact is, actually initially the current will be negative. Why? Because the inductor actually like the inductor current is increasing. Fine, inductor current is increasing, and what is happening is that the load voltage, right? Load voltage is reducing. Why? Because like basically what will happen is load voltage will reduce up until this point, then it will increase. So if I subtract this, right? If I subtract this is negative. Current is negative. As current is negative, so current is negative, that means dVc by dt is negative. If dVc by dt is negative, voltage will reduce. So as voltage is reducing, what is happening? This current is reducing, and suddenly what will happen then? Like obviously this is very minuscule amount. Although I said to you it is constant, just by very small amount I'm talking about. So if this is reducing, right? Next, what is happening at this point? At this point, current suddenly becomes positive for the capacitor. As soon as the current becomes positive, it will charge. It will charge from this VC minimum to VC maximum. So the ripple will be something like this. Now here, right, you have to pay attention. So please pay attention here. And actually, I will derive a formula here, and that one you actually have to mug up, because deriving that actually takes a huge amount of time and effort. So it is VC minimum and it is VC maximum. Okay, so VC minimum and VC maximum. So in this case, what is my output voltage in from 0 to T on? My output voltage, right? VO is simply VC. And in this case, right, that this diode is off. So okay, I'm in case 1 only. This diode is off. So the voltage across the diode is what? Voltage across the diode is Vs, and this value, I don't know this value yet. So okay, I can assume this to be, I don't know the voltage. So I know Vc though. So what is my VL actually? So what is my VL? So VO is equals to Vc, and what is inductor voltage? VL is equals to Vs minus VO basically. And so I have found out this voltage. So now I will be able to find out diode voltage. So diode voltage, right? Diode voltage is simple only. This is grounded. So diode voltage is minus Vs. So VD is minus Vs, and that is simply off. Diode voltage is minus Vs, and that is simply off. So in this case, you can observe, obviously the inductor voltage is positive because Vs will be greater than VO average. This is a step down chopper. So as inductor voltage is positive, what does that mean? That means that it is greater than 0. That means my delta IL by delta T will be greater than 0. That is my IL will increase. Right? So that is what will happen. So my current will flow from source float and IL will increase. So that is the case. Next is case 2. So case 2 is from T on to T. So here my current has reached to IO maximum. So this I'm at this point. Now what are the voltages and current? So this time, right here, what is my chopper voltage? As my chopper was on, I didn't write the chopper voltage. That is, chopper voltage is 0 volts only. It is on, right? So load voltage, chopper voltage, everything I have written. Currents I have written. So IO, right? IO basically in this case, IL is IO max. Like what I will say is, in this case, right, just here my IL0 minus is IL min, right? IL0 minus is IL min. So if I replace here, right, with IO min, what will I get? Or IL min. This is IL min equals to, I'm just computing at t equals to 0. So this will be IO is what? IO average. This is a constant current, right? I am assuming load current is constant, IO plus IC. So IC will be equals to IL min minus IO. So this current, right? This current you have to take care of. You have to take care of this current. Why you have to take care of this current? Because if it goes negative, things will be really this is anyways negative, because my assumption is IO constant, right? IO constant or IO average will be between IL minimum and IL maximum. So this is negative, and exactly that is what showing here. It is negative. Okay. So next what is happening is that my IL TO minus is IO maximum. So now what will be my IC? IC will be again, this is not IO, this should not be IO, this should be IL. I can name this as IL, that will be easier. Just name this as IL minimum because I am talking about the inductor current. Okay, just hold on. Yeah, this is IL only, fine. This is IL. Okay. So basically what is my IC in this case? IC again is IL minus IO. So what is IL? IL is IL maximum. IL maximum minus IO. IO I will assume constant, so it is IO. So my assumption is obviously that IO lies between IL max and IL min. So IL max will be something positive, and exactly that is what is being shown here in the capacitor current. If you see, it is positive from here to here, but it is discharging because now the source is gone. And that extra current, like whatever current that capacitor has to provide, okay, so that for the reason it is reducing. So here, as my IL will reduce, IC will also reduce. Okay, as my IL is reducing, IC will also reduce. Okay, because inductor is de-energizing. So what is my chopper voltage this time? Chopper voltage is simply Vs. Why is chopper voltage Vs? Because the diode is turned on. As the diode is turned on, I can simply apply KVL through this here, right? So this will be Vs. And what is my VO? VO again is VC only, which is a constant value. I will assume VC is constant value. Okay. What about my VL? VL, right? Inductance voltage is simply plus and plus minus VO. Okay, inductance voltage is minus VO, and VO is positive, right? So hence this overall thing is negative. If this overall thing is negative, that means that delta IL by delta T is less than 0. That means my IL is reducing. Okay, IL is reducing. So now what, like IL is reducing, that hence as IL is reducing, that's why IC is also reducing. Okay, and at a certain stage it will go to negative after reducing. So this is the case. These are the waveforms basically. So it is VL1. VL1 is what? VL1 is equal to simply, I've already computed it. VL1 is Vs minus VO, right? VO average. So here, right, I can write this as VO average. That will be much more easier for us to understand. This is VO average. And this is also VO average. Okay. VL is minus VO, that is VO average. Okay, so it is VO average. So what I can say is I can use that formula, use that rule. What is that rule? That is the voltage second rule. Okay, so just hold on a second. Yeah, what is voltage second rule? It is that VL average will be 0. So if VL average is 0, what I can say is, what is VL1? VL1, or when it is on, is simply Vs minus VO average into alpha into T. Should be it is the area, and the negative area is how much? VO average into 1 minus alpha into T will be equals to 0. Okay, so basically my what do I get? So this cancels out, right? So VO average, I get this. So Vs alpha will be equals to VO average. So this is the value that I get, which we already knew. So VO average is Vs alpha. If my conduction is continuous, else this formula won't be valid. So you have to give an this disclaimer as well, like conduction is continuous. Okay, if my conduction is continuous. Okay, so this is the basically the volt second criteria, and from here you can easily find out the delta L that I just derived in the first question as well. So how can volt second criteria help us? So we can use volt second criteria using two things. Okay, so first I will use for the case 1 from like t equals to 0 to t on. Okay, so for t equals to 0 t on, what thing we know? What is the one thing we know? I know that my L, like this volt second criteria, I can derive always the voltage I can derive, and I can use it to find out the ripples of current as well. Okay, so L into dIL by dt is equals to VL. I know this, right? I know during on period what is VL equals to? During on period VL is simply equals to VS minus VO average. So this will be L, and as my assumption is I can convert this into delta IL and delta T, because I am talking about very small change in time, so I can write it like this: delta IL of T, basically the ripple in current, into delta of T. Now what is delta of T? Delta of T, right, is this time I am talking about from t equal to 0 to t on. From t equals to 0 to t on, what is actually happening? From t equals to 0 to t on, what is happening? So at t equals to 0, my IL 0 is IL min, right? And at t equals to t on equals to IL of t on equals to IL maximum. Okay, IL of t on equals to IL maximum. Now what is the change? Change is final minus initial, so IL maximum minus IL minimum, and what is that equals to? That is basically delta IL, right? That's why I have written it here: change in current divided by change in voltage, so change in time, sorry. So this will basically be, so this delta IL by t on. So change in time is what? Like final time is t on and initial time is 0. So t on minus 0 is t on, equals to what? Equals to VL. VL is equals to VS minus VO average. So it is VS minus VO average. And what is VO average? VO average is simply alpha times VS, right? So this is simply alpha times VS. So I can write this the next page, that my del IL will be equals to, this will be not function of t, del IL will be equals to simply VS, I can take common, 1 minus alpha into t divided by L, and L into like this is like t on is alpha into t, and L, yeah, this is the formula, basically this is the formula that we derive, right? So how else I can write it? I can write it like this, if you remember properly: 1 minus alpha into alpha divided by FL. Okay, switching frequency. So we already derived this, okay, there, but that derivation was pretty difficult, right? And you are thinking remembering the formula is pretty difficult, but this one is easier way out. So like you can derive, and this will not take you much time. Just this thing you have to remember: LIL by dt, and what is my inductor voltage, and I will derive for the next few choppers as well, so it will become easier, don't worry. Now like I will do the same thing for the second case, and we'll get the same results. Okay, so for the second case, my time is going from t on to t. So basically my current is going from what? My current IL is going from IL maximum to IL minimum. I'm going from IL maximum to IL minimum. So if I'm going from IL maximum to minimum, so basically this time, right, it will be finally is IL minimum, initially is IL maximum. So it is IL minimum minus IL maximum, which is negative of delta IL, right? Ripple is IL maximum minus IL minimum, so it is negative of that. And the surprise, the voltage is also negative, because this time VL is minus of VO average, right? And again I will use the same formula. So VO average is what? Alpha into Vs. So it is alpha into Vs. But this time delta T is what? Delta T is actually T off, right? Because the time period is T on to T. So T minus T on is basically T off. So this will be T off. I will multiply T off with it. So this will become 1 minus alpha into whatever it is, 1 minus alpha into whatever it is. Okay, sorry, yeah, 1 minus alpha into capital T, 1 minus alpha into capital T. So this becomes alpha into 1 minus alpha into Vs divided by FL. The same formula which I derived just in the previous slide, same thing. Now this is for the ripple. So you will use this criteria, volt second criteria, for finding out the ripple. What else we'll use? We'll use the current second criteria. So what does current second criteria tells us? Current second criteria tells us, if I find out the positive area, right? If I find out the positive area, that will give me the change in charge. Okay, change in charge, and the change in charge will actually give me the change in voltage. Okay, change in voltage, because here what is happening, as my current is positive in this region, capacitor is charging. So here the capacitor voltage will be minimum. So at this point, because the current was negative, and as the current is negative, so as IC is negative, dVc by dt is negative, hence Vc is reducing. So Vc is reducing, I stop here. Now current is 0, then it becomes positive. So from this point Vc is increasing, still increasing, now it stopped, because now current becomes negative. So this is the period where my Vc is always increasing. Okay, so my Vc will increase from this point from Vc minimum to Vc maximum, because the IC is positive. So here, this is the point where my this Vc will be Vc minimum, and this will be Vc maximum, because here the voltage will keep on increasing, here the voltage will keep on reducing. Okay, so this is the case here. Now what else can I say? So I have to, like, how do I compute this ripple? So what is my dVc by dt, if you remember? So basically my IC, right? IC is C dVc by dt. Another thing that we know is basically my delta Q, or the Q, basically Q is delta Q is C into delta Vc, right? C into delta Vc, if you remember this formula. So if I'm able to find out this charge, right, from here to here, what is the change in charge, I'll be able to find out the change in voltage, because I'm going from minimum to maximum. So I just need to find out the change in charge here, or the total charge, change in charge basically, or the change in charge or total charge basically here. Okay, so how do I find out? I have to find out the area of this. Okay, sorry, what is the area of this? So area, right, this is T2 and T3. This like I don't know yet the time period, so this is T2 and T3. So somehow this delta Q, right, delta Q will be what? Delta Q will be half into base into height. So base is T2 plus T3, I don't know these values, into height. What is the height? So this height, right, interestingly, this height is delta IL by 2, because its DC component is 0 and its ripple is what? All of the ripple will come across the capacitor, none of it will come across the load. Okay, the ripple that I am seeing in the inductor current, all of it will come across the capacitor, because capacitor will pass all the AC. So this is a pure AC signal. Why? Because the average, not pure AC, but like at least the most dangerous harmonic, the DC, right, is absent here, because IC average is 0. I told you starting. So this will be this will be half only. So this will be delta I by 2. By symmetry, this will be delta I by 2. Okay, so I need to find out all these things. I know delta I, right? Delta is like I have derived from here. So this actually, right, is delta IL actually, delta IL by 2. Okay, so I know delta IL by 2, but I don't know this T2 and T3. How will I find out T2 and T3? So for finding out T2 and T3, we will use the current second criteria. So what is the current second criteria? Basically the average, like IC average will be 0. That is basically the current second criteria. IC average will be 0. So if I find out the overall change, like overall current, right, throughout this, if I find out the overall current, average current, that will be 0. How do I find out average current? Basically the area of this over a cycle will be 0. Total area over a cycle will be 0. And what else can I say? Is that another thing that I can say is my T on this value, right? Basically my T1 plus T2 plus T3 plus T4 will be equals to capital T. This much I know, right? So let us use the current second criteria. So okay, this is here. I will use this later. First of all, I have to use my current second criteria actually. So yeah, this will be used later. So if I use my current second criteria, what I can say is I will copy this as well. This is VC will come to later. Let me first use the current second criteria. So it didn't copy everything. Like how is this coming? Also there is another proof for this. Like what is IC? IC is what? IT is dq by dt. If you remember, IC is dq by dt equals to C dVc by dt. Now for a very small amount of time, right? For small change of time, I can write this like this. This will be delta. This will be changed to delta q, and this will be changed to delta v, and dt will be simply cancelled. So delta q will be C delta v. So we can remember it like that as well. Okay. So that is the case over here. So here basically I want to compute T1 and T2 and T3, right? I need T2 and T3. So if I need T2 and T3, I will use the current balance criteria. So what is the area of this triangle? The area of this triangle is what? Delta I by 2 into T1 plus wait a second. Delta IL by 2. This I will let change to IL, else things will become messy here. So this will be delta IL by 2 into 1 by 2 into T1 plus T2. Not T1 plus T2, T2 plus T3. T2 plus T3. And this is equals to what? I can write negative as well. Negative. Okay, negative I have written. So this is negative. And what I can write is, this is one triangle. So its area is delta I by 2 into half into T1, and its area will be delta I by 2 into half into T4. So if I add those two up, both are negative, it will be T1 plus T4. So it will be delta IL by 2 into half into T1 plus T4. This will be equals to 0. Okay, this will be equals to 0. And basically what else I can say? I can say that delta IL by 2 will get cancelled, half will get cancelled. So one thing I can say that T2 plus T3 will be equals to T1 plus T4. This is the interesting fact here. So let me name this as some Tx. Okay, let me name this as some Tx, because this is very important to me. This T2 plus T3 is very important, because from this I will be able to compute. I know delta IL, I just need this T2 plus T3. I will replace this T2 plus T3 here. Okay, T2 plus T3 here, and T4 plus T1 here, right? So I will get 2Tx. So 2Tx basically 2Tx will be equals to what? 2Tx will be equals to simply capital T. 2Tx will be equals to capital T. So Tx equals to capital T by 2. Tx equals to capital T by 2. And what is Tx? Tx is T2 plus T3. So conveniently I got my value T2 plus T3, which will be capital T by 2. So basically, right, the charging time and the discharging time of the capacitor will always be T by 2. No matter what. So I can say T2 plus T3 equals to T by 2. And from there I will be able to compute. So basically now I will use this criteria. Okay, so my delta Q will be half into delta IL by 2 into T2 plus T3, which is T by 2. So it is equals to what? It is equals to C into delta VC or delta VO as well. You can say delta VO as well. So delta VC will be what? So what is delta IL actually? What is delta IL? So you can remember this formula as well. So it will be delta IL divided by 8C into T or it will be delta IL divided by 8 FC. Okay, so you can remember this formula as well, or you can, like, we know the delta IL form, right? You can write delta IL in terms of Vs and alpha. From there you can also write it. So I know already this delta IL in terms of Vs and alpha, that I will do. Before that, right, basically few things you have to understand is that about VO max and VO min. So basically VO, like this is delta VC, right? Delta VC is basically equals to delta VO, because VC is equals to VO. So your VO or VC maximum, okay, VO max will be simply VO average plus delta VO by 2, simple as, okay, and your VO minimum will be equals to VO average minus delta V divided by 2. So from here, few things I can say. Talk about the critical value of capacitor. So critical value, at the critical value of capacitor, critical value of capacitor is basically what? Critical value of capacitor delta will be when my VO minimum, right, will be almost touching 0. If it is negative, it can't be negative, right? VO cannot go to negative. Okay, that is the thing. So when it is 0, so basically my delta VC becomes 2 VO average. If you put here like VO minimum equals to 0, delta VC or VO becomes this 2 VO average. Now if you replace it in this equation, right, what will happen? So this will be 2 VO average equals to delta IL into 8 F C critical. So like your C critical will be what value? So this is a formula that you don't need to remember, just you can remember this one. Okay, you can remember this one, and from here you can obviously derive, right? Okay, this one also you can derive. This took me some time, so if you want to derive you can, but if you want to, like, you should know at least how to derive in the examination, or let's say you forget it, so you can derive it, right? So your C critical, right, your C critical value, if I have enough space here, so your C critical will come out to be delta IL divided by 16 VO average into FC. VO average into FC. Okay, so this should be your C critical. Okay, and what is actually VO average? If you remember, what is VO average? VO average is basically alpha into Vs, right? So I can change this in terms of alpha and Vs, and another few minute changes I can do. What is delta IL? So delta IL, if you remember, delta IL, right, like I derived it, you can always derive it is alpha into 1 minus alpha Vs divided by LF, right? This was my delta IL. Okay, so this, if I replace this, over here, what values do I get? So here, if I replace my delta IL, C critical will be simply equals to from where can I get it? C critical will be if I just replace delta IL, this will be alpha Vs will get cancelled. 1 minus alpha will be remaining here. In the bottom I will have 16 F square will be there, and LC will be there, right? So this will be F. Okay, so LC won't be there. Sorry, how have I written C over it again? This is Vs into, yeah, C critical will go over. This will be 2 VO average. Yeah, C won't be here, right? So this will be F square L. So this is the formula for C critical. Okay, this is the formula for C critical. So this one you can like just derive from here, and then you can remember, just remember this formula. This formula should be enough, right? This formula should be enough. If you remember this formula, that's good enough. Okay. And how did I derive it? That you should know, so that in case, just in case you forget in the examination hall, you are able to derive it. You are able to derive it. So how did I derive it? So I started from here, and like from the graph also you can see my voltage is increasing from here only, from time t1 instant. Okay. So t1 it is increasing up until t1 plus t3, right? Sorry, t2 plus t3. This duration it is increasing, then again this is decreasing. Why? Because the direction of the capacitor current, all of it depends on the direction of capacitor current. Okay, so these were basically few things about the lectures, and I will try to give you a few homeworks. So we will not be able to solve the questions today. So this question, I have few questions here, so take it as assignments, and in the next lecture I will solve all these questions. This is the first question. Take the screenshots. You can take the screenshot, right? All of this you can take the screenshots. This one you take the screenshot. Easy questions only. This one also you take the screenshots. This won't take much amount of time to solve the question. This one also you take the screenshot, and I think yeah, this one is the last one. I think this one is the last one. No, there is another question as well. So yeah, this one is the last one I think, and no, we have a lot of questions. So yeah, this one 12, and I think after this none of it. Yeah, this is the last. So all of this you can solve, and after in the next lecture, right, I will solve all this question, and after that. Hi everyone and welcome back to PrepFusion. I'm Anish, and today we'll solve the assignment questions that I gave you as homework in the previous lecture. So let's do this. So this is a gate question which has came in 1991. So a figure shows the circuit schematic of the chopper driven separately excited DC motor. So this is a separately excited DC motor. This doesn't have any armature resistance. They have not given any resistance. The single pole double throw switch operates with a switching frequency T on upon Ts is equals to 0.2. Basically they have given us a duty cycle, or you can say as the alpha. So alpha is 0.2. Basically Ts is what? Ts is switching time period, and T on is the on period of this switch. So basically T on means when this is active, and T off means when this is active, right? That's the differentiation between T on and T off. And double throw switch means like it can connect either this point or this point. Okay. Next, the motor may be assumed lossless. The motor may be assumed lossless with an armature inductance of 10 millihenry as explained, right? So L is 10 millihenry and it has no loss. That means it has no armature resistance. The motor draws the average current of 20 amperes at a constant back EMF of 80 volts under steady state. So IO average is what? Okay, sorry. This right? Yeah, this is IO average. Just hold on. IO average is what? IO average is basically equals to what do you say? 20 amperes. IO average is 20 amperes. So my IO average is 20 amperes, and my E is 80. But that is given. E is 80. Now what are they asking? They are asking us to sketch and label the voltage waveform VO, that is the output voltage waveform. They are asking us to find out. Also they are asking us sketch and label the motor current waveform, basically IO, VO and IO they are asking us, and evaluate the peak to peak current ripple. So first thing what you should keep in mind is here, right, we don't have any resistance, only inductance is present. So what is the voltage across the inductor? So this time, right, my L by R is 0. If R is 0, L by R is very high. So like this time, right, inductor will charge and discharge linearly. It will exactly charge and discharge exactly equals to linearly. Why? Because the voltage is fixed. So whenever my switch is on, whenever the switch is on, what will happen? So I will do it for the two cases. Whenever the switch is on and whenever the switch is off. So switch is on. When the switch is on, right? So this is the case 1. Case 1 basically means what is the VL? VL is equals to this VS minus E. So VL is VS minus E, which is a constant voltage, which is 20 volts, right? So this is constant. If this is constant, what is VL equals to? VL is equals to L DIL by dt. So the slope DIL, slope of the current, right, is constant. If the slope of the current is constant, then it will charge linearly, and like for the discharging case as well, it will be constant. I will show you that as well. So it will be, so DIL by dt during the on period will be basically 20 volts, right? 20 by L. L is 10 millihenry. L is 10. I will just do that real quick. L is 10 millihenry. So this will be 2 amps per milliseconds. 2 amps per millisecond. So this is the slope basically for the case 1. Now what about the case 2? So if I just draw the circuit of the case 2, case 2. So case 2 was basically what is my VL? So this time, right, the switch will move to this T off position. Okay, switch will move to the second position. So actually, right, I should have written it. Okay, that's fine. This is also fine. So now if I duplicate it and just change the switch position, so now, right, what will be VL? So VL is this voltage, right? VL is this voltage basically. This is my plus minus VL. This is my notation, initial notation. So this is what I will follow. So here if you have just apply simple KVL, VL will come out to be minus 80. So VL will come out to be minus 80. Okay. So this is again constant. So my DIL by dt will be this time minus 8 ampere per millisecond. That is, per millisecond it will reduce to 8 amperes. But what is the time period actually? Have they provided us the time period? They haven't provided us the time period. They haven't provided us the time period. So that is difficult. So they haven't provided us a TS. So I won't be able to say that whether the current will go to negative or positive. That I won't be able to comment. Okay. So the waveform will look something like this. This will be the output voltage waveform. So when when this switch is in this T on position, what is VO? VO is directly coming across this 100 volts. So VO is directly equals to 100 volts. Now when this switch position is in the second, when the switch is in the second position, that is T off. So my VO will be directly 0. Okay, sorry for this. VO will be directly 0 because if I apply KVL, VO is equals to 0 because this is shorted to ground, right? So that's why VO is 0 in the off timing and on timing. So this is T on. T on and capital T. Okay. T on and capital T. So what will happen is T on is 0.2 TS. That much I know. And current will increase and decrease. I don't know whether this will go to negative or not. But like the main thing is this slope, right? Actually, this slope is higher, much higher. Okay, then it will go to negative anyways. So because the amount that it goes to positive, it will go to negative anyways. I don't know because 0.2 T on is only there. So basically, right, it is 0.2 T on. So IO max will be what? So the positive change in current is 0.2 T on. It will repel to this value and then it will decrease. Okay. So I don't know what is T on answer, but it is 0.2. So basically, right, when it is increasing and decreasing, increase and decrease are not same for this. So here this is 0.2. So basically if I write this, right, so it is going from del IL, I'm talking about from 0 to T on. So if I'm going from 0 to T on, this del IL, right, this will be, I will multiply 0.2 TS, so this will be 0.4 TS. Okay, and if I'm talking about the negative case, so this del IL, right, this del IL will be what? This will go towards 0. So here this will reduce, so this will be, right, this will be minus, if I multiply 0.2 with it, 1.6 TIs. Okay, this is reducing this much and then increasing this much, only 0.2. So this will keep on reducing only, the value will keep on reducing only. This is actually not a stable circuit. Okay, This is not a stable circuit. This question is wrong. Question is wrong itself. Okay, because this is not a stable circuit. The current will reduce if you want to understand, right, what is happening. So during the from 0 to t on, this is increasing somewhat, and then this is always reducing, like reducing a much larger. Then again it is increasing somewhat. Then again reducing much larger. Okay, and this will keep on reducing. So actually, right, it doesn't have any IO average. It doesn't have any peak to peak ripple and all those things. So motor current will be like this. If I am able to solve this correctly, if you have some different idea, right, you can tell me. I will be able to understand this. If you have some different idea, you can tell me. But from what I understand, okay, yeah, what I understand, this will, like, this slope is very, very high. This slope is high, like the discharging slope is higher than the charging slope, because I have a E battery over here. This E is helping it to discharge. Okay, and this 100 volts is helping it to charge. So the current will be something like this. It will keep on decreasing. Okay, keep on decreasing. So this question is wrong. Okay, let's move on to the next question. Next question is actually pretty simple. So in the next question, a step down chopper operates from a DC voltage source Vs. It operates from a DC voltage source Vs and feeds a DC motor armature with a back EMF E from oscilloscope. So a step down chopper operates from a DC voltage source Vs and feeds a DC motor armature with a back EMF E from oscilloscope traces. Okay, so from oscilloscope traces, it is found that the current increases for time tr. Okay, it increases for time tr, falls to 0 over a time tf. So what happens? Step down chopper is there and DC voltage Vs is there to feed a DC motor armature with a back EMF E. So that's the same circuit. Right? So it increases to, okay, one thing is there. Once it goes to 0, right, I think this diode will be turned off, because this diode will be naturally commutated. So okay, that is another thing. So yeah, I mistake. This question actually isn't wrong. What will happen is, I just thought of it. So this will increase from 0. Okay, this waveform, right? I will tell you what is actually happening here. I'll just delete this thing. I'll tell you what is happening. So let's say we start from 0, right? We start from 0, L0 minus S0, just at the first like transient cycle. We start from 0. I increase to some value. This is what value? This value is 0.4 TS. Okay, 0.4 TS I increase to 0.4 TS. 0.4 TS actually is in milliamperes. Okay, 0.4 TS is actually in milliamperes. Okay, then it got reduced. Reduced to what? It is reducing because the slope is much larger, right? So it will reduce in a much faster rate, and what will happen is it will come to a 0, and as soon as it comes to 0, the diode will be turned off. Diode will turn off because diode will not allow negative current. So that's my mistake. How can the diode allow negative current? That is what I was thinking, right? Diode cannot allow negative current. So diode will be off and the switch is here. So okay, I'm sorry for that. Okay, is there any diode or not? Okay, there isn't any diode also. Okay, this is just a switch. Okay. But I think this is not a bidirectional switch. If this was a bidirectional switch, then things will be really difficult. So I think this is a unidirectional switch. If I assume this switches, right? This switches to be unidirectional. Unidirectional, right? Unidirectional. Else the question will be wrong itself. So if I assume the switches to be unidirectional, so current can only flow like this or like this. It cannot flow in the opposite direction, right? So here, if I assume it to be unidirectional, so it will reach 0 at some t dash time, okay, and this will always remain 0. Okay, this will always remain 0, right? Why? Because like that has current has been 0, so it is naturally commutated, and current cannot flow in the other direction. So the inductor voltage goes to 0 over here. Inductor voltage actually goes to 0 over here, right? So they are asking us this peak to peak ripple. What will be this peak to peak ripple? Simple, right? Either this T on, so this will be this peak to peak ripple. IL minimum will be 0, 0.4 TS, or not this is wrong. 0.4 TS or like this only, because I can find out this T dash as well, right? I can find out this T dash as well. So this will be a peak to peak ripple, as TS is not given. TS not given. I won't be able to find. So first of all, this 0.4, right? 0.4 actually is, first of all, you have to understand per milliseconds. So TS needs to be in milliseconds. Then only this 0.4 TS will be correct. So TS is in milliseconds. Units of TS is in milliseconds. That you have to understand. Okay. TS not given. Question incomplete. Okay, so this is the case, and a step down chopper operates from a DC voltage source Vs and feeds a DC motor armature with a back EMF E. Okay, a step down chopper operates from a DC voltage source Vs and feeds a DC armature, just like the previous case. From oscilloscope traces, it is found that the current increases from time Tr, falls to 0 over time Tf. So it increases from time Tr, so this is Tr basically, and then it decreases for a time period of Tf. Just the same graph here, same graph. Next, what happens? Tf fall to 0 over time Tf and remains to 0 for time To. So it remains to 0 for time To. In every chopping cycle, this is happening. It increases within time Tr, rise time, then it decreases within time Tf, that is fall time, and then it remains 0 for To, that is 0 time. Okay, and then the average DC voltage across the freewheeling diode. So like this is the same, like I will draw the circuit diagram. Circuit diagram will be something like this. I will just show you what is the circuit diagram. Okay, so this is the switch, chopper switch. Okay, and this is the freewheeling diode. Freewheeling diode will be connected in anti-parallel with the whole circuit. Freewheeling diode. What are they asking? They are asking us the average DC voltage across the freewheeling diode. Okay, average DC. First of all, this should be negative, right? They haven't talked, like actually this should be negative. Average DC voltage across the freewheeling diode can never be positive. So all of this, right? Actually, in the options they haven't given us negatives, but this should be negative. All of them should be negative. Okay, so here, right, one thing is for sure, when the current rises, this chopper will be on. Okay, when the current falls, basically this due to this inductance, it will still flow current in the same direction as this has some energy. So overall VO will be 0 and the current will flow in this direction. But what will happen is, as it's a source free network, what will happen, this will keep on reducing, the current will keep on reducing. At certain stage it will go to 0, and then this freewheeling diode will also be off, and then this will block only, like this will totally be off, and the voltage will still be voltage will be actually plus 80 volts. Okay, plus 80, because this voltage will be 0. Okay, so here I think few things are wrong. Okay, this is E0, this will be E0, right? This is not 100, this is E0. No, this is not wrong. Actually, this is correct only. This question is correct. And this is Vs. So just what I am explaining, I will just tell you real quick, right? Okay, I will tell you real quick what is happening. So in case 1, right? Case 1, like you should do this in seconds, but I have to explain, so I am taking this much time. But this question is very, very simple. So case 1, I am closing the switch. Okay. Okay, I am closing the switch. And if I close the switch, what will happen is that, what will be the diode voltage? Diode voltage will be, the VD is something like this, right? VD is something like this. Okay, so if VD is something like this, VD they haven't told us, but it will be like from P to N only. That then only we can understand whether it is reverse bias or not. So in this case, my VD is minus Vs. Okay, next. Case 2. What is happening in case 2? Case 2, right? Chopper is turned off. Okay, chopper is turned off. So chopper is turned off, but this inductor has to flow the current, right? It has charge to some current. It has to flow the same current. So it will flow through this freewheeling diode. So it will turn on the freewheeling diode. Inductor will turn on the freewheeling diode. Okay. So freewheeling diode is on. So as freewheeling diode is on, inductor will discharge. So if VD in this free, right, will be 0. So from 0. So here from 0 to TR, the current will rise. That's why this is known as TR. And from TR to, like I will say, my T equals to TR plus TF, the current will, like VD will be 0. And in the case 3, what will happen is that case 3 again, all of them will be off. Why all of them will be off? Here, right, actually the current reduces actually. Here my IL increases. Why does my IL increases? You will see that your VL, right, is positive. VL is what? VL is Vs minus E. As VL is positive, IL will increase. Okay, as VL is positive, IL will increase. Okay, next this here, right, here actually what is my VL, right, here in this case VL is actually minus of EO. So obviously IL will reduce, and IL will reduce until 0, right? It will go to 0, then it will stop because this will turn off. So as soon as this turns off, so this time my IL is 0, and IL is not changing actually. IL is not changing, it is constant 0. So my DIL by dt will also be 0. Hence my what is it? VD will be what? This voltage is 0. VD will be what? VD will be minus EO. Okay, VD will be minus EO. If I say plus and then plus, yeah, VD will be minus EO, right? VL is 0. VL is 0. Okay, so what will be the average voltage basically? So now I can plot the voltage, right? Plot the voltage like this, all this, right? You should do it in your mind, not like I'm explaining. That's why I'm writing all this. All this should happen in your mind, and the answer should already come up instantly. So the voltage waveform, right, will be something like this. So here initially from 0 to t on, it will be minus Vs actually, minus Vs. 0 to t on, it will be minus Vs. Then suddenly the diode will turn on, freewheeling diode will turn on, and it will be 0 for TF time, and then it will be EO, right? For certain time it will be minus EO for T0 time, and then again this same cycle will be repeated. Okay, so this will be the case basically. So what will be the value here basically? So this is the time duration. This is the duration TR. This is TF. And this is TO. Okay, so this will be Vs. This will be minus E and minus Vs. So this will be minus Vs into R. Like what is the area over a one time period? TR, TF plus TO, that is a one time period, right? Minus Vs into R, and this is 0, and this is minus E into T0 divided by totally TR plus TF plus T0. So this will be the answer basically. So like option C will match, I think. Yeah, option C will match. Okay, here this is not, this should be also minus. Sorry for this. This should also be minus. Just hold on. Everything should be minus. Actually, they should have shown the polarity like in gate, like previous year, right? In like this gate 2000 question. So there they didn't care much about the question paper and what. Okay, so here option C will be correct, but the correct framing would be they will provide a diagram, then they will actually mark the voltage terminals of the diode, and then you can find the average voltage. But like that, at those times they don't like do the questions that perfectly. Okay, so let's move on to the next question. This is the next question. So the next question, we have a power electronic converter shown in the figure, has a single pole double throw switch. The pole P switch is connected alternatively, so like switches through A and B. Okay, fine. The converter shown is a step down chopper, half wave rectifier, step up chopper, full wave rectifier. So this is not a rectifier because my V in is DC itself. Okay, how can this be rectifier? Okay, how can this be rectifier? Or like even if this V in is, let's say AC, right? Even if this V in is AC, this is directly passing the output voltage, and once this comes to this switch, right, again same as the output, like output voltage is directly sinusoid. So this is not rectifier. How can it be rectifier? Okay, so now what we can do is this case, right? Once this comes here and comes here, so once this is here, right, from A to P, okay, actually this can work as a rectifier as well, like because if this is a unidirectional switch, so only I will pass the positive cycle, right? Positive cycle will be passed. This can work as a rectifier as well, but actually this is not a proper rectifier, right? Proper half rectifier and full wave rectifier, we know how the circuit diagrams look. So obviously that is gone. So if I give it a DC input, what will happen is that once it is at A, right, the inductor will charge, and once it is at B, the inductor will discharge. Okay, so we have just studied about this, okay, just in the previous first question, I think this type of configuration, and that was a step down chopper. But if you want to understand this, right, if you want to understand this, that how is this a step down chopper, you can do with the inductor voltage equation, volt second criteria. Again, overall VL average will be 0, that much I know, right? Overall VL average will be 0. Okay, VL average will be 0. Okay, so if VL average is 0, if VL average is 0, so when this switch is at position A, what will be my VL will be simply equals to V in minus V out. Okay, and V in, let's say, some value Vs, right? So it will be, and VO is VO average only, so V in minus V out, okay, some positive value. Then once this goes to negative, so my assumption is current is continuous. Current is always flowing, so I'm assuming constant current. Then when this switches at B position, so what will happen is my VO will be, like, my VL will be minus VO, so this will discharge basically, and this cycle will repeat. Okay, this cycle will repeat. This is minus VO, and this is basically what, this is alpha into T, this is T. Okay, so here what I can say, like, this is the same configuration that we know, this is step down chopper. Okay, still if you want to prove it, so this will be V in minus VO into alpha into T equals to VO into T, and like your V in, right, V in will be just hold on, this is 1 plus alpha. Anything I'm doing here wrong, V in is minus V out, fine. T will get, okay, this is sorry, this is wrong, this is 1 minus, so not T, 1 minus alpha into T. That is what I was thinking, what am I making mistake on? So this alpha into V in will be equal to simply VO. Okay, so this equation is basically for what? This equation is for buck converter, right? It reduces the voltage. So obviously option A will be correct, step down chopper, that is buck converter. Let's move on to the next question. All these questions you can solve in seconds, but I'm taking time because I am explaining the things here. Okay, so let's move on to the next question. This question is also pretty good. I will just have a bit of water. So here a buck converter feeding a variable resistive load, so load is resistive, is shown in the figure. The switching frequency of the switch S is 100 kilohertz and the duty ratio is 0.6. The output voltage VO is 36. So they have told us output voltage VO is constant, 36. Okay, fine. Switching frequency is 100. So I will keep on writing the information that they are providing me. F switching is 100 kilohertz. F switching is 100 kilohertz. So basically my duty ratio is 0.6. Duty ratio is 0.6. And my output voltage is 36 volts. Now what do you say? You assume that the output voltage is ripple free. Okay, output voltage is ripple free, so it is constant. My assumption is output voltage is constant. The value of R that will make the inductor current just continuous. Just continuous means what? Boundary, right? Boundary condition. They're talking us about the boundary. Okay. Boundary of continuity and discontinuity. Okay, so in this case, if my IL inductor current is just continuous, that means my IL minimum will be 0. IL minimum is 0. If it is just continuous, that means my del IL will be what? 2 IL average, because IL minimum was equals to del IL minus IL, IL minimum was equals to IL average minus del IL by 2. So del IL is equals to 2 IL average. Fine. So they are asking us to find the value of R. So I will keep on like changing the value of R, and for what value of R, I will get the critical value, right? So I have taught you critical inductance, critical frequency, not frequency, critical alpha, but I haven't taught you this, right? So this is what gate does. Gate will want you to derive a new formula. So I have derived those, but like it's not of any use because you have remembered those formulae, but it's not of any use, right? You have to go with basics now, because I haven't taught you critical resistance. There are many critical things, like critical frequency, I can say, okay? Many critical things. How many critical things I can teach you, okay? So obviously you have to understand the derivation as well, and derivation is pretty simple. So when this inhibitor is on, right? When this inhibitor is on, what I can say, what is VL when this is on? So between time 0 to t on, my VL is equals to what? VL is equals to Vs minus VO. So Vs is 60 volts minus VO, that is 36. Okay, so 36 is basically 24 volts. 36 is basically 24 volts. Okay, 36 is basically 24 volts. And what is next? So this, right? This will be del IL, and then VL is this. So now I can use that criteria. What is that criteria? That VL is equals to L del IL by dt, right? So here I know my VL, I know my inductance. They have provided me the inductance value, that is 5 milli. Del IL is 2 into IL average. 2 into IL average, okay, divided by T on. Okay, I know T on. What is I know the switching frequency, so I will be able to compute T on. I need the value of R. So what will be IL average? What will be IL average? Basically IC average will be 0, right? Because it is a steady state if the capacitor voltage is constant. So what is IL equals to IC plus IO. So if I take the average on both sides, my IL average will be equals to IC average plus IO average, and IC average is 0 for steady state, that will be equals to IO average. And what is IO average actually? IO average is actually VO average by R. It is a pure resistive flow, right? And what is VO average? VO average is 36. That I already know. All information I have, right? 36. So VO average is 36 actually. One thing I should know is this case of continuity or not? So they have they provided us alpha? They have provided us alpha, right? If I multiply like 0.6 with this, it comes out to be 36. That is fine. So it is actually agreeing with the condition that my VO is equals to alpha into Vs. So this is 36. This is coming out to be 36. So I can say that this will be 36 by R. Okay, and like my assumption was continuous conduction, and they have provided us as well. So I could have found out my VO average like this as well, alpha into Vs, which is equals to 36. Okay, like this. So this will be 24 equals to 5 into 2 into 36 by R into T on. T on is basically T on is 0.6 into T. So if I divide this, right, this will become 10 raised to power minus 2 milliseconds, and 0.6 also I have to multiply, right? So this is in milli and this is also in milli, so milli gets cancelled. So I need to find out the value of R. So this is R critical actually, R critical, right? So R critical will be what? This, if this goes on that side 30, okay, no, this can't go on that side. R critical will go here, 24 will be divided here. So this will be 10 into 10 square divided by 0.6 into 36. Okay, this is the thing, right? So but have they told us to find in ohms? Okay, they have told us to find in ohms, so we need to find in ohms. So this will be kilo, this will be kilo, and if I divide this, right, 36 by this 5, okay, 24 is also here, right? I forgot 24 is also here. So 24 is also here, so this will be, right, if I 12 and 2, So this will be 1.2. 3 divided by 1.2. What is 3 divided by 1.2? 3 divided by 1.2 is 2.5. So this will come out to be 2500 ohms. So 2500 will be your answer to this question. This question is actually pretty good. What is the homework? Homework is you do it T off. Okay. So you do it as my time is going from T on to T off. So you try to find the value of R critical from not T off, from T on to capital T. So you try to find the value of R critical from this formula. Same formula I will use, just I will go from T on to T, and you check whether you're getting the same R critical or not. Okay, so 2500 will be answer. Let's move on to the next question. So this is the next question. So let's just read the question first. A DC to DC converter here is shown operates at a switching frequency of 10 kHz and a supply voltage of 250 volts. So I will write down the informations here only. So F switching is 10 kHz and my supply voltage Vs is equals to 250 volts. Okay, and assume capacitor voltage to be almost constant. Assume capacitor voltage to be almost constant. Then find the power delivered by the chopper if the inductor voltage is shown here. Okay, so how much is the power delivered by the chopper? One thing is we cannot use our simple formulas. Why we cannot use our simple formulas? Because VL is 0 for a certain instant, and if VL is 0, that means L DIL by dt is 0. That means there is no rate of change of current. Okay, that means basically current is 0 for a certain period of time. That is what it means if VL is 0 for a certain period of time. Or you can cross verify with this as well. So let's do this, right? Let's do this. So in this instant, my VL is constant, 62.5. So it will keep on increasing. To what value it will keep on increasing? What is the value? 62.5. So what is the slope? Slope will be 62.5 by L. This will be my DIL by dt from 0 to T on, right? So how much did it increase? How much did my delta IL went to? So my delta IL, have they given us the value of L? No, they haven't, right? So I will just assume L as L itself. So it will be, if I multiply 0.6 with it, okay, because my change in time is 0.6 into T. So this will be, just hold on, 62.5 into 0.6. So this will be 37.5 into T by L. Okay, 37.5 into T by L. Okay, and into T by L. So this is the change in current. Basically, this is change in current. And what next is this? Now this is the positive change in current. So current will increase because here VL is positive. Obviously, current will increase up until this value. Now let's check for this duration how much the decrease in current is. How much is the decrease in current? So they haven't provided us this VL. Okay, they haven't provided us this VL. That's very interesting. They haven't provided us this VL, right? So actually, if you see, that assume capacitor voltage to be almost constant. So this capacitor voltage is almost constant here. Okay, this voltage is some constant voltage, and this voltage is 0. So what is the diode voltage? Diode voltage will be something negative, right? Because this is equals to plus VO. So this diode will be turned off. If this diode is turned off, right, this inductor doesn't have any path. This inductor doesn't have any path. As soon as the voltage becomes 0, the inductor doesn't have any path for the current to flow, right? Current can flow only in this, like in this fashion, right? Current cannot flow in this fashion, okay, for this inductor. Okay, so that's why as soon as the voltage becomes 0, the current will also become 0, because this switch is off already in this T off period, total T off period. This switch is already off. You can understand with that as well. You can understand from here because they haven't provided us this minus VL, right? So this minus VL, actually you have to find it out. This minus VL, actually you have to find it out. How will you find out? This area and this area will be same. Basically the total charging and the discharging will be same. From there you can find it out. So basically I will just prove it to you. If I assume that my VL average is 0 over a cycle at steady state, right? So 62 into 0.6 T equals to VL into 0.4 T. Okay, so VL will be equals to 62.5 into 0.6 divided by 0.4. So VL will be equals to 93.75 basically. Am I correct here? Yeah, no, actually this is 0.2, right? Sorry. This will be even more than that. Okay, 62.5 into 0.6 divided by 0.2. Actually VL will be very high. Okay, VL will be very high. Okay, so it will be 187.5 volts. Okay, so it is 187.5 volts. Now if you want to cross verify that whether this value is same or not, you can check with the discharging equation. What is the discharging equation? So delta IL will be basically, what is the voltage? Voltage is minus 180. So I can write it like this. So VL is equals to minus 187.5. This is equals to L into delta IL by delta T. Delta T is 0.8T minus 0.60. Okay, so this delta IL will be basically minus, if I multiply 0.2 with it, right, 0.2 into 187, like the same thing I am doing only. So this is minus 37.5 divided by LT. So like whatever it charged to, it got discharged the same amount, but in a fast way. Okay, in a fast way. It will discharge in a fast way, then it will remain zero. So that is fine. Now next what is happening is that this value, right, this value is 37.5 T into L. Obviously I know the value of T, still I am writing it in terms of unknown. What have they asked actually? I don't even know. Okay, then the power delivered by the chopper. So right, those formula won't work here. Like your VS will be equals to a VO average will be equals to VS into alpha. That won't work here. I will show you, right? I will show you. So VS is 250. VS is 250. And if I want to find, like from the formula, if you want to use it, VO average will be alpha into VS average. Alpha into VS. So alpha is 0.6 into VS is 250. So 250 into 0.6 will be what? 0.6 into 250 is 150. Okay, now is this true? Is this really true? We'll see, right? They have told us assume the capacitor voltage to be almost constant. So this VO is constant. So when the switch is on, right? So what is my VL when the switch is on? When the switch is on, right? When the switch is on, my VL is actually equals to VS minus VC. VC is constant and VL they have given me. What is the value of VL? 62.5. So VL is 62.5. So 62.5. If I do subtract with VS, what will I get? VS is 250, right? So I will get it like this. This will be 187.5 volts. 187.5 volts. So this VL is 187.5 volts. So next, can you check in the other direction? So when this switch is off, right? When this switch is off, what will be VL? VL will be equals to minus of VO. Okay, VL will be equals to minus of VO for this duration when the current is actually flowing. When the current is off, then this diode will totally block the voltage, not this inductor anymore. So when the switch is off, VL is equals to minus VO. And what is VO? VO I just computed. VO have I computed? No, I haven't computed VO. So yeah, from here I have computed, right? VO, what is VO basically? From here I have computed what is VO. This is the value of VO, right? VO only. So if I see it is minus 187.5 volts, which is actually correct, which I computed here. If you remember, I computed here, right? With the average angle, average voltage formula or the volt second criteria. But from this formula, I am getting my V as this. So this is wrong, right? This is wrong. From the buck converter formula. So obviously VO this time won't be alpha V. So whenever the current is not continuous conduction. So this is a case of discontinuous conduction. So from here, this is a case of discontinuous conduction. Okay. It is a case of discontinuous conduction. So if it is a case of discontinuous conduction, that means that formulas won't work. You have to do the derivation. That's why in chopper things become very important. There are so many formulas, but all those formulas will be useless. So like let's say get 2025, right? Though like the students who will learn from other coachings, they will just mug up, like tell you to mug up the formulas, and that won't work. That won't work in the examination. So all their preparation will go to waste. So now let's what we have to find out. We have to find out the power, right? Power supplied by the this source. What have they asked? They have asked us the power delivered by the chopper. So here what we can do is we can do it either ways. So as the chopper here, right, no loss is happening, so I can write PS equals to PO. Okay, either one I find out, I will be happy with it. Okay, so here one thing I know, that my VO is constant. In the question they have given me that my VO, this assumed capacitor voltage to be almost constant. So as my capacitor voltage is almost constant, so VO is constant, and VO is basically what, like VC is constant, that means VO is constant, and basically IO will be also constant. Why? Because I have a resistive load. So IO, right, will be equals to VO by R. So it will be some constant value. So it is 18.75 amperes. Okay, it is 18.75 amperes. And what is this? So basically next is how do I find out? So either way, like IO is also constant, VO is also constant, and you know, whenever IO and VO are constant, I can directly write my PO will be equals to VO average into IO average. Okay, it doesn't matter because IO and VO both are constant, so your like power will also be VO average into IO average, right? VO into IO both are constant, VO into IO simply. So it will be 187.5 into 18.75. So this will be equals to what? 187.5 into 18.75. This will be 3515625. Okay, 3515625 625 watt. Okay, 3515625 watt. So this is the case. Now can we do, like the answer has been done, right? This is the answer, but let's cross verify whether what we have done is correct or not. So I want to find out PS, right? I also find out PS. So for PS I need to find out IS average. So how do I find out IS average? I can plot the IS, right? So basically when the chopper is on, my IS is what? When the chopper is on, my IS is IL basically. So it will basically follow the IL. So my IS will be IL when the chopper is on, and when the chopper is off, my current, right? Current is simply 0 because like this is turned off, like it is force commutated, so there is no current flowing. So this will be the value. Okay, question has been solved. I'm just teaching you extra stuff here. So this is this time zone is what? This is 0.6 into T. Okay, this will be T. This will be, this value is what? This value I have already computed over here, right? This value is 37.5 T by L. 37.5 T by L. Okay, and now I can simply find out this area, right? I want to find out IS average. So IS average will be what? 37.5 into T by L into 0.6 T into, okay, am I doing something wrong? No, this is correct only. 37.5 VL into T. Yeah, this is correct only. I thought like T will get cancelled somehow. Okay, 1 T will get obviously cancelled into half, obviously, right? So this is L actually. This value is L. Okay, but L they haven't provided us. Okay, that is the problem, right? Oh. They haven't provided us the L. Okay. We don't know the value of L. So without knowing the value of L, right, I won't be able to find out the current. Okay, that is the problem. Can I somehow no, right? I cannot somehow know the value of L. That is problem. So yeah, like with this IS, like if they would have provided the value of L, then I would have conclusively said. So let's see, let's proceed here. This divided by total time T. So TT will get cancelled. This will be 37 into 0.3. Just hold on. 37.5, but this should be independent of L, right? Into 0.6 divided by 2. This is 11.25 divided by L into T. Okay, this is my IS average. Okay, fine. Can I somehow find out this T by L value? T by L value, I don't think I will be able to find out. Can I somehow... Okay, T they have given me, but L I won't be able to find out, right? If I know T, right? If I know T, so within this amount of time I'm going to 0. From where to where? Within this amount of time I know I'm going to 0. So this 37.5 can know, right? I won't be able to say. Okay, so unfortunately if L is not given, right, I won't be able to comment like what is the peak value of this. According to that only this average area will be here. T I know, but L I don't know, right? That is the problem. Okay, so we won't be able to do it. Like if you are able to find it way, you can tell me in the like in our group and stuff. I wasn't able to solve this, so yeah, you can think of something else. So we'll move on to the next question. So answer will be 3515, that only. Okay, so this question is also very interesting. A DC to DC converter operates at a switching frequency of 10 kHz and supply voltage 250. Again same, assume the capacitor voltage and the current to be almost constant. So current and voltage, all these are almost constant. Find the efficiency of the chopper. What is the efficiency of the chopper? So here, right, currently actually I have losses. My R switch on and VD on, right? This VD on is 2 volts and this R switch on is 1 volts, but the switch, they haven't given us any switch voltage on voltage or the diode on resistance. Okay, so in the case one, what will happen when this switch will be on? When this switch will be on, basically my assumption is this current is constant and this voltage is constant. So if this voltage is constant, what is the have they provided us any voltage? No, they haven't provided us any voltage. So when this switch is on, right, how will the equations look like? So basically my this IO, right, what will be IO equals to, so from 0 to T on, what I can say is 250 equals to IO plus 10 IO. Why I can say? Because my VL will be okay, now VL will not be 0. VL will be this VL1, right? This let's say when this is on, the value is VL1. Okay, some constant value, that is VL1. Actually, right here, right, the load voltage, intercurrent, not the load current, actually load voltage, this is a bit wrong. The statement should be assume the load voltage and the current will be almost constant, because the inductor current will be rippling around some value. It will be very low, so that will be the correct option. So this, when this is on, right, the voltage let's assume as VL1, and like IO, this IO current is flowing, IO is constant. So this is IO times 1, that is drop, and this drop, so 11 IO. So my VL1, right, VL1 will be what? Okay, then yeah, that is fine. VL1 is simply 250 minus 11 IO. Fine. What about my VL2 when this is off? So from T on to T, what about my VL2? So I will apply my KVL here. So if I apply my KVL here, this is my VL2. I'll just write this properly. Plus minus VL2. So plus 2 plus VL2 plus 10 IO equals to 0. So VL2 equals to minus 2 minus 10 IO. So this is obviously negative because IO is positive. So this thing is obviously negative, right? So now what I can do, I can apply the volt second criteria. What is the volt second criteria? Volt second criteria. Okay, so basically VL1 into T on plus VL2 into T off should be, or I can write this like this, that this is 1 minus not 1 minus T minus T on will be equals to 0. Okay, okay. So what is VL1? VL1 is basically 250 minus 11 IO, 250 minus 11 IO, and I can write this T on as alpha times T. Alpha times T. What have they asked us? So where to find the efficiency, right? Alpha times T, and this is equals to what? This is basically equals to this side, right? This will be 1 minus alpha times T into VL2. VL2 is basically 2 plus 10 IO. I have just multiplied a minus sign. This is 2 plus 10 IO. So from here I will be able to find out my IO, because alpha they have given me, right? What is alpha? Alpha they have given me, like D is 0.8. So basically alpha is 0.8. This information I forgot to write. Alpha is 0.8. So here 250 minus 11 IO into 0.8. This will be equals to 0.2 into 10 plus IO. Okay, so here I will be able to find out this right. This will be 4. So this will be 1000 minus 44 IO equals to 2 plus 10 IO. So 98 equals to 6, not 6 actually, sorry, 54 IO, right? 54 IO. Okay, so your IO actually comes out to be almost 2 point, am I right here? Okay, am I doing something wrong? This is 4. Okay, this is 1000 actually, sorry, 1000, right? This will be 998. So 998 divided by 54 is 18.48, right? 18.481 amps. And your VO, right? VO will be simply IO into R. Basically it is a load, so it will be 184.81 volts. Okay, so this will be the VO and IO. So what have they asked? So what will be, basically they have told us the current and voltage are constant. If the current and voltage are constant, so your PO, right, will be VO times IO, which is, if I multiply this, 184.81, 3415.65 watts. Now there are two ways to go about it, right? PO you have computed. There are two ways to go about it. Either what you can do is, either you can find out your IS average, okay, because like what will be your PS? PS will be PO plus losses, okay. So and efficiency is what? Efficiency is PO upon PS. So if you can directly find out PS, or what you can do, you can find out loss, and you can write here, right, PO plus PS, because PO I know. So PS will be what? PS will be VS into IS average. What is VS into IS average? So what is IS average basically? What is IS? So IS, right? IS is actually equals to IL when this switch is on. Okay, it is actually equals to IO basically, because this current is constant. As this current is constant, but this current is not. This current is not constant, right? That is a bit different. This IL and IO current are different. Okay, so it's better to not go through this route. Okay, because there will be a bit of changes here. What can I do? Because they haven't provided us the L value. If they haven't provided us the L value, right, we can directly compute through the losses. How can I compute through the losses? So in case one, when this is from 0 to T on, this R is on. So what will be the loss across this switch? So P switch, right? P switch will be what? Across the resistor, it will be IORMS whole square into R. So what is IORMS? I have just computed. IO is constant, right? Because this IO is flowing here always. This IO also, actually this IO is a bit changed here, because this is IL actually. That is true, because it will flow from IL minimum to IL maximum. But if I assume the inductor current to be almost constant, like this much we have to assume. If I don't assume the inductor current to be almost constant, then I won't be able to do it. Okay, I have to assume that inductor current, like inductance is very large. If my L is very large, right, then So then you can anyway solve it. If L is very large, if L is very high, right? If L is very high, what you can assume that your IO, like this IL is also constant. If IL is constant, then this will be basically IO anniversary to R. So this will be IL square into R, and IL, like this is a constant value, right? That is 18.481. So 18.481 whole square into 1. So 18.481 whole square. Okay. So this will be 341,547 watts. Okay, 341,547 watts. What about this case? So here, right, what about the diode conduction loss? What about the diode conduction loss? So diode conduction loss, right, here again, if I assume IL is constant, then I have to write it here itself. So assume the capacitor voltage and inductor current to be almost constant. So where is it? Where am I? So P diode. P diode will be what? P diode will be basically VD on into IO, because this is constant, right? So what is this? IO is 18.75 and VD on is 18.481, I believe. 18.481 into 2, so it will be 36.962. Okay, so this is the loss here. Just hold on. Not this. Now what is the total loss? Right, I can find out the total loss. This will be equals to P switching plus P diode. Okay, so this will be equals to PO is what? PO is basically 3415.65 plus losses. What are losses? These are the losses, right? One loss is 341.547 plus 36.962 equals to 3794. So this is 3794.159. So what will be my efficiency? Basically, efficiency will be this into 363415.65. So this comes out to be almost 90%. This comes out to be almost like your efficiency, right? Almost 90%. Let's do it in a bit other way. Okay, let's do it in a bit other way. What is the other way? Basically, I can directly find out PS, right? How I can directly find out PS? So basically, my IS, like I will assume that only because L is very large. IS will be equals to IO for the period 0 to T on, and then it will be simply equals to 0 for the period T on to capital T. Okay, so basically what will be this? So basically, what is IO? I have computed, right? It is 18.481. So what is IS average? IS average, right? IS average will be basically 18.481 into alpha, that is 0.6 divided, like this is only average, 0.6 into T divided by T. So if I multiply 18.481, just hold 18.481 into 0.6, what will I get? I will get 11.0886. So now I have computed 11.0886. If I multiply this with VS is 250, it will come out. Why is this coming out so less? What is wrong? What is VS? VS is 250. Okay, what anything have I done wrong here? Okay, one mistake I have made here. Actually, right, this power, right? This power is a constant value, but this is always not happening. This is happening for t on to t. So I have to multiply. Actually, I forgot to do this. What is the power? Power over a cycle. So I have to divide by the time period as well, right? So actually, I messed this one up. So this is the mess one. Just hold on a second. Let me just check if everything is recording or not. Just quickly check. Yeah, this is recording, and yeah, this is also recording. Fine. Hello. Yeah. So one mistake I made over here, actually, right, this power, right, I have to compute within time period, because this is constant, this power consumption is constant, but I have to compute the time period, right? So this is happening from t on to t, that is from 0.2 divided by 0.2 into t divided by t. So this is right, actually, to multiply 36.962 into 0.2, so this will be 7.7, this is t only, 7.4 watts. Okay, and here as well the same thing, right? This is constant, this power consumption is constant, but I have to compute the power over a period. So this will be again 0.8 t divided by t. So this fell, right, 341.547 into 0.8. So this will be 273. Actually, this will not be 341, 273. Okay, 0.23 watts, 0.24 watts. Okay, and so like here, right, this will be wrong. Actually, I have computed the loss wrong. So it will be 273 plus 7.4. The total losses will be 280. So total losses, right, total losses will be, this will be 280, almost 280.6 watts. And if I add it with the current, like with the power consumed by the load, 3415.65, it will be almost 3696.3. So what will be the efficiency now into 3415 in 0.65? So this is 92%, 92.4%. So now this is a bit correct. This will be 92.4%. Okay. Now, what about this? What is IS average here? This is a 0.8. This is not 0.6. Sorry, this is 0.8. So this is 0.8. This, right, this value will be basically 18.481 into 0.8. So this is 14.748. If I multiply it with 250, what will I get? I will get 3696. So I'm exactly matching in my numbers, right? Exactly, my numbers are matching over here. So this value, my IS average, like my PS, right, from the case 2, like I will just change the colors over here. PS from this different color is VS into IS average is equals to 36.96.2. So like almost point by point I'm matching. So in this case also efficiency will almost be equals to 92.4%. Okay, so you can do it with this and this. I have just shown you the both the methods so that you will be able to understand how to solve each question. Okay, that is very important over here. Okay, so next, this question is pretty interesting. Why? Because here, right, a DC to DC converter operates at a switching of 10 milliseconds. Supply voltage is this. You have to calculate the ripple in load current. So I will just pause the video, try to solve it, because this question is a bit tricky. Okay, so a DC to DC converter operates at a period of switching of 10 milliseconds. So our time period, right, time period is 10 milliseconds. Okay, fine. And the supply voltage is 250 volts, that is VS is 250 volts, that is also fine. Next, what are they asking us? So next, right, they're talking about calculate the ripple in the load current. What is the ripple in the load current? So there are two formulas for ripple in load current. If you remember, I taught you for the linear case and for the non-linear case when the current is exponential. So here actually they have given us the inductance value. So I will just tell you one thing, is that whenever they have given us the inductance value, whenever they have given us the they have given us the inductance value. So whenever they have given us the inductance value, then you need to check. Check what? Basically tau. Okay, tau. Or generally, in general, right, if your switching frequency is less than 500 hertz, then also you need to check. Okay, so if you are checking for tau, right, what is tau? Tau is L by R. L is 50 millihenry, R is 10 ohms. So it will be 5 milliseconds. Tau is 5 milliseconds. To totally discharge or charge, how much time it will take? 4 tau, right? 4 tau. So 4 tau is 20 milliseconds. So this time tau is not very small than t. Tau, right? 4 tau is actually larger than t. So obviously this is the case of non-linear, or I can say exponential charging and discharging. This will not be the case of linear charging and discharging, as time period is not that high. Time period is low actually than the tau. So if you remember correctly, few things if you remember, like how to remember the Iomax formula. So Iomax, first thing what you remember is like this. You have to remember this. You have to remember. No choice for this, because derivation will take time for this. So this is Vs by R. Vs by R was there. Next, what is there? Vs by R actually gives us the unit. Next, there were few terms, which was 1 minus e raised to power something, then 1 minus e raised to power something. So if I remember, for this Iomax, right? Iomax, actually everything was negative. If I have maximum, this will be negative. So if this is negative, this means this is minus. Always this will be T on. The first numerator term will be T on only. T on by tau. And in the bottom I will have minus T by tau. Okay, this will be the thing. So this will be equals to what? Vs I know 250. R I know. R is 10. 1 minus e raised to power minus T on upon tau. So it is basically alpha. Right? So it is minus, like alpha is how much? Alpha in this case is 0.6, right? 0.6. Duty cycle is 6, so it will be 0.6. So this will be 0.6. T, okay, no. Sorry. Minus 0.6 T upon tau. So T is how much? T, capital T is 10 milliseconds and tau is 5 milliseconds. So into 10 divided by 5, and this will be 1 minus e raised to power minus t is 10 divided by 5, so it is e raised to power 2. So this will be 25, and this value I will just compute this value. Okay, so 0.6 into 2 exponential. If I do exponential, this will be 1 minus 0.3 divided by 2 exponential 1 minus this, so this is 0.86 actually, 0.8646. so this actually comes out to be, just quickly computed, 20.23. okay, this comes out to be 20.23. am I doing this correctly? 5, 10, yeah, everything is correct here. Only 1 minus this 0.7 by, okay, this will be 20.23. okay, and what about the IO minimum? So IO minimum, right, will be just the same formula, just here all the plus sign will be present, right? So that's how it is easier for you to remember. So IO minimum is basically Vs by R. Like I will just copy and paste. So if you remember one, right, other one will be easier for you to remember. Just remember the IO maximum, and IO minimum will be automatically in your mind. So this will be plus, this will be plus, so this will become 25. And okay, let's quickly compute it. T on is actually how much is it? This is 0.6, right? Alpha is 0.6, so 6 upon 5. So 6 upon 5, if I raise it to the power exponential, this is 3.3, right? So this will be 3.32. Okay, I have one minus as well. Okay, I have to subtract one as well. Okay, just hold on. Minus 2.32 divided by 10 upon 5 exponential plus 1 minus 6.389. So this IO minimum is into 2.32 into 25. This will be almost around 9 okay, 9.08 amperes. Okay, this will be almost around 9.08 amperes. So what is my ripple basically? What is my delta L? So my delta L actually comes out to be 20.23. I'll just quickly compute this again. Actually, I am having a bit of doubt. So 0.6 into 10, which is 6 milliseconds by 5. This will be exponential. Okay, fine. Plus 1 divided by 2 exponential plus 1. Yeah, this comes out to be 0.8, and if I multiply 25, this will be 20. Yeah, this is correct only. 20.23 minus 9.08. So this will be 11.124 amperes. Okay, this will be 11.124 amperes. So this will be the delta L. Now, if you would have used that other formula, what was the other formula? So this will be answer, this will be the end, right? This will be answer, this will be the end. But if you would have used this formula, linear, then what do you know? L into del IL by T on. Okay, because the on time is equals to VL, and VL is what? When the chopper is on, VL is what? VL is basically equals to, like, this is the L, right? VL will be VS minus this I into R, IO into R. So okay, just hold on. Yeah, what is IO into R basically? Do I know the average current? I yet don't know the average current. So basically, what is VS average, right? What is this? Just hold on. What is this? VS average, VO average is basically alpha into VS. So like it is for continuous conduction. So alpha into VS, I can do it like this. So my VO will be equals to alpha into VS. So alpha is 0.6 into VS. So 250 into 0.6. So it is 150 volts. What is IO average? IO average is basically 150 by 10, which is 15 amperes. Okay, yeah, but I know IO average, but one thing I'm making a mistake. What will be VO in this case? Actually, VL. What is VL in this case? What will be the VL value? Okay, actually, this inductor, right? This inductor should be actually present over here instead of here. There is a mistake in this question actually. The inductor, right? But the inductor can be present over here. It can compute the load current. This capacitor is almost giving some constant voltage. That voltage is basically this voltage, right? That is 0.6 into 250, 150 volts. Okay, fine. 150 volts I am giving. What is the inductor current? So sometimes this is increasing then reducing. Okay, actually, right, I don't think we will be able to do it because there is a capacitor as well. Okay, actually, right, this capacitor won't be present here. Sorry for that. Else the question will become very will it become very difficult? Yes, it will become very difficult. The capacitor is not present. I'm sorry, the capacitor is not present. Only this part will be present over here. So then this will be VS by R. This will charge and discharge through here. Okay, fine. So now if I give this, right, what will be the VL in the positive half cycle? So VL in the positive half cycle, this, right, here it is 250 and this is 150 volts. So current, how much current is flowing? 250 by 150, 100 by 10. 100 by 10, that is 10 amperes. This is 100 volts and this will be 50 volts. Yeah. So basically, what is happening? I'll just show you. So what you can do is, when this is on, right, when this switch is on, so basically I can say that my VO is equals to VS. V is equals to VS when the switch is on, right? So what is my VL at that point of time? VL, right? VL will be like this, name this voltage as VR. It will be VS minus VR. Okay. And when this switch is off, it will be VL will be minus VR basically. So from here I can compute the VR. Okay. So that I am able to find out my inductor voltage. So VR is constant because I'm almost assuming constant current. Like obviously it is rippling, but still I'm assuming constant current. So this will be VS minus VR, and then here minus VR, and this is alpha into T, and this is T. So this is VS minus VR into alpha into T should be equals to VR into 1 minus alpha into T. So here VS into alpha into T, this is VS and T gets cancelled, alpha VS, and that side, right, what happens is that side becomes VR alpha will get cancelled and just VR will be remain. So VR, right, VR is equals to alpha into VS. So VR is equals to alpha into VS, which is VR is equals to 0.6 into it, that is basically 150 volts. So basically if I just choose for this turning on time, right, so I will use this formula. So this will be L is how much? L is 50 millihenry, okay, into del IL that I need to compute. T on is 0.6 into T equals to, which is in milliseconds, I think 10 milliseconds. So this will be 10 milli, okay, 10 milli. And what is the VL now? VL is actually during the on time, it is VS minus VR, which is 250 minus 150, which is 100. Okay, so this comes out to be, this is actually 5, so this is 20 into del IL equals to 20 into 0.6, so this will be 12 amperes. Okay, so this comes out to be 12 amperes, and actually what we did we compute 11. So this was actually pretty close, but still we are off by, like, the error is 10%, right? Error is 10%. So obviously we won't be able to solve it like this, okay, because like there is error of 10%. Okay, so there is an error of 10%. So obviously this is the wrong method. So whenever, like, this is inaccurate, right? Because we are just assuming a non-linear curve to linear, so obviously it will be somewhat inaccurate, right? We'll get the answer nearer to our value, but obviously we are linearizing it, approximating it, so we will get inaccurate. If let's say our tau was very, very less than capital T, then obviously that will be almost linear, so we won't have to worry about that. So that's why this is inaccurate. This will not be the answer, okay, because I am assuming it is linear. Okay, I am assuming it is linear, but actually in real life it is not linear. That's why we have to use this formula. Okay, so yeah, I hope you enjoyed this lecture. We actually solved very, very interesting questions here, and like fewer own questions and like fewer gate questions. And trust me, like, we have studied a lot about step down chopper. Everything has been covered for step down chopper. I hope you are confident. And for step up and step up down, right, we'll move a bit fast because basic concept, all those things are clear. We'll move a bit fast for step up and step up down chopper, and then we'll study a bit about Fourier series analysis of the supply current, and that will be it. Basically, that will be it for the choppers. Hey everyone, welcome back to PrepFusion. I'm Anish, and today we'll start our lecture 4 on choppers. So we have learned about step down choppers, which are also known as buck converters. So we gave it a considerable amount of time so that we can clear our basics, and that is the most important chopper, buck converter. That is the most one. That is a chopper that we mostly use in industries and all those things. Now in this lecture, we'll study about step up chopper, also known as boost converter, and we'll do a few assignment questions. We'll see if we are able to do in this lecture, or we have to take another lecture for the questions. So what is step up chopper? Basically, step up chopper, right, will basically give you the output average voltage more than the supply. Okay, more than the supply. But you might say how that will happen. Obviously, power is consumed, right? As power is consumed, the current will reduce. The amount of current that it gives at the output, that will reduce. Okay, that you have to understand. So here, first a few assumptions are there. Obviously, that if I am like analyzing a buck boost converter, basically the IO, right? IO should be continuous. That is, the output current should be continuous. Or best what I can say is this, right? Yes, I'm feeling really sleepy. This inductor current, actually, not the IO. This inductor current must be continuous. Sorry for that. Like everywhere, right? Inductor current must be continuous. Then only we can apply all the formulas and volt-second criteria, all those things. So then only the average voltage formula will come up. So inductor current is continuous. Then IL minimum is greater than 0. Then power electronic devices has to be idle. And obviously our assumption will be we will get our VO greater than VS. How will that happen? When we will do the analysis, there we will understand. Few key points are here. First of all, to design a step-up chopper, an inductor is mandatory in series with the supply. So this is basically the construction. So you should remember, whenever you see this type of template, right, whenever the inductor is directly connected across the supply and the chopper is parallel, like in between, in the middle of both supply and the load. If you remember, chopper was in series with the supply in the step-down chopper, and inductor was towards the load side, and in the parallel side there was a diode. So everything has been interchanged. And next what will happen is that this inductor, right, this inductor actually come up here for buck boost chopper, and this switch will be here and the diode will flip. Okay, when you will study buck boost chopper, you will understand. So yeah, you have to remember this at least, like the circuit diagrams for each chopper. If you are able to identify, right, it will be useful. Like if you are not able to identify, then also you can solve the question with the basics, with the voltage second criteria, but that will take you more time. But if you know what you are expecting, then it's easier, right? That's why obviously you should be able to identify by looking at the diagram, looking at the circuit diagram, what type of chopper is this. High switching frequencies power electronic devices are typically required to design step-up choppers. Why high frequency? I will explain later on. Okay, basically because, right, this inductor needs to energize and then de-energize here, and this inductor needs to be connected to the supply for longer amounts of time so that it gets more energy. So that's why high frequency is there. That's why they switch close and open, so close and open, so it will be connected to the source for a longer amount of time. I will explain this later. During the on duration, the inductor stores energy from the supply. So when this chopper is on, right, when this chopper is on, what will happen? This DC voltage will directly come across this inductor. This is 0 volts, and if I apply the KVL, so if DC voltage source is directly connected across the inductor, what will happen? It will linearly increase. It will linearly increase. The flux will linearly increase, and obviously it will linearly energize. Like current will linearly increase. Okay. Next, since passive elements like inductors can only act as an energy source for short durations, it is crucial to maintain continuous operation. So that's why the switching frequency is very high, because once I open this chopper, right, what is happening? This inductor is present, and this inductor is actually like still current is flowing like this only, but this inductor is losing its energy to the load. Okay, this inductor is losing its energy to the load because right now it will provide more voltage to the load. Okay, more voltage to the load. How when we do the analysis, there we'll see. And then what will happen? It will slowly lose out its energy, because a steady state, what will happen? It had higher amount of current, so it was increasing linearly. Okay, let's say it had IL max. Then what happened is now let's say this is R, right? If this is R, so what will be the steady state will be Vs by R, and that Vs by R will always be somewhere here. So the current will reduce exponentially and it will be settling. So energy will reduce here, right? And that is the reason why we have to keep on keep on this chopper switch on in brief times, because it has to energize to the supply. I want to increase the current through this so that it can pump that extra energy to the load. Don't worry, when we will do the analysis, we will understand. Just giving you a brief overview now. Since passive elements like inductors can only act, okay, I have already read it, to maintain an almost constant load current, the duty cycle alpha should be greater than 0.5. This condition I will come to. How duty cycle has to be greater than 0.5 to maintain this almost constant load current. I will come to. Like here, right, one thing you should just know is basically your T on should be greater than T off. Why is this the case? I will explain. And as my T on is greater than T off, obviously my alpha or duty cycle will be greater than 0.5. Okay, so let's come to analysis of converter. In steady state. So analysis of converter in steady state. So what will the analysis of converter in steady state? Just taking an example, like how am I getting more voltage? How am I getting more voltage? Just I will take example, okay? And these type of question I have done, but I will like these similar type of question I have done previously as well. I think it was gate PYQ. Now here there is a switch which is at position X from 0 to T on. So basically, okay, not at position X. Sorry, it should be opposite around. It should be opposite. So what I will do is I will just change this positions, right? X and Y, which is at position X from 0 to T on. So this is at position X from 0 to T on. So totally my inductor will totally come across the voltage source, and is at position Y from T on to T. Fine. So from 0 to T on, what is actually happening? 0 to T on, what is actually happening? Sorry for that. My inductor voltage, right, is 100 volts. Like I'm really sleepy and didn't got enough sleep. So my inductor voltage is 100 volts, and is as my inductor voltage is 100 volts constant. How can I write my inductor voltage? It is dIL by dt, right? So basically dIL by dt is constant. So what is IL basically here? IL will be a linear function. So IL, right, will be, if I write it, it will be 100 times T, okay? And IL max will be 100 T on, okay? It will be 100 T on. So like it will go on until T on. Now from T on to T, right? From T on to T, from T on to T, it will be what? Basically, right now what will happen? The steady state, right, the equation of the current, IL of T will be what? It will be Vs by R Vs by R is basically Vs by R. Current will be Vs by R 1 minus e raised to power minus T upon tau, and obviously plus initially it has some current, right? Initially the inductor has some current. What is the current? That is 100 times T on. So at T equals to, okay, this should be T on, right? T minus T on, sorry for that. This should be T minus T on. Yeah, I have written it correctly. Now let's basically deduce this, right? What is happening? What is happening here basically is that as this has some initial current, right? So inductor will actually produce some current. Inductor will actually, sorry, not voltage, that will be very high. So at, like, my one thing is for sure that my 100 T on, right? 100 T on will be higher than Vs by R. Okay, 100 T on will be higher than Vs by R. Okay, that is for sure. What is Vs by R? Vs by R is 10 by 100 by 10. So T on will be, T on has to be greater than 1 by 10. So for this chopper to work as a boost chopper, right, T on has to be greater than 1 by 10. What do I mean by that? I will just explain in a second. Okay, so T on has to be greater than 0.1 seconds. So let's assume a number. Let's assume that my IL T on minus, right, is basically 200 amperes. Let's assume this number, it reaches to 200 amperes somehow, or depending on the value of okay, what value of T on, okay, depending on the value of T on. So it reaches to 200 amperes. So how will my circuit look? So here, right, my VO is what? My VO is what? So at the starting my VO is 0, right? There is no current, so my VO is 0. From 0 to T on, 0 to T on, my VO is simply 0, right? No current is flowing, it is open circuit, so it is simply 0. Now as soon as the switch is closed, what will happen? As soon as the switch is closed, okay, I will just copy this circuit. Not closed, right? As soon as the switch is moved to position Y. Okay. This is VL and this is VR, right? Now what I will assume is, the assumption is obviously what will happen, inductor will de-energize, right? The voltage will reduce. But my assumption is it is almost constant because the overall time period switching frequency is very high. That is why I have told you high switching frequency. If I have high switching frequency, here the voltage of inductor will reduce. You're correct. Voltage of inductor will reduce. Why? Because this is 200 amperes and my Vs by R is what? 10 amperes, right? Vs by R is 10 amperes. Here I've written 10 amperes. So it will go from 100 amperes in this region, right? From T on to capital T, it will go from 100 amperes to 10 amperes. It will reduce. The energy across the inductor will reduce. Okay, but it reduced very slowly, right? Let's say the switching time period is so less that it went back to this Y position and then again came back. Okay, then again came back. So that's why the voltage reduced is very low, and I assume that the voltage is almost constant. So what is the VL during this period? So during the on period, VL on is what? VL on is basically 100 volts. Okay, 100 volts. And what is VL off? So here, right, what is the current that is flowing just at the instant when the switch is moved to position Y? Current flowing is 100 amperes. So 200 amperes. So this voltage will be what? VR will be what? 200 into 10, that is 2000. Okay, 2000. And VL equals to 100 minus 2000, so which is minus 1900. So obviously it will discharge. Okay, it will discharge very fast, but the switching period is very fast also. Okay, it will totally come back as the switching frequency is very high. Okay, so VL is minus 1900, or what you could have written? You could have written like this as well. You could have written like Vs minus VR, and from there you could have find out the VR. Okay, from there you could have find out the VR. So VR is 2000 volts for what period? VR is 2000 volts for what period? From, like, I'm assuming that it is almost constant, although it will reduce, but I'm assuming it is almost constant. So VR is equals to 2000 volts for the period T on to capital T. Okay, so that is a period for which my VR is 2000 volts, and for other period is 0. So what will be the average voltage of the output? Average voltage of the output will be 2000 into, now what is the, I don't know the on period, right? I don't know the on period, so we will assume that the on period, okay, or the alpha for this switch is basically 0.8. Okay, alpha for the switch is 0.8. So this will be 0.2, basically T is the T off into T divided by T. So this comes out to be 400 volts. Okay, so yeah, this comes out to be 400 volts if I multiply 0.2. Right? So here what you observe is basically my VO average, right? VO average is actually more than the VS. VS was 100 volts, but I am getting 4 times that. But one thing you have to keep in mind, the drawback is I'm getting huge voltage across the load. So even though I'm boosting, but this is not the peak voltage. Peak voltage is something else. Peak voltage is actually 2000 volts. Okay, so that is huge. So that you have to keep in mind. That thing you have to keep in mind. So for a boost converter, just I have shown you one example that how am I boosting the voltage. How am I boosting the voltage? Basically, I am boosting it to a very high value. Then it is remaining at that, and the average within that period gives me 400 volts. Okay, the average gives me 400 volts. Okay, now let's come to the step up chopper. So if I come to the analysis of step up chopper, we'll analyze in the steady state obviously. So this, right, I will show, and I will just write here like the subtopic, how to boost voltage. So what is case 1? Case 1 is from 0 to T on. So when this switch is closed, right? When the switch is closed, my inductor will charge. Okay, and it will linearly charge. Why? Because my VL is equals to Vs, which is greater than 0. Hence my DIL by dt is greater than 0. Hence my IL will increase. Okay, simply my IL will increase. What are the other currents? Other currents are ID. So ID is the diode current, which is equals to IO equals to 0 ampere. So the load is totally off right now. Load is totally off, and the SCR is SCR, not the SCR, the switch. The switch, chopper switch has been just triggered. What is the voltage across the diode? So voltage across the diode, right, will be simply minus VO. Okay, will be simply minus VO, and it will be 0. Like basically, if there is a R load, right, R load, then it will be 0, and if there is a RE load, it will be minus of E. Okay, minus of E. So this is for a R load. Okay, RE or RLE, or like RLE also you can say, RE, RL, whatever you want to say, right? Okay, fine. Now let's move on to the next case. But here one thing you observe is that my IL is increasing. It is increasing to whatever I have explained in the example, right? Example. So now what happens is the chopper, right? Chopper is actually forcefully turned off. Chopper is forcefully turned off. So my chopper is forcefully turned off. Okay, chopper is forcefully turned off. So now what I can say is, as chopper is forcefully turned off, right? Like I've used force commutation. So if this is on, this diode will turn on. Why this diode will turn on? This inductor will change its polarity so that it can turn on the diode. It needs to flow its current because IL of T on minus has reached to its maximum current, IL max, and inductor will try to flow that same amount of current. So now this will become like load and source will become this. So my IO at T equals to T on plus will be basically equals to IL max. Okay, it will be the inductor current basically. Okay, and so what will happen is my assumption is IL max is greater than Vs by R, else the chopper will not work as a boost converter. Chopper will not work as a boost converter. IL max has to be greater than Vs by R. Okay, or for simple R load, this is the case for R load. Okay, and for RE load, it is Vs minus E divided by R. This is the case for a RE load. Okay, so here what will happen is that what will be my VL will be Vs minus VO. Okay, so we will assume constant, assume some constant voltage. Assume, why am I assuming it? Assume constant. How can I assume? I can assume as constant as my switching frequency is very high. So I have got very less time. Like it will reduce. The VO will reduce, but it will reduce very low amount. So I'm just approximating it. So it will be almost constant. So if I approximate it to be almost constant, the output voltage, right, will look something like this. When the chopper is on, the output voltage is simply 0 because the chopper is on. This is shorted, right? Shorted. So output voltage is 0. The inductor voltage is Vs. When the chopper is off and the diode is turned on automatically by the inductor, the output voltage will be this Vs plus VL, right? Vs plus VL. So this is also, I am assuming that this is some constant voltage. So this is Vs plus VL when the chopper is off in this region. Chopper is off, and again it is 0. But what another case could be happening is that for RLE load, when the chopper is on, the output voltage actually is minus E. Sorry, not minus E, plus E, because the current is 0. So drop across the resistor is 0. Inductor doesn't have any change in current as the current is still 0 at and steady state. So the voltage across the inductor will also be 0. Just the E will be present. So if I have RLE load, then I will get a graph something like this, that when the chopper is off, my voltage will be equals to E. Okay, and when the chopper is when the chopper is on, the voltage will be basically E, because no current is flowing through the output. When the chopper is off, the voltage will be directly equals to what? Vs plus VL. Okay, it will not depend on E anymore, it will be Vs plus VL, so it doesn't matter then. So yeah, this is for the E factor if E is present. Okay, let me change the colors. This will be much more confusing. Okay, what about the diode voltage? So when the chopper is on, the diode, right, diode voltage, it will have to block some negative voltage. It will be minus Vs plus VL. How is it minus Vs plus VL? It is minus VL minus VL. Just hold on, this is plus minus, so yeah, this point, right, this point is minus Vs. Okay, no, this is minus. If I apply KVL through this, it will be minus Vs plus VL plus VD plus VD. Okay, so it will be actually Vs minus VL, not this, it will be Vs minus VL. So this will be the value of the diode voltage, because if I apply KVL, right, this will be like yeah, if I apply KVL here, it's plus minus, so this is minus Vs plus VL plus VD, and this is VO is 0, VO is 0, so it will be VD will be equals to Vs will go on that side, Vs minus VL. Yeah. One important point is, if let's say I don't have a simple R load, I have a R LE load, or E is present. If E is present, right, so the right hand side will be simply E. Okay, so if I again apply KVL, this will be minus Vs plus VL plus VD plus E. So right now, right, this will be Vs, this will come down more lower, right, this will come down more lower. Okay, why this will come down more lower? Basically, this is Vs minus VL minus E. Okay, so due to the subtraction, extra subtraction of E, I will come down more lower. It will be more reverse biased. Okay, so this will be the waveform for RL and RLE load. So for chopper, right, for chopper, this voltage will be Vs minus VL, not Vs plus VL. As one thing you have to notice is that VL, I have chosen my VL polarity like this. My VL polarity, right, is this. I will just show you. VL polarity is like this. So from 0 to T on, the VL is positive only. If I compare with respect to this notation, from T on to T, my VL is actually negative. My VL is actually negative. So if my VL is actually negative, right, what does it mean? It means that like VO will increase, because VO will be totally Vs minus VL, and VL is negative, hence it increases, VO increases further. That's why VL is negative. So obviously, even though here it is written Vs minus VL, but it will be more positive. Chopper voltage will be more positive. It will block the forward voltage. And here Vs minus VL, this VL is positive only. Okay, this VL is positive only, so it will reduce. Actually, what is happening? A Vs minus VL, right, is 0 for like if it is not a RE load, and if it is a RE load, it will be minus E. Actually, these two things, right, are equal. These two things are equal actually. So your diode actually voltage will not block anything. It will be almost towards 0. Okay, so yeah, that is the thing about the voltages, currents. So when the from 0 to T on, the inductor current is increasing, then again the inductor current will reduce. Why? The voltage, inductor voltage is reducing, and it is discharging, because from IL max it is going to IL min. Okay, it will obviously, it can't go to totally Vs by R. It will again charge after that, so it will be rippling. So there will be a ripple. Okay, this will be a delta, right? What is the ripple of the output? So in this case, right, output current actually is something like this. The VR and IO is this. Like I will come to the graph next as well. So here, like this will be the output current will be a replicate of the voltage drop across the VR. So it will suddenly, it is 0 before that, before T on. After T on, suddenly the diode will turn on and it will reduce. It will just follow the inductor current. Okay, in the period from T on to capital T, and from the period from 0 to T on, it is 0. Okay. Next, what about VL? What about inductor voltage? What about inductor voltage? Inductor voltage is equals to Vs when the chopper is on. When the chopper is on, it is equals to Vs, and when the chopper is off, right? When the chopper is off, it is equals to V minus of VO minus Vs. So basically, what does it mean here? What does minus of VO minus VA mean? So if I simply apply a KVL, right? This is VO, let's say, and this is VL, and this is Vs. So minus minus Vs plus VL plus VO. So there, on if I take it on the right hand side, it will be Vs minus VO. So this should be Vs minus VO. So this is actually Vs minus VO. I can write it like this as well. Like instead of this minus sign, extra minus sign, I can write it like this as well. Like, or why am I writing like this? If I just take this minus sign inside, right, it will be Vs minus VO. But why am I writing it like this? Just to show the significance that VO is greater than Vs, and overall this thing becomes negative. As this thing is negative, it will be somewhere around here. So overall, this is negative. Overall, this is negative. So this will be minus VO minus Vs. Okay. So this is the inductor voltage, and from this voltage waveform only, we will be able to find out our current. Average voltage. Okay. So current waveforms are same only. The chopper will follow the inductor current for the period 0 to T on, and it will be 0 for the period T on to capital T. The diode current or the output current will be same as this graph VR. So it will follow from T on to T, capital T, the inductor current, and it will be 0 for other periods. Okay. So these are the waveforms basically. Now we'll do the few derivations. So first derivation is the source average current. Source average current is also equals to the inductor average current, right? Because this time the inductor is connected in series inductor is connected in series with the source. The inductor is connected in series with the source, half into delta L into capital T plus IL minimum into T divided by T. Okay. So what I can say is this will be half into delta L into T. Okay, half into delta L into T plus IL minimum into capital T. Okay, so like you can see, and what will this come out to be? This will simply be, if I observe, like if you just break this down, delta L. What is delta L? Delta L is this ripple, right? So I haven't marked that delta L here, so I'll just mark it very quickly. Delta L is basically the ripple. Okay, so delta L is a ripple. So if my delta L is a ripple, right, if I break it down, what is delta L? Delta L is basically equals to IL max minus IL min. Okay, delta L is basically equals to IL max minus IL min, and your ID will be something like this. And what about your IS average? So this will be IS average, which will be equal to IL average, and IS RMS will be what for this type of waveform, right? Your IS RMS will be simply this value. Basically this we have derived previously. Okay, so now, right, whatever we'll do, so how I used to derive previously, I used to derive all the expressions from this waveform. Previously, if you remember, the inductor was connected in the series with the load, so I was deriving all the current expression with respect to the load current. Now I will derive all the expressions with respect to the supply current, because I know the RMS value of this supply current, and from there I can derive. I'll just explain, okay, as we move along. So how do we compute the VO average? For this, right, we need to find out the volt second criteria, because here, right, I like my VO average will be basically Vs plus VL into 1 minus alpha into capital T divided by T. This will be my Vs average. So for this, I need to draw the inductor voltage waveform. So inductor voltage waveform is this, and I will use the volt second criteria. So here if I want to use my volt second criteria, right? So this VO is some constant value. Okay, so what I can do is that I can write this let's put it this way only. So I will use my volt second criteria. So this will be Vs into alpha into T should be equals to this value is what, VO minus Vs into 1 minus alpha into T. Okay, so this is some constant value. This VO is some constant value that is appearing across the output for the time T off, right? So what will be this? So this here, right, this alpha into T Vs gets cancelled. I have only been left with Vs into T, and on this side I have Vs is equals to 1 minus alpha into VO, right? So our VO average, right, VO average comes out to be Vs by 1 minus alpha. Okay, so our VO average will comes out to be this, so we don't need to write this expression anymore. Okay, we can ignore this. VO average formula will be this, and if alpha is if alpha is greater than 0.5, obviously this will be very high. This value will be very high, right? That is one of my VO averages. IO average you can simply compute with the help of VO average minus E by R. If E is 0, then it is VO average by R. And the ratio of VO average and IO average this time, standard ratio, not IO, sorry, Vs will be equals to 1 by 1 minus alpha. Okay, this will be greater than 1. Okay, this product will be greater than 1. What about the RMS? So now, right, I will obviously derive everything with respect to this. Well, actually this will be like this is not multiplied, this will be divided, right? Yeah, it will be Vs by 1 minus alpha. Why is this 1 minus alpha? Have been explained previously. You can find out your output power with respect to the losses. If losses is 0, if chopper is idle, PO will be equals to PS. Analysis of load. So now, right, I will derive everything with respect to the source current or the inductor current. So obviously my load is active for only T off period of time. So my IO load average current will be 1 minus alpha into the source current. Basically area will be reduced. So again you can see IO average by IS is 1 minus alpha. It is the inverse of the voltage relation, simply like a transformer. Your IO RMS, just I will take the under root of 1 minus alpha, I will get it. PS same, right? It will be basically Vs into IS average. This should be in the supply side, not in the load side. Sorry for that. Okay, here I should have written analysis of supply PS. Yeah, PS should be here only, not here. Like this is the standard relationship for a step up chopper, but you have to understand only valid if IO is continuous, else everything else will change. All the things will change. Okay, and from here, from this equation, we can see that if the chopper is ideal, that even if the chopper is not ideal, right, what I can observe is my VO average into IO average will be equals to Vs into IS average. Okay, if the chopper is not idle, then you have to check. We have to check for other things. Okay, so yeah, that is one thing. And like for analysis of chopper, what will be the chopper average voltage? It will be simply equals to VO average, because chopper is directly connected across the output. Okay, why? You can observe, right? You can observe chopper. If you observe, the chopper is directly connected across the output. Like when this diode is off, that is the other case. It is 0. When the diode is off. When the diode is off, this chopper is on, so this is 0 volts, and when the chopper is off, this is simply equals to VO, so this will be VO average only. VO average is 1 minus alpha into VO. So VO average is what? This like chopper voltage will be VO average only, which is Vs by 1 minus alpha. Okay, you can observe from here as well, from this graph as well. If you observe from this graph, okay, where is the chopper graph? Here, right? So it will basically Vs by 1 minus alpha. Okay, so now if I go to some other parameters, RMS basically 1 minus alpha into 1 root. Chopper current, it will be alpha times IS average, because chopper is supplying the getting the source current for T on period of time. Then the current is 0. So obviously it will be alpha times IS average, like everything I'm deriving with respect to source current. Then your diode current, like ID average will be IO average, because whenever the diode is on, the load is also on, that means the ID average will be equals to I average. Whatever you computed for load, that will be followed for diode. Chopper efficiency, same thing, right? PO upon PS. Sorry, here I've done one thing wrong. It is PO upon PS. So this will be simply PO is this. Okay, this is nothing wrong actually. This should be PS minus losses. Sorry. Yeah, if I do PS minus losses, I will get my PO and divide it by PS. So I will get my efficiency of the chopper. What about VOAC? What about VOAC? Basically ripples and all those things. All those formulae you know, right? How to find out, like subtract the RMS value, all those things. So all those things we know. And now let's do the analysis on inductor current. So ripple I have already explained. It is IL maximum minus IL minimum. So from 0 to T on, like now, right, finding out the ripple is very simple. I will not derive any formula. I will just directly solve for linear case. Okay, we are solving for linear case. If my switching frequency is very, very high. Okay, from 0 to T on. Okay, from 0 to T on, your VS will be simply equals to VL, right? Because that chopper is off and VS is VL. And what about my L di dt? L into DIL, that is equals to DIL dt, right? DIL dt. So I can like linearize it because my time period is very small. So basically it will be VS will be equals to L delta IL by T on. Okay, delta IL by T on. So from here I will be able to compute my ripple. What is my ripple? Delta IL equals to Vs into T on. T on is alpha times T divided by L, or I can write it like this: Vs into alpha divided by FL. So this is like, is this a formula? No, right? I will recommend you to derive this because it will take you merely 10 seconds to derive. Okay, so no need to remember this formula. Just derive this formula, right? Just derive this formula. What is the ripple of inductor current? This will be very, very helpful. And from that you will be able to find out your maximum inductor current, minimum inductor current, and you will be able to find out your other parameters. Now critical value. Let's come to critical value. Critical value of duty cycle. Whenever there is a critical value, that means it is just on the boundary of conduction. Boundary of conduction, right? Conduction and like no conduction. So in this case, my IL minimum will be actually 0. If my IL minimum is 0, basically my del IL, right? Del IL. If my IL minimum is 0, basically my del IL is equals to IL average. Is equals to 2 IL average. Okay, so this is my del IL. So now what else I can say? What else I can say is that what is a del IL? If you remember, what is a del IL? Delta IL, it is alpha into Vs by FL. Okay, now I am talking about the critical angle of this alpha, right? So alpha will change to alpha C. So alpha C will be equals to 2 IL average. IL average is simply IL max also I can write, or you can write IL average. 2 IL average. What is IL average in terms of IO? That also you can specify into FL divided by. You don't need to remember all this. Just I'm deriving with the formulas so that you can also derive the formulas in the examination all. So divide by simply Vs. Okay. So this is my critical value. Okay. So I will recommend you to derive this. No need to remember, derive. Next, what about critical value of inductance? Same equation you use. Okay, here same equation you use. Instead of L, you replace it with LC. So what will happen is that I'll copy and paste this. I'll copy and paste this whole thing. And L will be replaced with L critical. Okay, L critical equals to alpha into Vs divided by F2 IL average. Okay, so again you can derive this, right? You can simply derive this. No need to remember all these things. You can simply derive it. Okay, like what you can do is, like you can replace your Vs and this IL average. Like this is basically Vs by Is average, right? Because this is source current. Alpha Vs by 2FL Is average. So I will just derive you what is actually the ratio between Vs and Is average. If you remember, basically one standard relationship I had derived, right? One standard, like this is the chopper parameter, one of the fictitious input resistance. So one relation we know that VO average by IO average, not IO average, V average by Vs equals to Is average divided by IO average equals to 1 by 1 minus alpha, right? This much I know. So what I can do is I can find the ratio of VO and IO. So what is Vs in terms of VO? So Vs in terms of VO is Vs is equals to 1 minus alpha into VO average. So this one I can write like this one, I can extend here. This will be 1 minus alpha into VO average, right? Vs is this. Now what about IO? What is IO in terms, what is IS in terms of IO? So IS is equals to IO by 1 minus alpha. IO average by 1 minus alpha, okay? So now what I can say, one thing I know that VO average, if for a pure resistive load upon IO average, is basically R. So this ratio changes to R and this goes above. So actually this becomes one minus alpha whole square into R simply. So my resistance actually increases. Okay, my resistance increases, not increases, so it reduces. 1 minus alpha reduces, right? And it makes sense, right? If my resistance reduces, obviously I will give more voltage. Okay, more voltage. So yeah, this is just a fictitious parameter, and this, right? This I can replace it here because this is Vs average on Is average. So this, right? This will be equal to simply critical resistance will be simply equals to 1 alpha into 1 minus alpha whole square into R divided by 2f into, okay, this is only 2f only, fine, this will be 2f. So like, do you need to remember all this? How many formulas you can remember? Okay, that's impossible. Just try to understand how am I deriving it and try to derive it every now and then, how you can derive, or like try to solve questions. That also is a good option. So this is for the chopper parameter and the critical value of inductance. Now we'll analyze the chopper, step-up chopper with a capacitive filter. So if there is a capacitive filter, what will happen? Again, it will pass all the AC components, all the ripple components, it will pass. The load voltage and load current will almost be constant. So all device elements are ideal, and your IL, right? This IL is continuous, and your VC, my assumption is voltage across the capacitor is constant, hence the output voltage is also constant. Okay, so case 1 from 0 to T1, again the same thing will happen. This inductor will simply energize. So same analysis, that my VL is equals to Vs, hence that is greater than 0, hence my DIL by dt will be 0. Okay, so DIL by dt is greater than 0. So now what I can say is my IL is increasing. IL is increasing. So as my IL is increasing, what else I can say? Like IL is increasing and it will increase to some value. Okay, it will increase to some value. What about my diode voltage now? Now it will make sense because my capacitor voltage is constant, some value. So diode voltage will be minus Vc, right? Diode voltage will be minus Vc because this voltage is 0. Okay, now it is making sense that I have to reverse bias. Previously it was 0, but just trust me, this chopper will actually turn this diode off. Okay, so diode is off. Okay, Vd is less than 0, hence diode is off. That's for sure. So that's why my ID current, right? ID current will be simply 0 amperes. One more thing, although I am assuming that the voltage is almost constant, but some current will flow, right? Some current is leaving from this IC. So IC is equals to minus IO, which is actually less than 0. So my dVc by dt is less than 0. Hence, my Vc is also reduced. Although assumption is it will reduce to a very low, like it will reduce by a very low amount, but still it will reduce somewhat. Okay, very low amount, but it will reduce. From T on to T, interesting things are happening. This switch is closed. So as soon as this switch is closed, right, my VL is equals to Vs minus Vc. Okay, VL is fixed to Vs minus Vc, and as soon as my VL gets fixed to this value, what will happen over here is as soon as my Vs gets fixed, okay, so Vc is actually higher than this Vs that we know, as it is a step up chopper. Okay, so the VL voltage will be negative and it will discharge. So as it is less than 0, so dIL by dt is negative. Okay, dIL by dt is negative and it will discharge. Okay, so again, what else can I say? That this extra ripple current, right? Extra ripple, whatever this inductor will provide, because this inductor has huge amount of current. Okay, so the constant current will flow through this and the ripple will flow through the capacitor IC. Okay, so this time I can say you the different currents and voltages. Basically my IL, right? IL will be equals to IC plus IO. So the ripple current will flow through the capacitor and the DC current will flow through the load. Okay, and this is equals to basically my IS. What else can I say? My chopper current is 0 because chopper is forcefully turned off. It is forcefully commutated. What is the chopper voltage now? Chopper voltage, right? Chopper voltage is basically minus Vc. It is less than 0. Okay, minus, oh no, it is not minus Vc, it is plus Vc. Okay, it is greater than 0, but still it is in the forward blocking mode. And obviously, as my this is negative, IL will reduce. So not this will reduce, IL will reduce, right? This will be negative, and as this is negative, my IL will reduce. Okay, so as IL reduces, what can I say? That like IL is reducing, and what about the capacitor voltage? So this time, right, actually my Vc is actually Vs, just hold on, am I doing this correctly? Minus plus, yeah, Vs minus VL, and VL itself is negative. That's why this will be positive. So my Vc, right, Vc will be not Vc, sorry, my IC will be positive. Sorry. My IC will be positive. Why my IC will be positive? That extra current, right, whatever that will flow through the capacitor. So my IC is actually greater than 0 because my IL is very large than IO, right? So basically what will happen? The capacitor will charge. IC is greater than 0. That means my dVc by dt is greater than 0. That means my Vc will Vc voltage will increase. Okay, so this will be the case. So the waveforms will look something like this. My VO, right? So I have assumed that although VO is almost constant, just assumption is basically it will ripple a bit, very low amount of ripple that will ripple, and that also will compute. So this will reduce from 0 to T on. Why? Because capacitor is discharging, there is no charging happening. Then from T on to capital T, this is again increasing. Okay, this is again increasing. Why? Because the source is present, and source and inductor are actually helping the capacitor to charge. Okay, so this is happening. VD, this time VD is actually easy. When this is off, right, it is simply equals to minus of Vc or VO. When this is off, this is equals to minus of VO. Okay, now when this is on, when the chopper is on, what is the voltage? Voltage will be plus of VO, or plus Vs minus VL, I can write, or plus of VO. So these are the voltages across the chopper and the diodes. The current waveform will be same for the inductor because it is like from 0 to T on, it is increasing, then again decreasing, increasing, then again decreasing. The capacitor current waveform is actually interesting. Why? Because this is this, right? I have assumed the load current to be almost constant. If I assume the load current to be almost constant, like, although here, right, it will reduce towards 0, capacitor is discharging, but my assumption is almost constant. So I will keep this constant value. Okay, from when the diode is on, when the diode is off and the chopper is on. After just the chopper is off and the diode turns on, what will happen? It will just follow the AC part of the inductor current, and the DC part will be taken care from the inductor also. So AC part will flow from this. So this is like the constant part will go to the load, and the AC part will come to the capacitor. So this value will be instant, it will change. This value will be IL max minus IO, and this value will be IL max minus IO. Okay, so it will ripple around IL max minus IO, IL min minus IO. This the ripple value will be IL max minus IL min. So this ripple, right, of the capacitor current I am talking about. I am not talking about the load, because load is I have assumed the load is almost constant. So this delta IC will be equals to IL max minus IL min. This will be delta IC. And your VL, right? VL will be simply equals to VS when this is on, and this is VO minus VS. Fine. When this is off, and this VO, right? This time this VO is actually VO average because the capacitor voltage is constant, so it will be VO average only. And we generally use our boost chopper with capacitive filters only because we don't want the load to be discontinuous, right? Previously the load was getting discontinuous, load current was getting discontinuous. We don't want that. We basically don't want that. Okay, so next, like this chopper currents and all those things will be same only. IO will be continuous, that is my assumption, and VL is this only. Okay, fine. Now this will be V average minus VS by. Okay, so the standard relationship will be same, this won't change. And like now one important parameter we need to compute is VC, like the ripple in the output voltage. Although I have told you to assume that the output voltage is almost constant, but obviously it will vary a bit, right? Obviously it will vary a bit, but why? Because when the that capacitor is off, the voltage is reducing, okay, and then when the capacitor when not the capacitor is off, when the chopper is on and the diode is off, the voltage is reducing, there is no source, so capacitor has to act as a source. Obviously the voltage will reduce, very small amount, but it will reduce. And when the diode is turned on, chopper is off, then obviously the voltage will increase because current across the capacitor is increasing, the source and the inductor are helping it charge. Okay, so this is the thing. So here how can I write down the formulas and all those things? So here there will be two cases. Case 1 will actually be this: your IL minimum will actually be greater than IO. Whenever your IL minimum is greater than IO, then we'll do the case 1. And what does this mean? This IL minimum is greater than IO. Basically in the second half, right, in the T off period, your IC will be always positive. So this means during T off, IC will be greater than 0 amperes. During T off, IC will be greater than 0 amperes. Okay. Now, what can I say? What can I say? Is that what is the current second criteria? Current second criteria tells us that the average area of the current waveform for the capacitor will be 0. Okay. And from that, right, we will be able to compute, or like with the help of current graph, we'll be able to compute the, what will you be able to compute the change in voltage. Because here, just at this instant, what is this instant? This is T on. My IC is greater than 0, so IC is positive. If my IC is positive, that means what? dVc by dt is greater than 0. So from this point, from T on point, my voltage is increasing. Okay, my voltage is increasing, I'm following, and my voltage is increasing until here. So this is capital T. My voltage increased until here, then my voltage started to reduce. So this will be the point will be VO minimum, okay, or VC minimum, and this will be the point of VC maximum, because throughout this whole period my voltage is increasing. And how much has my voltage increased? By just computing the area and dividing by C, I will be able to compute the increase in voltage. So delta VC is VC max minus VC min. Basically, if I compute the overall area here and divide by C, what do you mean by that? So delta VC is, if you remember, Q equals to CV. So if I find out delta Q divided by C, I will be able to compute it. So for easier computation, right, I will choose this period. Okay, because here I don't have any IO max, IO min, I have just only IO. So throughout here, what is also happening? So here, at this point, if you assume that the current was always positive, so at this point my voltage is maximum. So from VO maximum, I am going to VO minimum. So basically this will be actually minus delta VC. Okay, why? Because my final is VO minimum and initial is VO maximum. So final minus initial is basically minus of delta VC, this, right, equals to basically the change in the charge. What is the change in the charge? Basically the area in this region. Area is negative, which is minus IO. IO is some constant value. My assumption is IO is some constant value. IO into T on. This is the area. Divide by C. Okay. So minus minus will get cancelled, and your delta VC will be simply IO into alpha by FC, right? Simple formula. So do you need to remember? No, just remember how I derived it. Okay. And how is the graph? So this is the first case. First case is pretty simple. But case 2 is a bit typical. Why the case 2 is a bit typical? Here my IL minimum is actually less than IO, right? So what will happen is that in between, right, during the off period, the capacitor will also reduce its voltage because the current will go to negative. So from this region to this region, the voltage will increase. Then from here to here, the voltage will decrease. Now I am getting two parts where the area is negative. So that is a bit difficult for me to compute. So I will compute only this region, the positive area. So at this point, if you understand, at this point, my current was always negative. So voltage was decreasing. At this point, now current become positive. So from here, my voltage will only increase. So this is the point where I get my VC minimum. And here, so my current is positive, voltage is increasing. Here the current changes its direction just after this. So just after this point, the voltage will reduce as the current has changed its direction. So this point will be VC maximum. Okay. So here what I can say, like that's why I tell you always go with the graph. So I will only compute this area. What is this area? So basically my final is VC max, initial is VC min. And what is this time period? This time period I don't know. So I will divide this time period into two parts. Basically, let's say this is T1 and this is T2. Okay. And this overall thing, overall is what? Overall is T off basically. When the chopper is off, but the inductor is directly connected across the input. Okay. So here, what is the slope of this? Can I compute the slope of this? I can compute the slope of this. This slope will be same as what? This slope will be same as this slope, right? This inductor slope. Whatever reduction there is, all the ripples, all the reduction, all the changes will be passed through the capacitor and the load current will be constant. So what is this? What is the slope? So what is the slope of this current waveform? Simply if I compute the voltage and divide that by inductance, I will find out. So this slope is basically what? Like what do I know? I know that my like my inductor current IL is equals to IC plus IO, and IO is some constant value. So your IC, right? IC will be simply IL minus capital IO. IO is constant. So by the rate whichever IL is reducing, this IC will also reduce. So this will be simply DIL by dt, right? The slope will be DIL by dt. This will be the slope. Okay. So what is DIL by dt in this case? Basically, if you know, DIL by dt is equals to, so my VL is what I know, VL is L DIL by dt, right? And VL is fixed. What is VL? VL is basically equals to VO. VL is basically equals to VO, right? So it is VO or VO, not VO, sorry. It is VS minus VO, sorry for that. It is when this is off, right? It is VS minus VO, yeah. VS minus VO equals to L DIL by dt. So if I divide it, right? If I divide it, and my VO is actually greater than VS, right? So this is actually VS minus VO average, which is constant value, VO average, divide by L equals to my DIL by dt. And here, right, VO is actually greater than VS, that's why this is negative. So already the sign has been taken care of. Okay. So now what else can I say? Just hold on. That this slope is negative in itself. So for T1 period of time, I'm going here. So this is the slope and I'm going to 0 with this. So initially my current was this IL max minus IO min. I'm going to 0. So what will be basically the change in charge? So what do I know? The thing that I know is my delta VC will be simply equals to integration of the area of the current waveform divided by C. So what is the area? Area is half into IL max minus IO ILmax minus IO into T1. So this is the positive area basically. Okay, and after this, what is happening? This this is correct only. ILmax minus T1. Another thing that we know is that overall this area, right? Overall this area should be equal. So basically this is the current second criteria. I just forgot to use. So I have to use the current second criteria as well. I forgot to use. This is the delta VC that I will compute. But according to the current second criteria, what I can say is that my IC average will be 0. So basically this value, right? This positive area will be equal to negative area. That means this will duplicate this. This will be equal to the negative area. Negative area is what? Minus half into ILmin minus IO. ILmin minus IO into T2 plus IOmin into T1. So all these equations will be present, and throughout all these equations, right, we will be able to solve. So I will take an example question and we will solve this. So because with this unknowns, right, I won't be able to get a perfect expression here. For the case 1, I was able to get a perfect expression, but for all this case 2, I won't be able to get a perfect expression. I have to use this all current second criteria and all those things, and from there I will be able to derive. Okay, so few things we already know. VC max will be VC average plus delta VC by 2. VC min will be VC average minus delta VC by 2. And what will be the critical value of capacitance for case 1? This was the case 1, right? When my IL minimum is actually greater than IO. When my IL minimum is actually greater than IO, what can I say? I can say this, right? I can say that again I will use this same thing. This formula only. So the delta, like basically what do we mean by critical? Critical means my VC minimum will be just equals to 0, will just touch to 0. So my delta VC will be 2 times VC average. So that I can replace in the formula, previous formula. So basically what did I know? I knew that my IO into T on was equals to delta VC C dVC by dt, right? Yeah, this by C. So delta VC is equals to 2 VC average. So C critical equals to 2, not 2, this IO into alpha will be in the bottom, 2 VC average into F. Okay. Okay, so your C critical will be basically IO into alpha divided by 2 VC average into F. Okay, this will be the thing. And what is VC average? VC average, if you want to write it in terms of VS, it is basically VO average. What is VO average? VO average, one thing we know, VO average, right, is basically VS by 1 minus alpha. This much I know, right? So I will replace this here. So this will actually become IO into alpha 1 minus alpha divided by 2 VSF. So do you need to remember? No, right? You can simply derive it. And again, VS by IO will be like this much. I can again convert this into R, like R formula, and from there also you can deduce. Okay, all this you can deduce. Okay, so now I will just give you a few assignment questions, and in the next lecture we'll solve all this. So you can take the screenshot of this one, and this one, and this was the my question, and this question is the most interesting one. Try to solve it by yourself. Okay, and in the next lecture I will solve all the questions. Thank you for watching, and I will see you in the next. Hi everyone and welcome back to PrepFusion. I'm Anish and today we'll start the lecture 4B, that is the continuation of the previous lecture. We learned about step-up choppers, we learned about the expressions of step-up chopper, then we derived the expression for step-up chopper with capacitor. So main thing about choppers is, are you able to understand how we are deriving the formulas, because the formulas may not work sometimes. So in the last question of this lecture, we'll see the formula will not work. So let's start to solve these questions. So in this lecture, we will mainly solve the questions that I gave you in the previous lecture. So this is the question from GATE 2008. So in this circuit shown in the figure, the switch is operated at a duty cycle of 0.5. So my alpha is 0.5. A large capacitor is connected across the load. Okay, so if the capacitor is very large, right, so like the voltage delta VC will almost be 0, so VC will be almost constant. And also they have told us the inductor current is also inductor current is continuous, so IL is continuous. So all those formulas will work. So here, right, what is actually happening when this switch is closed? My inductor voltage is directly equals to 20 volts. So I can draw the graph, right? I can draw the graph of inductor voltage. They are asking us the average voltage across the load and the average current through the load, right? Average voltage across the load will be some constant value, that is the VC, right? That is the VC or VO, and the average current through the diode. Average current through the diode will be basically the average load current. Why? Because average current through the capacitor at steady state will be 0, right? So these are the first thing. So VO average will be equals to VC, and ID will be equals to IC plus IO. And if I take the average, right, your ID average will be equals to IC average. IC average is 0 at steady state, because steady state capacitor will behave as open circuit, plus IO average. Okay, so basically what will be my inductor voltage waveform, because I can apply the volt second criteria. So inductor voltage waveform from 0 to T on, this as this switch is on, what will happen? My inductor voltage will be directly equals to 20 volts. So it will be 20 volts, it will energize. And from this is T on, and from T on to capital T, right? T on to capital T, what will happen? This switch will be open and this diode will be turned on as this inductor needs the current to flow. As the inductor needs the current to flow, so my inductor voltage will be Vs minus VO, and VO will be higher than Vs. That's why I will lie in the negative axis, and this will repeat. So this will be basically ID, not ID, sorry, this is VL, right? VL, inductor voltage. So this is plus 20 volts and this is 20 minus VO. So from here, right, I can compute my output voltage, right? Output voltage. So basically my using the volt second criteria, you are able to notice, right, I am not using the formula. Although I know this is a boost converter, the formula will be 1 minus alpha. It's better to practice it this way, because you can solve with formula. Okay, that's fine. You can do the formula. You can put the formula values. But it's better to do it this way, because it makes you a good habit, right? It builds up a good habit that whichever circuit comes, whether this is continuous or not continuous, I'll still be able to solve it. That's why I solve it like this. But always try to solve from the scratch. So it's fine. It can take you a bit of time, but that's like once you are in the mood, right? Once you're in the zone, this will not take you that much amount of time. So overall area will be 0. So 20 into T on plus 20 minus VO. I know VO is negative. I know 20 minus VO is negative. So I'm adding it. So I'm adding a negative area so that the overall area becomes negative. So T minus T on equals to 0. So this will be 20 T on will get cancelled, and I will be left with basically 20 T here, and on that side this will be VO into 1 minus alpha into T. So basically your VO will be 1 minus alpha 20 by 1 minus alpha, which is basically 40. I knew this, just cross verifying whether I'm getting the same answer. But what is your IS? Your IL, right? IL is equals to basically IS. So your IS is basically equals to IL is equals to 4 ampere. So I will assume like they haven't given us any values for L, so I will assume L is very high. So whenever this S is on, right, so IL is 4, that's fine, and that is equal to the chopper current. But whenever this is off, ID is equals to my IO, that is 4 amperes, right? 4 amperes. So the load current is equals to 4 amperes for half time period, for half time period. Although this voltage is constant, so this ID, okay, they're asking us the average current of the diode. What is the average current of the diode? So my diode current, right? Diode current is equals to IL for the period. What for the period? T on to T, capital T, and it is equals to 0 for the period 0 to T on. Okay, so that is the thing. So basically, what is my average diode current? ID average will be what? ID average will be all the load. I'm not talking about load current. I'm talking about the ID average current. So it is equals to IL into T minus T on, because IL is constant, divided by capital T in a period. So T minus T on is what? 1 minus alpha. So it will be 1 minus alpha into IL. So it will be 0.5 into IL. IL is 4, so it will be 2 amperes. And you can check, right? You can check like the overall power must be conserved. So like this IL average, ID average will only be equals to IO average. So power must be conserved. So 20 into 4 should be equals to 40 into 2, which is exactly correct. So 40 and 2. So option C will be correct in this case. C will be correct. Okay, so ID average is 2. Let's go move to the next question. So in the next question, they have given us this chopper feeds a resistive load from a battery source, and MOSFET Q is switched at 250 kilohertz with a duty ratio of 0.4. So my switching frequency is 250 kilohertz and my duty ratio is 0.4. Okay, duty ratio is 0.4. All the elements of the circuit are assumed to be idle. All elements of the circuit are assumed to be idle. So everything is idle here, so there will be no power loss. What are they asking? So the average source current in amperes in steady state. So what will the average source current? So for this, right, we have to first find out the VO average. If I am able to find out the VO average, I will be able to compute my IO average. If I am able to compute my IO average, this IO average will be equals to ID average will be equals to like 1 minus alpha. Because think what do I know? First of all, let me write down the equations. So first of all, this is a boost converter. That much I know, right? That much I know. Still, I will derive it with the inductor voltage. Fine. Next, what is the point? Next point is few equations I can write, few KCLs I can write, right? So here, this is ID, just similar to the previous question. This is ID, and this is my IL. This is my ICH. This is my IC. This is my IO. So what do I know? One thing I know is that ID equals to IC, capacitor current, plus IO. Now on an average, if I take the average throughout the in the steady state, my ID average will be equals to my IO average. This much information I know because IC average will be 0 in steady state. Okay, fine. That is one point. Next point is, what about VO average? So again, we can find out the VO average from the volt second criteria. Same thing I will do is that this is the inductor voltage T. So here, what is happening is that actually, right, well, the best thing what we can do, right, we can write this as negative. If I write this as negative, right, you will not get confused because I know VO is more than VS. So let's take VO as 30 or 40. So 40 minus 20 is 20. So this is minus 20 volts and this is plus 20 volts. So I hope you get the fine print, right? What do I mean by this? Else you can write this as VL1 as well. VL1. So whatever you choose. So just don't get confused with this unknown choosing. So that is the one thing that I want to point out. So what is my VL? Again, same thing equations will follow. So when this chopper is on, when this MOSFET is on, basically VL will be 12 volts. And when this is off, right? When this is off, so my VL will be this. So my assumption is elements are assumed to be idle. First, my assumption is that this output voltage, right? It is like this source current, inductor current is continuous. That is my first assumption. Still, I will check that. So if I go along with this, so here this will be VO, like negative of VO minus 12, right? Because on this side I have 12, this side I have VO, right? This diode is turned on, and this will follow. So again, if I compute from the whole second criteria, this will be 12 times alpha into T equals to VO minus 12 into 1 minus alpha into T. So obviously this will go away. Only 12 divided by 1 minus alpha will be remained, which is VO, and VO is equals to 12 divided by 0.6. So 12 divided by 0.6, yeah, because this is 0.6, so this will be basically VO average will be, this is 0.6, so this will be 20 volts. Okay, now how do I check whether the current is continuous or discontinuous? So what I can assume is I can find the L critical for this case. I can find the L critical. What will be the L critical basically? So what I can do is, during the on period, how much is this inductor getting charged to? So VL is equals to L DIL by dt. Okay, so VL is 12 volts. L I don't know. L I know the value. Okay, but I want to compute L critical, right? I want to compute L critical, and this value, right? IL average. IL del IL is del IL. Okay, this is the del IL, and in case of critical value, this becomes what? This becomes 2 times IL average. So I will keep this in check. I will compute this later on. Obviously, don't worry. Okay, I'll keep this in check and I'll compute this later on. So if these type of difficult question comes up, so sometimes it will take more amount of time. So you can skip it for now and you can solve the easier questions in the first round. Then you can go for the difficult questions. So L critical expression comes out to be what? 12 into alpha into T divided by 2 into IL average. This is the expression that I will keep in check. If my L critical, like if my L is greater than L critical, then IL will be continuous. If it is lower than that, then I don't have enough continuous. I don't have enough inductance present to keep the circuit in full continuous mode. I will check that. Don't worry, I will check that. Okay. So what will be my IS average? What is my IO average? So IO average, I know VO average, right? I know VO average. VO average I found out 20 volts. So my IO average will be VO average, as is a pure resistive load, by R. So VO average is what? 20 volts. 20 divided by R is 10. So this is 2 amperes. I believe it was 2 amperes, right? Yeah, 20. Okay, 20 divided by 20 itself, so it will be 1 ampere only. Okay, so next is, what do I know about IO average? IO average is basically equals to ID average. So ID average is my IO average. And what is my ID? ID, again the same thing, right? ID is 0 for 0 to T on, duration of 0 to T on. It is equals to IL for the duration T on to capital T. So my ID average will be equals to what? ID average will be equals to IL average into 1 minus alpha, because 1 minus alpha into T, capital T divided by capital T, that is my ID average. So from here I can find out my IL average, or the source current average. So this is equals to IO average, which is equals to 1 ampere. So my IL average from this equation, I will be able to compute. My IL average will be 1 by 1 minus alpha, which is 2 amperes, right? Sorry, not 2, sorry, alpha is 0.4, so it is 1 by 0.6. So what is 0.6? 0.6 is actually 3 by 5, so this will be 5 by 3 amperes. Okay, so source current, average source current will be 5 by 3, although there will be ripples, but the average value of source current will be 5 by 3. Okay, I hope you got the point now. This much I know. Then the peak to peak source current ripple in amperes. What is the peak to peak source current ripple in the amperes? So the peak to peak source current ripple in amperes is what basically they are asking us about the del IL. I need to find out the del IL anyways. So what will be my del IL? Del IL, like same thing, right? L del IL dt into T on equals to VL. Okay, so let me find out this peak to peak ripple. Del IL equals to VL is 12 into alpha is 0.4 into T is like, this is the switching frequency, so my time period will be what? It will be 1 by 250 milliseconds. So although they want us in micro, right, because inductor is in micro, so inductance is in micro, so I will write this as 4 microseconds. So this will be basically into 4 micro, and in like inductor has also its value in micros, so I will not replace it, I will just replace it with 100, and yeah, that's pretty much it. So this, right, this will be how much? This will be 25, and just hold on, how much will be this? This will be 12 into 0.4 divided by 25, 0.192 amperes. So your delta IL, right, delta IL will be 0.192 amperes. So here delta IL is 0.192 amperes. Now let's say if my if my inductor is critical or not, I'm deriving all this. If my inductor is critical or not, that I need to find out. So my delta IL, right, is 0.192 amperes, and what is my IL average? IL average is, if I remember, IL average is 2 amperes, I believe, or no, 5 by 3. Now what is my IL minimum? IL minimum is IL average minus delta IL by 2. So this is actually coming out to be somewhat like something greater than 0, right? Greater than 0. So definitely IL will be continuous. So then all formulas valid. All formulas are valid. Okay. If by chance your formulas were not valid, then you wouldn't have been able to like solve it like this. You have to choose some other formula, right? So homework is find out the L critical. Find out the L critical for this case, and like tell me in the WhatsApp group, or like write down, like find it out on your own. Okay, so this is the solution to this question. I hope you understood everything, right? One more thing you can see is that the input power and the output power will be same. Basically, my as chopper is ideal, so my PO will be equals to PS. How is that the case? So here if you observe that my PS is what? PS is simply VS into IS average. As only current is continuous, then only this is happening. VS into IS average. So VS is how much? 12. IS average is 2. So it is 24 watts. What about PO? PO should be VO average into IO average. So what is this equals to? So VO average is basically I think, have I computed it? It is I think 20 volts, right? Yeah, it is 20 into 1. Okay, where am I going wrong here? This is 212. No, IS IS average is 5 by 3 actually, not 1. Sorry. IS average is 5 by 3, not 2. That's my mistake. This is 5 by 3. So this is 4. This is 20, right? This is 20. Sorry. And this also will be 20. So PS equals to PO, all those are same. So yeah, this is the answer. So yeah, option C will be correct, and that's the question. This is a good question. This is a very very good question that came in GATE 2013. So let's solve this next question. Next question is also very interesting. A DC to DC boost converter. They have specifically mentioned that this is a boost converter. So it's shown in the figure below. It's used to boost 360 volts to 400 volts. So like my VO, right? VO average is 400 volts, and my VS is 360 volts at a power of 4 kilowatts. At a power of 4 kilowatts. So power is 4 kilowatts. So if power is 4 kilowatts, what do I mean? So my IO average is basically 4 kilowatts by 400, that is 10 amperes. Okay, so this is 10 amperes. This much I know. Okay, all devices considering are ideal, everything is ideal, so PS will be equals to VS. So I can directly compute my IS average as well. IS average will be what? IS average will be simply equals to like this power, right? 4 kilowatt divided by VS. One more thing, as considering the inverter current is continuous, the RMS current in the solid state switch. So as the inverter current is continuous, then only I can apply this. So what will be my IS average? IS average will be simply 4 kilowatt divided by VS. What is VS? VS is 360. So this will be some value. This will be basically 9. So 100 by 9. Okay, this is 100 by 9. So this will be the IS average. All these things I know. I know. But they are asking us about the RMS current in the switch. So what will be the RMS current in the switch? So RMS current in the switch basically will be, it will be, this is almost continuous, so I can say IS like ICH RMS will be simply under root alpha into IL, right? Or IS, okay, whatever this value is. So this will be basically like this I know, this I have derived in the lecture itself, in the previous lecture. This I know. How do I know this is under root alpha? Because I'm assuming that IL to be almost constant. So my can I assume that? Yes, I can. Like there will be minute errors here if I assume that, because you can use that formula as well. This will be this, right? This will be actually IL RMS. This will be IL RMS. Okay. So here, what will be my IL RMS? How do I compute my IL RMS? You can compute your IL RMS by computing the IL min and IL max. So how do I compute my IL min and IL max? So again I will use the same formula, del IL by T on, okay, L di dt equals to L equals to VL. What is the VL when this is on? This is on, the VL is 360, right? 360. So this will be, del IL will be 360 divided by 10 milli into T on. What is T on? T on is T on have they provided? Okay, they haven't provided us any switching frequency. That is the problem. Okay, power of all devices are ideal. Okay, if they haven't provided us any switching frequency, right? Okay, that is the issue. That is the problem then. If they haven't provided us any switching frequency, right? I cannot proceed here. Okay, I cannot proceed here. So I will assume what will I assume? So F switch not provided. F switch not provided. Assume IL to be constant. Okay, my fingers are really hurting me because I just cut my nails and cut it wrongly. Okay, so assume IL is constant, right? As they have not provided. So how do I compute alpha? Alpha, right? I can directly compute from this relationship, because I know for a boost converter the relationship is something like this, that VO average by VS will be 1 by 1 minus alpha. So VO average is 400 divided by 360 equals to 1 by 1 minus alpha. So this is 10 by 9. So 10 by 9, right? This is 10 by 9, fine. So if at the top I have 10, at the bottom I will have 9. Okay, 0.9. 0.1. Alpha, if alpha is 0.1, yeah, then it will fine. So alpha is basically 0.1, right? Alpha is 0.1. So alpha will be 0.1. So my ICH RMS will be 0.1 under root into IL RMS, which is equals to IL because IL is constant. 0.1 under root into IL. IL is what? IL equals to IL average because I have assumed it as constant. So I know IO average. I know IS average. IS average is 100 by 9, which is equals to IL average, which is constant. So this will be under root 0.1 into 100 by 9. So this will be 100 divided by 9. 3.513 amperes. Okay, 3.513 amperes. So this will be the answer of the chopper RMS current. So unfortunately they haven't given us a switching frequency, so I won't be able to comment. I will comment that okay, that's switching time period is very large, very small, so hence it will be almost continuous. As my switching period is very small, right? What will happen? Del IL will be very low. Del IL will be very low, and hence the current, I can say, ripple will be almost constant. That's why I told you at the starting of step up chopper that we keep the switching frequency very high. That is, time period of switching is very low. Now let's move on to the next question. This next question is actually very good. Please do try to solve it. So here a DC to DC converter shown in the figure is charging a battery bank B2 whose voltage is 150 volts. So this is charging 150 volts battery from B1, okay, and whose voltage is 50 volts. The value of the inductor is given, the ideal switch is given, operated with switching frequency of 5 kilo. So they have given us the switching frequency of 5 kilohertz, okay, with duty ratio 0.4. So alpha is actually 0.4. Once the circuit has attained steady state and assuming the diode D to be ideal, the power transferred from B1 to B2. How much is the power transferred from B1 to B2? So what you can do is you can say this, right? You can say power transferred PO will be equals to PS as how can I say this? As ideal. The chopper is ideal, right? Ideal chopper, AV elements are ideal, no losses are happening. You will say PO equals to PS. So what is your PS basically? So can I find out PS? I need to find out either IS average or IO average, right? This much I need to find out. How do I find out IO average? So that will be difficult, right? Finding out IO average will be difficult. Yeah, because there is no element here. So what you can do is you can find out the ripple here. So during the on state, what is the voltage across the inductor? The voltage across the inductor when this switch is on, right, it is 50 volts, directly 50 volts coming from the battery B1. Okay. $50 volts. Okay. Next, when this switch is off, right, so the inductor will try to flow some current. As inductor tries to flow some current, the voltage across the inductor comes out to be 50 minus 150, which is minus 100. So this voltage is minus 100, and this continues like this. So you might think the inductor voltage will be something like this, right? So here if you want to do this, right, what is your alpha? They've given us as 0.4. One thing what you will notice is this is 0.4. So this is alpha into capital T and this is capital T. So if you find out the area from 0 to capital T of the inductor voltage dt, what will you find out? You will see that it is 50 into alpha into T minus 100 into 1 minus alpha into T. So this actually comes out to be 100 alpha into T and minus 100. Okay, and what is alpha T? alpha t, right? Alpha into t is what? Alpha into t is basically alpha by, so okay, there is, this one has also t, right? Sorry. This one also will have t. So I can take the t common at the outside. I can take the 100 also common at the outside. 100, I can take 100 common at the outside. Can I take 100 common at the outside? No, there is 50t as well, right? Yeah. Okay, this will be minus 100 and this will be plus alpha into t. So this will be, sorry, hundred into t, right? Now here, what is my alpha? Alpha is 0.4. So 0.4 means 4 by 10. So this will be 60. So 60 minus 100 t equals to minus 40 into t. So I'm saying it is something negative. It is not equals to 0. So obviously it is not possible. The inductor voltage, right? Average inductor voltage at steady state will be always 0, no matter what. Average inductor voltage at steady state will be always 0. That means what is happening? That means my current IL is not in continuous conduction mode. Okay, so why do I say it? So now I have to make like average, this condition must satisfy that the average voltage of inductor throughout a cycle must be 0. So basically this waveform, right, whatever I have drawn for the inductor, that is still wrong. How is it wrong? Basically what is happening, I will explain. So what is happening is that this first part is correct, that this will, like whenever this chopper is on, all this will always charge to Vs, okay, and this, the current here, right, in this speed the current is increasing. Now as soon as the chopper is turned off, the voltage becomes negative and current will decrease. Now it will actually decrease earlier than it was supposed to decrease, right? So hence the inductor will be open circuit for a certain period of time. The current to the inductor will be 0 for a certain period of time. Hence current will not be, hence the current won't be continuous, okay, across the inductor. Current won't be continuous. What do I mean? So here it will reduce to here, then it will again turn on here. So let's name this as beta extinction angle, or whatever you want to name. You can name it. This is beta and times t. So actually what is happening is that one thing I know, my VL average will be 0 no matter what. So basically what is happening, 50 into alpha into t should be equals to minus 100 into beta minus alpha into t, not minus, sorry, plus, because positive area and negative area will be same, okay. So I know alpha, right? I know alpha is 0.4. So this 50 gets cancelled. This is 2. So this is 0.4. TT gets cancels. This is 2 beta minus 0.8. Okay. So beta will be equals to 0.6. Beta will be 0.6. So at 0.6 times t, the inductor is getting completely discharged. So as the inductor gets completely discharged, what will happen? So this will open circuit. If this is open circuit, this diode is also off. This is also open circuit. And the rate of change of current is also 0. So this voltage becomes 0. So the inductor voltage, right, is 0 basically. Inductor voltage is 0. Okay, it is not flowing any current, it is 0 simply. Okay, and this diode is also off, so there is no current flowing through it. This diode is totally blocking this 50, 150. So diode voltage now becomes minus 100. If you know what do I mean, please plot it. Please listen to me carefully. The diode voltage here becomes minus 100. Previously the inductor was keeping this diode on. Now as the inductor has totally reduced to 0, and current cannot flow in this direction, because actually what is happening, current wants to flow in this direction, but it will not, because the diode will not allow, and the diode will come across a reverse voltage of minus 100 volts. How is it coming across the reverse voltage of minus 100 volts? This inductor is getting short circuited. Why? Because the changing current is 0. It is remaining, the inductor current is remaining at 0, hence DIL by dt will be 0. Hence this whole 50 volts will come at the anode and the whole 150 volts will come at the cathode. So the diode voltage will be minus 100 volts, hence the diode will be reverse bias. Okay, I hope you understood this. Now beta is this. What do I actually need to find out? I need to find out the power transferred from B1 to B2. What is the power transferred? Power transferred from B1 to B2 will be simply PS will be Vs into Is average. Is average. Or what is Is average? It is simply IL average. So if I want to draw the current, right? If I want to draw the current, what will be the current? So current will be simply inductor current. I'm drawing the inductor current because this is the inductor voltage, right? So as the inductor voltage is constant, the current will increase linearly from t equals to 0 to alpha t. Then again, as the voltage becomes negative, the current will reduce linearly from t equals to t on to t equals to beta t. Then it will remain at 0 for a certain period of time from beta t to capital T. Then again, this same thing, this same cycle will be repeated. Okay. So this will be t on 0.6, t 0.8, not this point, not 0.6, I think this is 0.4, 0.6 t, and this is capital T. Okay, and this is basically my IO max, or this is 2 times IO average. You can say that as well. No, this is not. This will be not 2 times IO average. This will be IO max. So what they have asked us to find, not IO max, sorry, IO max also. This is IL max also, the intercurrent max. So they have asked us to find the average value. So the average value will be here. If I want to compute, basically it will be half times IL max times this t, right? This is 0.6 t. Width is 0.6 t divided by total time period. The area upon time period will be my, what will be basically my IL average. So what is IL max basically? So IL max is basically from here to here, the voltage is 50 volts and the slope is what? Slope is dIL by dt is 50 by L. So IL max, I can compute minus 0 del IL by dt. dt is t on into L equals to the voltage. Voltage is 50 volts equals to Vs. So this is Vs, right? Just using the same equation from the time period 0 to t on. So my IL max comes out to be, this is 50 by L into t on, that is alpha into t, right? Alpha is 0.4 into t, and yeah, that's pretty much it. And L also they have given, right? L is 5 millihenry. L is 5 millihenry. So this will be 5 millihenry. Okay. So as this t is also in milliseconds, I think. T is how much? T, right, will be 1 by f. So I will just write this f in this. So this will be actually, here this tt gets cancelled. I will put this value here. Okay. This t and this t gets cancelled. So I am remained with half into IL max. IL max is 10 into 0.4 divided by, this is inductance, right, in 5 milli, and also the frequency, like this t I can write as 1 by f. So 1 by f is what? 5 kilohertz. So this will be 5. Okay, milli and kilo gets cancelled, and this is 0.6. T also gets cancelled, right? This t and this t gets cancelled. So what am I left with? So this is 20, like this will become 2 will get cancelled. This will be 0.4 into 0.6 divided by 5. 0.4 into 0.6 divided by 5. Okay, sorry, actually, right, I have already cancelled this 5 over here. Still I am writing this 5. So this 5 is already getting cancelled, right? So this is only 0.4 into 0.6. So this comes out to be 0.24. So this value comes out to be 0.24 amperes. So IL average is 0.24 amperes. Now I can simply compute the power, right? Power is what? PS is what? PS is simply Vs is 12 into 0.24, not 12 actually. This is 50, right? Sorry. Vs is 50 into 0.24 amperes. So this will come out to be 12 volts, and this will be your answer. So this is a very, very good question. Please revise it again so that you are able to understand the concept what is happening. And this is a case of discontinuous conduction, and this is a latest question. So this type of question can come in the future as well. So a DC to DC converter with supply voltage 12 volts, calculate the ripple in the load voltage. So you have to calculate the ripple in the load voltage. So again, whenever for a step up chopper, right, whenever we are computing the ripple in the load voltage, you have to remember the waveforms. So if I assume the voltage to be almost constant, what I can assume is, or the current to be almost constant, what I can see is my waveform, the capacitor current waveform, right? Capacitor current waveform will be something like this. If you remember, when the chopper is on, obviously this circuit is disconnected. So obviously the current will be constant, but in the negative direction, because my IC will be minus IO, and I have assumed my IO to be almost constant. That is my assumption basically. So this is my IC and this is T. So this is negative. Fine, this is negative. This is minus IO. Next, as soon as the chopper turns on, as soon as the chopper turns off, what will happen? All the current will flow through, all the AC current, right, will flow through the capacitor, right? This current will be constant. So here, what will happen? This will increase. IO is constant and this will reduce. Okay, IO is constant and this will reduce, right? So here, my assumption is this will actually not touch 0. This will touch somewhere here and the cycle will stop. Okay, then again it will start from negative. And it will go like this. So this will be alpha times T and this will be capital T and it will go along like this. What are these values? This value is basically IL min minus IO. IO is the constant value because IO load current is constant, and this will be IL max minus IO. IL max minus IO and IL min minus IO. Okay, so this is the case. This is the case. So here what I can say is that this is the case 1. Case 1 I have assumed, and in this case, right, in this case basically whatever like the thing I have derived, that my delta VC dVC by dt is equals to area under the current, okay, either during the on period or on off period. So delta VC will be basically dVC by dt, C into dVC, C into delta T is T on, okay, equals to the area in this region, right? Area in this region, that is a charge transfer basically. So it is basically IO into alpha times T. So this much I know, right? But is this the case really? Is this the case? We have to see. So for this, for us to see, right, they have provided us the data, so we have to see the data. So here I have to, first of all, I have to compute the ripple. So output voltage I know, input voltage I know. Okay, so my VL, like inductor voltage, let me check if the inductor voltage is satisfying or not. They haven't provided us the duty cycle. So obviously I will assume that the duty cycle is as such that continuous conduction is maintained. So this is the default condition. Right? VL. So when the chopper is on, basically VL will be plus 12, and when the chopper is off, VL will be what? Minus 12, right? Minus 12, because this is 12 and this is 24. So overall VL will be minus 12. So from this I can directly see that my delta, right? Not delta, sorry. Yeah, alpha will be 0.5 basically. Alpha will be 0.5. So basically this is 12 and minus 12. Okay, so here, so this will be alpha into T and T. Okay, so here this will be what? This will be 12 times alpha into T equals to minus 12 times 1 minus alpha into T. So basically my, not minus, so this will be plus on a negative area gives to positive area. So my alpha will be equals simply 0.5 from here. So if my alpha is 0.5, or like you can derive from the voltage as well that your alpha is 0.5. So if my alpha is 0.5, right, now I will be able to compute my ripple. Have I written the formula? No, I haven't. So my ripple, right, delta IL will be what? Delta IL is actually delta IL is LDI dt T on equals to VL during the on period. So L is how much? L is 150 micro, and what is my T? Switching frequency they have given us 20 kilohertz. So T will be basically 1 by 20 into 1000. I will convert this into micro. So this will be 50 microseconds. 50 microseconds. Okay, so L is 150. So this is right. Delta L will be what? Delta L will be 12 into alpha is 0.5 into like capital T, which is 50 microseconds, 50 micro, and this side L is also 150 micro. So this becomes 6 by 3. So this is basically 2 amperes. 2 amperes, right? Delta L is 2 amperes. Now what is my IO? So my assumption is that IO is a constant value, that is 24 by 48. So 24 by 48 is 24 by 48. This I can say as IO average as well. 24 by 48 is basically 1 by 2, which is 0.5 amperes. Now what will be this minimum value? So this, what will be this minimum value? Will this be over the x-axis or below the x-axis? So IL minimum minus IO I need to find out. What will be this value? So for this, right, I have to obviously find out IL minimum. So IO average will be equals to y. IO average will be basically equals to my IL average, right? Or no, it will not be equals to IL average. Sorry, it will not be equals to IL average. IO average will be basically equals to my ID average, and my ID average is basically, if I almost do this ID average and my, if the circuit, my IL average will be what? IL average will be simply, if we go by the formula, my IL average will be basically ID average by 1 minus alpha. This will be the IL average, right? So it's like, it is just inverse. So my IL average will be something, IL average will be basically ID average by 1 minus alpha. Alpha is 0.5. So ID average is 2, ID average is 0.5. So this will be 1 ampere. My IL average will be 1 ampere. So what do I want to know? I want to know my, this value, right? This value. I want to know IL minimum minus IO. So that is the minimum value that my capacitor current will go to. So IL minimum, what will be IL minimum now? IL minimum will be basically equals to IL average minus del IL by 2. Right? All these things I have derived previously. So IL average is 1 minus del IL by 2. Del IL is 2. So del IL by 2 is 1. So this will be 0 amperes. So this is just at the continuity stage, just at the continuous stage, right? Just continuous. Okay, so if this just continuous, what about IL minimum minus IO? What about IL minimum minus IO? So IL minimum is 0 minus IO. IO is 0.5, right? IO average is 0.5. So that kind will be constant, 0.5. So this is coming out to be IC just at t equals to 0. Okay, or t equals to t on, coming out to be negative. Now if this is coming out to be negative, right, that means I have to move to case 2. So things will be different here. Move to case 2, things will be a bit different here. So curve 2 will be something like this, right? So this will be minus 0.5 because it is changing suddenly. So IC at t equals to 0 is changing to minus 0.5 suddenly, right? So yeah, this will be minus 0.5. Yeah, here also this will reduce to this minus 0.5 and this will remain like this. Or no, this is a bit wrong actually. Actually this is a bit, oh no, this will be minus 0.5 only. Yeah, correct. This will be minus 0.5 only because average is fine. Yeah. So it will directly reach this minus 0.5 here only. Okay, so these are the two time instants. Now what do I need to find out? So IC graph will be something like this. It will be minus 0.5. Why? This will be when the chopper is off. What is the current through the load? Current through the load is 12 by 24, which is 0.5 amperes. But current through IC is in the opposite direction. So I'll just show you the circuit diagram here. Copy and paste the circuit diagram. So here, when this chopper is on, this diode is off. So this current IO, who is providing? This capacitor. So this capacitor is providing this current IO. What is the current? 24 by 48, which is 0.5. But I have assumed my initial direction of IC as downwards. So I am going in the opposite direction. So that's why this is minus 0.5 and it will be constant. My assumption is it will be constant. The load voltage is constant. So it will be constant. Then what will happen? Then just at t equals to t on, this will turn off. This I will forcefully commutate it. Then what will happen? This diode will be turned on because inductor wants to flow continuous current. So inductor current will flow. Okay, inductor current will flow. Then that ripple, right? This current will be constant. This current is 24 by 48, that is 0.5. That ripple, extra current will be provided to the capacitor, will flow through the capacitor. So what is the extra current? That extra current is IL max, because throughout this whole period when this chopper was on, right, this inductor was charging. This inductor was charged to IL max. What is the IL max? What is the IL max? IL max, if I want to compute, right, IL max will be IL average plus delta IL divided by 2. So IL average is 1 plus 1, which is 2 amperes. Okay, out of this 2 amperes, right, out of this 2 amperes, whichever inductor is trying to flow, out of this 2 amperes, half will go to this load. Okay, and remaining 1.5 will go to capacitor, because capacitor will allow the sudden change. So suddenly the current will change to 1.5 amperes. So as soon as the current changes to 1.5 amperes, then what happens is that this current will reduce, right? This current will reduce because now inductor is de-energizing. As the inductor is de-energizing, the inductor current will reduce. Inductor current will reduce. Okay, that is my assumption. My assumption is this capacitor voltage is almost constant. Okay, that is the assumption. So this is reducing, and at certain point, my IL, right, my inductor current will be at 0.5. So as soon as the inductor current becomes 0.5, what happens is that as soon as it reduces below 0.5, that extra amount of current the capacitor has to provide now, because capacitor is provide, like, these voltage is constant, that is 24. So 0.5 amperes of current must flow always. So capacitor will provide that extra current. Let's say inductor is providing 0.4 amperes. Now capacitor has to provide 0.1 amperes to totally get this to 0.5 amperes. So that's why I will have a negative area. So now my capacitor actually discharging. Initially my capacitor was charging within this region window, but now my capacitor is discharging. So the total amount of discharging and charging will be same, because IC average will be 0 and the steady state VC will be constant. Okay, so the positive area will become negative area. But what am I interested in? They have asked us to find the ripple. So at this point, at t equals to t on, the capacitor voltage will start to increase as the current is positive. So as soon as the capacitor, this current becomes negative, the capacitor voltage will start to reduce. So this is the point. Where my VC is VC minimum, because after this the voltage only tries to increase. Okay, and this is the point. My VC is VC maximum. Why? I'll just explain once again. So if I start from here, if I start from this point, right, or if I start from this point, okay, so here the current is negative. As the current is negative, capacitor voltage is reducing at this point. So after this, right, capacitor voltage starts to increase. So this is the point where the capacitor voltage is lowest. Then capacitor voltage starts to increase. Why? Because the current is positive. Hence the dVc upon dt will be positive. Hence it will increase. So as dVc upon dt is positive, as the capacitor voltage is increasing up until here, then again the current direction changes. Current become negative. So again from here at this point, the voltage will reduce. So only the increasing portion is this one. So this is the portion where I will get a ripple. My capacitor voltage will grow from VC minimum to VC maximum. So now I can use that formula. What is the formula? The formula is VC equals to C dVC by, IC equals to C dVC by dt. Or what I can say is the change in current, right? The delta Q will be equals to C times delta V, VC. So what is my final and initial? So final is VC maximum, and initial is VC minimum. So that's why this is delta VC only. This will be C. And what is the charge transfer? Charge transfer will be basically the area, this positive area, right? This is the positive area. So what is this area? So this I have to find out T1. How do I find out T1? So for us to find out T1, right? Basically what I can do, I can take help of the inductor slope. Okay, so how do I find out T1? So from this point to this point, how is my inductor current changing? So my IL is going from, what is the value of IL here? The value of IL at this point is IL max, that is 2 amperes. And it is reducing to what? It is reducing to 0.5 amperes, because after that capacitor supplies the extra current. So I can use this, right? So what do I know? What equations I know? I know L dIL by dt equals to VL. This is during the discharge equation, right? So this is during the off period. So here what is my VL? VL, right? When this chopper is off, VL is simply this VS minus 24. So VS is 12 volts. So it will be minus 12. So L is what? L is 150 micro, and this is DIL. DIL is a change in. So what is the final current? Final current is 0.5. What is the initial current? Initial current is 2 amperes divided by delta T. The change in time is from here to here. Change in time is T1. T1 should be equals to VL. What is VL? VL is minus 12 because it is discharging, right? That's why this is minus 12. So T1 will also be in micro. So I will compute in micro only. So T1 will be what value? T1 will be simply 150 into 1.5 in, divided by 12, and this is in micro. So this value will be what? This value will be 150 into 1.5 divided by 12. So this will be 18. T1 will be 18.75 micro. So this duration is 18.75 micro. So this duration I have found out is 18.75 micro. And what is T2? What is T2? T2 basically, if you see this, what was the total of duration? So this total is 50 micro, and this is 0.5 and 0.5. So this will be 25 micro each. So this will be just hold on. This will be right. This will be actually 25 micro. So this is 6.25. This right is 6.25 micro. Okay. So you can confirm with this. So now I know this width and I know the height. So I will be able to find out the area. So basically, if I want to find out the area will be, so delta Q will be, change in charge will be half into this width, height into width. So it is 1.5, width is 18.75 micro. So I'll just leave it at micro, which is equals to what? Which is equals to C into delta VC. So what is C? C is 470 micro. 470 into delta VC, that is exactly what I want to know. Delta VC is the thing that I want to know. So micro will get cancelled, and my delta VC, I'll just quickly compute it. It will be equals to 1.5 into 18.75 into 0.5 divided by 4. This is actually very low. Delta VC is actually very low. Okay. Okay. Am I doing anything wrong over here? 470 half. Okay, yeah. So it is 0.03. So if I want to write this in millivolts, right? If I want to write this in millivolts, this will be 30 millivolts. Okay. So your delta VC will be 30 millivolts. This will be answer. Okay. You compute with the case 1 formula. You know the formula for case 1. Compute, like what is the homework? Homework is use the case 1 formula and see what is the value that you are getting. Okay. What is the value that you are getting with the case 1 formula? And another homework is like equate with negative area. Equate with this. These two are homeworks. This will only clear your concepts. Equate with negative area. So what is negative area? Negative area is this portion, right? Negative area is this portion, this and this. So you try to add these two areas and here check what is the delta Q, and this will also give you the delta VC. Why? Because from here my voltage is reducing. So I am at my VC maximum. My voltage is reducing. It is still reducing. It will reduce until this, right? Next cycle, until the next cycle of when the chopper is turned off. So if you compute the overall negative area, that will also give you the thing. Okay, you don't need to use the current second criteria here because that will be very hectic. Okay, you can use that obviously, but you don't need to use it. So basically that's it for this question. This question was very good, and like whatever questions we did, right, all those are very good, and I hope you're understanding this. Not just mug up the formulas, try to understand what how to solve each question, okay, with basics. Okay, you can develop your own methods. Just try to solve each question, try to see each question, and then you can develop your own methods. So thank you. Hi everyone, and welcome back to PrepFusion. I'm Anish, and today we'll start the lecture 5 of this DC to DC converter. So we're nearing the end of this chapter, and this is not a long chapter, this is a short chapter only. So we will today study the buck boost converter without capacitive filter, and with capacitive filter we'll do the analysis. Then we'll do a few questions on buck boost converter. So what is basically buck boost converter? Basically with the help of buck boost converter we can both increase and decrease the voltage level, right? Either we can, like, with respect to the source. I'm talking about the average voltage level. So what are the few assumptions that we need to keep in mind? This should be my IL is continuous, not IO. IL is continuous. Basically my inductor current, right, it is continuous. That is my first assumption. And second assumption is obviously it has to be greater than or equal to 0. IL minimum has to be greater than or equal to 0. If this is satisfying, right, then this also has to satisfy. Then all the power electronic devices are ideal. And obviously VU, we cannot specify here the relationship between VU and VS. So just you have to remember the circuit diagram. This much you have to remember. Previously at the starting, just try to remember what we have learned, right? Try to summarize how we used to like get buck converter, step down chopper. Inductor was connected in series with the load, okay, and the inductor wasn't connected directly to the source. Then we got to boost converter. Where we boosted the inductor, where we energized the inductor. Then I turned off this chopper. Chopper was here, switch was here. Then what happened was this instantly energized. This instantly gave me a huge output voltage, right? And due to that, the output voltage was more than the input voltage. So in case of buck converter, the inductor was here, the chopper was here, freewheeling diode was here. In case of boost converter, the inductor was here, chopper was here, and the diode was here, if you remember. But in case of buck boost, everything changes, okay? In case of buck boost, the chopper is here, right? So all the three places, this is the same position as the step down chopper, same position as the step down converter. Inductor is here. Instead of freewheeling diode, we have an inductor here. Inductor will be energized when this chopper is on and will be de-energizing when the chopper is off, okay? And how will it happen? So the current through this is this direction, right? So the same direction of current should flow. That's why the diode is connected like this, so that it allows the current to flow, okay, during the T off duration. And the diode is connected like this. So this much you have to remember. This diagram, you will, with practice, you will be able to understand. And anyways, once you go into the analysis, you will automatically understand whether this is a buck boost or buck converter. So few key points about the buck boost converter: suitable for medium power ratings, not too low, not too high. Because here, right, we are both increasing and decreasing the voltage, so currents are also changing. So this is suitable for medium power rating. In a buck converter, only DC voltage source supplies power to the load. So in a buck converter, if you remember, the DC voltage source supplies power to the load, because when the chopper is on, what happens? It energizes the inductor and it like gives power to the load. When the chopper is off, the inductor de-energizes through the freewheeling diode. So only the source, like DC voltage source, is supplying the power to the load. In a boost converter, both DC voltage source and the source inductor provide power to the load. In a boost converter, both DC voltage source and the source inductor provide power to the load, okay? So like what happens is that when the chopper is on, in case of boost converter, the inductor energizes, so the DC voltage source is actually energizing the inductor. Then once the chopper is off, right, so here I have diode, so now the source again is energizing the inductor as well as the load, okay? Not per se energizing, because what is happening, the inductor actually is de-energizing, the current is reducing, but that's a different point. At least the voltage is increasing. So in a boost converter, both DC voltage source and source inductor provide the power to the load. How? Because when the chopper is off, this inductor has energy, initial energy, and the source already has energy, right? So both of these together actually supply energy to the load, if you remember the circuit diagram. In buck boost converter, only the inductor acts as the source of power to the load during the off state. So here during the off state, both the DC voltage source and the inductor acts as a source to power the load, okay? And the source inductor power to load. And in the buck converter, only during the on state, the load is receiving power from the source, okay? But in the buck boost converter, right, during the off state, the inductor is actually supplying the power to the load, and during the on state, the voltage source is actually supplying power to the inductor. There is no direct connection between the source and the load for a buck boost converter, okay? I hope you get this point, few key points. Now we will directly come into the analysis part. So here, initially, my inductor is actually directly connected across the supply, same as the boost converter. Just the positions have been interchanged. So IL is in this direction now. So what will be my VL? VL is equals to VS. As VL is equals to VS, that is greater than 0 volts. That means what? That means my DIL by dt is greater than 0. That means my IL will increase, okay? So DIL by dt is greater than 0. That means my IL will increase. What other things I have? I have ID equals to IO. Just hold on, I will check if everything is recording or not. Yeah, everything is recording. ID equals to IO equals to 0 amperes because load is open circuit, right? Load is open circuit. So load has discontinuous current, but inductor current should be continuous. That is the most important part. What is the chopper voltage? Chopper voltage is 0 basically. It is on, right? Chopper voltage will be 0. What is the diode voltage? Diode voltage, right? So this, if this is simple R load, so this current is 0. So that means this drop is 0. But what is the drop here? So it is this point is directly connected across Vs. So it will be minus Vs. Okay, minus Vs for a R load. And it will be E minus Vs. Actually the load is connected other way around, then right, it will be some other way. So we are not talking about RLE load, but if I am talking about RE load, so like the load, right, if I have RE or RE load or R load, so R will be same only, but RLE, right, it will be connected somewhat like this. If I want to show to you, this will be the polarity of RE load. Okay, so if I have RE load, right, if I have RE load, the load will be connected somewhat like this. So if this current is 0, so this negative comes here. So obviously for RE load, this will be minus E minus Vs. So anyways, this will be negative only. So the diode will be off. That is for sure. RE load. Okay. Anything else currents I have given? So IL will increase, and it will increase linearly because it is directly connected across the source. And IL is equals to what? IL is equals to actually the source current. This for the first half period. Okay, next the chopper, like my current is increasing, so IL gets to maximum, IL max, just before T on, just when the switch is turned off. So chopper forcefully commutated. Chopper is forcefully commutated. Okay, so it is forcefully turned off. So what I can say is that what will be my IO at the time t equals to T on plus, it is basically equals to IL, right? It is basically equals to L, because do remember I have changed my IO direction and my VO also have changed the direction. Do remember this is not the conventional direction as the previous case. Okay, just I have like interchanged them. So IL will be equals to IO, so it will be equals to IL max. Okay, so that is fine. That is one thing. What is my VL this time? So my VL, right, like my VL was like this. If you remember, like my initial notation of VL, I will just put it here. What is the initial notation of VL? This is my VL. So in this case, my VL is actually negative. You will see, you will observe that your VL, right, will come out to be minus VO actually. Like you will observe that. Okay, and VO is some positive value. We'll see, we'll just find out VO is some positive value. So VL is negative, which is less than 0. So obviously anyways, we know, right, this is a source free network, it will discharge only. So my IL will obviously reduce. So as my IL reduces, my IO will also reduce. Okay, IO will reduce from IO max to like IL max to IL min. Okay, and my chopper currents, source current, all this will be 0 only, right? Chopper current, source current, all this will be 0 amperes. Okay, then next is what? Next is the VCH. What is the VCH? VCH will be this Vs minus VL. What is VL? VL is minus VO. So VCH, right? VCH will block forward voltage. It is Vs plus VO. Okay, that will be what your VCH. Yes, that is what your VCH is. So VCH is this voltage. All these are fine. So IS, all the elements I've written. Okay, so how the graphs will look? So the graphs will look somewhat like this. So VO will be equal to VL, the inductor voltage. Okay, like I'm assuming like both are same only, I can interchange with VO and VL. So VO will be equals to VL when the chopper is off. Okay, it is directly coming across the inductor, so it will be equals to Okay, sorry, one thing I have made a mistake. This should be minus VL. Okay, according to my polarity, this should be minus VL because VL is positive. Okay, this is positive. So if I assume this polarity, right, things will be a bit different. Okay. Yeah, if I assume this VO is equal to minus VL. So VL in itself is negative. So I will write here minus VL. Although VO is positive, but VL is less than 0, right? I have specified here itself that VL is less than 0. So just one thing, my VL will be less than 0 during the off period. Okay, and when the chopper is on, obviously the output has no load connected. So if it is a pure R load or RL load, it will be simply 0 volts. Okay, for the on duration. And what about diode voltage? So diode voltage will be equals to minus Vs plus VO. Okay, in the negative direction, obviously here, right? Diode voltage I have already computed. Okay, for R load, okay, if the current is 0, if the current is 0, it will be R load, but it can be VO as well. So whatever the VO is, I don't care. So I will just assume a variable here. Okay, I will just assume a variable. If it is VO, so it will be basically, I will just assume that the voltage, output voltage is VO. So it is minus VO. Why is this minus VO? Because this is connected in the opposite polarity. So that's why I want to, according to the load, the VO can change. Okay, I'm just naming the VO as a variable. Minus VO minus Vs. Okay, and when the diode is on, obviously it will be 0 voltage. What about the chopper? Chopper will be Vs plus VO when the diode is on, right? It will block the forward voltage as like derived here. And what about the current? So current will go from IL mix to IL minimum to IL maximum during the on period when the source is directly connected across the inductor, and then it will go from maximum to minimum during the off period and when it is de-energizing through the diode and through the load. So VR will be same only, the resistive load voltage VL, right? VL will be equals to VS when it is directly connected across the source, and it will be equals to minus VO when it is directly connected across the load, right? Load. So these are the equations, and from this we will derive our expression for the voltage, for the average voltage, right? So what about the currents? Again, like IS equals to ICH during the on period, and it is equals to IL. So it will just follow the inductor current during the on period, and then it will go to 0 totally. Okay, and then ID and IO will follow the inductor current during the off period, and then it will go to, then it will be 0 for the other periods completely. So these two currents will not be continuous, but IL, inductor current, must be continuous. Okay, and VL is same only. So like these few formulas, IL average, again IL average is same. So again we will derive everything with respect to IL average. Again we'll derive everything with respect to IL average. So IL average is this value. IL average, like if it expand, same thing we are doing. This is the same graph we have been solving multiple times now, and IL RMS will be this same formula that I derived many lectures back. So what will be IS? What will be IS then? So IS, right? IS will follow only for the T on period. So basically IS average will be only alpha into IL average. Simple, right? Only for the T on period. So if I do alpha into IL average, actually your IL average, right, it will be equals to IO average by 1 minus alpha. I am getting this from where? I will just explain in a bit. Okay, I will just explain in a bit, don't worry. So if I want to find out IO average is what? IO average is basically, if I will just write this in rough. I will just write this in rough, that the output current is following the inductor current only for the off period. So what will be the IO average? Else it is 0. So IO average will be equals to 1 minus alpha into IL average. Okay, so IO average equals to 1 minus alpha into IL average. So this will be basically during the off period. During the off period, I am following the load. Basically during the off period, I am following the load. Okay, so this is my IO average. And so now, right, I will just like replace IL average is what? IL average is equals to IO average by 1 minus alpha. So I have done the same thing, IO average by 1 minus alpha. So basically my IS average in terms of IO average is IO average into alpha by 1 minus alpha. Same for IS RMS. IS RMS will be ICH RMS into under root alpha into IL RMS, right? IL RMS I can write, which will be equals to same thing, just under root of this whole thing into IO RMS. So this will be the case. Now what will be the, for the load, what will be the VO average? Again, VO average I can directly find out from the voltage expression. So again, the positive area should be equals to the negative area. So positive area is what? Positive area is Vs into T on equals to VO into T minus T on. Okay, so Vs into alpha T equals to Vo into 1 minus alpha into T. So basically my Vo average, right? Vo average comes out to be what? I will divide this here. So it will be Vs into alpha divided by 1 minus alpha, correct? Vs by alpha 1 minus alpha. So this will be my Vo average. Okay, and like IO average you can compute, like if it is RLE load you can compute Vo average minus E by R. Now interesting fact over here is, if my alpha is greater than 0.5, what will happen? If my alpha is greater than 0.5, let's take an example, let's take 0.6. So if I take 0.6, this will be 0.4 and this will be 0.6. So this will be, if I do the math correctly, it will be 3 by 2, which is 1.5. So if my alpha is greater than 0.5, it will work as a boost chopper. Okay, it will work as a step up chopper. If my alpha is less than 0.5, like here I have written the summary, if my alpha is less than 0.5, the buck boost chopper will act as a step down chopper or a buck converter. Take example 0.4. If I take 0.4, this will be 0.6 and this will be 0.4. So this will be 2 by 3. So this is less than 1. So obviously this will step down the output average voltage. Okay, I hope you understand. If my alpha is exactly equals to 0.5, the Vo average will be exactly equals to Vs. Okay, just like transformers and stuff. Okay, AC transformers. Now what will be my VORMS? So VORMS, right? VORMS will not be this. VORMS will be basically alpha by 1 minus alpha whole under root. Okay, Vs into alpha by 1 minus alpha whole under root. This will be my VSRMS, VORMS. What will be output power? Output power will be simply load power minus supply power minus the losses. What is the supply power? Supply power is basically equals to Vs into Is average. Okay, this will be my supply power. Yeah, here I've written this, but this should have written previously actually. So just hold on, I will just copy and okay. So what is IO average? So IO average I have already derived you, right? It will be 1 minus alpha IL average. Why? Because it is just following the IL during the off period. So I can convert this IL average in terms of IS average, right? Like IL average, IS average is what? IS average is equals to alpha times IL average. So IL average will be equals to what? IS average by alpha. Exactly, I have replaced that only. So like same thing I have just done there, and same thing I have done here as well, right? So again IORMS will be just the opposite of the thing that I did there. 1 minus alpha by alpha whole under root. So all these things you can derive. Don't need to remember. I'm just showing you how you can derive all this. Okay, how you can derive all this. Now again, this standard relationship between input and output for this should be a buck boost converter. Only thing is that here, right, this should be actually IL needs to be continuous, not IO. IL needs to be continuous. Like I will change in the previous cases as well. Okay, so let's like what is the chopper efficiency? Same, right? It is basically PO upon PS. So it will be, this will be, right, PS minus losses. So here I can write this better, that it will be PO upon PS, and PO is basically PS minus losses. Okay, this will be your basically efficiency. Now let's do the analysis of load. Analysis of load is the same thing basically. Like if you find the AC component, what is the AC component? VORMS minus VO square average, and from there you can find the voltage ripple factor. All these things we know. Okay, your voltage ripple factor, this won't be changed same anymore. Like this will be different, so this will be according to the formula. So just remember this one is enough, right? This one is enough, and from there you can always derive. Okay, so yeah, all these things are there. Now let's find out the ripple of inductor current. So how do you find out the ripple of inductor current? If we have obviously continuous conduction, right? So from 0 to t on, what is happening? Case 1, from 0 t equals to 0 to t on, what is happening? Basically L di dt is equals to VL, right? L dIL dt equals to VL. Okay, so L into what? L into delta IL. That is my, so when the chopper is on, right, just it was minimum because it was discharging before that. Chopper is on, so now it will charge. I will just bring the circuit quickly here. Let's bring the circuit. I'm talking about 0 to T on, right? 0 to T on, what is happening here? My inductor current is increasing, right? Inductor current is increasing. So if inductor current is increasing, I'll just bring the circuit. If the inductor current is increasing, obviously it will go from what? It will go from minimum to maximum, as assumption is continuous conduction. So obviously it will finally is IL maximum, initially is IL minimum. So IL maximum minus IL minimum is equals to del IL divided by time duration is T on minus 0, that is T on only, equals to VL. What is VL? VL is equals to VS in this case. So basically my del IL will be equals to Vs alpha capital T, or T can come down what? F into L. Okay, this will be your IL. Or you can, what you can do is you can derive with respect to the output as well. So when this diode is on, then that also you can derive. You will get back the same expression. Okay, that is a homework. Derive with respect to the time zone between 0 to T on to T, capital T. So homework is what? Derive with respect to T on to capital T. Okay, that is what you need to derive. Okay, so all these things, IL max, IL min, all these formulas, Now what will be the critical value of duty cycle? The same thing as I think derived in the boost chopper, same only. So critical value means my IL min will be equals to 0. If it is equal to 0, that means my IL average or my IL del IL, right? Del IL will be simply equals to 2 IL average. Okay, 2 IL average. So here what I can say that what is del IL? I just derived del IL was equals to alpha Vs by FL. So del IL is 2 IL average equals to alpha S. Alpha this time, right, is critical, so it is alpha C Vs divided by FL. Okay, so your alpha C will be what? Alpha C will be simply 2 FL. IL average is there obviously. FL by Vs. Now what is your homework? You derive for pure resistive load. Okay, you just change this expression in terms of R, write this expression in terms of R. So homework is derive for pure resistive load. Okay, that is your homework. Okay, all these formulas you don't need to remember. You need to understand how can I derive this, because that it is there are so many formulas. You just see, right, for choppers you just see how many formulas are there. Don't remember these formulas. Let's just learn how to derive this. Then next, critical value of inductance. Same thing, same formula I will use here as well. So critical value of inductance, this thing will be same, right? This thing will be same only. Here just instead of alpha C, the thing will change to LC. So this will not be alpha C anymore. This will be LC. Okay, L critical. So L critical will be equals to 2 alpha Vs by 2 IL average into F. Okay, so this is my L critical basically. So again, what I will I have derived this in the boost converter. Just again, your homework is derive this. I'll just copy and paste the same statement. Derive this for pure resistive load, right, with respect to R. So yeah, this is about it. And what will be the input resistance this time? It is Vs DC upon Is DC. What is Vs? What is VO basically? VO is alpha by 1 minus alpha into Vs. So Vs will be 1 minus alpha by alpha. So it is Vo into 1 minus alpha by alpha. And what is Is? Is will be just the opposite. Is will be just the opposite. It will be IO average. This is again Vo average. IO average alpha by 1 minus alpha. So this will be Vo average upon IO average, which is basically R, right? So it is R into alpha square by 1 minus alpha. Whether this will increase or decrease totally depends on the value of alpha. Totally depends on the value of alpha. Have I done it correctly? No, this is not wrong actually. I've written it opposite. So this will be 1 minus alpha whole square divided by alpha square. Okay. So this will be my Rn as resistance seen from the source, right? Source. But this is just a fictitious resistance. Okay. Now, like when we'll analyze the capacitive filter. So when we analyze the capacitive filter, first analysis is that our IL will be continuous. Our IL will be continuous. That is the first assumption. IL is continuous, like the previous case also, and VC will be almost constant. VC will be constant. IL minimum will not be equal to 0 on all devices are ideal. Okay, same analysis that we did previously as well. So here, right, this VL is fine. This L should come here. Okay, things will get very messy. Fine. Okay, so let's do the analysis. Simple analysis only. It's the same thing only. So when this chopper is turned on, okay, this is triggered. So what will happen is that this VL will be totally equals to VS. VL will be equals to VS greater than 0. So it will energize. So my DIL by DT will be positive. Okay. So if my DIL by DT is positive, okay. So IL will will increase basically. So if IL increases, then that means basically IL is increasing, it is energizing, right? It is energizing. What about the other current? So basically my ID, right? ID is actually here, not in the between. Sorry for that. ID is here actually. So ID will be 0 because diode is off, right? Diode is off. How is diode off? I will show you that. Okay, ID is somewhere around here. Okay, it's fine. So ID is somewhere around here only. Okay, and it is 0. ID is 0 because diode is off. How is it off? Off. You can say check the voltage. So VD is what? VD is this minus VC, which is equals to VO. So minus VO minus VS, right? So it is some negative. Obviously, it will be off. So ID is off. Now, what about VO? VO, right? VO is equals to VC, which is almost positive, which is almost constant. Another thing you have to note here about IC. I haven't wrote down the IC. I have wrote down here, but here I haven't wrote. Okay, so IC is here. IC is here, and IO, right? IO actually is not in that direction, or is IO in that direction? Okay, have I wrote the IO direction wrong? No, actually, right. IC direction this time will be other way around. Sorry for that. Yeah, I like it will be entering into the positive terminal, right? Always. So IC will be this direction. So this time IC is equals to minus IO. Hence, obviously, it is negative. Hence, that means what? That means basically my dVC by dt is negative. That means my VC will reduce. Okay, slope of the voltage is negative. That means my VC will reduce. Simple as. Okay, VC will reduce, but my assumption is it will reduce to it will reduce by very small amount. It will not reduce by a very large amount. That is my assumption basically. Okay, these are the voltages. I have computed VD. VCH is obviously 0 in this case. VCH, right? VCH is 0 in this case. VCH is 0 volts in this case. Okay. What about the case 2? Case 2 is when the chopper is turned off forcefully. So chopper forcefully commutated. So if the chopper is forcefully commutated, what will happen basically? So this will turn off. As this turns off, my IS source current is 0. So here, right, I forgot to wrote down this. Okay, I forgot to wrote down about IL and all those things. So IL is equals to basically what? It is equals to IS equals to ICH. These three currents, right? Here IS equals to 0, which is equals to ICH. Okay, these are 0. What about my VCH? So VCH, right? I haven't wrote down about VCH. VCH polarity is something like this. VCH polarity is something like this. So VCH will be simply equals to Vs minus plus VO. Okay, because this is on the opposite polarity, so this will be plus VO. Okay, and what about the other voltages now? Obviously VD is 0 because it is on. We can check from the current direction as also. First of all, I have to move this ID here. So ID equals to IL. That thing I know. Okay, ID equals to IL, and my just before that, right? ID is equals to IL. I'll go before this. Before this, important point is my VL. Where are the other colors, man? I'm not able to find. So VL is equals to minus VO. Okay, this is my VL polarity, right? If you remember, this is my VL polarity. So VL equals to minus VO, hence it is negative. That means basically my IL will reduce, right? IL will reduce, and my IL is equals to what? IL equals to ID equals to, what is the direction of current? This, right? Okay, fine. This C should come over here. IC and IO. So IL equals to IC plus IO. Okay. So obviously all the ripple components will be taken care by IC, and IO will be constant. So IO will be constant. This will be constant. Okay. This will be constant. And all the ripple components will be like whatever increase and decrease there is on the IL, that will be taken care of by the IC. Okay, so like as here, what is happening? IL is reducing. IL is reducing, right? IL is reducing. So IL is reducing. That means IO is constant. So IC will reduce. So if IC reduces, that means what? If IC reduces, at certain stage, what will happen is that IC will go negative, and if IC goes negative, right? If IC goes negative, then dVc by dt will go to lower than 0. Okay, dVc by dt will be less than 0, and the voltage will basically, am I correct? This is IC, yeah, and this voltage is like, this is IC, right? And here, okay, this is de-energizing. So obviously IL will reduce. As IL is reducing, IC will reduce. Yes, IC will reduce. As IC reduces, okay, still it will be some positive value only, but no, it cannot be positive value. After certain stage, it will reduce, right? So your VC will also reduce. Okay, basically IC is reducing. Certain stage, from positive, initially it will increase. Okay, as IC is positive. So for certain periods of time, your VC will increase, then VC will reduce again. Okay, because your IC will be positive for a certain period, then it will be negative. That's why it will reduce again. I hope you understood those points. Like these we have taught in boost converter. So exactly that will happen over here. Basically, right, this average voltage VO, like when this is turned off, when the chopper is turned on, the connection between diode is not there, right? So basically this capacitor is simply discharging through the load. As this capacitor is simply discharging through the load voltage will decrease. Okay, load voltage will decrease. But here what is happening is that if, like, one thing is that if your IC minimum is greater than 0, then in this region it will always increase, because IC minimum is positive. Okay, it will not go. But if your IC minimum is less than 0, then obviously after increasing it will decrease. Okay, we'll take that case as well. So but my assumption, like here, right, my assumption is IC minimum, the capacitor current is greater than 0. If IC minimum is greater than 0, then for the off time, right, off time, my delta VC will be greater than 0 basically. That is the thing, right? Because IC minimum is greater than 0, it is positive, so voltage will only increase. Hence, that's why output voltage also increase because it is directly connected across the load. Okay, so this is my assumption for the waveforms. VD I have already told you, this is minus Vs plus VL. Have I computed it? No. So VD we will compute what is for the this case, right? Yeah, for this case it is minus VO plus Vs. You can say VL is Vs basically. Yeah, minus VO minus what, not VL actually, sorry, not VL. This should be minus VO minus Vs. Minus VO minus, so this will be VO, right? This should not plus, this will be minus VO. Next, what about VCH? VCH is Vs plus VL. VCH is Vs plus VL. So it is basically when the chopper is on, it is basically 0 volts, and here when the chopper is off, it is basically Vs on this side and VO is on the other side in the opposite polarity. So it is in the forward blocking mode. Okay, Vs plus, not VL actually, this will be Vs plus VO. Okay, current is same. Or when the like chopper is on, it is energizing the inductor. When the chopper is off, it is de-energizing the inductor. Same thing, right? And here IC, as I was talking, this is the IC minimum, right? Where did it go? This is not IL maximum actually, sorry. This is IL maximum minus IO, right? IL maximum minus IO. IO is the constant current, and this is IL minimum minus IO, which is the minimum value. If this value actually goes to negative, then obviously my capacitor will discharge, and this is minus IO basically when inductor is not present at all. Okay, so yeah, this will be the values, this will be the VL, so it will be equals to plus Vs and minus VO for 2 periods, and from there we will be able to compute the average voltage that we have already computed. So IS and chopper current, it will follow the input for the T on period, then it will be totally 0, and just IO will be constant value IO, and VL is this only. And like ID, have I drawn ID? No, right? This should have been ID. There should have been an ID, right? There isn't an ID. Instead of VL, right, I could have drawn an ID. I'll just quickly do that. Actually, that is better. Yeah, I have drawn the diode current. Now what you can do is you can simply like write down the standard relationship here also. One important point to note here is this is about IL. When IL is continuous, this will be the standard relationship for buck boost converter. So like let's now analyze the ripples of voltage. We have analyzed the ripples of current. We will analyze the ripples of voltage. Simple. Again, there are two cases here. Two cases, right? Two cases. Case 1 and case 2. When case 1 is what? Case 1, basically my IC minimum is what? IC minimum is greater than 0. That means what? That means my IL minimum is greater than IO. It's greater than IO. Okay. So if my IL minimum is greater than IO, then exactly this is the graph, right? This is how the graph will look for the current, capacitor current. So I will be able to simply derive the change in voltage, change in ripple voltage. So it will be simply equals to, I'll just quickly write it, just hold on. So delta VC is this, VC max minus VC min. So now what I can say is, I can say this, right? I can say that my IC is C dVC by dt, this much I know. This much I don't know, dVC by dt. So in this period, right, in this period what is happening? This is always negative. This is always negative, and in this period this is always positive. So in the on period this is always negative. That means it is always discharging. As it is always discharging, what does that mean? That basically means that my voltage here was VC max and then it got reduced to VC min. So VC min minus VC max is minus delta VC. So minus delta VC into C is obviously here, and this is the period of T on. What is the capacitor current? Capacitor current is minus IO. Okay, capacitor current is minus IO, or I can say IO average. So okay, I need to, yeah, Okay, I forgot to multiply the T1. So this is anyways, this is constant, right? So area is minus I1 to T1. Like we should have written it like this. I written it a bit wrong. Actually, the way to write it is like this, that it will be the charge transfer, right? It will be the charge transfer. So what is the charge transfer? Basically the area of the current. So delta VC is equals to C delta VC is equals to delta Q basically. So like this we are able to find out. So minus delta VC. So our delta VC will be what? Delta VC will be basically alpha into IO average divided by FC. This will be my delta VC, and like you can derive it. And the homework for you is case 2. Okay, so homework for you is case 2. This much you do. Like we'll get the same results and same formula. Just do it for the case 2. And what is the case 2? Case 2, right? Case 2, what will happen is, I'll just show you. In case 2, basically, in case 2, our IC minimum will be less than 0, negative. Our IC minimum will be less than 0. So what will you get? Okay, our IL minimum will be less than IO. Okay, so here what will happen is that it will reach 0 somewhere here. Somewhere here it will reach like it will reach 0 beforehand, and like it will go somewhat like this. Okay, so our IL minus IO minimum will be here at this level. Okay, so this time will be T1, for which the period my IC is positive. This period is T2, and this is basically capital T. This is T1, right? So now I hope you can derive all these things, and you don't have to derive. Let's just what my recommendation will be, just find the area of IC of T from T on to T on plus T1 should be equal to, this is amount of charge, right? This is amount of charge, change in charge, and here this will be delta VC into C. Just you use this. Okay, use this. Like you cannot obviously derive a good expression for this with respect to the question. Only you will be able to solve this. So just solve this, and from here you will be able to find delta VC. Okay, that is how you find delta VC. Okay, so this is VC max and VC average and all those things with respect to delta VC. And what are the critical value of capacitance? Again, this is for the case 1. Case 1, critical value of capacitance. Like what formula I know? What formula do I know? This is the formula, right? I just derived here. Delta VC is equals to alpha IO into FC. So critical value means what? Critical value means my VO minimum, not VO, sorry, VC minimum is 0. Basically, my delta VC will be equals to 2 VC average. Okay, so this is 2 VC average equals to delta IO average into critical, right? My value of capacitance is critical, so it is going lower. So it is FC is C critical. So C critical will be what? It will be alpha IO average into VC average. So basically IO average into VC average is VO average. So VO average is R. So alpha into IO average into VC average, right? Yeah, average divided by F into VC average. Okay, so here basically IO average is IO only, and VC average is VC. So it is IO average upon VC average. So it comes out to be this R. Okay, this comes out to be R. So this will be alpha FR. Okay, so you can write it like this as well. 2 is here also. 2 alpha by 2 FR, right? So yeah, this is how you can derive. Okay, like don't remember, just know how to derive all these things, right? Now we'll solve a question for case 2. There is not a fixed like formula. All you need to do is basically from the question itself you have to write down all the expressions. Okay, so now let's do it for the few questions. Let me just drink a bit of water. A buck boost DC to DC converter shown in the figure is used to convert a 24 volt battery voltage to 36 volt battery. So basically it is increasing the voltage to feed a load of 72 watts. So I know a load is of 72 watts and this load is 36 volts, right? Voltage is 36. So obviously my IO average I can directly find out. IO average will be 36 by 72. So this will be 1 by 2 amperes. Okay, and basically my F switch is 20 kilohertz. Okay, with an inductor of 2 millihenry. F switch is 20 kilohertz with an inductor of 2 millihenry and output capacitor of 1000 microfarad. So this capacitor is 1000 microfarad, C is 1000. Okay, L is 2 millihenry. Fine, all the data I am just noting down. Heavy huge data is there. The peak voltage across a solid state switch. The peak voltage across a solid state switch. Now this, right, this can be solved in two ways. Okay, one is you find out the ripple. Okay, then you find out the peak voltage. Other is you don't find out the ripple. So what will be the peak voltage coming across the switch? So it like switch voltage, right, either can be 0 or it can be, if you remember, it can be 24 plus VO, right? 24 plus VO. So my VS, right, VCH or the chopper voltage is either 0 or it is some VO plus VS plus VO. So VS plus VO. Now this VO, right, has some ripples. This VO has some ripples actually. So this is equals to, like, I know what question they tried to frame, but the question what happened was became easy. Okay, became easy. I'll just explain in a bit. So VCH is equals to VS plus VO, and like many people what they did was like VS is 24 and VO is how much? VS is simply 36. So this will be plus 36 and this will be simply 60 volts. And they got their answer as correct. But this method, right? This method is not correct, and this is not the intended way on which they wanted the students to solve the question. Actually, what they wanted this, right? When this switch is forcefully turned off, what is when this switch is forcefully turned off, what is happening is that the capacitor voltage is actually increasing from minimum to maximum. If you remember, from minimum to maximum. So at the instant at which the switch is turned on, at this voltage, right, I have VC minimum. At this node I have VC minimum. Okay, and at this node is fixed 24. So the maximum voltage that will come across the chopper, right, actually this voltage, right, this voltage actually is varying. Although we assume this is almost constant, but this has still some ripples. I'll just show you the waveform. This is the voltage, right? So at this instant my chopper is turned off. So at this instant the voltage is VC minimum, and this will be the maximum potential that will come across the switch. Okay, when the VC chopper voltage is VC minimum. Okay, so I'll just quickly draw this. Okay, then this will increase. Sorry for that. T off and reduce and increase. So here what I can say, so this is the voltage VC minimum. This is what I want to find out actually. How do I find out? So basically, right, I need to find out the ripple, and from ripple I know VO average they have given me. This is VO average, right? VO average they have given me. VO average is basically 36 volts, right? So how do I find out ripple? So del V, right? Del VC, what was it? It was basically area under the current waveform. Okay, under the current waveform. If you remember it correctly, I need to bring out the current waveform as well, right? Copy the current waveform as well. This was the current waveform. Yeah, this one. So my assumption here is, again, IL minimum will be greater than IO. So all those things I have to take care of. Okay, like answer is 60 volts, almost equal to 60 volts, as the ripple is very, very low. That's why. So I need to find out IL minimum and IL maximum. For that, I need the current waveform of this, right? So I need to find out del IL. So IO average I know, right? IO average I know. So how do I find out del IL? So first for this, right, I first of need to find out del IL. So what is del IL? L DIL by dt is equals to Vs. Okay, so del IL will be equals to alpha into Vs divided by F divided by L. So alpha is what? So whenever these values are given, right? Whenever these values are given, inductance values is given, capacitance values is given, then you need to check all this. Okay, I will just write this down quickly. I will just write this down. If inductance, capacitance value are given, then you need to check. Else, if they are not given, how will you check? You will assume constant. Okay, so very important point here. If inductance slash capacitance values are given, then only check all this. Okay, so so this is the case. So here, right, alpha into Vs by FL. Alpha they have given me. Alpha they haven't given me, but I can find out the alpha, right? I can find out the alpha. I can find out the alpha with respect to this voltage ratio, right? This is a buck boost converter. So what is the alpha? What is the alpha? Alpha, right? Alpha will be what? Alpha by 1 minus alpha is equals to VO average by Vs. So VO average is 36. This is 24. So 36 by 24. So this is 3 by 2 equals to alpha by 1 minus alpha. So alpha is, if I assume this as like 3 times 3, yeah, what would be this? So this will be 3 minus 3 alpha equals to 2 alpha. So this will be 5 alpha equals to 3. So alpha will equals to 0.6. Alpha will be 0.6, right? Yeah, alpha is 0.6. If alpha is 0.6, this is 0.6 by, yeah, 0.6 exactly. So alpha is 0.6. Now we'll put this value. So I know T, have they given us the switching frequency? They have given us the switching frequency, which is 20 kilohertz. So I will write here, my del IL will be alpha is 0.6 into Vs. Vs is 24, I believe. 24 by switching frequency 20 kilo into, what is the inductance? Inductance is 2 milli. So kilo and milli will get cancelled. Okay, so this will become something like this. This will be 12. This will be 5, and this will be 3. And (0.36). Okay, so del IL will be 0.36 amperes. Now if del IL is 0.36 amperes, what is my IO min and IO max? So what is my IO min? IO min will be IO average. IO average is how much? IO average is 0.5. So 0.5 minus 0.36. IO average minus del IL by 2. So this will be 0.18 by 2, 0.18. So if I subtract 0.18, right, what will be it? It will be 0.32 amperes. Okay, and your IO max will be 0.5 plus 0.68 amperes. Okay, one mistake I have made is that like I was computing the this IL average, right? Wrong. It is exactly not equals to IO average. Actually, my IL average, if I write my IL average in terms of IS and ID, diode current, so if I write KCL at this note, my IL is equals to IS plus ID, right? IS plus ID. Now ID is what? ID is both IC plus IO. So exactly that is what I have written. Now if I take the average on both sides, so IL average will be basically equals to IS average plus IO average, and IC average will be 0 over a cycle, because and steady state the average capacitor current is 0. We assume it as open circuit. So IS average, right? So what is IS average? So IS average, right? IO average I know, I just divided it by power. So what is IS average? IS average will be same thing only. IS average will be simply 24 by 72 equals to 1 by 3 amperes. Okay, equals to 1 by 3 amperes. So okay, these things are written. So 1 by 3 is 1 by 3 plus 1 by 2. So this will be 5 by 6. Okay, IL average, five by 6. So IL average is 5 by 6. So IL average is actually 5 by 6, right? This is 5 by 6, this is 5 by 6, and this is like I'm computing the IL minimum and IL maximum. IL minimum and IL maximum. So what will be IL minimum and IL maximum? IL minimum will basically 5 by 6 minus 0.81. So this file, right? I'll just quickly compute it. 5 by 6 minus 0.18. This will be 0.653. 0.653, which is actually greater than 0.653, which is actually greater than IO average. And this value, right? This is 5 by 6 plus 0.18. So this will be 1.1034. Okay. So now what is my IC minimum? IC minimum will be IL minimum minus IO. Okay, so this will be basically 0.653 minus 0.5. 0.5 is the average current, that is the constant current that I am providing. So it will be 0.153. So it is positive. That means that previous formula is valid. Okay, so this is the hard work that we have to do. So don't worry, like in actual examination I hope much simpler questions will come. This is anyway simpler, because once we'll see that if you use that formula, right? What is the formula? Basically C into delta VC equals to delta Q. So I will just compute the current, right? This area of this period. So I will compute area of this period. What is the area of this period? It will be basically so delta VC will be what? Delta VC will be delta Q. So it is area of this. So what is the area of this? Area of this will be like I will just draw the graphs here quickly. So this, right, this IL minimum minus IO will be what? This IL minimum minus IO will be simply 0.153. 0.153. And this IL maximum minus IO. So IL maximum minus IO will be simply I have to add I think another 0.4. Not 0.4. 0.35, right? 0.36 or 0.36 if I have to add. Simply this added 0.36, right? 0.653 plus 0.36. Yeah. So I will add here 0.36. So 0.153 plus 0.36. This will be 0.513. Okay, so now I can compute the area. Basically, what is this T? This is the T of time, right? This is the T of time. Okay, this is basically equals to 1 minus alpha into capital T. So delta VC, right? Delta VC will be what is this delta I? This is delta I, right? Delta I L into half into T off. Okay, T off is common, plus this IL minimum, this 0.153 into T off again, T off by T, right? So this will be 1 minus alpha basically. Okay, and obviously I have a C at the bottom as well, C. So what will be the values here basically? So delta IL is, I know delta IL is basically 0.36. So this is 0.36 into 1 by 2 plus 1.53 into 1 minus alpha. What is 1 minus alpha? 1 minus alpha is, I think it is 0.6, so it will be 0.4. 0.4 by C. What is C in this case? C is actually 1000 microfarad. So I can assume this as 1 milli, right? 1 milli. Yeah, actually I forgot there is a T on in this formula as well, right? So this T on is also there. So alpha into T. So this, there will be actually 0.6 divided by, what is the frequency? Frequency is I think it is 20 kilohertz. So 20 kilo. So everything will get cancelled basically. So this milli and kilo will get cancelled here. So this will be divided by 20 into 0.6. So this will be a very low amount, right? Like this ripple, right? Delta VC will come out to be 0.004. Actually, this is very low amount. So it doesn't get picked up in the numerical NAT answer type. So that's why your actual answer, right? Actual answer will be what? Your VC minimum will be what? It will basically equals to VC average, which is equals to VO minus delta VC divided by 2. VC average is 36 volts, I think. Yeah, 36 volts. 36 volts minus 0.002. So this will be 35.998. Now if I calculate the VCH maximum, it will be simply VS minus VC minimum. Okay, so VS is how much? Sorry, this will be plus VC minimum. Oh, sorry, plus if it, okay, sorry, this will be maximum, right? This is the maximum voltage block. Sorry, actually, my bad. This won't be minimum. This won't be minimum actually. This will be maximum. Sorry, maximum. So here, this will be the VC maximum. So this will be VC max will be how much? VC max is simple only. It is 36.002. So this will be 60.002 volts, which doesn't make any difference because we have to write only 60. So your answer gets same. But someday, if the ripple is very high, then VC max will change. Okay, I think they tried to frame the question like this. So, but they couldn't, like, due to the values. If the capacitance was a bit low, right? If the capacitance was a bit low, then this ripple would have increased. And if this ripple would have increased, then definitely 60 won't be the answer anymore. So just I'm explaining you the future questions. Okay, explaining you the future question, what can come in the future of examination. Let's come to the next one. This is a very, very good question. Okay, even though like many educators, what they'll do, they will just directly write this. Will not explain you anything. Okay, actually what the examination the exam like question who framed the question, right, tried to like make you solve what he tried to make you solve, but actually question become very simple due to the value of the capacitance. Okay, so yeah, let's go to this next question. Next question is pretty simple. Here they have told us the input voltage VDC of the buck boost chopper varies from 32 volts to 72 volts. So Vin or Vs varies from 32 volts to 72 volts. Assume that all components are ideal. Inductor current is continuous and output voltage is ripple free. Assume that all components are ideal. Inductor current is continuous and output voltage is ripple free. So output voltage is ripple free and inductor current is continuous. So these things we know. The range of duty cycle D of the converter for which the magnitude of steady state output voltage remains at 48. So my output voltage needs to be remain at 48 volts and my IL is continuous, inductor current is continuous and my voltage is constant. Okay, VO constant. So how do I do this? Simply by changing the duty cycle ratio. So as my input Vs is changing from 32 volts to 72 volts, how can I change the duty cycle ratio? Basically I know for a buck converter, if the IL is continuous, VO upon Vs will be alpha by 1 minus alpha. So if my VO is the lowest, 32 volts, then what alpha I need? So this will be, sorry, if my Vs, so Vs is 32 and VO is 48. Okay, so alpha I will need is alpha by 1 minus alpha. So this will be basically 4 by not 4, so 48. This will be basically 6 by 4, right? So this will be 3 by 2. So if this is 3 by 2, so alpha is simply 3 by 5, right? Is it 3 by 5? What am I thinking? Yeah, it will be 3 by 5, I think. Yeah, it will be 3 by 5. And if my VO is Vs is 72, right? VO will be 48 only. This will be 72. So now my alpha has to be lower now. Okay, so this is basically 8 is 6 by 9. So this is 2 by 3. So if it is 2 by 3, then what does my alpha needs to be? So this will be 3 alpha equals to 2 minus 2 alpha. So this is 5 alpha equals to 2. So alpha will equals to 2 by 5. Okay, so alpha range, right? Alpha need to lie between 3 by 5 and 2 by 5. Okay, so basically option A will be correct. So this question was not much like we don't need to do much brainstorming. Everything has been given to you. Okay, everything has been given to you. Okay, so you try, like I will just pause the video for this question and this question. You try out this and this question, these two questions, and I will just soon come back and solve all this. Okay, these are the good questions that I picked. So these two questions you try to solve by yourself, and I will solve this after this. So what have they asked in this question? So if I just zoom in a bit, right? In the circuit shown, all elements are ideal. And switch S is operated. All elements are ideal and switch S is operated at 10 kilohertz. So here my frequency is what? Frequency is 10 kilohertz. Okay, and 60% duty ratio. So duty ratio 60%. So alpha is 0.6. Okay, alpha is 0.6. The capacitor is large enough so that ripple across the output is negligible. So that means this VO is constant, and if VO is constant, then IO is also constant, right? IO is also constant. So IO is equals to 75 by 5, which is 15 amperes. Fine. So then next, what are they talking us about? And at steady state acquires a voltage as shown. The peak current in amperes drawn from the 50 volt source. So what is they are asking us? The IS maximum, right? Peak current from the source. They are asking us the IS maximum. Okay, so they are asking us the IS maximum. What is IS maximum? Basically, it is basically the inductor maximum current at t equals to t1. At t equals to t1, I'm actually achieving the maximum current, right? That is what this is asking. So okay, so basically this will be the IL maximum, right? IS equals to IL. This will be the IL maximum. So I need to find the inductor maximum current. How do I find it? Further, I need to find the ripple delta L, right? What will be delta L? Delta L, L dIL by dt, I know, T on equals to VL, that is Vs this time, which is equals to Vs. So what is T on basically? What is alpha? Alpha, they haven't told me, but I like this voltage is constant and my assumption is inductor current is continuous. So if inductor current is continuous, what can I say? Okay, duty cycle also they have told me. So duty cycle is 0.6. And if I just find out like this buck boost chopper, this is a buck boost chopper configuration, right? Buck boost chopper configuration, because inductor is connected in between. So if I just, for my own safety, if I just check this relation, VO average upon Vs is equals to alpha by 1 minus alpha. Is it satisfying or not? So what is alpha? They have given me 0.6 by 0.4, so it is 3 by 2. So VO average will be 3 by 2 into Vs, which is 50. So this will be 75 volts. So this is correct. Okay, so this is satisfying. That means inductor current is continuous. So whatever I am doing is correct. Okay, I don't need to draw waveforms or anything. If inductor current wasn't continuous, I have to draw a waveform and then derive from there, right? But here it is continuous, so don't have to do anything. Okay, L they have given, L value they have given. So my delta IL will be basically Vs is 50 into alpha into T will go in the bottom. L is how much? L is 6.6 milli. 0.6 milli into 10 kilo. Okay, so what is alpha? alpha is 60% duty cycle, right? So 0.6 gets cancelled. This is 10 times this kilo and milli gets cancelled. So this is 50 by 10 basically. This is 5 amperes. So delta L actually is very good, right? Delta L is basically 5 amperes. So now I know delta L, but I need to find out average inductor current. So how do I find out average inductor current? That will be a bit difficult. So here my current, right? Delta L, how do I find out average inductor current? So one thing I know what will be IS average. So this relation will also follow, right? This relation will also follow that my IS average by IO average will be basically IO average into alpha by 1 minus alpha. This relation will follow, right? This I have derived previously. So this will be IO average is how much? IO average is 15 amperes. So 15 into 3 by 2. So this will be 7.5 into 3, that is 22.5 amperes. So what is my IL average? So IL average, right? IL average will be, I have derived this in the previous question. It is basically equals to IS average plus IO average. So my IL average will be basically 22.5 plus 15. Okay, 22.5 plus 15. So this is correct, right? 37.5. Am I correct here? 2.5 plus 15. Yeah, this is 37.5. Okay, so now I need to find out my maximum source current. So what will be my maximum source current? So IS maximum will be basically equals to IL maximum just at t equals to t1. At t equals to t1, it will be IL maximum will be what? It will be IL average plus delta IL divided by 2. So IL average is what? IL average is 37. This is amperes, right? 37.5. And 7.5, not 7.5, sorry, this is 5 by 2, right? So this will be 2.5. So this will be 40 amperes. Okay, so 40 amperes will be answer. Now for many students, right, this will be very difficult. But did I use any formulas here? I try to use as minimum formulas as possible, right? Because I derived also like what will be IL average, what will be IO average, what will be IS average in terms of that. But here I use minimum formula. This formula is the most standard one. This one and this VS average, and to check the value alpha. Those two formulas I used, and this one is just I derived, right? I derived in front of you and then I wrote. Okay, and this one already I know. How can I write this? Same, just you write the equations here. You write the case here. If you write IL is equals to IS plus ID. Okay, and what is ID? ID is IO plus IC. So then if I take the average on both sides, IL average will be equals to IS average plus ID average, and ID average is equals to IO average plus IC average. IC average will be 0 because steady state capacitor behaves as open circuit, so it will be totally equals to IO average. So your IL average will be equals to IO average plus IS average. From there you can get all of the derivation, right? So I hope you understood. Like for many, trust me, for many students this will be very difficult. If you just try to mug up everything, it will be very difficult. That's why you need to go conceptually. You need to solve conceptually the questions. Okay, it is very important. Now let's solve this question. A DC to DC converter operates at a period of switching of 0.1 milliseconds. So my time period is 0.1 milliseconds, and if the inductor current is on the edge of continuous and discontinuous conduction, calculate the ripple in load current and turn on time of the switch. So if the inductor current is on the edge of continuous and discontinuous, basically if it is on the edge of continuous and discontinuous, my IL minimum, right? IL minimum will be simply 0 amperes. Okay, IL minimum is 0 amperes, so my delta IL will be 2 into IL average. So they are saying calculate the ripple in load current and turn on time of the switch. So I have to compute the alpha as well. So this much I know, it is on the edge of continuity and discontinuity. So obviously inductor current is just on the continuous state. So then I can still write the relationship. This is a buck boost chopper, right? If this is a buck boost chopper, VO average upon VS will be equals to alpha by 1 minus alpha. If VO average is 500 and VS is 100, so alpha equals to 5 minus 5 alpha. So alpha will be equals to 5 by 6. Okay, alpha equals to 5 by 6. So alpha will be equals to 5 by 6. That is, so this IC, right? This IC actually will be in the opposite direction, not in this direction. Sorry for this. Okay, I know alpha equals to 5 by 6, and that is the okay. Turn on time is what? Turn on time will be basically what? T on will be alpha into capital T. So 5 by 6 into 0.1. So what is this? I will just quickly compute it. Like in micro, I can compute 5 by 6 into 0.1 into 100. So this will be 8.33 microseconds, right? Or 100 or no, not 100 into 1000, right? 83.33 microseconds. This is a T on. So this part is simple only. But how do I compute the ripple? So ripple is what? Del IL LIL by dt, that is T on, equals to VL or equals to VL. VL is what? VL is VS at this period. It is VS. So this is the VS. This is also very simple, right? This question is also very simple. So VS. So basically my del IL will be equals to, what is VS? VS is how much? VS is 100 and inductor is also 100 micro. This is a micro, and this T on is also micro, 83.3 micro. A T on I just computed the T on. So yeah, this del IL will also be what? Del IL will be 83.8 milli. That will be too high, right? Okay, yeah, 83.3. So del IL is actually pretty high. Okay, del IL is actually pretty high. It is 83.3 amperes. So it is huge ripple. 83.3 amperes, huge amount of ripple, right? Very high ripple. So all that ripple has been taken care by the capacitor. Okay, by the capacitor is taken care. So this will be answer, and this is very high, very high. But still, this will be correct only because in the question they have given that we are on the edge of continuity, boundary of continuity and discontinuity. Okay, so yeah, that's it about buck boost chopper, and mostly everything is finished for choppers. Just a bit of analysis of the supply current we'll do with the help of Fourier series, and few miscellaneous concepts are left for choppers, and like then we'll study about commutation of. Hey everyone, and welcome back to PrepFusion. I'm Anish, and today we'll start a new topic, that is the Fourier series analysis of our supply voltage which we obtained of the load voltage which we obtained from the choppers, and obviously we'll study about the commutations. So what we have been doing, we have been turning off the switches, right? Forcefully turning off the switches. So how do we actually forcefully turn off the switches? How is that procedure followed? So that also we'll learn in this different commutation circuits. There are different force commutation circuits for which we'll learn the methods. Okay, so yeah, these two topics we'll cover. So it will take around 2 lectures. So first lecture will mainly analyze about this Fourier series and a bit about commutation circuits, and in the next lecture we'll totally wrap up our commutation circuits, and that will totally wrap up this chapter, that is choppers. Okay, so first of all, let's give us a quick recap, right? So our step down chopper, like we mainly focus on the waveform of the output voltage of step down chopper. Output means this, right? This voltage. This is much easier for us to analyze. So here, like if you remember this, that our step down chopper was built like this. That switch was here. This was a freewheeling diode, and whenever this switch was on, our output voltage was equals to Vs, and whenever this switch was off, our output voltage was equals to 0, right? Because this freewheeling diode was on, as the current is continuous. So this was the output voltage waveform, right? VO when the chopper is on is Vs, and when it is off it is 0. So this value is Vs basically. This value is Vs. Okay, so like we basically want to write the Fourier series of this. Now unfortunately we don't have any option but to remember the Fourier series, but it's almost similar, right? The Fourier series will be almost similar for the rectifier. Okay, for the 4 I summarized, For the 4 types Fourier series I summarized here. Also for that was for load current, right? Load current, but not load current, that was for supply current. Okay, and here it will be for output voltage, and in the inverters it will be also for the output voltage. Okay, so here this, right, this will just, you have to remember a bit this, right? So V of t, I can break it down in terms of different harmonics like this, alpha into Vs. What is this alpha into Vs? This alpha into Vs is basically the average value. So this DC value will always be there no matter what. So I will always add this DC value, and remaining this, right, all of this is AC. So this is DC plus AC. So overall, if I find out the average of V of t, only this DC part will remain. That's why this will come out here outside. So you can remember it like this. This is the DC part. That will always be there. This is the average part, right? DC part. And this is the AC part. Okay. AC part. This is the harmonics, right? This is the harmonics that I don't want. I don't want AC on my output because this is a DC to DC converter. Okay. So here, how do you remember this? So basically, you can remember it like this, that this 2 times Vs means what? This is, what is the peak to peak? What is peak to peak? Peak to peak is Vs, and if I multiply 2 with that, I will get 2 times Vs. So basically, whatever this comes out in the numerator, right, it is always 2 times peak to peak. If you remember, I explained in the that Fourier series of the supply current as well, right? So it is 2 times V peak to peak. Okay. 2 times V peak to peak. Now this, right, this is always constant, right? Divided by n pi, that is constant. For a square wave form, we get a Fourier series like this. Like the, if you have studied sequencer systems, you will know. Next, this sine alpha omega. Sorry, this sine n alpha pi. So this one will be constant, right? This one will be constant. So here, this part you have to remember. This is a very, very important part. What does this say basically? This says that it can remove the harmonics, because the sine n alpha pi will be 0 for some values of n alpha, right? And whenever it is like 0, right, that harmonic will be totally eliminated. I will come to that, come to this more later. So next is cos n omega naught t minus n alpha t. What is omega naught? So here, right, omega naught is basically, I will just have forgotten to write it, that your omega naught is basically 2 pi upon t. Okay, what is t? T is the switching frequency, right? If you remember particularly, a switching time period, t is 1 by f, 1 by fs, right? 1 by fsw, switching frequency. So I hope you remember all this. We have just finished, like we're just finishing chopper. So I hope you remember all this. So this is so here, right, sine will not come. Previously sine was coming, but here sine will not come. Why is sine not coming? So if you observe, right, this is actually not totally even per se. Okay, this is not totally even, that's why. Yeah, but like this part you have to remember actually, like this part you have to remember that first of all you write the average value alpha Vs, that will always remain. Then you write the amplitude of this sinusoid or cosinusoid waveform. What will be the amplitude? It will be 2 times the peak to peak. 2 times the peak to peak is Vs is the peak to peak. Vs minus 0 is the peak to peak. So 2 times that is 2 Vs divided by n pi. Then you write sine n alpha pi. So that you have to remember. This part you have to remember, and this is very, very important part. We'll come to this later. Next, you have to write cos n omega naught t. Omega naught is basically the fundamental frequency minus n alpha pi, and others will be just the multiple. N alpha pi will be here as well and here as well. Again, this will lag. Okay, this part you have to remember, this will lag. Why is this lagging? Because, like, if you remember that your current waveform will start like something after this, right? If the current waveform starts after this, so what will happen is basically there will be a delay of the current waveform. That's why this is lagging. Okay, so yeah, that is basically it. Now what about this portion, right? What is this? So let's take few cases. So if my alpha is 1, right, let's take a case where my alpha is 1. So if my alpha is 1, what does that means? That means my T on is equals to T. So the switch is always on. So it is constant DC. So then what harmonics will be removed? So here, right, if my n is equals to 1, then that harmonic will be removed, right? Because if alpha equals to 1, this term gets replaced with sine n pi. Sine n pi. And when is this n pi like 0? At every n equals to 1, n equals to 2, n equals to 3. So all the harmonics are removed, right? But here specifically n equals to 1 harmonic are removed. Okay, so all harmonics are removed anyway, okay, because it is pure DC, right? It is pure DC. Then like no that step down or step up happens, right? That is of no use to us. So obviously that is the main thing. But fundamental thing is first harmonic is removed. I will come to more of this. First harmonic is removed. Other harmonics are also removed, but mostly I'm focused on this. First harmonic is okay. Next, let's like take another value, alpha equals to half. So if alpha equals to half, then what is my T1? T1 is T by 2. If T1 is T by 2, that means what is it? It is sine n pi by 2, right? So then now what harmonic will be removed? Now if n equals to 2, right? N equals to 1, it hasn't been removed because n equals to 1 means sine pi by 2, which is the peak value, which is 1 simply. But n equals to, if I put here n equals to 2, it will be again sine pi, and again sine pi is 0. So again second harmonic has been removed. Second harmonic has been removed, and all of its multiple. Second harmonic and all of its multiple, integral multiple has been removed. So 2, 4, 6, all of this will be removed simply. So second harmonic and all of its integral multiple, right? Same for first, like basically here all harmonics will be removed simply. Just write the same thing. Okay, so I can change the color of this as well. Now this pattern will follow, right? You can choose for other examples as well. This pattern will just follow. So what pattern I get? So it depends on the value of alpha. If I choose a particular alpha, for that particular alpha, right, particular harmonic will be removed. So basically I can say here, if my alpha, right, here, right, as T1 was equals to T, then my first harmonic was removed. As T1 equals to T by 2, so my second harmonic was removed. So if my T1 equals to T by N, then basically that, for that I am sure that nth harmonic will surely be nth harmonic will be removed. Okay, so yeah, nth harmonic will be removed and its multiple, that point is there. So here what will be the value of alpha? Alpha will be simply 1 by n, right? So it follows the inverse relationship that whatever the value of alpha is, let's say alpha is 0.25, so it is 1 by 4. So fourth harmonic will be removed in that case and its multiple. So this is a good thing to know, and these type of questions can be asked. So we'll take one question, and in that question everything related to the supply voltage for the Fourier series analysis will cover. Okay, so for a step down chopper of given below figure, so this is a step down chopper of given below figure, DC source voltage is equals to 230 volts, load resistance is equals to 10 ohm. Okay, load resistance is 10 ohm, DC voltage source is 230 volts. Take a voltage drop of 2 volts across the chopper when it is on. The duty cycle of for a duty cycle of 0.4, so duty cycle is 0.4. so all these are given, so I'll just quickly write down the data. So alpha is 0.4, VD on is 0.2 volts, Vs is 30 or what was it, 230, right? Yeah, it was 230 volts. R is 10 ohms. Okay, take a voltage drop. What is R is 10 ohms? Okay. Yeah. So all these are given, right? So what are they asking us actually? They're asking us the average output voltage in volts. So average output voltage in volts is pretty simple, right? It is basically the chopper step down chopper average voltage. This result we know that is alpha into Vs, but is it Vs this time? No, right? It is not Vs, because what is coming across my output is actually when this chopper is on, right? There is a drop across this chopper, that is 2 volts. So actually the output that I'm getting is 228 volts instead of completely 230 volts. So obviously that one I have to write. So we'll just draw the waveform. Okay, that is simple only, right? And I will assume continuous conduction. And if you observe, right, what is R by L? So L value, right, they have not given us L value, so I will assume L is very high. So I will write here L not given, assume L to be very high. Okay, so if my L is very high, right, I am assuming continuous conduction. So T, and this is V output. So when the switch is on, when the chopper is on, now I hope I don't need to draw the circuit and all. If the chopper is on, what will happen? Current will flow. If current flows, this chopper will also have its own drop, that is 2 volts. So 2 volts will be dropped, and at the output, what will I get? I will get simply 228 volts. So this will be 228 volts. Then as soon as the chopper is off, what will happen? The voltage will go 0, because the FD will turn on now. Fueling diode will turn on now. Okay. So then this will be off, like from 0.4T. From 0.4T, this will be off till T. Then again, the cycle will follow. Now finding the average of this is pretty simple, right? Not of a much headache. So this will be V average is equals to 228 into T on upon T, simply T on upon T, which is alpha into 228. So alpha is 0.4 into 228. So this, I will just quickly compute this. This will be 228 into 0.4, 91.2. 91.2 volts. Okay. So this value is 91.2 volts. So this is the average output voltage. So first one is done. This was what? Part 1, right? Yeah, first one is done. What about the second one? Second one is the RMS output voltage. RMS output voltage is also simple, just under root alpha into 228. So Vs has become now 228 instead of 230 volts. So this VO RMS will be similar only. This will be under root alpha. Under root is, I will just write this under root alpha into 228. So this will be 0.4 under root into 228. So this will be 144.2 volts. 144.2 volts. So all these are done. Now next is the chopper efficiency in percentage. So if I have to find out the chopper efficiency, obviously I need to find out the output power. It will be PS minus losses. So what are the losses basically? Loss will be what? PS is how much? PS is simply Vs into Is average. So what is Vs into Is average? So Vs into Is, like I have to find out IO average, right? And IO average will be simply Is average, because no, it will be not that, because it is not contained in series. So what is IO average? Okay, so for this, right, I need to find out Vs into Is average minus Vd on into Is average, because these are connected in series basically. So this, right, this will be simply, if I take common Is average, this will be Vs minus Vd on into Is average. So here, what is my IO average? For me to find out IS average, right, I have to find IO average, because what will happen is whenever this chopper will be on, IS will be equals to IO. So I will just draw the waveform of IS. Like all these things should be in your mind instead of drawing the waveform, but still, if you want to visualize, when the chopper is on, then my IS will be IO, because constant current, right? Freewheeling diode is simply turned off. Then once the chopper is turned off, freewheeling diode will conduct and it will totally carry the IO current. So now IS current will be 0 because chopper is off, and chopper current is equals to source current, and this will follow. Okay, so this value will be IO. So what will be IS average from here? So simply it's the same thing only. This is 0.4 T on, right? 0.4 T on. So IS average will be simply IO into alpha, right? So like even though you remember the expression for step down chopper, what is IS average and all those things, still, so like what is IO basically? So IO will be equals to IO average because it is constant, will be equals to IO average, which is equals to VO average by R, because there is no overall drop across the inductor is 0 throughout a cycle. So VO average is how much? VO average is simply 91.2 and R is I think 10. Yeah, R is 10. So this will become 9.12 amperes. So this is the current, right? This is the average output current. Now I have to compute the average supply current. So what will be IS average? Just have to multiply 0.4 with it, right? So 0.4 into 9.12. 9.12 into 0.4. It will be simply 2.5. Oh no, I have made a mistake. 9.12 into 0.4. Not 2.5. It will be 3.65. Okay. So this will be your average supply current. Now I can find out the PO, right? What is PO? PO will be simply 228 because it was VS minus VD on into IS average, that is 3.65. So this will be 228. So this will be equals to 830 on 831.744 watts. So but what do I have to find out? I have to find out PS upon PO. So what is PS? PS is simply VS into IS average, right? So it will be simply VS is 230 into IS average is 3.65. So it will be, okay, something I have made a mistake over here. So 230 into 3.65, 839. So it is actually pretty good. Okay. So your efficiency, right? Efficiency will almost come out to be this PO upon PS into 100%. So PO upon PS 7 into 100, 99. Point 076, 0.08%. Okay, so this will be your efficiency. Now what have they asked? Anything else? The AC voltage ripple in percentage. So what is the ripple? If you remember the ripple factor, it was simply VOAC upon VODC, right? That was the ripple factor, and it is important for the DC side. Okay, if you remember, we used to compute the ripple factor in the DC side, not in the AC side. In AC side, what we used to compute? We used to compute the distortion factor, the displacement factor, all those things we used to compute, right? Because that is like, I want AC there on the AC side and I want DC on the DC side. So how much far away I am from the DC? So that is the concern to me. So those type of things I will compute in the DC side. So here in the DC side, I am computing the ripple factor. Voltage ripple factor. What is the voltage ripple factor? It is simply VOAC upon VODC. So VODC I already know, that is the average value. What is the VOAC? VOAC will be simply what? It will be simply under root VORMS whole square minus VODC whole square. So the remaining part will be simply AC, and I don't want that AC part, right? In case of that AC supply, you remember we used to compute total harmonic distortion, because I want only the fundamental component and everything except that is trash to me, like all the harmonics of the fundamental component, if you remember. Okay, this will be VODC. So obviously this will come out to be VORMS upon VODC whole square and minus 1. So VORMS minus 1. Okay, so what is VORMS? VORMS we have computed, it is 144 point something, right? It was 144.2 and VO average is 91.2. So 144.2, 144 point, what was it? 144.2, 91.2. Everything is to 144.2 divided by 91.2 whole square minus 1 under root. This will be 1.224. Okay, 1.224, and in percentage if I want to compute, this will be 122.47 percentage. Okay, this will be the percentage basically. So this will be my voltage ripple factor. Next, let's read the fifth part. Fifth part is for eliminating fifth harmonic from the output voltage wave of the DC chopper, the ripple factor will be. So if I have to eliminate the fifth harmonic, what changes I have to make? If I want to eliminate the fifth harmonic, basically I have to make, okay, I will write here, to eliminate nth harmonic, what do I have to do? Basically my duty cycle, right? Alpha should be equals to 1 upon n. So I have to eliminate here fifth harmonic, it would be 1 by 5. So basically my alpha will be equals to 0.2. Now they are asking us to compute the voltage ripple factor. So now for this particular alpha, what will be my VO average? VO average will be again 228 into 0.2, right? So this will come out to be, just quickly compute to 0.2. This will come out to be 45.6 volts. Okay, and what will be my VORMS? VORMS will come out to be 0.2 under root into 228. So it will be 0.2 under root into 228. So sorry, yes, 102 volts. Okay, so now I want to compute the voltage ripple factor again. So it will be same only, basically 1 by VORMS divided by VO average whole square minus 1. So here 102 divided by 45.6 whole square minus 1 under root, it will be almost 2. Okay, or I can say 200%, right? Why? Because the duty cycle is very like low, right? So I am moving away from the DC part, but I am removing the fifth harmonic. So if for some reason fifth harmonic is very important, like removal of fifth harmonic is very important, then this type of thing is useful. Else like my voltage, like I have huge number of fields, right? Because this is moving away from the DC. Easy part, right? So basically now we'll study about commutation and few commutation circuits. Before going into fully commutation, right, I want to quickly recap few points which we studied in the first chapter. What was the first chapter? So there I have mentioned about commutation. What was natural or line commutation? Natural or line commutation means it occurs only in AC circuits where the device turns off automatically due to the supply, as the current through the device becomes zero. Okay, for current through the SCR becomes zero due to the presence of the supply, due to the AC nature of the supply. Okay, so it happens naturally. That's why it is known as natural or line commutation. Next is forced commutation. So what is forced commutation? Used in DC circuit where additional circuitry is needed to turn off the device. Here, right, as like the current or the supply doesn't cross the natural zero, then it is not possible to naturally commutate the device. So we have to use some force circuitry which will turn this off. So here, right, as the supply, okay, in DC circuits, right, what do you know? In DC circuits, the supply is fixed. Just hold on. Supply is fixed. Hence, we cannot use natural commutation. We need to use our forced commutation. So forced commutation is used where is supply fixed? Generally in choppers, you right, it is a DC to DC converter. So here I supply is fixed. So I won't be able to turn the device off with the help of the supply. I need some other methodology. And in inverters as well, inverters convert DC to AC. So in that case as well, I need a forced commutation circuit. So additional circuitry is required that can involve complexity and increase the cost of the overall device. Next, circuit turn off time. This concept I hope you remember. The time duration during which the device is reverse biased and remains off is referred to as the circuit turn off time. This is crucial for ensuring the device is properly turned off and ready for the next cycle. Why this circuit turn off time is important? Because after turning off the device, right, after the current becomes zero, as soon as the current becomes zero, the voltage should not be positive. Why should not be positive? Because it needs some time to release the stored charges. Whatever stored charges it had in the junction, right, in the junction it has some stored charges. Due to those stored charges, the current was flowing, but I need to remove them. Why? Because I basically want to completely want to discharge the device, right? Completely want to keep it at off state. So I need to place it in reverse bias state. Okay, I need to place it in reverse bias state. Okay, so next is commutation circuit. Commutation circuit is basically what is it? So this is an external commutation circuit with the help of which I actually turn the device off. So what does the commutation circuit do? It basically brings the anode current less than zero, and as soon as the anode current is less than zero, then what happens? The current is somewhat negative, or it becomes zero instantly, and the voltage through it becomes negative. Okay, voltage through it remains negative for a certain period of time, and then it totally becomes zero. Okay, so here, right, in this case, the main important point is my circuit turn off time will be actually greater than the thyristor turn off time. What is the thyristor turn off time? The time after which all the stored charges are removed. So here, right, TQ is what? TQ, all the stored charges are removed. Okay, all the stored charges are removed. So now as all the stored charges are removed, so I want my TC, right? TC is basically my circuit turn off time, or like this is the thing that I will specify. Okay, TQ is will be specified by the manufacturer of the SCR, like the manufacturer of the SCR will specify me TQ, because they will tell me, look, this is a safe time until which if you like keep turn off the devices in this time period. Okay, you need this much of minimum time period to turn off the device. This is the minimum time required for the device to turn off. Okay, it is the minimum time required for the device to turn off. Okay, minimum time, as all the charges need to be depleted. Okay, as soon as the turning off process starts, from that time instant to the end time instant, this is the minimum time at least I need to give to turn off the device. Minimum time. Time required turn off the SCR. Okay, it is the minimum time required to turn off the SCR. So that is the case, right? That is the thing here. So yeah, now what is TC, right? I will like give this TC. Basically I will give circuit turn off time greater than TQ, so that I give ample time to my device so that it turns off. Okay, let's say in the circuit, right, in the whole circuit, I suppose my TQ, right, TQ is 5 microseconds. Okay, and my circuit turn off time is 4 microseconds. What does that mean? That means I will ensure as soon as I start my turn off process, from 0 to 4 microseconds, I will turn off the device. Okay, total turn off the device. But the manufacturer has said to me that TQ is 5 microseconds. That means the minimum time SCR requires to deplete all the stored charges is 5 microseconds. But I am only giving it 4 microseconds to deplete all the stored charges. So I am doing something wrong here, right? So my TC, right, should always be greater than the TQ, so that I give the SCR ample time to deplete all the stored charges. So basically, why the current is negative? Current is negative to deplete all the stored charges which are present in the SCR. Okay, that's why current is negative. If you remember, I explained this in the chapter 1. Okay, so that's why your TQ should be less than TC. Okay, at least at minimum it can be equals to TC. Okay, I hope you understand these things. So here a few things I have mentioned about the turning off process. So SCR turns off, turn off means transition from the on state to the off state, capable of blocking forward voltage. So if I turn off the device from on to off, what will happen? If the voltage is still positive, right? So what will happen? It will come from the forward conduction to the forward blocking stage. So from the forward conduction to the forward blocking state. Okay, so that is the thing here. The dynamic process of changing from conduction state to forward blocking state is called commutation process. So in case of SCR, we are like going from the conduction to blocking state. So that is actually known as the commutation process. If forward voltage is applied to the SCR, at the moment its anode current falls to 0, the device will not be able to block this forward voltage, as the carriers in the 4 layers are still favorable for conduction. So what I will do, as soon as the current becomes 0, the voltage cannot instantly become positive. If the voltage instantly becomes positive, it will still not be able to block that voltage, because still some stored charges are present in the device. Due to the stored charges, what will happen? Again, conduction will happen. So I have to design my commutation circuit as such that as soon as the anode current goes to 0, the SCR current goes to 0, the voltage should also remain negative for a certain period of time. Then it can go positive, so that all the depleted charges are removed from the junctions. So here, right, due to what? Due to the presence of charges just hold on. In the depletion region. The device will therefore go into conduction immediately, even though gate signal is not applied. Okay, so even though gate signal is not applied, device will again go back to conduction if I instantly apply forward voltage as soon as the anode current is 0. Okay, so to solve this problem, it is essential that the thyristor is reversed biased. Thyristor is reverse biased for a finite period after the anode current has reached 0. So that is the reason, right? So basically here, like the summary is given. So the thyristor turn off process requires the anode current to fall below the holding current. A reverse voltage is applied to thyristor for a sufficient time to enable it for the reverse blocking state. What is the sufficient time? That sufficient time is the TQ, right? Because after TQ, all the charges, right, which was stored will be removed. Okay, so basically this is the process of removing the stored charges. removing okay. So this is the case here. So like few things are also mentioned here, like what was if you remember what was thyristor turnoff time consist of and all those things, right? If you remember, these are not important. Just to quickly recap and read those points, I have already explained this in previous as well, how actually thyristor turns off and all those things, division, you can read those points, right? So one more important point is the circuit turnoff time. Just explain, right? What is circuit turnoff time? Circuit turnoff time is basically the time I will give to the circuit for it to totally turn off, right? What is that? Basically, what does it mean? What does it mean? Like in definition wise, it means it is defined as the time between the instant anode current becomes zero and the instant reverse voltage due to the practical circuit reaches zero. Okay, so basically, the anode current goes to zero, then the voltage across the thyristor is negative, right? As it is reverse bias. So after it becoming negative, then the next instant when it gets to zero. So for the period for which the voltage was negative, okay, and the anode current is zero, that is the period of the period is known as the circuit turn off time. So I will write here in short, the period for which the voltage is negative. The period for which the voltage is negative it basically means that period is known as the circuit turn off time. Okay, so and why do we need the voltage to be negative? Simple, I explained, right? Why do we need the voltage to be negative? To give it enough sufficient time to deplete the stored charges. So that is the reason why my TC must be greater than equals to TQ. TQ, the manufacturer of the ACR will provide me that this much minimum time you need to provide so that the charges are removed. But in the TC, I will compute the TC through different circuits. Okay, I will compute that just in a bit, and there we'll see whether I am giving it enough time or not. And another important thing is that basically safety factor. What is safety factor? Basically, it is TC upon TQ. So what does safety means? I want my device to safely turn off. So I want to give it ample time to deplete the stored charges. So I want to give it, let's say, a safety factor of 2. That means if my circuit turn off, if my thyristor turn off time is 2 microseconds, I will give it 4 microseconds so that it can deplete all the charges. Okay, so what will be 4 microseconds here? That will be the TC. What will be TQ? TQ will be 2 microseconds. And what will be the safety factor? It will be 4 by 2, that is 2. That I explained like previously in the question, that I want to have a safety factor of 2 so that I have twice as much amount of time to deplete the charges, even though some mess up happens. Let's say like for some reason I wasn't able to deplete it in 2 microseconds. We have to have a safety margin or a factor, right? That's why engineers generally choose the safety factor. Next point is thyristor with slow turn off time are called converter grade SCRs. This we already know. I think I have explained, like in phase control rectifier, cycle converters, and AC voltage regulators. And thyristor with fast turn off time are called inverter grade ACS, and these type of thyristors we use in inverters, and like we can use other devices as well, MOSFETs in inverters as well. So in inverters, choppers, and in force commutation converters we use fast turn off time because I need to have faster turn off time, right? I don't want to have slow turn off time because here I have to use force commutation, and that has its own complications. In case of natural commutation, it will be reverse bias anyways for a good period of time because it has natural, like the voltage waveform naturally goes to 0 for a good period of time, right? Sorry, voltage waveform naturally becomes negative for a good period of time. Okay, so these are the things that you need to keep in mind. Now, what are the different thyristor commutation techniques? So I will study about force commutation because natural commutation is already done, and for that we don't need to study anything. It naturally commutates. So in force commutation, we have mainly 5 types of commutation and 5 types of different circuits: class A, class B, class C, class D, class E. And out of this 4 we will study. Okay, class A, class B, class C, class E, and out of this 4, right, only these 3 are important, and these 2 like analysis of this one, class C, will be very, very simple. Just class B and class D will be a bit difficult, and few things you may have to remember. I'll just explain those things. Okay, and if you haven't yet studied AC transient up until now, please go back to the prerequisite part and study AC transient. And if in the prerequisite folder there is no AC transient videos present, right, just let me know in our WhatsApp group or something. Maybe I have forgotten, but most probably I will not, and I will put those prerequisite. Like I have explained this previously as well, that you need to study AC transient, basically the LC oscillators part. That is very important. I will put that there. So class A generally won't come in the examination. Mainly B, C, D will come in the examination, and B and D are bit hectic. C is the most easier one, and E we will study, and E only is mainly for the ESC and like other exams perspective. But for GATE, these four will like these three are main important. Okay, most important. So class C commutation is what? Class C commutation also means load commutation. Why? Because through the load itself we are commutating. How it is happening? So here, what are the different commutating components? Commutating components are the inductor, okay, and the capacitor are used are the commutating components used in the circuit. These components are connected in series with the load. Okay, the circuit is designed to be underdamped. Why underdamped? Because if you have studied control systems, because undamped I cannot, because undamped the response will be something like this without R, and there will be some R in the system. That's why undamped I cannot design, and undamped I don't want. Why do I want underdamped? Because in underdamped, right, my response will be something like this. It will be oscillatory, okay, oscillatory, and I will cross the zero, and as soon as I cross the zero, at that point of time the thyristor will simply turn off. Okay, the thyristor will simply turn off. Okay, so if you remember quickly, if you have studied control systems, you may remember, right? The circuit is designed to be under, okay, the values of L and C are carefully chosen. Just the values of L and C are carefully chosen to achieve the desired commutation characteristics. The values of L and C are carefully chosen to achieve the desired commutation characteristics. So we'll see what do you mean by this. So generally there are two types of figure in class A commutation. One is this, one is this. Now we use this when the values of the resistor are small, we directly connect it with the series of L and C. And if the value of the R, right, is very, very high, then what we do, we connect this C in parallel with the R. The response will be like the shape of the response will be nearly same. Few things will be different. I will explain just when you go bit by bit. So here, right, first of all, when this SCR is on, okay, when this SCR is on, then what is the transfer function I will get of the current in Laplace domain? So if you have studied Laplace domain, well and good, yeah, but obviously you have studied, I hope. So here, right, if the SCR is on, if the device is conducting, my assumption is device is initially conducting, so SCR on, so SCR is on, so what is my IT of S will be simply what, like in Laplace domain, this will be Vs by S, right? This is a step. This will be SL, this will be 1 by CS, and R will be R. So it will be Vs by S divided by SL plus 1 by CS plus R. Okay, so like if you remember a few things, this will become S by, like if I take LC common, S by LC, this will be S, if I take L common, this will be S by, okay, I have to multiply S also, right? If you multiply SL on both sides, this will actually, okay, S will go away, right? Yeah, SS will go away. This will be S square, right? Yeah, S square. Just hold on. So this will be like, this will be Vs by S square L plus 1 by C plus Rs. Now if I take common 1 by C, if I take common L, right, if I take common L, this will be Vs by L divided by S square plus R by L plus 1 by SC. Not 1 by C, 1 by LC. So this format, I hope you remember. Like here, right, the coefficient is this, and like this is the response of a simple. If my system is underdamped, right? If a system is underdamped, then my response will be something like this. If you remember, very good. If you don't remember, just go back to your control loads and see the time response chapter. There, you have studied 4 cases: undamped, underdamped, overdamped, and critical damped. So you just check the result for the underdamped case. Okay, we will not go into that analysis, that will just waste our time here. So if my transfer function is something like this, then my response will be something like this. Okay, Sin omega t upon t. And what will be my zeta? Zeta will be r by 2 c by l, if you remember, under root c by l, and omega n will be 1 by under root LC. Okay, this is the natural frequency. Omega t is a damped frequency. It is omega n into 1 minus zeta square. And here, as my zeta, like I am doing it for the underdamped case, so my zeta will be less than 1, and as my zeta is less than 1, so my r will be less than 2 by under root LC. So here, right, this will be overall less than 1, and from there I can equate. So in this case, how will my response look like? So the response of the current will look like something like this. And if you remember one thing, as soon as I reach 0 here, even though the naturally if this LNC were not present, if this LNC were not present, what was the simple current? Current was simply Vs by R constant. It is a DC current constant. Now as soon as I like keep a LNC here, what will happen? The current will oscillate. The current will oscillate simply. Okay, so even though this is not the best way to do, because like it is changing my output current response, so this is just a way to understand things. So current will oscillate now. Okay, as the current oscillates, what will happen is that around this 0, as the current crosses 0, right, it cannot go negative. Current cannot go negative because my SCR won't allow current in the opposite direction. So as soon as I reach 0, the device will turn off here. Okay, SCR will turn off. SCR turns off. SCR turns off. And if you remember correctly, what is this basically? So this is the envelope, right? This is the envelope, and this is the point at which the sine function becomes 0. So what is this value? This is the point where my sine omega t or omega t equals to pi. Okay, first pi it crosses the 0. So that means t is equals to pi by omega t. So this value will be pi by omega t. So at t equals to pi by omega t, SCR will be off. So obviously the turning off of SCR, like at the instant at which SCR will turn off, depends on basically the omega t, basically the component's LNC, right? Omega t is dependent on the LNC and R obviously. So it is dependent upon that. So this is actually mainly used for series inverters. This is not used in voltage source inverters and all those things. So this is not that useful to us, but still you should know how does the current goes to 0, right? How does the current goes to 0? So here, what is the conduction time of the SCR? Conduction time of the SCR will be from 0 to omega t into t, right? TC basically. Omega t into TC, because after that, what will happen? It will be simply 0 to pi. I can say 0 to pi, right? Because after pi, the SCR will simply turn off because the current cannot go negative, and as soon as the SCR turns off, everything vanishes. Everything just vanishes, right? So this will be omega dt into C equals to pi. So the period for conduction of the SCR will be TC will be pi by omega t. So here, right, in this case, there is no parameter known as circuit turn off time, because that's it, right? As soon as the current goes to 0, the SCR is off forever. So circuit turn off time, you can say it's infinity because it has enough ample time to discharge, right? So those things are here. So basically you can, like, this is the only formula that you can take away, and this is not even a formula. This you already have studied in control systems. So like you can write this in short notes, or you don't need to write. Okay, you know what is omega t is 1 minus omega n whole square, and omega n is 1 by under root LC. Okay, 1 by under root LC. So that is the case. So you can study it for the figure B as well. Figure B, the things will be almost similar. The difference will be here, right? The current, steady state current is not equal to 0. Like there, the steady state current, I don't know what was steady state current, because there, if the capacitor is open circuit and the inductor is short circuit, steady state current is going towards 0. Okay, because you can see from the response itself, right? I'm going towards 0. But here, the steady state current won't be 0, because at steady state, what will happen? The capacitor will be open circuit, inductor will be short circuit. So this will be connected here, and this is open circuit, so all the current will flow through this. So the steady state current will be simply Vs by R. If the R is very high, we use this type of resistors, right? So this is not for small resistors, this is for large resistors. Okay, this is actually for large resistors, not for small. This is a typo. Okay. like you don't need to over analyze this, just how much I am telling, that much you need to know. Okay, so here for large values of resistor we use this. So at steady state, what will be the current? So steady state current will be this, right? I steady state will be Vs by R. Okay, so I steady state will be Vs by R. So here what will happen is that my waveform, right, waveform will not go to zero early. So steady state, it will try to be like this. So steady state current is like this, so it will oscillate around this value. Okay, it will have, like, it is still under damped, so it will have damped oscillations around this value. Okay, so it will start from somewhere here. Okay, this will reduce. Okay, so here what will be the case basically? The case here will be, important point is the zero crossing, right? The zero crossing was supposed to be here. So this was supposed to be zero crossing. This value is what? This value is pi by omega d basically. Okay, this value was supposed to be pi by omega d, but now this has shifted. Zero crossing has been shifted. Zero crossing has been shifted to here. Okay, so I can write here that my zero crossing shifted. So my zero crossing has been shifted. So if my zero crossing has been shifted, it has been delayed. I can say it has been delayed. So my conduction time will be more now basically. That will be just the difference, else nothing will be more. Okay, so my conduction time will increase. Tc will be greater than pi by omega d. Basically my conduction time will increase. Okay, so this is basically what will happen. Then case 1, then figure A, I can say this is the figure B. Okay, so this much analysis you just need to know. So next, this is a very interesting question. This is not under any commutation, but this is an interesting question for which you don't need any knowledge of this commutation and stuff. Just need a knowledge of LC oscillators and simple inductance also, that will work. So here in a DC to DC converter, switch Q is switched at a frequency of 10 kilohertz. So switch frequency F switch, right? Switching frequency is 10 kilohertz and with a duty ratio of 0.6. Alpha is 0.6. Okay, all components of the circuit are ideal. All components of the circuit are ideal and the initial current is in the inductor is 0. All components of the circuit are ideal and the initial current in the inductor is 0. So basically what I can say is IL 0 minus is 0 amperes. Energy stored in the inductor in millijoules. So do keep in mind, right? I have to find energy across the inductor in millijoules. This is very important. At the end of 10 complete switching cycles. So like, what is the switching cycle basically? So let's take a case for one switching cycle. What is happening? So at t equal to 0, this SCR is turned on, right? And this SCR will be turned on till what? So SCR, I will just take one case, SCR on from 0 to T on, or I can say 0.6 capital T. So as soon as the SCR is on, right, how will the circuit look? So if the SCR is on, this voltage is 0, this voltage is 50, and if I apply simple, like initially the voltage across the inductor was 0. It may change, but it is 0. So if I compute the voltage, right, in the KVL, the diode voltage will come out to be negative. So diode will be turned off. So the circuit, right, circuit will look something like this. This will be the inductor, diode will be off, this will be the voltage source. This will be 50 volts and this will be also 50 volts. Okay, and this is inductor, this is L, this is inductor, this is 10 millihenry. Okay, so what I'm observing is a constant voltage source is getting applied across the inductor, and what happens? It linearly increases the current, right? The inductor current linearly increases. Why does it increase linearly? Because if you remember, VL is equals to L dit by dt. So the slope has been fixed of the inductor current. So my L dit dt is simply VL by L. So it is 5 amperes per milliseconds. Okay. So like I can compute, like I can see what is happening for one cycle, and then I can repeat that. So for one cycle it will linearly increase, right? So I'm starting from, if I integrate di, it will be from I equal to 0, initial current was 0, then it will reach to I equals to I equals to t is what? T equals to 0 to t equals to 0.6 t on, and 5 is here, right? So this is still, remember, this is in 5 5 ampere per milliseconds. So my t, right, this capital T also is milliseconds, so that unit will be sorted. So here this will be, I will be equals to not 0.3 t, 3 capital T. What is t actually? T, right? If I want to compute t is 1 by f. So I want to keep everything in milliseconds. So it will be 0.1 milliseconds. It will be 0.1 milliseconds. Okay, so it will be 0.3 0.3 milliseconds, right? It will be 0.3 milliseconds. Not 0.3, sorry, like it is a milliseconds, it will be 0.3 amperes. It reaches to 0.3 amperes. Now at 0.6, right, there is some force commutation circuit which will simply turn this off. Okay, there is some force commutation circuit which will turn this off. Now as soon as a SCR turns off, how will the circuit look like? So circuit will now change. So if the SCR is turned off, right, SCR is turned off, what will I say is that, okay, so SCR has been turned off. So this is off, and this inductor is carrying current of 0.3 amperes. It needs some path, right? It needs some path to flow that current. What will inductor do is, inductor will forcefully change its own voltage to turn this diode on. So this diode will be turned on. Okay, so it will change its own voltage because this path is not allowed. Current flow is not allowed through this path. So obviously it will flow current through this path. Okay, so inductor is actually now de-energizing through this voltage source, 50 voltage source. Now what is my VL? VL has been fixed now. What is my VL? This time my VL is actually, if you remember, it is discharging basically. VL is minus 50. Okay, so basically my current will reduce now. My current will reduce. So again, the same equation, minus 50 is equals to L dit dt. So minus 50 by 10, that is 5 ampere per millisecond. 5 ampere per millisecond equals to 0.3 to I, right? So this is my di basically. So okay, sorry, this is fine only. And this time, right, time will be what? Time will be from 0.6 t to capital T, one time period, because after that time period again this SCR will turn on, and as soon as this SCR turns on, right, the voltage across the inductor gets fixed to 50 volts. So that will simply turn this diode off. And why will it turn off? I will say, okay, that will just simply turn this diode off. So here this will become what? I minus 0.3 is equals to minus 0.4 into 0.1 into 5. So this is basically minus 0.4 into 5, that is minus 2. Minus 0.2. So T is 0.1, right? 0.1 milli. So this will be 0.1 amperes. So I at the end of first cycle, half cycle, it will be 0.1. So it will linearly decrease now. So what will happen basically, if I just draw the current waveform, right? Draw the current waveform IL of t. So it will start from 0, linearly increase towards 0.3. Okay, then what will happen? It will again linearly decrease. The slope will be same, magnitude of slope will be same, but it will only be able to decrease till 0.2. Why? Because even though it is discharging to the same 50 volt source, like the magnitude of the source is same, but the discharging period, right, is lower than the charging period. So overall the current will increase, because this period, right, this period is total 0.6 t. It has more charging period. What is the discharging period? Discharging period is only 0.4 t. So some amount of current will be still be left out at the end of the first cycle. This is actually 0.1, not 0.2, 0.1, sorry. Okay, so this is 0.1. So this same thing will be repeated now. The same thing will be repeated again. It will increase by 0.3 from 0.1. It will go to what? It will go to 0.4. Again, it will reduce by 0.2. So this will be 0.2. So after every cycle, right? After every cycle, how much actually is my current increasing? My current after every cycle is increasing by 0.1 amperes. I can write here, after every cycle. So this is not a stable circuit, obviously, because current is already increasing till infinity, right? That is not a stable circuit. This is not a practical circuit. Theoretically you can do all this, but practically you cannot. So after every cycle, current is increasing till current is increasing by 0.1 amperes. So for 10 cycles, what will be the current, final amount of current? After 10 cycles, the current, right, IL of t at t equals to 10 capital T, it will be simply 10 times 0.1, right, because it is increasing by 0.1 every time. So it will be 1 amperes. And how do you compute the energy across the inductor at any particular instant of time? Because it is asking us to find the energy at the end of 10 complete cycles. So it will be half energy of the inductor at t equals to 10t will be half Li square. So it will be 1 by 2 into 10 milli. So 10 milli is there, 10 milli into I square is 1 square. So this is anyways coming in milli like units, right? So this will be 5 millijoules. Okay, so answer will be 5. Remember, this is in millijoules. Answer will be 5. They have asked us to tell the answer in the correct unit, right? 5 millijoules. So answer will be 5 millijoules. So this was about the class A commutation and just a simple question, like basic question. Okay, so let's now study about the class B commutation. What is class B commutation? So class B commutation is a bit difficult, so you have to listen to me very carefully here. Okay, now listen to me very carefully. So first of all, few assumptions we'll take. First assumption is our current, right, I naught will be constant. Our current will be constant, and before the turning off process has been started, the main thyristor is on. So at t equals to 0, my assumption is at t equals to 0, I will start my turn off process, and before that, right, my thyristor was on. It was totally supplying that fully current IO, okay, whatever current was there. Next, VC0, initial voltage across the capacitor, polarity mentioned here, will be Vs. This is my assumption, okay. And my IC max will be greater than the IO. IC max means was the maximum capacitor current that will be, whatever that will flow will be greater than IO. This also has a purpose. I will explain this later on. Okay, lot of assumptions. Okay, so how will the circuit look t less than 0? Circuit will look something like this. Whole current will pass through this, okay, and here this will naturally commute this auxiliary thyristor. So this auxiliary thyristor won't be turned on, and this diode will also be not turned on. So as the current is 0, what I can say is basically initially the the capacitor will be charged to Vs. I will explain this how is this getting charged to Vs, that I will explain later on. Okay, so now in mode 1, what do? I actually trigger this thyristor. Okay, I actually trigger this thyristor. How do I trigger? Is this thyristor in forward blocking mode? So if I compute the voltage across this thyristor, right? So what is the VTA? VTA if I compute, so VTA will be something like this, right? So it will be something like this. So VTA will be basically minus Vs plus VTA equal to 0. So VTA will be equals to Vs, okay? VTA will be equals to Vs. So my VTA is simply equals to Vs, and it is in the forward blocking mode. So it is just waiting to get triggered. And as soon as this will get triggered, right, will it turn off the thyristor? No, the thyristor will still be on, but we'll see when will the thyristor will be turned off. That also we'll see. Okay. So what will happen at t equals to 0? At t equals to 0, TA is triggered. Okay, as it was in the forward blocking mode, TA is triggered, so it will turn on. And why it will turn on? Which current will flow? This capacitor will discharge through this auxiliary thyristor. This TA is known as the auxiliary thyristor. Have I mentioned this previously? Okay, I haven't. So like TM, right? And TM, and I should mention all this. So here TM actually means the main thyristor, and TA actually means the auxiliary . Okay, T actually means the auxiliary thyristor. So now what I can say, so basically the current expression will be something like this. The current through the thyristor will be current due to this LC oscillator, and if this LC oscillator is initially charged, right, then the current expression will be something like this. Okay, go through the prerequisites, go through the LC oscillator, they will see. Okay, although you can understand here as well that initially inductor current was 0, so it will try to keep it. So here if I put t equal to 0, it will still be 0. So that is why the in the current expression there will be sine and not cosine. Okay, and the voltage will be Vs by under root C by L. Why is this under root C by L? C by L, if you remember, under root L by C is characteristics impedance. So this circuit has characteristics impedance of under root L by C. That's why this is Vs by under root L by C, and C goes above. Okay, so this capacitor is discharging through this, and this circuit will simply form a LC oscillator. That is fine. All that is fine. Okay, so this portion I call this as my maximum capacitor current. This is the current. This is the maximum current that can flow through the capacitor. So what will be the maximum capacitor current? ICM. It will be simply Vs into under root C by L. Now what will be the voltage across the inductor? So I know the current across the inductor. It is in series, right? So I can compute the voltage. Voltage will be L di dt. Okay. So it will be simply L di dt, right? Dt. So here if I compute the differentiation of this will be simply omega n will come at the coefficient of this, and this will be simply Vs by C by L, and L will be multiplied. So this will be simply Vs into under root LC, and I have omega n as well. So omega n in itself is 1 by under root LC, if you remember correctly. Omega n in itself is 1 by under root LC, and here I have cos omega n t. So voltage across the inductor will be Vs cos omega n t. Voltage across the inductor will be Vs cos omega n t. Okay, so here I want to know like when does this auxiliary thyristor actually turn off, because there is a LC oscillator forming with this auxiliary thyristor, and as soon as the current goes to 0, right, this will turn off. Why this will turn off? I will explain that. Okay, I will explain that. So here if I want to know some other thing, basically like IC is this, right? IC is simply this. If you remember, IC is this. Okay, it like Ohm's law, current to Ohm's law, current should always enter in the positive terminal. Okay, if I want to compute this like one thing, if I want to compute the capacitor voltage. Okay, so what will be the capacitor voltage? Basically capacitor voltage will be simply VL minus VC, right? So there are two ways to compute capacitor voltage. VC will be simply minus VL. Why will that be the case? Because VL is computed something like this. If the current is like current flowing is like this, right? So this is plus minus. Just hold on. This will be plus minus. Okay, this will be VL, right? So because actually how is the current flowing? Current is flowing like this, right? That's why current is entering into the positive terminal. So this will be plus minus VL. So actually this will be not be minus, this will be plus. Or how else you can cross verify whether you are correct or not? You know this, right? Basic Ohm's law. VC is VC0 plus integration 1 by c 0 to t ic dt. Okay, so this is one formula, right? So here what will be the thing? Vc0 is what? Vc0 is simply Vs plus 1 by c into ic dt. Ic is what? Ic, right? Ic, if you remember, Ic is actually minus of ITA, right? If we apply simple KCL at this node, because no current is flowing through this, because this path has no current flowing. So the overall throughout this circuit, right, no current is flowing. This IO is still flowing. Okay, turn off process hasn't even started yet. So I can say that IC will be equals to minus ITA. So this will be simply minus Vs under root C by L. You have to listen to me here carefully, right? Under root C by L sine omega n t dt. So this will be t. This will not be omega t. This will be t, right? That is what is in the fundamental equation of capacitance. So this will start from 0 to t. So here, if I just do a few things, right? So this will still be Vs, and this will be simply 1 by c into Vs into under root c by L. And actually what happens is that integration of minus sine omega n t is positive cos omega n t, if you remember correctly. So it will be positive cos omega n t, and do remember I have to put the upper and lower limits as well, 0, and obviously don't forget there will be 1 by omega n as well due to integration simply. So what will this become? So this will be Vs plus, what will happen is this will become under root LC, and this C and this C will cancel. This will be under root LC, and this under root L will come out, and this will simply be Vs by, this will simply be Vs. Okay. Is there anything else here that I'm missing? Minus sign. What is the integration of minus sign? It is simply positive cos, if I remember correctly. Yeah, it will be simply positive cos or something. Okay. Am I making a mistake over here? This is minus IT, fine. Equals to 0. Okay, yeah, this is correct only. So this will come out to be what? Cos omega n t minus 1. Okay, and due to this minus 1, right, this Vs will get cancelled, and I will be left with Vs cos omega n t, and that is what I exactly said here as well, right? Vc will be equals to Vs cos omega n t, which is the VL basically. So this is the Vs, and at like when will the ITA will become 0? So at that point the auxiliary thyristor will turn off. So when ITA becomes 0 amperes, TA turns off. Okay, so basically when does it happen? So 0 is equals to, it is fixed, right? It is when this sine function goes to 0. So it is basically at t equals to, when omega n t is equals to pi, that is t equals to pi by omega n. And what is omega n? It is 1 by under root LC. So it will be pi under root LC. So at pi under root LC, the thyristor, the auxiliary thyristor actually turns off. Okay. And what is the value of the voltage at that point of time? What will be the voltage across the capacitor? Voltage across the capacitor at pi under root LC will be simply equals to minus Vs. Why? Because if I put here, like what is cos pi? It is minus 1. So it will be minus Vs, right? And capacitor doesn't want to change its voltage instantaneously, and inductor doesn't want to change its current instantaneously. So two things will be constant. The current will be constant and the voltage across the capacitor will be constant. So thyristor has turned off. Why? Because the current through it has been 0. So it has been turned off. Okay. So if this path is open, we'll go to mode 3. This was the mode 1 actually, if you understood. And not mode 3, mode 2. In mode 2, this thyristor will be turned off. But inductor wants to still keep some current. What is that current? That current is how much? That current is 0 for now. But after this instant, the current will increase, because this will form a LC oscillator, because now this has minus Vs and this will try to discharge. Okay, so this will form a LC oscillator basically now. Okay, so my inductor current IL is equals to 0 amperes. My ITM is still IO right now, or I can say this will turn on this diode. Why will this diode be turned on? Because if you understand one thing, what is the voltage across the diode? If I just copy this circuit, okay, because as soon as the TA turns off, right? As soon as the TA turns off, what will happen? As soon as the auxiliary thyristor turns off, this is the voltage across the diode, right? Plus minus D. Is it correct? The correct notation here, right? So this will be plus minus VD. So this will be plus minus VD. Minus VD. Okay. So here, right? If I just measure the voltage across the diode, this is minus Vs. So if I just apply a simple KVL here, because the inductor doesn't needs to change its voltage all of a sudden. Okay, it will but still it needs some path. It needs some path to flow its current, because at the next point it was expecting that the current direction will change. Current direction will be something like this, right? At the next point, because initially the current direction is something like this, because ITA was positive, remember, right? And ITA was decreasing. Because why? Because the function was something like this. It was sine, right? And as my omega n is increasing, after pi by 2, after omega n t equals to pi by 2, the current will only decrease. So current was still in the same direction. This is still positive, but this is decreasing. Now as this is decreasing, what will happen? At some point it will go to 0. Fine, this has gone to 0. But inductor still understands that we are in a LC circuit. So at the next point, current has decreased to 0, but at the next point it will try to flow the current in this direction. Okay, so it will try to flow the current in this direction. So what will happen is it will turn this diode on. This diode will be turned on. Okay, so here diode will be turned on at this instant as TA is turned off. So TA is turned off, so diode has to turn on. D has to turn on for continuous flow of current. Fine. So next what will happen is that this diode will be turned on, and this SCR is already on, right? I haven't turned this off yet. I haven't seen a case for which this will turn off, but this will turn off soon. So now what will happen is the initial voltage across the capacitor is minus Vs. Okay, still I will mark down the polarities here. This was my initial, if you remember, this was my initial polarity of the capacitor voltage, and this was my initial polarity of the current. This was the polarity of the capacitor current IC, and this was the polarity for inductor current. Polarity was this, right? It was equals to ITA. This was IL, right? And this is simple ITA, which is 0. So current will now flow in this direction because it is in negative direction. For diode, this is in the forward bias direction. So my initial VC is minus Vs, and my ITM I have already written it. ITM is simply equals to IO plus IC. Okay, because some current is flowing here through here as well. So what is the equation basically? If you just get the equation, right? What was the equation? Equation was this. If remember equation was this. Okay, so equation is this for ITA, but IC, right? IC equation was minus ITA, right? So minus IC. So basically ITM will be equals to what? IO is some constant value, output load current is some constant value, minus Vs, or I write this in short notation, ICM sin omega n t. Okay, minus ICM sin omega n t. So this will be negative now. This will be negative, right? Or okay, one KCL. Okay, I made the KCL wrong because this IC will be incoming here and this ITM also will be incoming. Sorry for that. So this will be actually minus IC. So this will be actually plus, because IC in itself is negative. This will overall become plus. Okay, but do remember this whole thing is negative because this value, right? Omega n t is greater than pi. So omega n t greater than pi means I am in the negative values of sine. So this is for this time period. And what will happen at certain instant, this ITM, right, will go to 0 because this is negative, because this is reducing IO. And when will that instant happen? That instant will happen basically when my IC is minus IO. So I can say here, at IC equals to minus IO, ITM will be 0 amperes and SCR will be turned off. Okay, SCR will be simply turned off. So what else I can say? What else I can say is that so when is this condition basically? So I have to equate this as 0 IO plus ICM sine omega and t. So this is what sine inverse minus of IO by ICM, or I can say pi plus theta, right? Pi plus theta is also correct. So this will be omega and t is equals to pi plus sine inverse IO upon ICM. Okay, I hope you understand this, that here, right, the sine value was coming negative, so that's why I have to do pi plus theta. Okay, I hope you understand this thing. I hope you understand the coordinates. This I think I have explained many times now in mathematics classes as well. So what will be my time t at which this will actually turn off? What will be the time at which this will turn off? So this will turn off basically at pi under root LC. Like I can take this under root LC common, right? Like 1 by omega is under root LC, pi plus sine inverse IO by ICM. So at this instant, actually the SCR has turned off. Now officially my main thyristor has turned off. Okay, so this is the main thyristor, right? Main SCR. So here what will happen? So this, right, basically what I can say is pi plus sine inverse IO by ICM, and yeah, this will be the value. And this, right, this I can write this as a unknown as theta x or something. You can write this. Okay, nothing, no worries, but you can write this. So this is the time at which my SCR will be officially turned off. So what is the voltage now? What is the voltage now? So if you want to know the voltage, can see the voltage. What is the voltage VC now? So VC expression, if you remember, it was simply Vs cos omega and t. Sorry for the interruption, actually my recording got stopped. So I was here, right, the capacitor voltage. What will be the capacitor voltage at that particular point of time? So it will be basically equals to minus Vs cos of sine inverse IO upon Ix, because pi plus theta is minus cos theta, if you remember. So cos pi plus theta is minus cos theta. So it will be minus IO by ICM. Okay, so like let's name this voltage as some negative residual voltage. Okay, VR is equals to this Vs cos theta x. I've named this as theta x, so you can name it like that. Now my assumption was ICM is greater than IO, and it has to be greater than IO, right? Because I cannot take the sine inverse of a value which is greater than 1. Okay, I can at max take it equals to 1. So it has to be like that. That is why the reason was that my assumption has to be applied is because obviously if my ICM is not greater than IO, then I will never be able to make this ITM 0, right? I will never be able to make this ITM 0. That is the reason. So here one more case is that if my ICM is very higher than the IO, right, then basically my time, right, my time at which the thyristor will turn off will be simply equals to T will be equals to pi under root LC itself, because this, right, ICM will be very large. It will be almost sine inverse 0. So this will be almost equals to pi under root LC, and my VC is equals to minus of VR. VC is equals to minus of VR. So what I can say is what will be the residual voltage then? Then my residual voltage will almost be equals to Vc will be almost be equals to minus of Vs. Cos inverse 0 is almost Vs, right? Cos of 0 is almost 1. So here one important point I can say is that what will happen to the SCR? Will it be in the reverse blocking mode or in the forward blocking mode? I will obviously see that voltage. So few key points I've written. IC will flow in the opposite direction of the ITM, so it will reduce the ITM. Okay. Now you might say, sir, who will provide this IO current? Who will provide this? ITM has been turned off. Who will provide? We'll see. So at when my IC is equals to minus IO, at this time instant, the ITM is 0, hence the ITM turns off. Okay, and at what region it is? So this diode is still on. Okay, and current through this inductor is still what? IO. Okay, in some direction, that is in this direction, right? This direction. So after this point, what will happen is this IO current, right? This IO current will remain constant, and there is no path for this current to flow from here or here. So what will be the inductor voltage? In this point, right, the inductor voltage will be simply 0. Okay, why? Because my IL is a constant. Okay, so L dIL by dt will be 0. Hence, this will be simply VL will be simply 0, right? Constant. Okay. So this will be the case here. So here, what I can say? What can I say? I can say that what is the voltage across the thyristor? What is the voltage across the thyristor? VTM will be equal to simply minus VR. Hence, it is in the reverse blocking mode. Reverse blocking mode. As my IO is constant. Okay. So all these things we know. Now we will move on to the mode 3. So this was the mode 2 up until from time equals to pi under root LC to this theta plus omega n. After this, we'll move on to mode 3, and mode 3, this thyristor will also be turned off, and at this after this instant, this will be in the reverse blocking mode. And for what moment it is in the reverse blocking mode, we'll see. So in mode 3, what will happen is that my IO is constant. So my IO is constant. Okay, IO is constant. My VL is 0. What about my VC? VC will now linearly increase, right? Why will VC will linearly increase? Because obviously the supply is the main source, right? The supply is basically providing everything. So VC will linearly increase because the current is constant. So I is constant, C dVc by dt, slope is constant, so it will linearly increase. So what will be VC? VC will be simply equals to like 0. What was the initial voltage? Initial voltage was minus VR. So this was the initial polarity that I assumed for VC. Minus VR plus 1 by C IC, right? And IC is constant. IC is simply IO. So it will be IO into dt from 0 to t. So this will be VC of t. So this will be minus VR IC into t. Okay, so basically, right now, next what will happen? When will this again go to forward? Because my like VC simply equals to VTM right now, and if I put it equals to 0, this will be simply equals to minus VR, right? So when will this go into the forward blocking mode? Okay, so this is greater than t equals to pi under LC. So when will this go into the forward blocking mode? When this when my VC of t is just equals to 0. Okay, when my VC of t is just equals to 0, because this will now rise linearly, right? So at when VC equals to 0, TM goes to forward blocking mode. So when is that instant? So that instant is simply minus VR plus, now this t, right, this t I have assumed to start from here, like this is the 0th instant for me. So this is some dummy variable t dash, okay, just my dummy variable because for simplicity. So what will happen is that minus VR into IO upon C into, I will say T circuit turn off time. Why I will say circuit turn off time? Because at T dash equal to 0, that TM thyristor just turned off, and up until T dash equals to T circuit turn off, the thyristor will be in the reverse blocking mode. So that is basically my circuit duration of for which the thyristor was in the reverse blocking mode. So T circuit turn off time will be simply equals to VR by IO into C. Okay, so this will be T circuit turn off time. How do you remember? So like this, right? This is the unit of ohms and this is C. So R into C is simple time constant. Like that you can remember. So this will be your T circuit turn off time. Okay, duration for which your circuit or your SCR was in the reverse biased. Okay, so this will happen. Now as soon as this tries to increase more, right? As soon as this tries to increase more, what will happen? Basically, after this, right, my VC will increase. So what is basically my VO? VO is simply VS minus VC, and after this my VC okay, yeah, VS minus VC. Okay, fine. Okay, so now this is fine when my VC is 0. So at some time instant, my VS will reach my VC will reach VS as well. So what is the time instant? So at T equals to, like, let me write this, VC is equals to plus VS. VS is equals to minus VR plus IO by C into T. Okay, actually this T, right, this T dash is something else. I will just mention it later on. So T dash equals to VS plus VR divided by IO. Okay, into C so this will be simply one important point you have to note is that at this point, right, my VC will be just at VS. Now as soon as my VC is greater than VS, what will happen? My VO will be negative, and VO can never be negative because I have a freewheeling diode. So FD will be turned on at this instant, right? FD will be simply turned on. So this is the mode 3 at which the FD will be turned on. So what is the actual time basically? So actual time, right, is basically equals to pi under root under root LC will be at the top. Okay, or I can write this as like this, the pi under root LC plus when the SCR was actually turned off. Okay, I have to write it like this. This is very difficult for me to write. So pi under root LC plus sine inverse. You don't have to remember this formulas. You have to know how to derive. How am I deriving? Okay, because remember this much is really difficult, right? Sine inverse IO upon ICM plus this T dash, right? This is the duration for which the capacitor will linearly charge, and after this the freewheeling diode will turn on, and SCR and the capacitor will not charge anymore. What is the final voltage of the capacitor? After that it will not charge. It is plus VS, because as soon as it reaches above VS, right, as soon as it tries to go above VS, the freewheeling diode will turn on. So it will remain at VS as like the initial condition. I assume, right, the initial capacitor voltage was VS. Exactly that has happened here. So graph waveforms will be something like this. So IO current will be always constant in both all the modes, mode 1, mode 2, mode 3. In mode 1, what will happen? Thyristor main current is still constant, that is IO. So this value is IO. Now what is IC? IC still it will work as a LC oscillator, because at this T equals to 0 instant I have triggered my auxiliary thyristor. Okay. Now as soon as I have triggered my auxiliary thyristor, what will happen? This will work like a simple sinusoid, and then as soon as I reach this point, right, my IC tries to go negative. So thyristor will not allow negative current because all the current was flowing through thyristor because that diode was off. So now the inductor will turn on the diode, and the SCR and the auxiliary thyristor will be turned off. So at this point, TA is off. Okay, then what will happen? Then what about the capacitor voltage? Capacitor voltage is simply the differentiation of the capacitor current, right? So it will still work as AC oscillator, and at this point, right, at this point it will be simply minus VR. Okay, actually this was not the point. When it is 0, when this is 0, this will be maximum actually. Okay, at that point it will be minus Vs, I think. Yeah, it will be minus Vs at that point when the auxiliary thyristor will be turned off. After that, what will happen is that capacitor current will still flow and it will oppose the main thyristor current, okay, as the diode has turned on. So what will happen? It will reduce the main thyristor current, and hence from this point the thyristor current, main thyristor current is reducing from IO to 0. As soon as it reaches 0, the main thyristor has turned off. And what is the voltage at this point? The voltage at this point will be some residual voltage minus VR across the capacitor. Then what will happen? The diode is still on. Okay, I'll just bring the circuit diagram. That will be the best. What is the circuit diagram? So here the diode is still on. So what will happen? The capacitor will linearly charge because a constant voltage source is getting applied and a constant current is also flowing. So inductor voltage will be 0, but the capacitor will linearly increase its voltage, right? So it will increase its voltage linearly, but the instant at which the capacitor voltage becomes Vs, right? So from minus VR it goes to Vs. The instant at this, right? This is basically the this is actually not TC. Circuit turn off time will be something like this. This is not TC. Circuit turn off time will be here, right? When this is equals to 0. So TC will be something like this. Circuit turn off time, right? Here. So at this point my capacitor voltage is going to negative, and hence the voltage across the capacitor voltage is going to 0, hence the voltage across the thyristor will also be almost 0. After that it will try to go to positive, okay, and it will be positive after that. So it will be in the forward blocking mode. So this is the circuit turn off time basically, and this is the duration for which the capacitor was linearly charging, and then after this instant the FD will be on. So from here, right, after mode 3 the freewheeling diode will be turned on. FD will be turned on, okay, from here on this region. So all this is happening. After this, again I am reaching back to my same state, that is plus Vs, because I proved it, because it will stay at Vs and it will remain like that because everything will be open circuit. Only the freewheeling diode will be turned on, and then again the thyristor again is in the forward blocking mode, and as soon as I trigger this thyristor again, VO will be simply Vs. Okay, so again the same cycle will follow. I hope you understood. So few parameters, few key results you have to remember is that this result. What is the peak value across the main thyristor? If you remember, the peak value across the main thyristor is always equals to IO. It never goes above it because the capacitor actually capacitor current flows in the opposite direction. So it tries to reduce the current. So all these things we need to know for buying a particular part, right? What are the peak values, maximum values? So peak value across the thyristor is, main thyristor is IO. Peak value across the auxiliary thyristor. What is the peak value across the auxiliary thyristor? So if you remember, auxiliary thyristor turns off when the current goes to 0, okay, across the capacitor. Before that, I reach the peak value of the capacitor current, that is ICM. What is ICM? ICM is Vs into under root C by L. So this value Vs into under root C by L, if you remember this correctly. So all this will depend, right? So you have to buy a auxiliary thyristor which can support this much of current. Now main thyristor turns off at this instant, right? At this instant main thyristor actually turns off. So if my ICM is very large than this, then my turn off, the instant at which the main thyristor turns off is simply pi under root LC, right? And what is the circuit turn off time? Circuit turn off time is basically when this is not TC, yeah, this is TC. Basically when my voltage goes to 0, right? From minus where it goes to 0. So this will be the circuit turn off time as explained here as well. I've explained here as well, right? C circuit turn off time. So this will be simply, I can write this TC also you can write, or you can write it like this, that this will be T circuit off. Okay, this is the time I am providing for the circuit to totally be off. Okay, so this should be greater than the turn off time of the SCR. SCR should deplete all the charges inside it before this, right? Else it may damage the SCR. What is VR? VR is simply this, right? V is cos sin inverse IO upon ICP. This you already know. Okay, then like this, how to derive this also you know, right? So T auxiliary will be like for how much period the auxiliary thyristor is conducting. It is simply for the first half, right? This pi period. Okay, after that this is turning off because simply the capacitor current is going to negative. So all these things you should know, and this type of commutation is actually used in choppers. Okay, although not many questions has come from this, but you should know all this, right? You should know all this. Okay, now if I just modify the circuit a bit, okay, things will change a bit. If I modify the circuit a bit, if I connect a diode across it, what will happen? Basically, if the diode D2 is turned on, right, it will automatically turn on this TM and TA, because in antiparallel diodes can never turn on together. Okay, it will naturally commutate. Okay, so if TA auxiliary thyristor or TM turns on, if TA or TM turns on, then D2 will be off. If D2 is on, it will automatically turn off TM and TA will be off. Okay, T and TM will be off. So in this case, basically what will be same is that mode 1 and mode 2 will be same, because either TM was always on in mode 1 and 2. So if mode 1 and 2 in the previous case, mode 1 and 2 of previous case, TM was on. So if TM was on, basically these modes will be same. That analysis will be same. You can just repeat and go over and watch again. That analysis will be same. But at mode 3, at T equals to what? T equals to that particular theta, right? If you remember that value, T equals to under root LC pi plus sin inverse IO upon ICM. At this point, my TA actually turns off. And as soon as my TA turns off, anyways auxiliary, not TA, sorry, TM actually turns off. As soon as my TM turns off, both TA and TF are off. So obviously my D2 will be on now instead of any other thing, right? D2 will be on. D2 will be on. So if my D2 is on, how will the circuit behave? That will observe. Okay. So we'll directly jump into the mode 3 as my D2 is on. So what was the voltage across the initial voltage across the capacitor? Initial voltage across the capacitor will be simply equals to minus VR, if you remember. It will be simply equals to minus VR, right? So from this instant, right, it will be simply equals to minus VR. So VC at this particular instant, T equals to some value Tx is minus VR. If you remember, it was some residual voltage, right? What was the IC, right? IC will be something like this. IC should incoming, right? This was the initial assumption. Yeah, IC should incoming here. It should be incoming. So basically, what will be my IO now? So my IO, right? IO equals to incoming minus outgoing, ID2. Okay, fine. And this will still work like an oscillator. And if you remember, what was my IC? IC was actually equals to minus ITA, which was equals to minus ICM sine omega. If you remember it from mode 1. Minus ICM sine omega and T. Okay, it will still work like an oscillator. Now, at the instant when this current goes to 0, when this ID2 goes to 0, then only this diode will be turned off. So what is the ID2 actually? ID2 is basically IC minus IO. Okay. So here, as soon as my IC reaches IO, ID2 will be turned off, right? ID2 will be turned off. So as soon as my IC at some value reaches IO, right? IC equals to IO, D2 will turn off. And what happens is my IC reaches IO, that I will see. Okay, so let me take some time. Okay, let me take some time at T equals to Ty, this IC reaches IO. And what is basically Ty? If you remember, right, it should be something plus theta, right? Plus theta, because it is greater than pi. We are at the region where I am pi plus. I am greater than pi. Okay, the period is greater than pi. So if you just compute the values, if you just put the value over here in ICM, right? If you put this value 2 pi minus sine inverse omega t, so 2 pi minus theta will be minus of sine theta. So sine theta will be this, that is sine of IO by ICM. So this will be simply IO by ICM, and this will be ICM, right? If you just compute this value, Ty will come out to be this. Okay, so this is the instant at which the D2 diode has been turned off. Okay, instant D2 is off at this Ty. So simple computation, sine trigonometric angle computations I am doing, nothing else. Okay, this you can do. This much I am leaving it to you. D2 will be off. What is the voltage at this point? What is the voltage? What is the voltage across the capacitor? VC at the instant VC of t at Ty. What was the expression for VC of t? Expression for VC of t, if you remember, it was simply Vs cos of omega and t. So if I put here, right, this will be what? This will be simply Vs cos of, like, omega n is cancelling out, and this will be what? 2 pi minus some theta value. So this will be 2 pi minus theta. And what is cos 2 pi minus theta? Cos 2 pi minus theta is simply Vs cos theta. Okay, and if you remember, minus of Vs cos theta was Vr. Just go back to the pages. Like, what is theta? Theta is this value. Okay, so minus of Vs cos theta was minus Vr. So this will be simply plus Vr. Okay, just what I have done, I have changed the voltage. Okay, that's it. That's all I have done. Nothing else. What it will do? It will basically change the circuit turn off time. Right? It will change the circuit turn off time. Why it will change the circuit turn off time? Because from, okay, will it really change the circuit turn off time? Because here, right, it moves from, because this voltage is, okay, this voltage is still 0. This voltage is still 0. Okay, it remains still 0. So basically what happens is I keep the voltage across the thyristor Tm 0. Even though it is 0, that also will be assumed as the circuit turn off time. As soon as the D2 diode turns off, what will happen? The voltage across the thyristor will be some positive value, right? It will block forward voltage, because again it will linearly charge again. Okay, VL will be 0. So my assumption will be circuit turn off time will change. What will be circuit turn off time? Circuit turn off time TC will be Ty minus Tx, because my assumption is my voltage across the thyristor VTM is less than or equal to 0. Even if it is equal to 0, that also comes under the circuit turn off time. So this will be 1 by omega n 2 pi minus theta minus pi plus theta. Basically what am I doing? Basically Ty is 2 pi minus theta in terms of theta, and it is pi plus theta. This much computation I hope you can do. What is Tx? Tx is the point at which the main thyristor was actually turned off. Okay, at this point, if you remember, at this point. Okay, and theta is this. Okay, this much you can do. This much I am giving it to you. Okay, this much computation you can do. Okay, I trust you. So this will be under LC, and this will be like theta will get cancelled. This will become 2 theta, and this will be 2 pi minus pi. This will be pi minus 2 theta, right? So this will be the value pi minus 2 sin inverse theta. So this will, like, the circuit turn off time will be changed. And don't worry, this won't be asked. Don't worry. Okay, don't need to remember all this. Just try to understand how to derive. Okay, that's it, right? You can't remember all this. Now, after this instant, what will happen is that the diode will be turned off, and the what will be the voltage? The voltage across the capacitor will be plus Vr, and if the voltage across the capacitor is plus Vr, and this is plus Vs, right? So if I just compute plus minus Vr minus Vs plus Vr equals 0. So still the freewheeling diode will be turned off, because what will be the output voltage now? Output voltage will be Vs minus Vc, right? As soon as this diode D2 turns off, right? So output voltage will be Vs minus Vc. Previously, what was the output voltage? Output voltage was simply Vs. Okay, so this will be Vs minus Vr, and my assumption is obviously Vr is less than. Obviously, Vr has to be less than Vs. So still, right, FD will not turn on. Okay, FD will not turn on, so FD will be off here. This is wrong actually. FD will not turn on. What is wrong? So FD will be still off as the voltage, as the output voltage, right? Output voltage is simply Vs minus Vr, which is still greater than 0. That is fine. If voltage greater than 0 is still plausible. So then again, the same circuit I come back to again. Again, when the capacitor voltage will go at Vs, it will go at Vs, then the freewheeling diode will turn on. So what will be the equation now? The equation of current, IC, no, not current, current is fixed, right? IC is fixed because constant current is flowing. So my VL will be simply equals to 0 because constant current is flowing. So my Vc of t will be, what was the initial voltage? Initial voltage, if you remember, it was VR plus VR this time, plus, like you can compute the computations, it will only increase t dash. I will just assume this as t dash, else confusion will be created. So at t dash equals to some time t z, let's say, my Vc of t will be simply equals to Vs, and as soon as it becomes Vs, my Vo becomes 0 and my freewheeling diode turns off, because after this instant the voltage will try to go negative and freewheeling diode will not allow it. So FD will be turned on. So as my FD is turned on, again I will follow the same mode. Okay, so basically I will just repeat till mode, okay, this is mode 2 and this will be actually mode 4, 3 will change here, this, right, this will be mode 4 and this duration will be simply mode 4. Okay, so this duration will be mode 4. After this, obviously my FD turns on. Okay, I know this is a bit hectic. Please do rewatch it, recap it again, because like I've just tried to keep few things within yourself, and don't worry, this much won't be asked. Still, I'm teaching you all this. Okay, so this is Tx. Okay, and this was Ty. At this instant, my voltage across the resistor became positive again, and this is Tz. At this instant, my SCR, the capacitor got open circuit again, and the capacitor voltage will again come back to Vs. Same procedure. Just this has been modified. Okay, why this has been modified? Just to have a variable with us, that is the circuit turn off time. We can control the circuit turn off time as well. Okay, just to have that. These are all modifications. That's it. Nothing much to worry about. Okay, so your TC, right? TC won't be this. This TC will be basically Tx minus Ty. Okay, TC will be simply Tx minus Ty. This will be circuit turn-on time. Now, here I have one question. This question I will give you homework, and in the next lecture, I will solve this question and complete the other commutations, that is class C and class D. Those are the most important ones. This is also important. If you couldn't understand, please do rewatch it, because I understand this is a tough lecture. And hi everyone, and welcome back to PrepFusion. So today we'll study the final lecture of choppers. So in this lecture we'll study more commutation circuits, that is the class C and class D, and we'll do questions on commutation circuits. Before that, I gave you a homework on the previous lecture. That was this question, right? This question has a circuit given, and this followed a, like if you observe this is a class B commutation circuit, right? So generally very few questions come from class B, but still, so few things it's good to remember if you are able to remember, right? So for commutation circuits, it's good to remember, just draw the circuit diagram, and beside that write down the formulas and try to derive it by yourself. So practice deriving those. So if you're good at deriving, right, in the examination hall, even if you forget, you will be able to derive those formulas. So here circuit is given, DC chopper is given, the main thyristor is THM and the auxiliary thyristor is TH-aux. The load current is constant at 10 amperes. So load current is constant at 10 amperes. THM is on and auxiliary thyristor is triggered at t equals to 0. So auxiliary thyristor is main thyristor is turned off between what? So when will the main thyristor turn off basically? So the main thyristor, right, it will turn off when the current through the this auxiliary thyristor, right, at first at pi under root LC, what will happen? So this has been charged to Vs, although they haven't mentioned it. This has initial charge of Vs, and what will happen? Some current will flow through this auxiliary thyristor, right? Then some current flows through the auxiliary thyristor. Then this current reduces, right? Because initially the current will be 0, then this will peak out, then this will reduce. So when will this go to 0? This will go to 0 at pi under root LC. So Iox will be equal to 0 at pi under root LC. Then as soon as it goes to 0, right? As soon as it goes to 0, this auxiliary thyristor will be turned off. Then all of the current will flow through this diode and the main thyristor. This diode and the main thyristor. Okay. So what will happen is that then next what I can say is that at pi under root LC this turns off, and then this diode turns on, right? And until when this will conduct? This will conduct until this current, right? This current is IC, like here the current is IO plus IM plus IC. So when IC actually reaches to IO, that is 10 amperes, this will turn off, right? So when will that happen? That will happen again, it will follow sinusoidally, right? It will follow sinusoidally. Basically my IC is equals to what? IC is equals to ICM sine omega n t. So when this reaches, basically initially the current direction was like this, that's why ICM this should be negative, actually should be negative, because thyristor current was like this, right? And then what will happen? Current direction will change. Current direction will be something like this. Okay, so at what time this will reach to basically IO, right? When this will reach to IO, then the main thyristor will be off. Okay, then the main thyristor will be off. So IC will be equals to minus IO. Then what I can say is not minus IO, plus IO, right? Because okay, my direction of current was something like this, but initially current was flowing like this, but now it will be plus IO, sorry. So when will this happen? This will happen at pi under root LC plus, if you remember it correctly, it will be sine inverse, if I take the LC common, right? IO upon ICM. What is ICM? ICM, if you remember, it was Vs, like you can remember it like this, Vs upon the impedance, characteristics impedance, it is C by L. So Vs is 230 and C by L is what? C by L is C is how much? C is 10 micro and this is 25.28 micro, right? So what will this value become? I will just quickly compute it. This value will be simply 25.28 under root into 230. This value will be 144 something like that. So this is very high, right? So this will be almost 0 if you see, because our IO is what? IO is 10 amperes. So ICM is like 10 times it, right? More than 10 times it. Okay, almost 15 times it. Okay, ICM is 15 times it. So this is very, very large. So this will almost be equal to 0. Okay, so basically our pi under root LC will be what? L is 10 into 25.28 under root into pi. It will almost be equals to 50. Okay, so this value will almost come out to be. So our time from which our thyristor Tm will be off, right? This Tx will be basically equals to 50 microseconds. And after this, what will happen? Main thyristor will turn off. It will not go into forward blocking mode. It will go into forward blocking mode after some time. That is when the voltage will shift from minus VR to plus Vs. Then it will go to forward. No, not minus VR to 0. Then it will go to that forward blocking zone. Okay. So yeah, they have only asked us the THM is turned off between. So it is not turned off between the 0 to 25, not possible, right? Not between 25 to 50, because after 50 the thyristor is turning off. Yes, this is correct. And this is telling us the thyristor will turn off after 75. No, this is turning off after 50. So here option C will be correct. Although the question totally is not complete, but still, like from the option itself we can understand that the thyristor will turn off after 50 microseconds. So this will be the answer to this question. Let's start with this new commutation circuit, that is complementary commutation. So this is class T commutation, also known as complementary. Why is this called complementary? Simple reason is, if this T1 is turned on, right, this T2 will be automatically turned off. So that's why they are complementary of each other. One turns on, other one will turn off. So here, what will be my initial, like assumptions are, initial capacitor voltage again is plus Vs. The notation is like this. Then for t less than 0, you can assume anyone to be on, but I will not anyone here, right? Specifically one device has to turn on. So T2 will be on. For t less than 0, T2 will be on and T1 will be off. Okay. So if T1 is if my T2 is on, right? So what will I say? If my T2 is on initially, what is the voltage across this resistor? So voltage across this resistor, this is plus plus Vc and 0. So this will be some forward voltage, right? As soon as I trigger it, this should turn off. So basically, if I copy this circuit, okay, and I just draw the condition for t less than 0. Okay, so initially I assume that my T2 is on. So if my T2 is on, what will I say? I will say this is my plus minus VT1. So my VT1 equals to simply Vs, right? Because initially the capacitor voltage was simply equals to Vs. So it is in the forward blocking mode. If I trigger T1, it will turn on, and this is the same point told that at a time only one thyristor can be turned on. Hence, it is called a complementary commutation. So let's assume that at t equals to 0, I trigger my thyristor T1. At t equals to 0, T1 is triggered. So if T1 is triggered, what will happen? So if T1 is triggered, right, some current will flow. Okay, what will be that current? Will that current be Vs by R? No. Like through this resistor, what is the current? Through this resistor, what is the current? Through this resistor, the current is what? What is the voltage across this resistor? The voltage across this resistor is simply Vs. So current will be what? Vs by R. Current is Vs by R. Okay. Now what about this? Now this, right, actually this forms a RC circuit. If you understood this very well, this forms a RC circuit because this potential, like this is Vs, like this overall point, these 2 points are what? AB, and across AB I have a resistor and a capacitor connected, right? Across AB I have a resistor and a capacitor connected. Now what will happen? As soon as this T1 will be turned on, right, this T2 will be off. Why will this T2 will be off? If I measure the voltage now, this is my VT2, right? So I will apply simple KVL again. So what will be the KVL give me? So this will be plus Vc plus VT2 equals to 0. So VT2 equals to minus Vs. Now again, what is this? This is basically negative voltage. So my thyristor will go into reverse blocking mode. So as soon as this T1 is triggered, right, T2 will instantly turn off. T2 off. So as my T2 is off, right, what happens is that this current is anyways Vs by R, but what happens is this R and C are in series because here current here is 0. Current through here is 0. So R and C are in series. So if R and C are in series, what does it mean? It becomes a simple RC circuit with a constant voltage source. So here, if I just draw the circuit quickly, what will happen is that this current, right, let me name this current as I1. Okay, and this current as I2. Okay, can you tell me what will be the steady state value of I2? The steady state value of the I2 will be 0 simply. Okay, the steady state value of the I2 will be 0. And what is the initial current? Initial current, if you observe, this is plus Vs but in opposite polarity, right? So overall the potential difference across the resistor is 2 Vs. So it is 2 Vs by R. So initial current is 2 Vs by R. Okay, so basically my I1 current, like I'm doing this fast because I hope you understand transient very well. So I1 will be Vs by R, I2 will be 2 Vs by R, initial current, and obviously this will decay down to 0. Steady state capacitor will be open circuit, simple RC circuit. So this will decay down to 0 minus T upon tau, and do keep in mind that tau is what? Tau is RC. Okay, tau is RC here. So what about the voltage now? So if I want to compute the voltage, right? If I want to compute the voltage across the capacitor, so capacitor voltage will go from minus Vs to plus Vs, because at steady state this will be open circuit, this R will be open, no current will flow, hence this whole voltage will come across the capacitor itself. So at steady state what will happen is that, like my Vc of t will be simply, it will start from minus Vs. So if I want to write the equation, right? If I want to write the simple equation, that Vc infinity is what? Vs plus Vc0, that is minus Vs, plus minus Vc infinity, that is Vs, into e raised to power minus t upon tau. So this will come out to, if I take common Vs, right, this will come out to be 1 minus 2 e raised to power minus t upon tau. Okay, and tau is RC, that we already know. Now one thing you have to understand is that when will like this voltage, right, go less than because what you have to understand is that this T2 has been turned off, right? And what is this T2? T2 is actually equals to minus Vc, basically my Vt2, right, is equals to minus Vc. So initially it was in reverse blocking mode because my Vc was simply Vs, right? Vc was simply Vs. Now as soon as my Vc will touch 0, right, at the point where my Vc will touch 0, the thyristor T2, the voltage across the thyristor will be something positive, because what is happening, the voltage is increasing. Am I correct? This is 0. Okay. The voltage is going from plus Vs to minus Vs. Just hold on. Yeah, because initial polarity was something like this. Initial polarity was something like this. Initial voltage was plus Vs. Okay, I'm doing something wrong here. Sorry for that. I'm doing something terribly wrong here. Just hold on a second. Because initial voltage was plus Vs, right? Yeah, initial voltage was plus Vs, then final voltage will be minus. Sorry. This will be negative actually. Okay, this will be, initial voltage will be plus Vs, final will be minus Vs. This will be plus. Okay, sorry for that. So this, right, this will be actually minus 1 plus. So at t equals to 0, what is the voltage across the capacitor? At t equals to 0, voltage across the capacitor is Vs. At t equals to infinity, what is the voltage across the capacitor? It is minus Vs. So what is happening? The voltage is reducing. Okay. So as soon, let's take an example, right? As soon as it reaches, let's say minus 1 volts. If it reaches minus 1 volts, Vt2 will be something positive because it is negative of Vc. Okay. So it will be plus 1 volts. So I want to find out the circuit turn off time. So for me to find out the circuit turn off time, I have to find out the period for which the SCR has been reverse blocking mode. So when this Vc is positive, then this voltage will always be negative. So as soon as the Vc touches 0, the polarity, like the blocking voltage across the SCR will change from reverse blocking to forward blocking. So at t equals to Tc, basically circuit turn off time, Vc will be 0, and at that point T2 will be in the forward blocking mode because I want to compute the circuit turn off time. So that is very important parameter, as explained previously as well. So I will just equate this equals to 0. If I equate this equals to 0, basically my e raised to power minus t upon tau equals to 1 by 2, or my, what I can write is tau equals to, not tau, t equals to tau L into, okay, t will be simply equals to tau L into, this is the circuit turn off time. This is the duration for which my SCR will be reverse blocking mode, and like all the charges that are present inside the SCR will be depleted. Okay, now let's take another condition, is that when this is the case 2, okay, case 2. Now at steady state, like let's take the steady state, because let's say after very high amount of time, right, what will happen, this thyristor will be in the forward blocking mode, and this capacitor will get still charged to Vs. Okay, and as soon as this gets charged to Vs, what will happen is that my SCR, right, is in the forward blocking zone. So if my SCR is forward blocking zone, I can again trigger my T2 SCR this time, not T1. So I will choose another time, that is T dash, right. So this will be almost tau ln2. Okay, so I am taking another time very much after this, right, when this capacitor gets charged to minus Vs. Okay, when this capacitor gets charged to minus Vs, I will assume new time, that is T dash, and at T dash equals to 0, T2 is triggered this time. T2 triggered. Okay, T2 is triggered. So T2 is triggered. So what I can say? I can say again the same analysis, right? This time the thing will be this T1 will turn off. Why will T1 turn off? Because if I want to compute the voltage, right, as T2 is on, T1 will be simply turned off because the voltage across the thyristor T1 will be something negative. Because what is my VT1? VT1 is equals to VC plus VC, but VC itself is negative. VC itself is negative. That's why this is minus Vs, and hence it goes into the reverse blocking mode. That's why this is in the minus Vs, and it goes into the reverse blocking mode. So it goes into the reverse blocking mode. So again, you can say the same thing, that same analysis you do. Okay, you do the same analysis, that my IT2 will be what? IT2 will be this Vs by R plus, at steady state this current will be 0, and initially what was the current? Initially the current will be like this is on, right? So the current will be something like this. This is actually negative. So this will be 2 Vs by R again. So this will be 2 Vs by R e raised to power minus t upon tau. Okay. So again, when will your thyristor T1 go into the reverse blocking mode? When this voltage, right, becomes 0. Okay. Then again this thyristor will go to from reverse blocking to forward blocking mode. So what will happen? VT1 will be 0 when Vc is equals to 0. That means basically this TC1, right, circuit turn off time of the first thyristor is same. Although I will tell you where is the difference. I will tell you that as well, like if I want to make them different. But here this will be same because R and C values are same. Okay, tau is R by C, RC. Tau is RC. Okay, tau is RC. So these are the waveforms basically. What is happening is that the thyristor IT1 current, right, it will settle to Vs by R1. Okay, for this time period T, it will settle to Vs by R1 because this capacitor will be open circuit for when this thyristor T1 is triggered, right? This capacitor will be open circuit. I have the circuit drawn there as well. Okay, yeah, this capacitor will be open circuit, right? So all of the current will flow through this. This will be open circuit, and hence all of this current will flow only. This current won't flow. Okay. Next, what is happening? Next, if I want to talk about IT2, so somewhere in this region, again the thyristor T2 will be in forward blocking mode. Again, if I trigger this, then again the current will increase to 2 Vs by R due to this capacitor, and the flow of current will be something like this and this. So now it is flowing from R1 directly and then from R to C T2, right? So like this. So I have changed the resistors, and if I change the resistors, right, so the time at which the thyristors have for like time for which the circuit turn off time will change according to the resistance values. So when this T1 is on, right, the circuit turn off time depends on this path, right, on this path. So basically it depends on R1. So tau then becomes R1 C1. So that's why I have chosen the R1 and R2 like that. So that it matches with T1. Okay, that is the reason. Now when this T2 is turned on, then circuit turn off time is dependent on this path, right, and this is through R2 and C. So again, time constant R2 and C. It becomes R2 and C that time. This path is constant current. Okay, when this T2 is on. So I hope you understand that point. And your VC, right, it will go from minus Vs. So it will go from plus Vs to minus Vs when the T1 will be triggered, and when the T2 will again be triggered, it will go from minus Vs to plus Vs, and like this it will go. So once this will turn on, once this will turn on. So this is the complementary commutation basically. So these questions are easy only. They are not used in choppers. Their application are in current source inverters and parallel inverters. Okay, so these are few important results that you should know. What is the peak value across the thyristor? The peak value of the current across the thyristor will be at t equals to 0 instant, right? So when at t equals 0 instant, this current is constant, right? This current is constant anyways, V by R2. Okay, if they're same, if they're different, I'll just check once. If IT1 peak, right? IT1 peak will be Vs by R2 and 2 Vs by R1. Okay, this is wrong actually. This will be Vs by R2 and 2 Vs by R1. Vs by R2 and 2 Vs by R1. and TC1 again, it depends on this path, right? This path. So obviously it will, time constant will be R1C, and for TC2 it depends on this path, so time constant will be R2C. So like this you can understand. Now one thing is important. So if they have, if these values are different, right? TC1 and TC2 are different, and you have to have at least, like, you have to have one circuit turnout time, right? One circuit turnout time. Which circuit turnout time you will choose, or which circuit turnout time you will mention. So what is your TC? TC is basically safety factor into TQ, right? TC is basically safety factor into TQ. Now here what is happening, let's say if two devices has different turn off times, right? SCR turn off times. TQ is the SCR turn off time, the minimum time after which all the charges will be depleted. So I will find out TC1. TC1 will be what? TC1 will be simply R1CLN2. Okay, TC1 will be R1CLN2, or I can write it like this only. Safety factor, like safety factor is constant, is equals to TQ1, and TC2 equals to safety factor into TQ2. Now from this, right, you get two expressions. Okay, which one should you choose? Which one should you choose? So let's say, let's take a few numbers, right? Let's take a few numbers. This TQ is 2 micro, okay, 2 microseconds, and safety factor is 2. And this TQ1 is 1 microseconds, and this safety factor is 2. Same safety factor, right? So here, according to these expressions, for the first thyristor, I can have a circuit turn off time of 4 microseconds. For the second thyristor, I can have a circuit turn off time of 2 microseconds. Now, which one will you choose? Will you choose this TC2 or TC1? Which one will you choose? You will choose always the like worst case. So worst case is this here, right? So I need to have at least a circuit turn off time of 4 microseconds for me to satisfy this condition. So I will choose TC1. Okay, because if I choose a circuit turn off time 4 microseconds, so I am giving this T2 also ample time, and extra time even, you say, to deplete all the charges. Even though it only needs 2 microseconds, I am giving it more time, to 4 microseconds. So you choose the maximum of TC1 and TC2. So you choose the maximum. So at TC, right, you have to choose at least one. You will choose the maximum of TC1 and TC2. And what is TC1 and TC2? TC1 and TC2 are actually related with R1 and R2. So you will choose the maximum of R1 and R2. Okay. Okay. So that is the case here. So yeah, basically that is an application is mentioned used in current source inverters. These are the few cases. And now let's do a question. This question is pretty simple. This question came in GATE 2006. Basically, a voltage commutation circuit is shown and has the value of capacitor C if each thyristor has turn off time of 50 microseconds. So they have given us turn off time of each thyristor is 50 microseconds. Okay. Then what we have to find out? We have to find out basically the what we have to find out. Okay, they haven't mentioned anything. I think we have to find out the value of C, right? We have to find out the value of C. So I have forgotten the question. C in microfarads. Okay. So what is the value of C in this case? So here, right, I have R1 and R2 are both the same values, only 50-50. Okay. So things are simple basically. Like if you know the circuit very well, if you can always derive. I have derived it in front of you. So basically, what will be the circuit turn off time? TC will be safety factor into TQ. So this is the minimum amount of time that the device requires to deplete all the charges, but I am giving it a safety factor so that I give more time, ample time for it to deplete all the charges. Safety factor is 2 in this case. They have mentioned safety factor is 2, right? Safety margin is 2. So safety factor is 2 simply. So my TC will be 2 into 50 micro. That is 100 microseconds. So what is my TC? TC is 100 microseconds equals to TC is 100 microseconds equals to L, if you remember, it was tau ln tau ln2, right? So tau is what? Tau is RC, because if R and C are same. If R and C were different, then we have to think about something, right? So R and C are same. This will be ln2. R I know, R is 50. C I have to find out. So C will be equals to simply 100 micro by 50 into ln2. So what will this come out to be? I will just quickly check this. This will be 2 upon ln2. So 2 upon ln2. This will be simply 2.8854 microfarad. So this value will be 2.8854 microfarad. So answer will be C, 2.84 microfarad. Now we'll study the class D commutation, and that will be the last commutation. So in class D commutation, the circuit looks something like this. Just remember this, mainly the numericals can come from B, C or D. Okay, so from here only the numericals will come. So here few assumptions we have, and what are the assumptions? Again, IO is constant, that means the load is highly inductive. My main thyristor will be on before the operation, before the turn off process, and VC initial voltage across the capacitor will be plus Vs. Now, do you identify this something similar? If you identify this something similar, then you are focusing on the class, else you are not focusing on the class. Because what is this? This is the class C commutation circuit, right? This is the complementary commutation circuit. Okay, 2 thyristors and between a resistor is connected, right? So almost like a class C, although there are no resistors here, but almost like a class C. Class C. Okay, classic commutation circuit. So let's analyze the circuit before t equals to 0. So if I analyze the circuit before t equals to 0, what will be the voltage across the auxiliary thyristor? So my VTA, right, minus VT, if I apply KVL in this loop, minus VTA minus VC will be equals to 0. So VTA will be equals to minus of VC. Okay, VTA will be equals to minus of VC. That means it is less than 0, so it is in the reverse blocking mode. And I will assume, my assumption will be that this like diode was initially off, there was no current flowing. This is 0 current. Okay, this is in steady state, this is 0 current, so this is also 0 current. So inductor voltage is also 0. Okay, but what about the diode voltage? This is my diode voltage, right? So if I again apply a KVL, so this will be simply minus VC plus VD equals to 0. So my VD will be equals to VC. Okay, my VD will be equals to VC. So this will be something positive. This is Vs, right? So this is greater than 0. So obviously diode will turn on. The diode will turn on, obviously. Okay. So capacitor will discharge through this LC. This will form a LC circuit, right? Because here whatever IO current is going out, this current will be same. So here, right, the current is IO. Okay. Here the current is ITM plus IC. Okay. Again, like this current is IC. This current is IC. So ITM current will be what? ITM current will be simply IO. And this IO current is coming from here. Okay, so overall this current will be IO only. This will form a LC circuit. Okay, so here this diode will be turned on just at t equals to 0. This diode will be turned on. So at t equals to 0, D is on, and we will form a LC oscillator. And in the LC oscillator, right, what is the initial voltage across the capacitor? It is Vs. So basically what will be the voltage equation? So if I just write the voltage across the inductor and the capacitor, this is my VL, right? So here what I can say is VL equals to VC. And what is VC? VC will be simply like as it is a LC oscillator, it will be cos omega nt. Omega n is 1 by under root LC. So VL will also be this. VL will be Vs cos omega nt. And what about the IC? IC will be C dVc by dt, right? IC is C dVc by dt. So it will be simply C into 1 by under root LC into Vs into minus sine omega nt. So this will become what? This will be simply equals to minus Vs by under root C by L. Sin omega nt. Okay, so this will be minus Vs under root C by L sin omega nt. And like I forgot to mention that this is also known as voltage commutation or impulse commutation, because through voltage we will turn this off. So current becomes this negative, right? Because negative current, why? Because current is outgoing from the positive end of this capacitor. This capacitor is actually discharging now, and inductor current will be positive. Okay, so yeah, that is that. Now next what will happen is that as soon as this reaches to 0 or this goes above 0, then the thyristor, right? Thyristor voltage will be in the forward blocking mode. Okay, thyristor voltage will be in the forward blocking mode. So here, or what I can say, as soon as the current reaches 0 here, so this diode will be turned off. This diode will be turned off simply. As soon as the current reaches 0, this diode will be turned off. Okay, and the voltage across the diode will be something negative, hence it will not turn on. Okay, so here what I can say is that at like when IC equals to 0, diode will be off. Okay, diode is turned off. So if diode is turned off, what does that mean? That means like this inductor current will also be 0 and this inductor will be disconnected from the circuit. L will be disconnected. Okay, inductor is disconnected and inductor is disconnected, so this diode will turn off. And when will this happen? This will happen when this IC is 0. When is this IC 0? When my omega and t, basically my what is my IC equals to? IC is equals to minus Vs under root Ca by L sin omega and t. So basically my omega and t equals to pi. That means my t is equals to pi under root LC. Omega n is 1 by LC. This was a LC oscillator, right? So as soon as my current at this time period pi under root LC becomes 0, so inductor will be open circuit basically. So inductor will have 0 current and it will be in steady state 0 voltage. It will be open circuit. What about this voltage? Now what has my capacitor voltage become? So capacitor voltage at pi, right, is basically equals to minus Vs, because if you put here omega and t equals to pi, this will be minus Vs. So Vc of t equals to pi under LC will be minus Vs, right? So this will be minus Vs. Hence, if I like compute the voltage across the this auxiliary thyristor, right? What it will be? It will be VTA. Again, this polarity is wrong. This should be something like this. Yeah. VTA is equals to negative Vc. Hence, Vc is this time Vs. This will be Vs only. Okay, because like this auxiliary thyristor was anyways off, this current is 0, this inductor became open circuit, this current is 0, so capacitor current is also 0. As the capacitor current is 0, the capacitor will remain at the same voltage, that is Vs minus Vs. So overall this will become plus Vs. And what is the voltage across the diode? If you want to compute the voltage across the diode, Vd will be simply equals to Vc, which is minus Vs. Hence diode is off, confirmed, the state is confirmed, right? So what has happened here is that after this what will happen? After this I will trigger my SCR TA, and as soon as I trigger my SCR TA, this thyristor will be turned off. This thyristor will be turned off. Okay, as soon as I trigger TA, this thyristor will be turned off. Okay, so that is the case here. So as soon as I turn on this thyristor will be turned on. Why? Because it's a complementary commutation. Okay, I hope you understand just in the previous case. I will prove it to you as well. Okay, so here what will happen is if I at any time, so when will I trigger this thyristor? I will trigger this thyristor at t equals to t on. Okay, I will not trigger this instantly, because if I trigger it, right, this thyristor will be turned off instantly, right? Why I will tell that as well. This is complementary commutation. So but basically the on time for this thyristor is t on. So I will trigger the auxiliary thyristor at t equals to t on. Okay, I will trigger the auxiliary thyristor at t equals to t on. So if I trigger it at t equals to t on, what will happen? Because I want my main thyristor to be on at least for t on duration. Then it can turn off, because that is the purpose I want, right? I want to forcefully keep it on till t on. Then I want to turn it off for a step down chopper, basically. So then TA will be on and TM will be off. How will that happen? I will explain just in a bit. If I have the circuit, right, this is mode 3. So this, right, this mode is just for the waiting time. This mode is just for the waiting time. Basically, I will just wait for my thyristor, okay, to trigger. So this mode is also known as the waiting mode. Okay. So as soon as I trigger my thyristor, right, this will get triggered. This will be on. So if I now compute the voltage across the main thyristor, okay, this is the VTM. So what will be VTM? VTM will be minus VC plus VTM will be equals to 0. So VTM is equals to VC. And what is VC? If you remember, right, the VC has not changed yet. VC is simply equals to minus Vs, right? No current is flowing. So VC is equals to minus Vs at this instant. So obviously it is minus Vs. Hence VTM is less than 0. Hence it is in the reverse blocking mode. It is in the reverse blocking mode. Okay, so this is in the reverse blocking mode, right? So this is the state at t equals to t on. The thyristor TA has been triggered, and this thyristor instantly turns off as due to complementary commutation, as explained earlier as well. So I will turn this off. Now what will happen is that this has no path, right, because this is still in the reverse bias zone. So all of the current will flow through this path, right, because this free wind out will still not turn on. Okay, I will explain that as well. So if you want to compute this voltage, right, if you want to compute this voltage across the freewheeling diode, so this will be simply VFD. So basically what will be a VFD? Minus Vs plus Vc minus VFD equals to 0. So VFD, right, VFD, like Vs is minus Vs, so VFD is minus 2 Vs basically. So VFD is still minus 2 Vs, it is negative. So freewheeling diode will not turn off because Vc is minus Vs now. Freewheeling diode will not turn off, right? FD is still off, but it will turn on. When it will turn on, I will explain that as well. Okay, so basically what will happen is that now IO current, right, IC will be equals to IO, constant current. So now what will happen is that IC will be equals to IO, the constant current. Constant current. Okay, so IC is equals to IO, the constant current. So if IC is equals to IO, the capacitor will charge linearly. So the voltage is currently minus Vs and current direction is something like this. So voltage will increase now. So it will go from negative to positive. Okay, it will go from negative to positive. But until when it will go to positive? So until the freewheeling diode voltage becomes 0, then this freewheeling diode will turn on. Why? because the voltage is increasing. The voltage is increasing. The instant at which the voltage becomes more than the supply voltage, what will happen? The voltage across the freewheeling diode will be something negative, which is not possible. Okay, then the freewheeling diode will turn on. Okay, freewheeling diode will turn on. That part is sorted. So until then, when it will happen? So this will happen still like this. So IC is this. IC is IO. So IO is equals to C dVc by dt. C dVc by dt. So now if I integrate on both sides, this will be IO into dt, and IO current is constant, equals to C dVc. And like, what was the initial voltage? This is from t equals to t on to t equals to t. And what is the initial voltage? Initial voltage is minus Vs to how much I will go? Some variable voltage Vc, right? Some variable voltage Vc. I want to write the capacitor voltage in time domain expression. So this will become Vc plus Vs equals to minus Vs. So at the time instant, 1 by Vc is basically equals to plus Vs. Then what will happen is that then this FD will turn on, right? Then this FD will turn on. But one more important point: when will the thyristor voltage will become positive? So when will this become positive? As soon as this, like, what is the thyristor voltage? It is simply equals to Vc, right? It is simply equals to Vc. As soon as the capacitor voltage touches 0, this thyristor voltage will become positive, and from this I can compute the circuit turn off time. So Vc is 0. Then what happens? My thyristor Tm, right? Main thyristor Tm is basically in the forward blocking mode. So when this happens, so I will equate this equals to 0. If I equate this equals to 0, this will be 0 equals to, I will write this capital IO, as this is constant, by C T minus T on minus Vs. So basically this will come out to be, this is almost similar as the previous case as well. If you remember, this is almost similar as the class B, I think. So TC, this is TC, right? TC will be equals to Vs by IO C plus T on. Okay. Yeah, but actually TC, right? TC is actually T minus T on only, because I just want to compute the period. So when does the thyristor turn off? At T on, and after T on, how much more period is the commutation time? So this, right, I'm wrong about this. This actually will be totally equals to TC itself, because for TC duration, after TC duration, what is happening? That this voltage is getting 0. So TC will be simply Vs by IO into C. Okay. TC will be Vs by IO into C, and this is a very, very important result. Okay. This is a very, very important result. So this is the circuit turn off time of the main thyristor. So this is TCM. Okay. So if, let's say, if the load was resistive, then what would happen? Then the voltage would have increased exponentially. Instead of increasing linearly, it would have increased exponentially, and from that also you can compute. Okay, and you know how to compute, because that is class C. You remember that is class C, right? So here, what will happen is that until which the capacitor will charge until Vs, right? After that, what will happen? The FD will turn on, right? For the same reasons. So here again, let's say at t equals to T4, FD will be on, because Vc will be Vs and Vo will be equals to 0. It will just try to go to negative. I can't go negative due to the freewheeling diode. Okay, so I will again write the same expression. Okay, this will be same only. here instead of Tc, this will become T4 minus T on, and this will become basically plus Vs, right? This will become plus Vs. So here this will become 2 Vs by IO into C equals to T4, and obviously T on will be added over there. So this will be okay. So T on plus C 2 Vs by IO. This will be the time at which the FD will turn on. Okay, this will be the time at which the FD will turn on. So as soon as the FD turns on, what will happen? What is the capacitor voltage at that point of time? Capacitor voltage is simply plus Vs. What was the capacitor voltage at the starting? It was plus Vs, right? Everything has reached back to its previous stage again. So now the next time when I will trigger my thyristor, then again the thyristor will turn on, and again this will become a LC oscillator. This will turn on this diode, and all of this will be repeated. So just this is the mode 4, and in this mode 4, right, why is this 2 Tc? Actually this value, right, if you remember, yeah, actually this value, right, if you want to understand this duration, right, if you want to write this T4 minus T on, you can write this as 2 Tc as well, 2 TCM as well. How you can write this 2 DCM? Because it is linearly charging. The rate of charging is linear, right? So for it to charge from minus Vs to 0, what is the total amount of charge it needed? It needed plus Vs voltage, right? Another plus Vs, it will need another Tc time. Okay, I hope you understand this. So for Tc time, it went from minus Vs to 0. Then for another Tc time, it will go from 0 to Vs. I will explain in the diagram as well. So this, right, this you can write it in terms of Tc as well. This is easier for us. So this will be T on plus 2 Tc. Okay. So from T on plus 2 Tc to next time period T, this will be the state. The state will be basically my FD will be on, and my this Tm will be off. Basically Tm will be off, and Ta will also be off. Everything will be off. Just the auxiliary thyristor will be on. Okay, and the diode will also be off. So as at the next time instant at T equals to T, again this thyristor will be triggered, main thyristor will be triggered. And how is this in the forward blocking mode? So you can observe that what is the voltage across the main thyristor? If you remember, what is the voltage across the main thyristor? This is the VTM, right? The voltage across the main thyristor, if you apply simple KVL over here, this will be simply Vs. So it is in the forward blocking mode. So I can simply trigger it at T equals to capital T, and then again the cycle will repeat. Same cycle. I will start from mode 1. So here is the graph, right? So if you observe, initially what is happening at T equals to capital T, let's say I triggered the SCR, main thyristor. As soon as I trigger the main thyristor, what will happen? This will be on, and as soon as this is on, right, so this will short circuit. So the voltage across the diode will be something positive, which will turn on this diode, right? So this will become LC oscillator. So if this becomes LC oscillator, what will happen? The current across the thyristor was IO, but it will also increase because the capacitor is also discharging. Capacitor is also discharging, right? So hence the current will increase. Capacitor current will follow like a LC oscillator. Next, what will happen? As soon as this capacitor current goes to 0, what will happen? This diode will be turned off. This will basically current is 0, so this will be turned off. And again, if you compute the voltage will be something negative. Hence the diode is reverse bias. So now I have the wait time. Now I will wait. This is the wait time. This is the mode 2. If you remember, this is the wait time. Okay, I will wait for my auxiliary thyristor to trigger. Wait until what? I will wait until T equals to T1, because at T equals to T1, I want to trigger the auxiliary thyristor, because at that instant, if I trigger my auxiliary thyristor, the main thyristor will be off, and exactly that is what I want. I want to turn off my main thyristor at T equals to T1. So if I trigger this at T equals to T1, this will turn off the main thyristor. So my main thyristor will be simply off, and as soon as the main thyristor turns off, the current across the main thyristor is simply 0. So the auxiliary thyristor carries the current, okay, and it is a constant current, because the flow of the current will be something like this, because diode is off, right? Flow of the current will be something like this. and again what will happen, it will linearly charge. So if you observe here, right, the voltage of the capacitor is linearly increasing. As the current is constant, the rate at which the voltage will increase will be linear. So from minus Vs, it was to, if you remember, the capacitor voltage was minus Vs at this instant. So from minus Vs to 0, it will take Tc time. For increasing another Vs, how much time it will take? Same time, because the rate is same, slope is same. This is a straight line, right? Slope is same. So if it has taken me Tc, what is Tc? Tc is basically a circuit turn off time. The period for which the voltage across the thyristor is negative, because capacitor voltage is negative, hence the capacitor voltage is the thyristor voltage, hence it is negative. So it will be 0 here for Tc period, and then again another Tc will bring it back to totally plus Vs, and hence the FD will turn on after this. Okay, FD will turn on after this. Okay, so these are the few things. Now here one thing, if you want to know the average voltage of the output, because if you understand one thing is during this mode 4, right, I think this was mode 4, yeah, this was mode 3, this is still T on. Have I written all the timestamps? I don't know. This is still T on plus 2 Tc. Okay, pi under LC T on plus 2 0 T. Oh, this, right, this will be actually pi under LC. I haven't written all the timestamps. Yeah, sorry for that. So here from T on plus 2 Tc, right, what will happen is that, what is the output voltage actually? The output voltage is actually, if you want to compute the output voltage here, Vo is equals to minus Vs plus Vc. So it is Vs minus Vc, right? It is Vs minus Vc. So at this T equals to T on, what is the Vc? Vc is negative, right? Minus Vs. So Vo is 2 Vs actually. Vo is 2 Vs. It is high voltage. Okay, it is very high voltage. And the voltage across the freewheeling diode is also 2 Vs. So the peak inverse voltage for the freewheeling diode is 2 Vs. Remember this, right? Peak output voltage is 2 Vs. Okay, it is not Vs. Okay, so that point you have to keep in mind. Like if you want to measure the voltage across this as well, I cannot measure the voltage across this, unfortunately. Can I measure the voltage across? I can measure the voltage across this. I can measure the voltage across this. Yeah, I can. So voltage across diode is 0 right now. Voltage across the TM is simply this plus Vc, right? Yeah. So one thing you have to understand, the peak voltage across the freewheeling diode is 2 Vs. So peak inverse voltage for this freewheeling diode will be 2 Vs. So what will happen here, right? Like Vs is fixed. Capacitor voltage is increasing linearly. So the output voltage will also decrease linearly. So the response will be something like this. Okay. So this is during the mode 3. This portion, right? This portion is basically mode 3. Okay, so for mode 3, this is a 2 Tc time period. For this time period, basically the voltage will not instantly go to 0. Okay, the freewheeling diode will not turn on after this. Like in ideal case, what we assume when the thyristor was turning off, right? When we were analyzing the step down chopper, I was assuming as soon as the thyristor is turned off, the voltage went to 0 because the FD turned on. But here there is some 2C gap after which the freewheeling diode will turn on. So voltage will not go instantly to 0. So my average output voltage expression will change. What will be the average output voltage expression? It is area under one time period. Area is what? This is T. Area is what? Area is this Vs into T on plus this value is what? This is 2 Vs, right? This is 2 Vs. Okay, so this is 2 Vs. So what I can say? I can say this as 2 Vs into height is 2 Vs and width is 2 Tc into half, obviously, divided by capital T. So the area will change, average voltage also will change, right? So you don't have to remember this formula, just remember this graph. This is important, right? Remember this graph and this circuit diagram, obviously. And remember each modes. So the peak current, right? What is the peak current across the thyristor? Peak current across the thyristor, if you observe this graph, it will be ITM plus IO, because capacitor was initially discharging when this was forming a LC oscillator. So when this was forming a LC oscillator, here the current through the main thyristor was IO, this IO current, and this IC current, right? So it will be ICM plus IO. What is ICM? ICM is basically Vs divided by under root L by C, if you know, that is the characteristic impedance. What is the peak current across the this auxiliary thyristor? Peak current across the auxiliary thyristor will be basically when this TM will be off, right? When this TM is off, the capacitor will be simply will be IO, right? This will be IO because this current is constant. Whenever the auxiliary thyristor is on, the current is IO basically. Okay, it is never anything else. So this will be IO simply. What about the diode peak current? Diode peak current, right? If I want to write the diode peak current as well, diode peak current will be all what? Just pause the video and tell me. Diode peak current IDP will be simply ICM again. Okay. ICM, this is ICM actually. And this is also this is ICM, yeah, fine. So this is ICM and ICM is this basically. What is TCM? TCM basically is circuit turn-off time. It is simply CVS by IO. Why is it CVS by IO? The capacitor voltage was minus Vs. It has to go to 0. Then only the SCR will be in the forward blocking mode. So that is the circuit turn-off time. That is basically C into Vs by IO. Okay. The current is constant. If let for example, if the load was resistive, right? It was simply the previous case. Basically the complementary thyristor case. So it will be RC into LN2. Okay. Depending on the load resistance. This more specifically I can write this as RL. Okay, because the capacitor will then charge what? Exponentially. Capacitor will then charge exponentially. The initial voltage was minus Vs and the final voltage it will try to go to plus Vs. Okay, but it will never go to plus Vs because FD will turn on as soon as it goes to plus Vs. Okay, so that is one case. Next is peak inverse voltage of the freewheeling diode is 2 Vs. Okay, peak inverse voltage of the main thyristor. Okay, where are we getting the peak inverse voltage of the main thyristor? Like you can compute the circuit turn-off time of the auxiliary thyristor as well, because initially the auxiliary thyristor was reverse biased, because in this region, right, when I'm like what is my VTA? VTA was equals to, when this thyristor was on, it is minus and plus. So VTA was equals to Vs. VTA was equals to VC when this main thyristor was on during this region. So as soon as this VC went from 0 to something less, right? Went from 0 to something less, this will go from negative. So what will happen is that, so this thyristor basically will be in the forward, not forward, sorry. Am I right here? Just hold on. This voltage, right? This was initially, if I just go back here, what was this voltage? Just compute it here, right? What is the VTA? I just computed. Yeah, VTA was minus VC. Okay, sorry. VTA was minus VC. I again did this wrong. VTA is minus VC. So VTA is minus VC. So basically this is something negative, like VTA is negative something here. And as soon as this goes here, right, this becomes positive. So it becomes in the forward blocking zone. So this region is the region for which the auxiliary thyristor is in the reverse blocking mode. Hence this is the circuit turn-off time of the auxiliary thyristor. Although this won't be asked, but let's go to know how do we compute this. Just don't remember the formula, just understand how do I compute this. The period for which the voltage across the thyristor is negative. Okay, next, peak inverse voltage across the TM thyristor. So peak inverse voltage across the FD we have understood, it is 2 Vs. That is, we have understood. How do we compute the peak inverse voltage across the TM thyristor? That is what I am trying to understand. No, I think this is something wrong. I think this should be Vs only. I tried to find it out, but somewhere I think in the results there was 2 Vs. I couldn't find it because somewhere in the question they gave it 2 Vs. I will just check it later on. Okay, so and another few results is like the minimum time for which the SCR will be turned on, because the minimum time has been fixed here. Why? Because I cannot turn this TA on here, right? What is the minimum time where I can turn this TA on? The minimum time is after this current becomes 0. When does this current become 0? It becomes 0 at pi under LC. After that only I can turn this on. Okay, and if after that if I instantly turn this on, then only this TM will be off. As this TM will be on, I cannot turn this TM on forcefully. So the minimum time that has been fixed by this pi under LC. That you need to keep in mind, because the latest by which I can turn this main auxiliary thyristor on when it reaches in the forward blocking mode. When does it reach in the forward blocking mode? It reaches in the forward blocking mode at t equals to pi under root LC. Before that, I cannot turn this on because this is in the reverse blocking mode. Current is flowing through the diode. Okay, so that is the minimum time of the main thyristor as well, T on of the main thyristor, because minimum time is fixed now. So alpha minimum, the duty cycle, minimum duty cycle also has been fixed here. Okay, so that is one constraint of this particular commutation. So from this, right, I will be able to compute my VO minimum, and this type of one question has came in the examination hall. That's why the formulas are here. Okay, so just how do you remember this? Basically, you remember like this, that how do you remember between class C and class D? So class C, you can remember it like this: when L and C are together, LC are together. When L and C are together, what can I say? When L and C are together, basically I can say it is a class C commutation. Okay, and when L and C are not together, L and C are not together, it is basically class D commutation. Okay, like this you can remember. Now these are few questions. You can take the screenshot and tie it by yourself. Okay, then I will solve all these questions. These are pretty simple questions only. This is the last question, I think. After this, we don't have any questions. Okay, one more question is there, and this question was the controversial one, which I had a bit of doubt. We'll see this question as well. Okay, so let's solve this question. Let's solve this question. This question, what is telling? Consider the chopper circuit shown in the figure. So the chopper operates at 400 Hz. So my F is equals to 400 Hz, and my assuming 50% duty cycle. So alpha is 0.5. Fine. So my T on is fixed. T on is what? T on is basically alpha into T. So it is 0.5 divided by 400 into 1000. I can compute this in milliseconds. This will be 2.5 into 0.5. This will be 1.25 milliseconds. Okay. Then the load current remains almost ripple free at 10 amperes. The load current remains almost ripple free at 10 amperes. So IO equals to constant at 10 amperes. Next, assuming the input voltage to be 200 volts and the devices to be ideal, the turn off time available in the thyristor THM. Okay, so what is the turn off time available to the thyristor? So it is basically asking us the circuit turn off time, right? Circuit turn off time, T circuit. Okay, it is asking us the circuit turn off time. So what is the turn off time available to the thyristor? What is the available turn off time that I am giving to the thyristor, right, to turn it off completely? Basically the period for which it is in the reverse bias. So basically input voltage is 200. So basically, right, this is a class D commutation because L and C are different. Here what I can say is that, like, you can assume time state if you don't know anything. So initially what will happen, this thyristor is on. As this thyristor is on, and I will assume that this has been charged to plus Vs. Okay, if this is charged to plus Vs, then this will form a LC oscillator. This will turn this diode on. Okay, so although this is given thyristor, but we'll assume this is on. So then at some instant this current will go to 0. Then this TH auxiliary thyristor will be in the forward blocking mode, and after that I will trigger this at t equals to capital T on, and then what will happen is as soon as I trigger it, this will be turned off, and what will happen, all of the constant current will flow through the load like this. Okay, and then capacitor will linearly increase its voltage, and at certain instant it will be equals to Vs, and at when this is equals to Vs, what will happen is that the main thyristor will be simply in the forward blocking mode just at the instant for the forward blocking mode. So it went from not Vs to 0, through 0, right, because the main thyristor voltage is equals to simply the capacitor voltage. So basically it will go from 0 to Vs. And what is the rate? So basically I can say that IO will be equals to C dVca by dt. And how am I changing? I need to find out the TC, right? So basically this IO is constant. IO is equals to C some value C, dVc is going from 0, final voltage is 0, and initial voltage was minus Vs. Initial voltage was minus Vs divided by period from T on to T on plus Tc. That will be simply Tc, because for this period the thyristor is in the reverse bias. Okay, so IO is what? IO is basically equals to 10 amperes. 10 divided by C. C they have given me. C is 2 micro. So we'll keep this as 2 micro right now. And I have to divide by Vs as well. Okay, so not Vs, sorry. So TC will be simply C is 2 micro into Vs. Vs is 200. IO is 10 amperes. Okay, so this will be 20 into 2, that is 40 microseconds. So circuit turn off time and the available time for the thyristor is 40 microseconds. The actual turn off time of the SCR or the device must be lower than this. Let's say if the TQ, right, if the TQ is, let's say, something 50 microseconds, so I have given it only 40 microseconds to turn off, but the charges will be depleted in 50 microseconds. So that is wrong, right? So this circuit will not work. So hence I have to change the capacitance value or do something. Okay, that's how you design the circuit. Okay, so now let's come to this next question. Previous question was pretty easy. Next question, a voltage commutated thyristor. So voltage commutated thyristor means class D commutation, right? This is class D commutation. Is shown. The chopper is operated at 500 Hertz. So basically my F is 500 Hertz. Next, with 50% duty cycle ratio, so alpha is 0.5. The load takes a constant current of 20 amperes. So IO is 20 amperes. IO is 20 amperes. So evaluate the circuit turn off time for the main thyristor TH1. Evaluate the circuit turn off time for the main thyristor TH1. Circuit turn off time for the main thyristor, again same formula. Okay, you can remember the formula or you can directly do it. So IO is equals to CVS by TC. So TC will be simply C is how much? C is 6 micro into Vs is how much? Vs is 100 volts. IO is 20 amperes. So this will be simply 30 microseconds. So TC is simply 30 microseconds. Okay. So here calculate the value of inductor L if the peak current through the main thyristor TH is limited to 180% of the load current. So what is the peak current across the main thyristor? So main thyristor actually includes the capacitor current as well as the IO current, constant current, right? So peak current will be the maximum value of the capacitor current plus the IO. So ITM, if you remember, I wrote you the formula as well. I am telling you the concept as well. So it is basically IO plus IC max. So, but I have to limit this within 180% of the load current. So it is 1.8 times the IO equals to IO plus ICM. From this I will decide the value of inductance. So ICM will be 0.8 into IO. IO is simply 20 amperes. And what is ICM? If you remember, ICM is equals to Vs by under root C by L. So it is simply Vs is what? Vs is 100 volts. 100 volts under root C. C is 6 by L equals to this is 0.8 into 20, right? 0.8 into 20 is simply 16 amperes. So L will be 100 divided by 16. Then I will square it. If I square it into 6, am I doing something wrong here? Maybe doing something awfully wrong. This is 234, that is fine. But this 6, right? Remember this 6 is in micro. Okay, 6 is in micro. So this will be 234. The 6 is in micro. Remember this. This is in micro. I am assuming inductor is also in micro. 234.375 micro Henry. So you can write this in milli as well. So this will be 0.234 millihenry. Okay. This will be the value of the inductance. Now, what about the last part? Last part is what is the maximum instantaneous output voltage of the chopper? So, like you have seen that I by wrongly written the maximum thyristor voltage to be 2 Vs because I was going through the short notes of like some other people and there they wrote it. Okay, and I know from where they wrote it because they would have seen the answer to this was given 200 volts, and they thought the maximum voltage across the resistor will be 200 volts. But actually, they just didn't even think. Actually, the like what this is asking us, calculate the maximum instantaneous voltage, output voltage of the chopper. Output voltage of the chopper is here, right? That is the output voltage of the chopper. What is the maximum instantaneous output voltage of the chopper? It is 2 Vs. If you remember, it is 2 Vs, and this is not the peak inverse voltage of the diode, okay, of the thyristor, of this main thyristor. Simply, this was charged to plus Vs, and this is also charged to plus Vs, right? So when this thyristor T2 is on, so overall the voltage becomes here, comes out to be 2 Vs, right? 2 Vs, if you remember here. Not not at this instant, when this is plus minus, when this TH2 is just triggered, okay? So the overall potential will be simply plus 2 Vs, just this graph, right? Just this graph, okay? At the instant when this is the instant where my auxiliary thyristor is triggered. Auxiliary thyristor is triggered. Okay, so basically it will be VO peak, right? So this is the first answer is this only. Second part is this. Third part is basically VO peak. What is the VO peak? VO peak will be 2 Vs, okay, as at T equals to what? T equals to T on, because at that instant the SCR auxiliary thyristor TA will be on, right, and capacitor will be at minus Vs, and source is Vs, so overall the voltage becomes plus 2 Vs. So this is Vs is 100, so this will be 200 volts, okay, this will be 200 volts. So yeah, that is the 200 volts. That's it. Let's move on to the next question. Next question is this: a voltage commutator chopper operating at 1 kHz is used to control the speed of DC motor as shown. The load current is assumed to be constant at 10 amperes. So IO is constant. IO is 10 amperes and F is 1 kHz. The minimum time in microseconds for which the SCR M should be on. What is the minimum time? Minimum time is the T on minimum, okay. The minimum time will be the moment at which I can trigger the auxiliary thyristor. What is the moment I can trigger the auxiliary thyristor? It is pi under root LC. So T on minimum will be pi under root LC. So pi, L is how much? L is basically 2 and C is 1 micro. So I can write this in like micro as well, because micro outside also I will get micro. So this will be 2000 micro into 1 micro. So this will be under root 2000 micro. So if I do 2000 under root micro into pi, so this will become 140.5 microsecond. So this is the minimum T on period, T on time for which the SCR has to be has to be on. Before this I cannot turn off the SCR because auxiliary thyristor cannot be on before this. That is the reason. Next, the average output voltage will be for the same condition. Average output voltage for this condition. Okay. Now many students will do a mistake over here. They will assume that average output voltage, this is simply a step down chopper, right? And average output voltage will be what? This is the first part, and the second part will be this A only, right? This A only B. A. A is this. B will be what? VO average will be simply what? For a step down choppers, formula is alpha into Vs. Alpha is, they have told us alpha, they haven't told us. We will find out the alpha, right? T on is this. So what is T? So it is simply T on by T into Vs is how much? Vs is 250. So T on is 140.5 micro. Okay. And I want to compute in terms of like T as well. T is what? T is basically, or I can write this as into F. Okay. Into F is 1 kilo, but I have to write 10 raised to power minus 3 as well, because to equate this in right units, into 250. Okay, so into 250 divided by 1000. So this will be 35.124 volts. Okay. Okay, 35.124 volts. So you will mark this, okay, and you will be wrong. Okay, why you will be wrong? Because you couldn't remember the voltage waveform. What was the voltage waveform? If you remember it correctly, the voltage waveform was something like this, right? Even though for an ideal chopper, that is correct, but this is not ideal. The voltage waveform is something like this, right? So I'll just copy this voltage waveform and take it there. I'll just copy this average thing as well, right? This was a very good question which came on GATE 2006. Okay, this was like way early. And nowadays I don't think they give much question on commutation, but they can as well, right, if they want to. So this will be the average voltage. What is TC? TC is basically, if you remember it correctly, or you can understand, like derive it as well, TC will be simply C into Vs upon IO. What is C? What is C? C simply is here 1 micro, 1 into Vs is 250 divided by IO. IO is I think 10 amperes, right? 10, yeah. So it will be 25 micro, but this duration will be another 50 micro, for which the voltage is not zero actually. Okay, voltage is not zero, so this has some non-zero voltage. So this will also come in the average voltage expression, which is written over here. So I will compute the VO average. VO average will be simply Vs into T on. What is Vs? Vs is simply 250. So this will be 250 into T on is I think 140 micro. It was 140 micro plus 2 Vs. This is 2 Vs will get anyways cancelled. So this will be 250 into 2 Tc. So this is 25 micro. So this will be 50 micro and divided by T. T is basically 1000 micro. Okay, so basically it is 1 kilo. 1 kilo means 1000 micro. So 250, this will become 1 by 4 into micro will get cancelled into 190. Okay, so 190 by 4 is how much? 190 by 4. This is almost equals to 47.5 volts. So this will be your answer, right? This won't be your answer. This won't be your answer. 35 won't be your answer. Your answer will be 47.5 volts. So just be careful of this. Okay, so you might get tricked. So just be careful of this result. Okay, so now let's move on to the next question. This is a good question again. This question came on GATE 2009. If the chopper circuit shown the main thyristor TM is operated at a duty cycle of 0.8, so alpha is simply 0.8. They are telling us, which is much larger than the commutation interval. They are explaining basically than the 2C, right? 2DC. Not 2TC. Basically the time period for which it needs to minimum on time, it is much larger than that. If the maximum allowable okay, like this spellings are wrong here. If the maximum allowable dVdt on the main thyristor, so dVdt of the main thyristor, dVtm dt max equals to 50 volt per microsecond. Okay, what should be the theoretical minimum value of C1? What should be the theoretical minimum value of C1? So how do I compute this basically? So when will this dVtm by dt will be maximum? So one thing may happen. This inductor is, I don't know why this inductor is present over here. Okay, this inductor is between this auxiliary thyristor and this. Okay, fine. This will form this, and okay. So here, when will this be maximum? When this TA is on, right? When this TA is on, basically when this voltage source is given, okay, then it is always constant, right? So basically what I am trying to say is that when main thyristor is on, it is always equals to 0. So there is no dVc by dt. When main thyristor is on, voltage not changing. So voltage will only change because it is constant 0. Voltage will only change when the main thyristor voltage is 0. So when the Tm is off, I will get some dVtm by dt, change in voltage. Okay, some non-zero dVtm by dt. Before that it was 0. So when this TM is off, right? When is this TM off? This TM is off for two cases. One case is when this TA is on, okay. Another case is when this freewheeling diode, okay, just hold on. When this freewheeling diode is on. When this freewheeling diode is on, right, the voltage across the resistor is again fixed. So I will only take this condition when this TA is on, then only the voltage is changing, because this voltage is also changing. This voltage is also changing. Okay. So I will say, I'll just draw the circuits. I will just bring it back. I'll just bring the circuits here. Okay, these circuits. Just bring this circuit, right? So I will say again, TM is off for two cases. One is when the FD is on. So when the FD is on, right, freewheeling diode is on, basically VTM is fixed. What is the VTM? VTM is 50 volts. Not 50, sorry, this is VS. So hence my change in voltage is again dVTM by dt is again 0. Okay, here as well, my dVTM when the thyristor is on, dVTM by dt is simply 0. Okay, this can trigger the SCR, right? If you remember chapter 1, okay, chapter 1 that I talked about, right? This can trigger the SCR. If the dVTM by dt is very high, this can turn on the SCR by mistake, okay? False voltage triggering, if you remember. So another case is when auxiliary thyristor TA is on. So when TA is on, what is the voltage across the thyristor? Voltage now is a variable. What is the voltage? VTM will be equals to VC. So dVC TM by dt will be equals to, just keep this on the side, dVC by dt. Okay, so what I can say over here. So what is the dVC upon dt? dVC upon dt is fixed when this TA is on. TA is on, right? Basically dVC upon dt is fixed. Why? Because IC is fixed. IC is simply IO. Have they told us the IO? They have. Okay, they haven't. Okay, what are they asking? They are asking, assume the current ripple through LO is negligible, so it is constant. What should be the minimum theoretical value of C1? Okay, fine, C1. So this they have provided. So basically they have provided dVTM upon dt. That is the maximum value. That is basically this, right? Else it is always 0. So they have provided as the value of dVC upon dt. That is equals to 50 volt per microseconds. Okay. So from this, what I can compute? I can compute basically, they have given us. So what is the minimum theoretical value of C1? So what is the IO in this case? So IO, right? What will be IO? So IO will be VO average by R, right? So here, right, one thing I will assume is that because they haven't provided us the L, so I will assume that L1 is very large. Okay, because if L1 is very large, right, what will happen? This TC, right, TC will be very low. What is TC? Okay, not L1 is, okay, that is wrong actually. TC is this, TC is VS upon IO. So VO average will also be 25. This, it does not depend on L actually, sorry for that, it does not depend on L. Okay, so here, right, this question has one mistake in it. I will just talk about it just in a second. So first of all, what is my VO average? I need to find out my VO average. What is my VO average? VO average is simply equals to this area, right? So it is Vs into alpha, okay, alpha duration, or I can say this as 0.8 into T plus this 2 Vs into 2 Tc into half, basically this divided by T. Okay, so here this is equals to Vs into 0.8, so this will be 0.8 Vs plus 2 Vs into 2 Vs into Tc is what? Tc is actually C into Vs by IO, right? Tc is C into Vs by IO, correct? Okay, but I am computing the IO itself, so that is hectic. So okay, I will just assume one thing. This is C1, right? C1 into Vs by IO divided by T. So what I will assume is here, right? What I will assume is my switching frequency is very high. Okay, which is much larger than the, like duty ratio is 0.8, which is much larger than the commutation interval. So actually, basically this interval is much larger than the TC. So here, right, if I write TC here, so actually in the question they have provided this correctly only. So I should have understood this. Else, like this question will be very difficult for you to understand, because you will not be able to compute TC. TC depends on C, and C is unknown to you. And for finding C only, you are doing all this. But here also C comes, right? That is difficult. So basically, in this statement, right, this is a very good statement here, which is much larger, although they haven't like said it completely correctly, which is much larger than the commutation interval. Basically, what they are telling us is that basically my TC, like my 0.8 T duty cycle time period, is much larger than the commutation period, for which the circuit is just turning off, right? So if it is much larger than this 0.8 T, then this I can assume this as almost equals to 0. So if it is 0, then this will come out to be 0.8 Vs only. So this actually comes out to be 0.8 Vs, which is for the ideal chopper case, right? So that we have to assume, this much we have to assume, else this will be very difficult for you to solve. So 0.8 into Vs is how much? Vs is 100. So this will be 80 volts. So what will be IO average? IO average will be V average by R. So this is 80 divided by 8. So this will be 10 amperes. Okay. R. 18 amperes. So IO is 10. This is constant. So I will put this IO value here, right? So basically, what I know this formula, right? I know this formula that my IO is equals to C dVc by dt when the auxiliary thyristor is on. So IO is 10 equals to, this is C1 dVc by dt max they have provided us. So this will be the minimum value of C1. This will be the minimum value of C1. My C1 can be more than this, because dVc by dt can be less than this, but C1 cannot be less than this. That's why they have asked us to find the theoretical minimum value. Because here, right, if this is maximum, this has to be minimum, because the product is constant. That's why IO is constant, that is 10. So if this is maximum, this is minimum, right? So I hope you understand that. So this is C1 into dVc by dt, that is 50 volt per microsecond. So C1 comes out to be 0.2 microfarad basically. Okay, so answer will be 0.2 microfarad. This is a C1 minimum value. Okay, theoretical minimum value. Okay, so C1 minimum will be simply 0.2 microfarad, which is option A. So this question was also very good. Option A is correct. This question is very good. So you can revise with all these questions. So trust me, like no one will do this type of analysis. Everyone will just solve this directly with the formula. Everyone will just solve this directly with the formula without explaining anything. I have to explain everything logically. Okay, like you can see other educators, you can see that. Okay.